Hello everyone, welcome to this Artificial Intelligence full course by Intellipaat. This particular AI course has been taught by our top industry experts associated with companies like Google, Meta and Microsoft. And I'm pretty confident that if you stay until the end of this video, you will understand artificial intelligence all the way from theory to practical implementation. In 2023, we saw the major AI takeover. We saw ChatGPT, Midjourney and Bard shaking the whole tech world. But you know what? These mammoth generative AI tools have emerged from the basic concepts of AI. For example, ChatGPT is a product of natural language processing. DALL-E or Midjourney are developed by image manipulation using transformers. And so are the other generative AI tools. And this free artificial intelligence full course is exactly going to help you understand the basic intuition behind all these concepts. Here's how the agenda for this artificial intelligence course looks like. So we're going to start with the introduction to AI, and then we will look into Keras and TensorFlow framework. Next, we will also discuss data handling with NumPy neural networks, multi-layered neural networks, etc. And then we will touch upon the important concept of artificial neural networks. Once we are done with this fundamental part, we will deep dive into deep learning. We will cover deep neural networks, recurrent neural networks, as well as GPU in deep learning. Towards the end of this course, we will also take you through the artificial intelligence interview questions, which are most commonly asked in most of the AI interview setups. But before we address all of these things, let us try to understand what exactly artificial intelligence is. So most Hollywood movies view AI as a villain, which will take over the entire world, starting from the Westworld to the Matrix to Mission Impossible Dead Reckoning as well. Even famous business figures like Elon Musk quoted that AI is far more dangerous than that of nukes. But is that really the case? You can let us know your thoughts about the same in the comment section below. Even with the Q-star model developed by OpenAI, the machines still have not reached the ability to outperform humans. But to be able to thrive in the digital economy, it's imperative to understand the notion of AI. Artificial intelligence is basically the science of making machines replicate some broader aspect of human intelligence. It starts with the basic idea of finding the next optimal step, representing certain and uncertain knowledge, solving optimization problems, text sentiment analysis, image detection and manipulation, to the real-time video activity tracking. And with this free artificial intelligence course, we are going to teach you one of the fundamentals of AI. But before we begin with this artificial intelligence course, hit both the subscribe button and the bell icon for Intellipaat YouTube channel.
Artificial intelligence has revolutionized the way people think, learn, and work in various fields from finance to healthcare and mobile apps. What's more interesting is that AI plays more of a role in our daily lives than we can imagine. From Siri and OK Google to various virtual player games and social media apps, AI is everywhere. It sure is the most happening topic in every business right now. It is the most wanted and exciting career domain right now in the market. Artificial intelligence or AI uses intelligent machines that build in a way that they react like humans. The primary process involved in making these smart machines is to carry out decision making, which analyzes and uses data available in an enterprise. It is similar to the human mind absorbing and synthesizing information and providing the required decision. So how does an AI work? AI systems work by investigating large amounts of data labeled training data, analyzing the data for correlations and patterns, and using these patterns to make predictions about future states. In this way, a chatbot that is fed examples of text chats can learn to produce lifelike exchanges with people, or an image recognition tool can learn to identify and describe objects in images by reviewing millions of examples. AI programming focuses on three cognitive skills: learning, reasoning, and self-correction. Learning processes. This aspect of AI programming focuses on acquiring data and creating rules for how to turn the data into actionable information. Reasoning processes. In this aspect of AI programming focuses on choosing the right algorithm to reach a desired outcome. In self-correction processes, AI programming is designed to continually fine-tune algorithms and ensure they provide the most accurate results possible. So there are four types of artificial intelligence: First, we have reactive machines. These AI systems have no memory and are task specific. An example is Deep Blue, the IBM chess program that beat Garry Kasparov in 1990s. Then we have limited memory. These AI systems have memory so that they can use past experiences to inform future decisions. Some of the decision-making functions in self-driving cars are designed this way. Theory of mind is the third thing. It means that the system would have the social intelligence to understand emotions. And finally, we have self-awareness. In this, AI systems have a sense of self which gives them consciousness. Now let's see what are the applications of AI. One of the best known healthcare technologies is IBM Watson. It understands natural language and can respond to questions asked for it. AI can automate grading, giving educators more time. It can assess students and adapt to their needs, helping them to work at their own pace. AI tutors can provide additional support to students, ensuring they stay on track. Banks are successfully employing chatbots to make their customers aware of services and offerings and to handle transactions that don't require human intervention. AI technologies are used in transportation to manage traffic, predict flight delays, and make ocean shipping safer and more efficient. That's it about artificial intelligence.
Why artificial intelligence? Now, AI, see, AI is a very, very broad term, right? Any computer system, any application that tends to simplify human job, right, can be called as an AI system. In the slides that are going to come forward, I'm going to explain the finer differences, right? But why AI, right? So AI, first of all, now artificial intelligence, to be precise, deep learning models, they are widely used in all the different domains that you have, right? Now, first of all, data science, if you see data science is used across all domains. You give me an example of any domain, right? And I can give you 5 case studies where data science can be applied in that particular domain, right? So if you see banking, industries, finance, banks, right? All of these, they have been using data science from 20-25 years back, right? They were using simpler models, but banks were actually the first of the businesses that were able to adopt data science and AI, and they knew that it is going to help them, right? Why were the banks first? Because generally, if you see, each and every bank will have their data stored in a structured format, right? Every customer's data will be stored. Even when computer systems were not there, you were able to save customers' data in, let's say, in a passbook and, let's say, ledgers and all, right? So banks, for your financial institutes, the transition was easy, because data science is all about, or AI data science, it is all about data, right? So if you don't have data, obviously, if you don't have data, you will not be able to leverage AI. So these financial institutions, they were actually very, very close to adopting AI because they already had data. They already had historical data about customers. Now, there would be some banks who would be saving this data properly. There would be some banks who would not be saving this data properly. Those who were able to save the data properly in databases, in different kinds of systems, were able to adopt AI before, right? So that is one. Medical science, your deep learning, your machine learning, your data science, it is very, very, it's used a lot in the medical science field, specifically deep learning, right? Why deep learning? Because image processing, identifying diseases by going through reports and all, right? That is something that your deep learning models can do. Can any kind of automation? Yes, Kunal, I'll come to that, but yes. So if I give you an example, you guys would have seen that self-cleaning robots, right? That we have these days. These are AI bots or something, robots which are going to scan your entire house. They're going to scan the layout of your house and they just go ahead and start cleaning your house, right? That is, these kinds of products are not exactly data science, but this is AI. Why AI? Because what this particular vacuum cleaner does is that it has sensors through which it is able to lay out the map of your house, right? And then all it does is that it goes ahead and it travels that particular whole area in a predefined pattern, right? So this is not exactly data science, but that will still be considered as AI, artificial intelligence, right? LLM will come under AI only, Raj. LLMs are large language models. All of this will come under AI. LLMs, to be precise, will come under deep learning. So basically, the models that we will be studying, using those models only, you can go ahead and you can start creating LLMs. Okay. Heavy industries, AI has been used a lot for supply chain management, logistics and all, right? Efficiently used in air transportation, identifying demand of customers, identifying demand in different seasons, during festive seasons, during non-festive seasons, identifying the pricing of tickets on the basis of the demand. All of that is something uh, that has been happening now for almost 5, 6 years, right? Change the face of gaming. If you are a gamer, you would know that your Xbox and PS4s and all, right, they come with these motion sensor games, right? You can, let's say, if you have tennis and all, right, you you can stand in front of the console. You can, it can look like that you are playing tennis. Let's say that you go ahead and you serve, and the character on the TV screen is going to replicate whatever you are doing, right? This is nothing but AI. This is ideally nothing but a random forest model, right? Your PS4s, your Xbox and all these actually use tree-based models to go ahead and do all the complicated stuff that you would be seeing, right? Reinvented the world. Obviously, now reinvented the world. I think ChatGPT can be the classic example, right? ChatGPT has actually reinvented the world, right? And a great help for humans, right? So now, if you see, it's not only business use cases where AI is helping us these days, right? Recently, I was studying something and I was able to see that an AI engine was created and it was deployed on a beach, right? A camera was deployed on a beach. Now, basically, for that given beach, if let's say a particular person is, let's say, swimming and they go deep inside the ocean, right? The system is going to come out with a alert, and it is going to alert the people who can go ahead and who can save them. Right now, this job earlier would have been done by coast guards, right? So you would have to deploy so many coast guards. They would have to be constant. They like constantly. They would have to see where people are, if they are going too much inside the ocean and things like that. Right now, all of these things can be automated. A classic example is defense, right? In defense now, across borders, right? Now you know that our country, India, being surrounded by China, Pakistan, and all, right? We are constantly on our toes, right? Now, the satellite data, the satellite image data that comes through, right? This data is now used, is fed to different deep learning models, and the objective of these deep learning models is to just to identify if there is any development, if there is any kind of motion that is happening across borders. So let's say if Pakistan decides to attack us tomorrow, right? They cannot just do that in a couple of hours. They will have to start planning for that, let's say a week back, maybe 2 weeks back, right? They will have to deploy uh, inventories, they will have to deploy their soldiers and all towards the border. Now, all of this movement can be captured by the satellite image data, right? And whatever image data is being captured, this is generally fed to a deep learning model, right? A CNN model. We are going to learn about that. And then the model is able to alert us that, okay, so let's say previously it was bare sand, right? It was nothing but sand. But let's say a couple of days later, uh, the there started to be movement at the borders, right? So let's say that there were different kinds of vehicles that were spotted, people were setting up tents and all, right? So the model will be able to say that, okay, there has been some difference in the terrain, and the model is going to go ahead and raise out flags, and then you can just go ahead, a human can go ahead and they can just manually cross verify, right? So obviously AI has been a great help of humans as well. Artificial intelligence is a field of computer science that emphasizes on the creation of intelligent machines which can work and react like humans, right? Now, if you see AI, is exactly, see, artificial intelligence is nothing but the creation of machines that can work and react like humans. So if a machine is able to work and react like humans, then at the end of the day, a machine is able to help out humans, right? Now, if you look at this definition will not only contain, let's say, deep learning or data science problems, right? It can be anything. Even as I gave you the example, right? Even a robo vacuum cleaner, which does not leverage data science, which does not leverage deep learning, is considered as an AI product, right? Why? Because it is doing what a human can do, right? It is actually doing the job of cleaning, which was supposed to be done by a human, right? But if you see generally, I would say 70-80% of the use cases, or 70-80% of the AI based solutions that you have are driven by data science, right? A classic example being a self-driving car, right? Now, a self-driving car is what? A self-driving car is an AI-based product, right? How does it work? It works because now I have a deep learning model which is deployed, right? This model takes as an input the constant images that the car's front and back camera are seeing, right? So if we focus on the car's front camera, so let's say you are driving on a highway, right? And in front of you there is a vast stretch of land. The road is totally open, right? Now the image, whatever image you are, or whatever area you are going through, that image is being constantly fed to this model. When I say constantly fed, it is not that, let's say, 5 minutes apart, 1 minute apart, right? 10-20 images are being sent per second, right? Each and every second, your 10 to 20 images are being sent to the camera, and within every fraction of a second, a prediction is being made. So let's say you are traveling, and in front of you, there is a vast stretch of road which is totally empty, right? Now, this image, which is being fed to a model, the model is going to predict that the image is totally open. You can drive at your own speed. So let's say that you have gone ahead and you have set the cruise control to 100 kilometers per hour, right? So the car is going to go ahead and the car is going to maintain that speed, right? Now let's say this keeps on happening for a couple of minutes, and then you see a car in front of you, right? There is a car which is in front of you, let's say 200 meters in front of you. The camera is able to identify the car. As soon as the camera is able to identify the car, right now, in the image that is being fed to the model, it sees a car in front and it sees the car in the same lane as you are. Now, there can be predictions. Now, the model can either predict for you to switch lanes, or the model can predict for you to go ahead and decrease the speed. Now, all of this is dependent upon how the models are tuned. Generally, these self-driving cars, they don't switch lanes as uh, very quickly. What they will do is that they will adapt their speed according to the speed of the car in front of you. Now, let's say the car in front of you was traveling at a speed of 80 kilometers per hour. So your car is going to gradually adapt its speed to 80 kilometers per hour, right? Now, we are assuming that your car has cruise control, which can adapt its speed, right? So that is generally how your self-driving cars work. And this is a typical, a classical example of artificial intelligence, right? Because here, if you see, your car is doing the job of a human, right? Car driving generally is considered to be a human skill. But now these days, we are able to actually do that through computers as well, right? ADAS feature in car is nothing but ADAS, right? All the ADAS based features in the car are nothing but combinations of sensors and your AI models that we have, right? Sensors are going to provide the data to the model, and through that data, you go ahead and you make predictions, right? Okay, now examples of AI, if you see your Alexa, your Siri, your self-driving car, your drones, all of this is AI, right? Now, drone, if you see a drone is not exactly data science, right? A drone is not exactly deep learning. A drone is considered as just a AI product. How does it work? It majorly works through sensors, right? Because you are flying, you need different kinds of sensors. gyro sensors and all, right? So, but in most of the drones, in most of the basic drones, there is no deep learning, there is no data science that is applied, right? So your artificial intelligence is a broader term, right? If someone says AI, artificial intelligence, that is not going to imply deep learning, right? Then it depends upon what specific aspect of AI they are talking about, right? In Formula One, they calculate data, how car is behaving in each and every corner of the track. This is how it decides to set up the car, what their brake balance should be, front wing and all. Exactly, Atish. So see, the all of these sports, right? They have been collecting data from way too back, right? And they have been analyzing data as well. Especially if you consider sports like your car racing and all, right? Because there the risk factor is also very high, right? They are going to take into account the friction coefficient, whether it is raining, whether it is sunny, whether it is bright, whether it is humid. Everything is taken into account, and accordingly, the details are shared to the drivers, right? That's what I know. All right. So intelligence can be defined as one's capacity for understanding self awareness, learning, emotional knowledge, planning, creativity, and problem solving, right? Now, see, intelligence can be any one of these, right? So artificial intelligence can be any one of these skills that you have, right? Maybe a model that is able to learn automatically, maybe a model that can help in problem solving, maybe a model that has emotional intelligence. All of that can be considered as artificial intelligence. Yes. So that's there to collect the data, that's there to collect the data and then analyze the data at a later point of time. So actually, I did not know that these dummies are installed with sensors. Okay, now artificial intelligence is intelligence in machines, commonly implemented in computer systems using program software. Accordingly, there are two possibilities. A system with intelligence is expected to behave as intelligently as a human. A system with intelligence is expected to behave in the best possible manner, right? So just this is just some theory. At the end of the day, artificial intelligence is your intelligence in machines. Your objective can be anything. Your objective of the machine can be to do the job exactly like a human does, or your objective can be to do a job in the most perfect manner, right? So when we are driving a car, obviously our objective is not to drive the car as a human does, because if AI is driving the car as a human does, and it will continuously keep on pressing on the horns, honking the horns, pressing the brakes, switching lanes and all, right? So again, it depends upon the objective, right? Mostly the objective will be to do something in an optimized fashion, right? Okay, now what makes humans intelligent? Now, there are five different aspects. Humans are able to reason, right? Humans are able to learn. Humans have the sense of perception. They can do problem solving and they can speak, right? Linguistic intelligence, they can speak. Now, out of all of these things, right? Uh, Almost everything your AI or your deep learning models can do, right? Reasoning, your deep learning models, you can create deep learning models which can go ahead and which can say that, okay, this customer is going to churn because this customer was not given enough discounts. This customer is not going to churn because this customer likes these products that you are selling. So you can go ahead and keep on selling those. Learning, there are reinforcement learning models which can constantly update themselves, right? So let's say you built a model pre-COVID, right? And it was predicting whether your customers are going to buy different products or not, right? Now after COVID, once when the customer behavior started to change, right? Now let's say before COVID, people were not buying masks. After COVID or during COVID, people were buying a lot of masks, lots of sanitizers and all. So your reinforcement learning models can go ahead and they can adapt themselves as and when the distribution of the data is changing, right? Perception, your models like convolutional neural networks, which we are going to study in short span, right? Are models which can go ahead and which can identify objects, right? You can deploy these models to identify any kinds of objects, and they have the power, like they have the vision distance which is much more greater than a human, right? So depending upon the strength of the camera, you can have a camera which can go ahead and identify objects for, let's say, 500 meters, 1 kilometers, and so on and so forth, right? Problem solving, again, this will align with reasoning, right? So any kind of problems, if you structure the model to solve a given kind of a problem, it will be able to solve that. Optimization problems, right? Optimization problems are what? Let's say if you have to go from point A to point B, what is the best possible route for that, right? If you have, let's say, 10 technicians and you have 50 jobs that they have to do, how can you assign these jobs to these 10 technicians so that they are done in a efficient and the most fast manner, right? Linguistic intelligence, you have NLP models, natural language processing models, and your deep learning models as well, which are able to work with text data seamlessly, right? So all of your Alexa, Siri, all of these are nothing but linguistic intelligence, right? Okay. Now, growth of AI, if you see AI, now see, I have been in this field since 2011, and artificial intelligence, or to be precise, deep learning, started becoming very common after 2016, 2017. That was when your libraries like TensorFlow, Keras, all of these libraries actually came into existence, right? Not existence, but these libraries were adopted by the industry and people actually started using these libraries. Before 2016, 2017, around 2014, right? No, 2015, I was actually asked to build a deep learning model. I had gone ahead and I had spent 2 to 3 months in building the model from scratch, right? And I was not obviously able to do, I was able to replicate the exact logic of the deep learning model, right? But the efficiencies or the computational efficiencies that these models have, right? Models in Keras and TensorFlow and all, right? That is something that I was not able to achieve. So my model would run for days, right? And then it will give me predictions. But then around 2016, 2017, when we were able to import these libraries in Python, when I went ahead and I ran this model for the first time, the same code that I had created, which was running for days, I was able to run it within hours, right? So that is when people started actually using deep learning, because they had the avenues or they had the libraries which will go ahead and help them building these models, right? Now, see, every data scientist, now there are two kinds of job, right? Either you can be a data scientist or you can be, let's say, a statistical uh, uh, researcher, right? Now 99% of you would actually aspire to be data scientists, because that is what the corporate life is all about, right? As a data scientist, your goal is to leverage these libraries, which, let's say, go ahead and let's say you have a library which builds deep learning models, right? So as a data scientist, your objective will be to go ahead and use those libraries to build models. As a statistical researcher, your objective would be to create these deep learning libraries, right? So in I am assuming, since most of you are here to upskill, are here to apply for data science jobs, right? So most, whatever our requirements are, will be covered by these libraries. And because these libraries are pre-built, we don't need to go ahead and we don't need to build all of these complicated models from scratch. That makes life very easy for us, right? And hence, if you see, after 2017, 2018, the application or the adoption of AI has increased exponentially, right? If you see back here, the share or market in million US dollars was 2004 20 million, and right now it is close to 60,000 million, right? Not right now. For 2025, it is predicted to be around 60,000 million, right? This is so this is nothing but it is saying that what your intelligence, right? How your intelligence can be explained or divided, right? Or what kind of intelligence humans possess, right? Humans possess all of these different five kinds of intelligence, and all of these five kinds of intelligence, right? This is something that can be adopted or that can be mimicked by your deep learning models, right? That this slide only focuses on that aspect, right? Your reasoning, right? So your deep learning models are able to reason. They are able to tell you, let's say if I talk about customer churn, they can tell whether the customer is churning or not, or why this is happening, right? Learning, there are reinforcement learning models which can constantly adapt themselves. They can update the weights, they can update their rules as and when the distribution of the data is changing. Perception, there are image processing models, there are CNN models which help in identifying different objects. Problem solving, this is similar to reasoning, right? So any kind of problem, you will have to create your model in a way to solve a specific problem. If you're doing that, the model will be able to help you in doing that. Linguistic intelligence is more to do with NLP, wherein things like your chatbots, your Alexas, right, your Siri and all, uh, Google Translate, right, all of these things come into picture, and all of this is nothing but your deep learning models. The artificial intelligence, if we only focus on that aspect of artificial intelligence, which is data science, this can be divided into machine learning and deep learning, right? Two kinds of models, machine learning and deep learning. Now, the only difference between machine learning and deep learning is very similar to the difference between a let's say a diesel car, right? So if you take a diesel car or a petrol car, for example, and if you take an electric car, right? Now, the objective of both, right, your petrol, diesel, or your electric car is what? The objective is to transport humans from point A to point B, correct? But the internal architecture or the internal, let's say, composition of both of these types of cars is totally different, right? So in a very similar way, your machine learning and deep learning, these are two different kinds of models, right? Now, machine learning, you guys will be aware, machine learning comprises of all the different kinds of models like linear regression, logistic regression, your decision trees, random forest, SVMs, whatever, right? So any predictive model that you have that is not a deep learning model will be considered as a machine learning model, right? Let's try to understand what deep learning models are. Deep learning models are nothing but these are models which try to imitate the function or the functionality of the human brain, right? It tries to replicate how a human brain works, right? So if you would have studied biology to a certain extent, you would know that human brain, right, it consists of millions and millions of neurons, right? These neurons, the job of these neurons is to go ahead and is to fire. So let's say it depends upon the activity that you want to do, right? So let's say as a human, you want to go ahead and you want to kick a football. When you want to kick a football, there will be specific parts of your brain that are going to light up, right? These are nothing but some specific neurons in your brain which have been pre-trained, right? So maybe back in school, back when you were small, when you started to learn how to play football, right? So all your motor skills, all of those things, right, whatever skills you would have developed, right, all of that learning would have been saved in some neurons of your brain, right? Now, let's say 20 years later, you were walking in a park, you saw a football, kids were playing, the football came towards you and you had to kick that football, right? When you decide to kick that football, your brain or specific neurons in your brain are going to send out electric signals to the different parts of your body, right? So let's say to your leg, to your eyes, whatever. Now, whatever you have to do, all of this is governed by your brain, right? Now, in a very similar way, we try to go ahead and we try to imitate all the deep learning models, right? These are created by imitating exactly how the human brain works, right? Now, all of the details, that is something that we are going to study about. Obviously, that is the objective of this course, right? But for now, all you need to understand is that there are some specific models within data science which try to imitate the functionality of the human brain. These models are known as deep learning models, right? And the difference between machine learning and deep learning only this, that any model which tries to, which comprises of neurons, right? It means that it is trying to imitate the function of a human brain. All of these models will be considered as deep learning models. any other model that you have, right? So take a linear regression, logistic regression, decision tree, whatever, right? All of those models will be known as machine learning, because if you see from a functionality point of view, all of these models, nowhere they have neurons, or they are trying to emulate how the human brain works. They have their own different mathematical logic through which they are created. All right. Okay. All of these things we are going to study that later. I'm not jumping into the technicalities now. Obviously we'll be covering those, but right now all you need to understand is that deep learning is that part of data science, or those models in data science which try to imitate the functionality of a human brain. All right. Now if you see here, this is more exactly like uh, this particular slide will help us in understanding the differences between these four terms, right? AI, machine learning, deep learning, and data science. Okay, so let's get started with the orange box, right? Now AI. Now AI, as I said, artificial intelligence can be two kinds of models. One, let's say a drone, or let's say a robo vacuum cleaner, and other maybe a self-driving car, right? Or maybe an Alexa, right? All of this can be considered as artificial intelligence. Now, if you see in this example, if I look at, let's say, the drone or the robo vacuum, right? They will come outside the purview of your machine learning and deep learning, right? If I take the example of, let's say, self-driving car, your self-driving car will come somewhere over here, because your self-driving car is an example of AI which leverages deep learning models, right? Okay, so artificial intelligence is the broader bucket. Anything, any machine that makes the job of a human easy to do, or that replicates the job of a human, is known as artificial intelligence, right? Every deep learning model can be considered as artificial intelligence, but vice versa will not be true, right? A robo vacuum cleaner will not be a deep learning model, or will not be a deep learning product, right? Whereas a self-driving car will always be an AI based product, right? So that is the first difference. Now, if you see within artificial intelligence, we have the broader bucket, which is machine learning, right? Now, machine learning, if you see any models, any of these supervised learning models, unsupervised learning models, right, that you would have studied, all of those models will come under machine learning. Within machine learning, there is a specific set of models which try to imitate the functionality of a human brain. Those are known as deep learning models. Now, just like in the case of machine learning, you had a target variable, you had features, you were using these features to predict the target variable. Exactly like that in this deep learning models as well, you will have a target variable, you will have the features, you are going to use those features to go ahead and make predictions on the target variable. It's just that the approach will be different, right? Just like a petrol or a diesel car, right? Your objective is the same, that is to drive from point A to point B, right? But it's just that in an electric car, the functionality is different. Exactly like that in these deep learning models, the objective remains the same. That is, you have to make predictions on data, but your functionality, your internal functionality changes, right? That is deep learning. What is data science? Now, data science is kind of a very general term. Data science is anything, or let's say any job that you are doing that involves data, that involves the creation of these machine learning, deep learning models in order to solve a larger business problem, right? That is known as data science. So what we are doing. So let's say if a client comes to me and they say that I can see that there is a huge churn amongst my customers. I want you to go ahead and I want you to solve this problem. Now, this problem cannot just be solved by, let's say, deep learning, machine learning. For that, you need to have systems in place which are going to collect data. For that, you are going to need systems that can display whatever output your machine learning or deep learning models are giving, right? So deep learning, when you see, let's say, data science or deep learning, machine learning from a consulting point of view, these models are not sitting independently, right? Yes, these models help you in making predictions, but along with that, you might have a dashboard which is going ahead and displaying the predictions to your stakeholders. You might have a database like, let's say, GCP or PySpark, Hadoop, whatever, which is storing the data, right? All of that is known as data science. Okay. No, Gautam, it is vice versa, right? Just now I have explained this, that AI can be anything. Any machine that is simplifying the job of a human will be known as AI, right? But all ML can be AI, but all AI cannot be ML, right? The example being that a robo vacuum cleaner is not using any machine learning, but that is also an AI based product, right? Alexa is your deep learning, right? Alexa uses deep learning models. So if I give you an example, right? So let's say you buy a car, right? You buy a car in order to make some money. Now, is the car going to help you do that single-handedly? No, right? Because for that car, you will have to need a driver. Maybe that driver, you enroll that driver to, let's say, Uber, Ola. The job of the driver will be to pick passengers from their location, drop them to the destination, right? And do this time and again, right? So your car can be, you can think of the car as the deep learning model, but the car independently cannot help you in achieving a given objective, right? You need to have certain players along with the car as well, which are going to work together in tandem to go ahead and make a business outcome come true. Your business objective was to generate revenue through that car. If my business objective is to generate revenue through a deep learning model, I can create the deep learning model, but the deep learning model sitting independently will not be able to do anything. I need to have systems in place which are going to leverage that deep learning model, which are going to uh, gather data, which I need to pass to that deep learning model. The model will make predictions. The predictions will then be fed maybe to a website, maybe to a dashboard, maybe to an application, which will then be consumed by maybe by stakeholders, by my customers and all, right? So all of this is known as data science. Okay. So Prageet, right? So your question is correct, right? So see, in case of a robo vacuum cleaner, right, it is only leveraging sensors. It is not making any predictions. Why? Because the layout of your home generally remains the same, right? All it is doing is that it is leveraging the sensors and it is identifying an area, or it is identifying a cleaning plan that it needs to adopt, right? But in case of a self-driving car, your self-driving car can adjust its speed, it can decrease the speed, it can increase the speed, it can change the lanes, it can take decisions on its own. The robo vacuum cleaner is, at the end of the day, it's a predefined functionality, right? So in case of a robo vacuum cleaner, the rules are already fed by a human, by let's say someone. And all it is doing is that it is replicating those sets of rules. It is not improvising on them. The robo vacuum cleaner, let's say, when it sees that, uh, let's say the terrain has changed, right? So let's say in at your home, you have put something because of which, let's say, the vacuum cleaner might not be able to go through that. So what it will do is that, because it is fed with the rules that if you're not able to go through a particular object, you can go beside that, right? It is not going to improvise, but a self-driving car can take decisions on its own, right? So that is the difference between the vacuum cleaner and the self-driving cars. Robo vacuum cleaner, so I'm talking about simple robo vacuum cleaners. Right now, I believe there are robo vacuum cleaners which have cameras as well nowadays. Now, if you have a camera, you are able to include images. You are going to take input as images, and then you might be able to go ahead and make predictions. But I'm talking about basic robo vacuum cleaners, right? All they do is that they do a predefined job. Now we are going to go ahead and we are going to understand now. First, we will see machine learning, what happens within machine learning, and then just one second. Yeah, so this is machine learning, and then we will see what deep learning is so that we are able to compare between these two. Do freshers get jobs for the post of data scientist, or do they need experience? So you have data science jobs for freshers as well, Sushant, right? So we have everything. So you can get, see, depends upon the level of, uh, like, see, I've been interviewing freshers, I've been interviewing people with experience, everything, right? I'll be very honest. For me, experience, yes, see, there are different kinds of roles that we have, right? That companies have. A company might have a role of, let's say, 0 to 2 years experience. I have also rejected people who had 2 years of experience in data science, and I knew that they didn't have any knowledge, right? They were lucky to be in a company wherein they were actually working as data scientists, but they were not able to do anything with it. I have also selected people with 0 years of experience whom I know they would have done some certification from somewhere. But these people had gone ahead and they had done their due diligence, they had applied themselves, they had worked on case studies, right? So, see, in today's world, all of you, we are living in a space wherein if you want to do anything, let's say if you want to do a project on, let's say, tree-based models, no one is stopping you. There is huge amounts of data that is present online, right? You have Google data sets, you have Kaggle, you have so many sources, right? You can go ahead and download that data. So, and from a learning point of view as well, right? Now, the like getting stuck in a code error or something, now it is easier to bypass. You have chat gpt, you have so many forums which can help you in solving whatever errors or doubts you might have, right? So it is not that freshers do not get the job, but I'll be very honest, if you think that just doing a course, by doing a course you can land a job, I'll be very honest, that will not happen, because there are thousands and thousands of people who are doing these courses. But along with that, if you are doing, see, it will be 20%, the course will constitute 20% of your knowledge. The remaining 80% you can only get when you are applying yourselves, right? So you need to apply yourself after each and every session that we are doing over here. Once when we start with the hands-on, keep on applying yourselves. I will keep on guiding you. I can give you all the steps and instructions that you will have to follow in order to make it into data science. If you follow that, I can guarantee this, that you will be able to land a good job. Okay. So, all right. All right. Let's go through machine learning. So this will be kind of a revision for you, right? Now, machine learning around us, I think all of this should have been done before as well, but we'll go through this. Now, product recommendations, you would have been using e-commerce websites, Amazon, your OTT platforms, Netflix, and all your social media platforms, YouTube, Instagram, and all, right? So you would have seen that recommendations work very fast nowadays. As soon as you click on a product, similar products, or let's say complementing products, the website is going to recommend to you, right? All of that is nothing but machine learning, right? Alexa is once again an example of your NLP. NLP is natural language processing. Natural language processing is generally applied with machine learning models, because text data is very complicated to process, right? Along with the complicated text data, if you also apply a complicated deep learning model, then in that case your time complexity is going to definitely go up, right? So Alexa and all, they use a bunch of machine learning models, right? Movie recommendations, your once again Netflix, Spotify, all of these recommendations are nothing but your machine learning models that we have, right? If you watch a given movie, you start seeing recommendations of movies which are similar, or let's say actors which are similar, directors which are common, right? All of this is machine learning. Traffic prediction. So when you, let's say, put down like route from point A to point B, then the estimated time, right? Your ETA that you get, the ETA is generally not based on your current status, right? So let's say if you're aware with the dynamics of Delhi, and if you have to go from Noida to Gurgaon, right? Let's say 4 p.m. you are sitting in Noida, the map is going to probably show you 6:30 p.m. for Gurgaon. Why? Because at around 4 p.m. Gurgaon might not have a very high traffic, but by the time that you will reach Gurgaon, maybe 5:30, at that point of time, Gurgaon will have peak traffic, right? So when it goes ahead and makes a traffic prediction, it does not take into account the current status. It takes into account the status of different locations at the time when you are going to reach those locations, right? And all of this is nothing but machine learning. Machine learning, I think all of you guys will be aware, machine learning is a subset of AI which gives a machine the ability to learn without being explicitly programmed. Data, not models, is the key to machine learning success, right? Now, if you see, machine learning, right, is different from uh, let's say a robot. So I guess you guys would have, I'm not sure if you have that in your city, but we have those robot restaurants, right? Where a robot is going to serve food to you, right? How many of you are aware of that concept, or you would have seen that in social media reels and all? So do you guys think that that robot is actually machine learning, or that robot is actually, let's say, leveraging deep learning or machine learning? It's in India as well. It's in Jaipur, it's in Delhi, Hyderabad, maybe, yes, Bangalore. All right. So if you see, right, uh, next time when you see that restaurant, go ahead, go inside and see what the bot is doing, right? That is not machine learning. Why? Because all the movements, all the gestures that that particular robot is doing is fixed, right? There is a predefined path, right? There is a predefined path on which the robot can just walk around. The robot cannot walk around freely, right? So if, let's say, the robot can go from the kitchen to, let's say, if the restaurant has 10 tables, it will have different paths in arriving to the 10 tables, which are pre-fed, right? This is not, the robot is not able to calculate all of this automatically. The job of the robot is what? That a human is going to come and a human is going to put the food on the plate that the robot has, right? Instead of hands, the robot will have a serving plate, sorry, a tray, right? Now, whatever food is being ordered, a human manually is going to place that food on the tray, right? And then a human is going to press a button. That button will tell the robot on which table the robot has to go. The robot will go to that table. The people who are sitting on that table are going to either manually take down the dishes, or the waiter is going to take down the dishes. Now, this is not machine learning. This is what? This is just a bunch of instructions that are fed to a machine. If you see, what is machine learning? Machine learning is the ability to learn without being explicitly programmed, right? Any model, anything that can uh, like learn on its own, that is known as machine learning, right? This particular example that I have given is not machine learning. It is just a bunch of pre-fed rules, right, that are given to the robot, and the robot is just doing that. Exactly, Atul. Right? So be very, very clear between the differences of what machine learning might be or what machine learning might not be. Right? Is this clear to everyone what machine learning is? Now, the case studies that you would have done as well, right? You would have only fed data along with the target variable to the different models. Did you tell the model that this customer is churning because of this, or this customer is churning because of that? The model was able to identify that on its own, right? That is what is machine learning, right? As a human, your job is to only give the resources to that particular model. The model will automatically identify patterns and trends, right? Now, what is machine learning? Machine learning algorithm is trained using a training data. Now, this is just the approach. A priori MBA, yes, Raj, that is correct. Now, I think the approach should be clear. We train the model on a training data. When any new data point arrives, right, then we make a prediction using that, right? So what is the how does these machine learning models work? Now, let's say if my stakeholder comes to me and they say that I want to create a model which will effectively predict whether a customer will apply or accept a loan or not, right? How can I do that? How can I know this for future customers? I need to have the data of my historical customers. I will go ahead and I will take that data of my historical customers. Let's say this particular bank had reached out to 1 million customers in the past for loans. And out of those 1 million, let's say 1,000 customers would have accepted the loans. Now, this data I would go ahead and I will pass to any machine learning model. Now, the machine learning models, the job of the machine learning model is to train itself on this data, which is known as training data, right? Does the job of the model gets over as soon as the training is done? What do you guys think? Once when the model is trained, is that it? Or does the model need to perform in anything else as well? No, right? What is the prior objective? The prior objective is to predict. So the main objective of the model is to make predictions on unseen or on future data. Now let's say for the same model, I go ahead and I give my let's say inputs. I give my details to the bank's website, right? What will happen? The model will take my details, right? It will go ahead and make a prediction that this person, the probability of this person applying for a loan is 95%. Now the bank can proactively reach out to me. Although this does not happen, you will still be getting 10-20 calls daily, right, from customer care teams and all, because they want to like be after you. But then a model is actually supposed to do that, right? So what do? We train using the training data. When any new data point is encountered, the model makes a prediction, right? Now the prediction is evaluated for performance, and if the accuracy is acceptable, machine learning model is deployed, right? Now, generally, you would have worked with the training and the testing data. Training data will be used to train the model. Testing data would be used to test the performance of the model, right? And if the model's performance is adequate, if you are good with the model's performance, you will go ahead and you will deploy that model, right? I hope this is clear, all the bunch of rules or all the bunch of steps that are written on the left hand side. All right. Now the different types of machine learning models, can you guys tell me the differences between supervised and unsupervised? All of this should be clear. What do we mean by supervised models? Supervised learning? Exactly, right? So supervised learning models, can you give me some examples of supervised learning models? Right? Yes, decision tree, fraud, no fraud, logistic regression, all of this, linear regression, all of this will be supervised. What are some of the examples for unsupervised learning? KNN is also supervised. Unsupervised will be k-means. Yes, clustering. What else? Hierarchical clustering. PCA, exactly. LDA, all of this is your unsupervised learning, right? Very good. Now, what is reinforcement learning? Now, reinforcement learning are uh, like is very similar to supervised learning. These models, they just have a feedback loop from the output to the input, right? So if let's say the output is incorrect, this feedback will be given back to the inputs and the model will retrain itself. So reinforcement learning is very, very similar to supervised learning. You have the target variable as well. The only difference is that when in case of supervised learning, the target variable is then not connected to the inputs back, right? In case of reinforcement learning, because we want the models to constantly update themselves if and whenever the customer behavior is changing, in case of reinforcement learning, there is a feedback loop as well, right? So these are the three different kinds of your machine learning models that you have, right? Time series will come under supervised learning only, right, Raj? Because you have a target variable. Your target variable means that it will be supervised learning. Recommendation system is also supervised learning, right? Now, just these are examples of all three. I think you guys are clear on this. Supervised learning is you will train the model that this is an apple, this is an orange, and then the model is going to predict, okay, this is an apple, this is an orange, right? What are the use cases? Spam, no spam can be one use case for supervised learning. What kind of a supervised model will this be? What is the exact name for such kinds of a model when I'm building, when my model predicts either true or false? Classification, right? Exactly. So this will be classification. This is supervised learning, classification. Unsupervised learning will be when we are trying to identify patterns in the data, that is k-means clustering and all. So my model, now in unsupervised learning, there is no target variable that is given, right? So there will be no target variable. My model needs to automatically identify patterns. Now, if there is no target variable given over here, what my model will do is that it will calculate similarity. Now it will see that there are different points which are very similar. So it will say that, okay, this is very similar, this is similar, this is similar, and this is similar, right? It will say that, let's say this is similar, this is similar, and this is similar, right? Ideally, it should go ahead and it should be able to group all of these points in similar clusters, right? So that is what the objective of your unsupervised learning model, specifically clustering, will be. Right? Exactly. Now, if you see unsupervised learning, if you're applying clustering, the output will be this, right? Use case, you can use clustering for recommendation systems, for building a recommendation systems. Now, this is a very basic recommendation system. Ideally, this is not how your complicated recommendation systems are built, right? Your complicated recommendation systems will take into account what the customers have watching. They will take that as the target variable, and then they will try to identify items or products or movies which are similar to the kind of products that the customer has been purchasing or watching, right? Now, reinforcement learning, what is reinforcement learning? As I gave you the example, right? In case of reinforcement learning, these are slightly different models wherein we actually either reward or penalize the model. We will reward the model if it makes a correct prediction. We will penalize the model if it makes an incorrect prediction. So let's say if there are 1000 points that the model had to predict on, and out of 1000, let's say 800 it was able to predict correctly. So it will be given a reward for those 800. For the 200, it will be given a penalty. Now, the objective of these models is to maximize the reward, right? So if let's say the reward is of +1 and let's say a penalty is of -1, if the model goes ahead and makes 800 correct predictions and 200 incorrect, then the total reward for the model will sit at 600, right? 800 minus 200. Now the model will try to maximize this value. This 600, it knows that the maximum it can get is 1000. So it will keep on reiterating itself until it is able to maximize it, right? So these are reinforcement learning models. I know that you have not studied any reinforcement learning models, but that's okay. Reinforcement learning is not very, very common, right? Reinforcement learning actually has now been taken over by deep learning, right? So what reinforcement learning was used for previously, now people are actually using deep learning for the same things. All right. A use case, self-driving cars. Now, self-driving cars, earlier it was reinforcement learning, but as I said, right now, all of these things have been replaced by deep learning. So now whatever we will be studying in this in this course, right, all of that will be will help us in understanding how all of these use cases actually work, right? Now, self-driving car, but if you see in case of a self-driving car, the training happens in such a way that now see these self-driving cars that you are seeing, right? The XUV 700 or let's say the Tesla cars and all, right? Now, all of these cars, the models that are deployed in all of these cars, right? These are deep learning models, right? Now, obviously, these deep learning models, just one second, guys, I'll be back. Right, right. So, if you see, right, what I was talking about is that these self-driving cars, when the models would have been trained, it's not that these cars, let's say the test car on which the model would have been deployed, the model would not have been perfect from right from day one. There would have been so many testing events, right, wherein the car or the model would have been exposed to different situations. On the first iteration, maybe the car was not able to handle itself as expected, right? Then the model retraining would have happened, right? So let's say during a situation wherein the car was supposed to apply its brake on seeing a dummy, the car did not, and the car crashed into the dummy, right? Now, once again, the model would have been retrained, right? So the feedback loop will tell the model that, okay, this is not what was expected to do, right? You are not expected to hit on that dummy, right? Now, then again, so there will be continuous retraining of the model. And now the final product that you are seeing, the final car that you are seeing, this car would contain a model which would have been tested thousands and thousands of times. And even today, right, when the cars are actually there on the road, real life data or actual data is being collected through the cars and is being given back to these companies, Mahindra, Tesla, whatever, right? And these companies are constantly upgrading the models, right? So what happens is that there will be continuous learning for all of these AI based or these deep learning models. There will be continuous learning wherein the models will continuously try to evolve and continuously try to better themselves. Okay. Now, these are some examples. Within supervised learning, obviously, you have linear regression, polynomial regression, decision tree, random forest, and all, right? Within clustering, you can have HVD, PCA, K-means, right? Within unsupervised, not within clustering, you will have all of these. Your association rules as well will come here within unsupervised learning. And then you have reinforcement learning, right? So I think all of this you guys have covered. These are some of the projects that you can explore within machine learning, but we will move on to deep learning. All right. Now, if you see the limitations of machine learning algorithms require good amount of training data. Now, it's not that deep learning models do not require a good amount of training data, but if you give huge amounts of training data, right, to the deep learning models, the model's accuracy and all will be much better as compared to machine learning model. Error diagnosis and correction can be difficult in case of machine learning models. Error diagnosis, identifying why the model is not able to perform, all of this can be difficult. Lack of creativity. If you see, machine learning models are hardwired, right? You cannot do any changes to a logistic regression model. It will work as it is defined to work, right? Whereas if I talk about deep learning, you will see in a few days' time that deep learning models are totally customizable, right? If you feel that the model is not doing a good job with 2 layers, you can add 3 layers. If you feel that the model is not doing a good job with 500 neurons, you can add 1,000 neurons, right? So the idea or the customization will be there. In case of deep learning models, you can customize these models depending upon the kind of problem that you're looking to solve, right? Time constraints in learning as it learns through historical data. So your machine learning models are not able to, let's say, extract all the information effectively out of the historical data, which your deep learning models can. The way these deep learning models are created, because of the fact that they work or they imitate the functionality of a human brain, they are able to actually extract more juice out of the data as compared to your traditional machine learning models, right? And that is where deep learning comes into picture, right? And that is where we'll try to understand deep learning. Now, see, I'll be very honest over here that it's not that machine learning is not good, right? Or it's not that the deep learning is the best. it always depends upon the use case you are looking to solve, right? In most of the cases, if I talk about my 12 years of experience, 80% of the projects that I have done are around machine learning still. Only 20% will be deep learning. Why? Because the 80% of the requirements that I have had were more suitable for machine learning projects, right? In most of the cases, your clients, your stakeholders, they are not looking for a very complicated model. They are looking for a model which they can take and they can deploy easily. Machine learning models are very easily deployable, right? Because they are smaller, they are not as complicated. But then there will be specific use cases. So if I give you an example, back in 2021, I had built a recommendation system for a company known as Verizon, right? Now, Verizon at that point of time had 80 million customers. Now, building a recommendation system, an accurate recommendation system. Now, they had recommendation systems which were built on machine learning models, but they were not performing very effectively. So then what we did was that we proposed to them that we can build a deep learning recommendation system, but obviously the cost will be high, right? So, but Verizon being a product company, they had the money, they had the resources, they went ahead and approved that particular project, right? Now, this was a situation, this was a typical situation wherein deep learning actually outperformed the typical machine learning models because we had 80 million rows of data. There were limitations were that memory, right? So we had to work on 1000 GBs of RAM, right, in order to just run the deep learning model even once, right? Our model training took close to 5 to 6 months. I'm talking about entire iterations, right? If we would have run the model 100 times, the entire running took close to 5 6 months. But once when this model was deployed, it actually outperformed the machine learning model in a very clean way, right? And till date, they are using this deep learning model, right? So it depends. If someone comes and asks you that what is better, machine learning or deep learning, your answer cannot be deep learning or machine learning. Your answer will be depends upon what you are trying to solve. If you are looking to uh, create a, or if you're looking to have a model which is simple, which is easy to understand, which you can productionize, which can give you real time predictions, it will be machine learning. If you're looking for a model which can solve a very complicated problem for, let's say, an unreasonably large number of customers, right? And you are looking for accuracy along with that as well, then probably deep learning is your model, right? Okay. Now, introduction to deep learning. Now, if you see, deep learning is a part of machine learning based on learning data as a representations, as opposed to task specific models, right? Now, if you see, your machine learning models are task specific, right? That is, your classification model will only work for classification problems. Regression models will only work for regression problems. That is not the case in case of deep learning. In case of deep learning, it depends upon you how you customize the activation functions, how you customize the layers, how you customize the neurons. All of this actually depends upon you, that how you make the model or the architecture of the model totally depends up to you. Right? Krunal, ML, not that much. ML can still work with, see, it depends upon uh, machine learning models per se are not very heavy, right? But let's say if you build a machine learning model on 10 million data points, then obviously you will need high computing powers, right? If I talk about deep learning, if you build the same model for 10 million customers using deep learning, maybe you need twice the amount of processing power because the 10 million data will also require memory. The deep learning model as well will require a good enough amount of memory. So machine learning models per se are not very heavy, but it depends upon the size of the data that you are working with. The output layer is the layer that gives you the output. Over here, if I have 4 neurons, it means that there could have been 4 outputs. So this could have been a classification problem containing 4 different classes, right? This center part is the deep neural network, right? This is the heart of the neural network, which goes ahead and which identifies the different patterns, right? Now, for example, if you see this input image, if I had this image, right, what the neural network does is that the neural network tries to identify different features, right? It will try to identify different vertical, horizontal, all the features, and it will try to reconstruct the face, right? Don't get worried about this example as of now. I will be explaining these details very slowly to you, right? How exactly the internal calculations happen, that is obviously the objective of this course. So we'll be going through that slowly, but the architecture looks like this. Now, if you see, this is why this is called a deep neural network. If you look at the number of connections, right? Each and every neuron from the input layer is connected to the neurons in the hidden layers and all, right? Hidden layers, input layer, output layer, neurons, activation functions, all of this, I am not starting right now. We will be starting with this tomorrow gradually, slowly, right? One by one, I'm going to introduce each and every concept, and then we are going to tie them up together slowly. Okay. But this is how your deep learning models generally look like. The architecture, this is how the architecture looks like. Okay. Coming to the uses, now why deep learning? If you see, as in when your amount of data exceeds, right, your machine learning models beyond a certain point of time, their performance is going to stabilize. So let's say if I give I give 50,000 rows to a decision tree model, it gives me an accuracy of 70%. Let's say if I give 100K rows, my accuracy increases to 80%. Let's say if I give 200K rows for machine learning model, my accuracy might cap at 80%. Right now, even if I'm giving 1 million rows, the accuracy might be 80% only. But if I do the same thing with deep learning models, the deep learning models will keep on extracting rules and patterns, specific rules and patterns, and they will try to keep on increasing the accuracy. The accuracy will keep on increasing as and when the amount of data that you are passing to these deep learning models is increasing. Okay. Yes, Raj. So all of that is due to forward propagation, backward propagation. All of that is something that we'll be covering. But yes, this is because of the fact that the deep learning models deal with error in a better way as compared to the machine learning models. Okay, now applications of deep learning, your speech recognition, it is used there. Self-driving cars, deep learning, obviously, your self-driving cars could not have come into picture if not for deep learning models. Automatic machine translation, your Google translation, all of these things, right? Speech to text, text to speech, all of this is deep learning. Your visual translation, you would have seen, we have apps these days wherein you, if you, let's say, click a particular image, it will be able to give you what text that particular image contains, right? So all of that can be done through deep learning. All right, so let's get started with the architecture now. See, this diagram that we are seeing on the right hand side. Let's try to understand what this means, right? First of all, we need to understand what this particular architecture means, right? What are the different layers? What are the different neurons and all, right? So every neural network, right? Any neural network that we create will have three types of layers, right? The first kind of layer that they will have will be the sets of features which are known as your input layer, right? So if you see, if you have, let's assume 20 features or 10 features in your data, then your neural network's input layer will contain those many number of neurons, right? So if you see over here in this example, it means that this particular neural network is taking in as an input three features, right? Now these three features can be anything, right? Then moving on to the far end, you have the output layer, right? The output layer is the layer that will give the output, right? Now over here, the output layer contains two neurons. Now, if your output layer contains only a single neuron, that means that it is a regression problem that the neural network is solving. If it contains more than one neuron, that is two, three, four, right, then it means that it is a classification problem. Why? Because in case of a regression problem, the single neuron is able to attain the continuous range of values, right? Whatever it wants to take. The neuron will be having a continuous function which can give it any continuous value, let's say in the range of 0 to 10,000, 20,000, whatever, right? But when it is a classification problem, or let's say that let's assume that the target variable that you have has two unique values, right? So let's say the first value is it will rain, the second value is it will not rain, right? Then in that cases, you need to assign two separate neurons to the output layer, right? Now, all of these things we need to define when we will be building these neural network models. After looking at the data, we need to define the size of the input layer. We need to define the size of the output layer. All right. So these are your inputs and outputs. Now, at the center, these two layers that you are seeing, right? These are known as your hidden layers of the neural network. This is the brain of the neural network. This is where all the calculations, all the pattern extraction happens, right? Now, there are two things to it. Hidden layers, if you see the number over here, there are two hidden layers, right? It's not that all the neural networks will contain only two hidden layers. They can contain one, two, three, four, five, whatever, right? Now, this is a hyperparameter that we need to define while building the neural network. It is your choice. It is up to you how many layers you define, right? Just like how many layers, how many neurons each and every layer will have. That is also customizable, and that also needs to be defined by the person who is creating the neural network, right? So this neural network that you're seeing, this will change if, let's say, my input features are not three, but five. As soon as my features become five, my neurons for my input layer will become five, right? If, let's say, my output variable was a multi-class variable, which was telling me, let's say, whether the size of a t-shirt is high, medium, or low, right? So in that case, it will have three neurons, right? One for high, one for medium, one for low. Every neuron is going to come up with a probability for each of the values that are there, right? So let's say for a given t-shirt, the probability of high is 80%, medium is 10%, low is 10%, right? So all of these three neurons are going to give you each value, right? One corresponding to high, one corresponding to mid, one corresponding to low. How the probabilities are coming, that is defined or that happens inside this particular part, that is the hidden layer architecture of the neural network. Okay. Now, if you see, the term deep usually refers to the number of hidden layers in the neural network. Now, for if I talk about ChatGPT, right now, ChatGPT is a model that is built on around 8 billion parameters, right? 8 billion parameters. It has greater than 100 layers in between, right? So these layers that you are seeing, hidden layers, ChatGPT model or models which are very, very complicated, models which are, let's say, created on image data, video data, and all, these models will have a high number of hidden layers because extracting the patterns that are there in the image or in the unstructured data is a complicated task, right? Hence, these models are also known as deep learning models, right? As in when your hidden layers go on increasing, right, your model complexity goes on increasing. Hence, these models are called as deep neural network, right? Traditional neural networks contain only 2 to 3 hidden layers, while deep networks can have as many as 150, right? Now, what do we mean by traditional? See, when you are working with normal structured data, right? So let's say when you are working with data for a bank, when you're working with data for a retail store, when you're working with data for a telecom store, right? You will probably have structured data. Do you guys know the difference between structured and unstructured data? Right? Yes. So structured data is tabular. Unstructured data can be anything, can be image, can be text, can be video, right? So see, the beauty of structured data or the simplicity of structured data is that even if I have million and billions of customers, my data structure, right? Let's say if I am collecting 100 different features, right? These exact 100 features will be populated for all the million, billion, whatever customers you have, right? And ideally, the data type will remain the same. If age is, let's say, integer, it will remain integer. If, let's say, Gender is object, it will remain object, right? Querying is easy, but apart from that, right, extracting insights or extracting patterns from numerical data is quite easy. So for your traditional neural networks, that is your problems which pertain to structured data, right? You will be able to solve any problem in the range of 2 to 5 hidden layers, right? 2 to 3 might be slightly less, but 2 to 5 hidden layers, you should be able to solve any kind of problems, right? But when it comes to unstructured data, that is where we might need to go as high as 100, 150 layers, right? But that is something that we'll talk about later. But the concept of deep neural networks comes from only this particular aspect. That is, your number of hidden layers can be customized to as much as you need, right? Deep learning models are trained using large sets of labeled data and neural networks architectures that learn features directly from data without the need of manual feature extraction, right? Now, one thing that is quite easy in case of deep learning models is that if you remember, in case of your machine learning models, you would be expected to do some kind of feature creation, right? Let's say if you have basic features like spend, quantity, visits, you might be expected to create features such as spend per quantity or spend per visit, right? Or let's say average quantity, average spend, average visits, things like that, right? Now, in case of neural networks, all of that is not required. What neural networks do is that, let's say if you have fed in 10 features, right? Neural networks will try to create as many combinations of these 10 features and see if the combinations that are coming out are helping you in predicting the target variable or not, right? So the architecture of the neural network is created in such a way that it will go ahead and it will create linear plus non-linear combinations of your input features, right? So let's say if I give in 3 features, right? Spend, quantity, and visits. The different neurons in the neural network they will go ahead and try to create different interactions between these 3 features, right? How that happens, that is the next example that I'm going to take, right? But that is an easy part with neural networks, that feature engineering is per se not required as much, right? All you need to ensure is that your data is clean. Your data does not have has, let's say, missing values, outliers, incorrect values, and all. If that is fine, you can feed in your data to the neural network, and the model will take the responsibility of creating any interactions of your input features that might help you in predicting the target variable. Okay. All right. So now let me give you an example of what do we mean by when we say or an example of how exactly neural networks work, right? Not exactly, but a simple example of what generally happens, right? Now, let's say we build a model that will go ahead and predict whether a house, or let's say that will go ahead and predict the price of a house, right? So the objective over here is to go ahead and predict the price of a house. I will take this particular architecture only. We'll consider 3 features, right? Let's say for the different kinds of houses that we have 3 features, right? One is the area, right? Then we have the location, right? Then we have the age of the property. All right. So I have 3 features: area, location, and age. And now if you see how, if you focus on this image, right? Or if you focus on this architecture of the neural network, now neural networks are also called dense neural networks, right? Artificial neural networks, dense neural networks, deep neural networks, all of these things imply the same, that you are working with a neural network. Okay. Now, why are they called dense? If you look at this, every neuron, right? Every single neuron that is present in this particular neural network has a connection with every preceding or succeeding neuron, right? Now, if you take a look at this neuron, this is connected with this orange one, or let's start from here. If you take a look at this neuron, right? This is connected from this neuron. This is connected from this neuron. This is connected from this, and this is also connected from this neuron. Also, if you go back one step, this particular neuron gets a connection from all the three previous neurons as well, right? So that is why, and that is what makes these neural networks as dense. Why? Because every neuron has a connection to each and every preceding and succeeding neuron. Okay? Yes. Right? Now, let's go back to our example. The data that we have contains the area, the location, and the age of a given property, right? Now, on the basis of this, we have to go ahead and we have to predict the price of this house, right? So in this example, all you need to do is that instead of two output neurons, there should have been only one single output neuron, right? Just assume that there is only one single output neuron over here, not two, right? Okay. Now, see, what will happen is that, let's say I have 100 rows of data, right? I have 100 rows of data, which corresponds to 100 different houses. I have 100 houses. My first row, let's say, contains, for some given house, it contains the area, location, age, and it contains the target variable, that is the price. Okay. Now, what happens in case when a neural network trains itself is that one by one, each and every row of the data is fed to the neural network, right? Now, in this particular neural network, what will happen is that in the first iteration, the first row of the data will go into the neural network. Now, let's assume that the first row of data, the area of the house was, let's say, 1000 square feet, right? The location of the house was, let's say, Noida, right? For example, and the age of the house was, let's say, 5 years, right? The house was 5 years old. So what will happen is that this data will be fed through this neural network, and the neural network will try to adjust its weights, right? I'll tell you about everything, how the weights adjustment happens and all. For now, let's just go through this example. Okay. Inputs are columns. Inputs are your features. Yes. Right. Now, see, if you focus on housing, or if you focus on how the price of houses are going to vary, there can be so many aspects, right? Now, a simple logic is that if the area is increasing, obviously the price will be higher, right? That is a very simple logic. Let's say if the area is 500 square feet, the price might be low. If the area is 1000 square feet, the price might be high, right? For your most of the houses, let's say for 80% of the houses, it might happen that as and when the area is increasing, the price is also increasing, right? But this also depends upon location, right? Now, let's say if the location of the house is Noida, maybe the price might not be as much. But if, let's say, the location of the house is South Delhi, right? Or let's say Central Delhi, then maybe area might not be a concern. Maybe even a smaller house, even a house which is, let's say, 500 square feet, might be selling for 1 crores or 2 crores, right? Then if you overlay the third factor as well, that is age. Now, generally, as and when the age of a house or age of a property goes on increasing to a certain amount of time. So let's say till the point of time that the property, let's say, is 20, 25 years old, maybe the price will keep on increasing, right? Because you have bought a house. Obviously, as and when the age goes up, the price of the land is going to go up, and the price of the property is also going to go up, right? But it might happen that after a certain point of time, let's say you are investing in a flat, right? After, let's say, 25 years, 30 years, the value of the flat starts to go down, right? So I might have a combination of, or I might have an interaction with age, wherein, let's say, if the age of the house is in the range of 0 to 30 years, the price might be increasing. But if the age of the house is in the range of 30 to, let's say, 50 years, 60 years, then the price might be going down, right? But then there comes one more equation, right? So let's say I have a property which is greater than 100 years old, right? Now, this property would ideally be a historical property. Now, if the property is historical, it doesn't matter what the location of the property might be. It doesn't matter what the area of the property might be. This property might sell for a very, very high price. All right. So now, let's try to see how this neural network will try to capture these patterns, right? Now let's assume for the general houses, for my 80% of the houses where I know that it's a simple fact that when the area will be high, right? When the area will be high and the location will be, let's say, a specific location, right? So let's say when the area is high and the location is South Delhi, right? The the price of the house might be, let's say, in the range of 2 crores to 5 crores, right? Let's say when the area is high, right? I am taking the second example. Now, once again, the area is high, right? But the location is not Delhi. The location is, let's say, Noida, right? Now, the price of the same property might be in the range of, let's say, 1 crores to 2 crores, right? Or let's say 50 lakhs to 2 crores, depending upon the area of the house, right? The third case, let's say I have a property, right? There comes a property wherein the area is low, the location is low, but I know that the age of this property is, let's say, greater than 100 years, right? As soon as I see that the age of the property is greater than 100 years, I know no other variable is playing an important part. By default, my property is going to go for a very, very high price, right? Then I might have one situation wherein irrespective of the location, irrespective of the area or age, my house is selling for a low price only. So let's say that there is a slum area, right? Uh, let's say in Delhi, there is a slum area and I have houses there, right? And these houses, irrespective of whether they are 200 square feet, 500 square feet, 1000 square feet, they are not going to sell for, let's say, more than 20 lakhs, 25 lakhs, whatever, right? So now the neural network, if you see over here, it is trying to extract all of these patterns from the data. Now, anytime a house comes that belongs in South Delhi and that has an area of, let's say, greater than some specific range, right? Let's say area is greater than 1000 square feet, right? This particular neuron will get activated, right? This particular neuron will fire. All the rest of the neurons are not going to fire, right? Okay. Let's say for some other data point, what happens? You get a property which is located in a slum area, right? So as soon as I see that the location is, let's say, some specific locations of Delhi, which might be considered as slums, I know that this neuron is going to fire. Whenever this neuron is going to fire, the neural network will actually go ahead and try to model similar interactions and patterns and will try to predict the price of the house as a smaller value, right? Now, all of these things the neural network will learn from the data only, right? But this is how generally your neural networks try to extract the patterns and all. And this is how the neural network is very, very similar to how the human brain works, right? Now, if you see the human brain as well, when you do a specific job, right? When, let's say, you are cooking, there will be a different part of neurons in your brain that are going to fire, that are going to send instructions to the different parts of your body. When you are, let's say, driving a car, different sets of neurons are going to fire, right? Now, see, over here, this is a very small neural network, but once when you explode it to a real size, right, a neural network then is able to capture or identify each and every aspect, right, of your data, right? Any small patterns, right? Even very, very small patterns, right? So now if you see this, the age of the property being greater than 100 years, this might be less than 1% of your data. But even for this, the neural network will try to extract patterns and it will keep a neuron specifically for those properties where the age is greater than 100 years and these properties are historical in nature, right? Let's assume that you also create additional variables. Let's say that you have a variable that whether or not there has been any suicide in any of the apartments. Now, irrespective of the fact that your house is 2000 square feet, 5000 square feet located in South Delhi, North Delhi, wherever, right? The neural network, if the neural network is able to identify this pattern, that whenever this particular variable is true, that let's say someone had committed suicide from a particular property, it knows that the value is going to drop, right? Abhishek, so what I'm trying to tell you over here is that the hidden layers, right? They try to combine your input features, right? They try to go ahead and they try to create interactions. Now, if you see over here, this first hidden layer neuron is a linear combination of area and location, right? The second neuron is once again a linear combination of area and location, but for a different sets of values, right? So your hidden layer neurons are trying to create interactions of your input variables only, right? And through that, they are trying to see how your target variable can be predicted. All the input layers are independent to each other. No, Sushant, they are not independent, right? If you see, they are connected to each other. Your See, input layer is only one, first of all the input layers, you don't have more than one input layer, right? If you're talking about neurons, so all the input neurons are independent. Ideally, see, that is the assumption. If you are feeding in any features which are correlated, then they will not be independent, right? Okay, you're saying interdependent. So interdependent, once again, if you are feeding in features which are correlated, then they will be dependent on each other. If you're feeding in features which are not correlated, then they will not be dependent on each other, right? All right. Any questions on this example? Now, once again, I will reiterate, don't worry about the complications as of now. I am gradually moving into things, right? If you want, I can take it one step higher and I can get into the technicalities right now. But I feel that if we go step by step, I think it should be easier to understand. So that's a good catch, but I will tell you why it is not, right? Now, what happens is neural network tries to capture two kinds of interactions. The first interaction that it will capture will be a linear interaction of the variables, and that you are correct that will be very similar to a linear regression model. But then comes the concept of the function, right? The function that you were talking about yesterday as well, right? Your previous trainer would have taken you through those, the sigmoid function, the tanh function and all, right? ReLU and all. So the activation function's job is to introduce non-linearity, right? I will be explaining all of these things. Right now, I have not gone into that, but your neural networks are a combination of linear plus non-linear transformations of your input features. Okay. All right. So let's move forward then. All right, now let's move forward. Now, this is the same explanation. A neural network is a computing model whose layered structure resembles the network structure of neurons in the brain with layers of connected nodes. It can learn from data, so it can be trained to recognize patterns, classify data, and forecast future events, right? Now, if you see the same thing, input nodes, your hidden nodes, and your output nodes. Hidden nodes can be any. The hidden nodes of a neural network is what corresponds to the human brain, right? Totally random, right? Let's say you want to predict whether the customer will buy a product or not, and you have a variable which is, let's say, the color of the t-shirt that the customer is wearing. So obviously this feature will not help you. So ideally you should not be passing on those variables which are not important. So for that, during the EDA, you should go ahead and you should exclude the variables which are not important, right? Feature engineering is automatically done. See, feature engineering, what I meant by this was that generally you are expected to create additional features. But EDA is more about eliminating missing values, taking care of outliers, eliminating columns which are totally random, right? So let's say if you have a column which is country and for all your customers, the country is the same, right? So this column has zero variance. If the column has zero variance, even if you pass this column to any model, it is not going to help you. So ideally, in an ideal world, if you're a good data scientist, you will first spend some time with the data, clean the data up, only consider those features which you feel might be important. At the end of the day, let's say 20 features you select, out of those 20, only 10 are coming out to be important. But at least you would have gotten rid of variables which you could be very sure that they were not important, right? So that is something that you need to do in the EDA process. Mostly, this is not feature extraction, right? This is EDA, getting rid of unwanted variables, doing your missing value imputation, doing your correlation check. All of this, I'm assuming, would have been taught, right? So that is something that you will still have to do. What exactly happens? Now, one more example is, let's say you have the images of dogs and cats. The neural network will try to identify the different patterns, right, within these two kinds of data points. Now, let's say for a cat, it sees that the tail is more fluffy, that the face is more rounded off, right? The ears are, let's say, upright, right? Let's say for a dog, it sees that the tail is not as fluffy. The tail is, let's say, straight. The face, let's say, is not round. It has a snout. The ears are, let's say, droopy. The nose is, let's say, big and black, right? So the neural network will try to identify all of these features, and on the basis of that, it will classify any image that you give. It will classify that whether it's the image of a cat or a dog, right? Now, this, what you are seeing over here, this is a CNN. This is a convolutional neural network. Once when we'll be done with our ANN, right, then the next topic that we need to study are CNNs, right? So we will be proceeding. The first kind of neural network model is ANN. ANN model is used to work with only structured data, right? The second model, once when we would have done ANN, the second model would be the CNN, which will be the convolutional neural network. The convolutional neural network generally works very well with unstructured data. That is your image data, your text data, video data. I hope this is clear to everyone that if we are able to understand the functioning of a single perceptron, we should be able to understand, or we should be able to apply the same to an entire neural network, right? Because a neural network is nothing but a combination of multiple perceptrons, right? So if your artificial neural network looks like this, right? Can you guys tell me in this, what can we consider as a perceptron, or how many perceptrons can we have in this particular image? If the condition is that a perceptron should has both input and output, then how many? 3, right? Exactly. So if you see, uh, one perceptron can be this, because this neuron is connected with two input layer neurons and giving one output. One can be this and one can be this, right? Now, if you go ahead and pick any one of this separately, that will become a perceptron. So that is what we'll be doing over here, right? Let us first understand the architecture of our, okay, this is just some biological neuron and all, right? So this is nothing but how the human brain works. In case of a human brain, this is not important. This is just some biology for you. But what you need to take from this slide is that in case of a human brain as well, right? You will have a neuron, right? You will have neurons, you will have perceptrons, right? The objective of a perceptron is to send a signal, right? And it sends a signal by taking it some inputs. Now the input will be what? The input is, let's say, your eyes. So let's say you are driving, and when you're driving, you see something in front of you. So your eyes will send in the signal that there is an object in front of me, right? As soon as the signal is sent to the brain, the perceptron sends a signal that, okay, you need to apply brakes, right? Now, all of this happens so quickly inside that obviously we know that as a human being, everything that we are doing is related, and everything is happening so fast that you will not be able to tell that, okay, you saw an object, then a signal was sent to the brain sent a signal back, and then you applied the brakes, right? So all of this happens very fast, right? But exactly in a similar way, we have our neural networks which try to do a very similar job, right? So now let's try to understand the artificial neuron. Now this, if you see, is a single perceptron. All right. So over here, we have broken down the neuron basically. So if you look at this, right, this is the neuron that we were talking about. The neuron, one single neuron has two functions inside it, right? If you see the first green box, the green circle and the blue box. Now, what exactly happens inside these two? That is what the objective of this particular module is. Okay. This box you can consider as the single neuron, right? The single neuron that we had seen previously, right? This output will be the output neuron. This will be our output neuron, and these are your input neurons. So if you see over here, you have n inputs. So when you have n inputs, the number of neurons that you will have in the input layer will be n. Okay, so the most fundamental unit of a deep neural network is called as an artificial neuron, right? It takes an input, processes it, passes it through an activation function, and returns the output. Such type of artificial neurons are called as perceptrons, right? A perceptron is a linear model used for binary classification, right? Now, ignore the last line. A perceptron, there are earlier, right, when neural networks actually came into existence, at that point of time, when the inception happened, right? At that point of time, we had only perceptrons. Then someone came and then someone said that, okay, if a single perceptron is doing this, what if we go ahead and if we combine multiple perceptrons together, right? So a perceptron as a single model would have been used 20, 30, 40 years back from now. But right now, there is no use of that because we have better models. We have models such as decision trees, random forest, and all, which do a better job as compared to a single perceptron. But when you combine multiple perceptrons together, you create a neural network. And a neural network is more powerful as compared to the ML models that we have studied, right? Now, let's try to understand what exactly happens inside a neuron or inside a perceptron. Okay. Uh, just one second. All right. Okay. So, see, in this slide, in this image, let's just try to understand what are the different parameters that this perceptron or neuron will take, right? Can you guys tell me what are the values x1, x2, x3, and xn? What do you understand by these? Inputs, right? So these are the input features. So these inputs will be what? These will be some kinds of numbers, right? Whatever data you have, it will be those numbers, right? So let's say if I take the example of the price of a house, x1 can be, let's say, the location, x2 can be the area, x3 can be the, let's say, age, and so on and so forth, right? So whatever features you have, x1, x2, x3, xn are those features, right? Now, w1 to wn are nothing but weights, right? What are weights? Weights are just like in the case of a linear regression model, you had weights which were telling you the importance of the different features, right? Just like that, every input feature will have a set of weights assigned to that, right? Now, these weights are going to govern that whether or not this feature will play an important part in this neuron, right? Now, go back to the example when I was talking about the case when only the location and the location and the area of the house will play a role and the age of the house will not play a role, right? In that case, what will happen is that the weight associated with the area and location will be high, and the weight associated with the age feature will be close to zero, right? How do we do that? We do that by assigning these different weight values. So now let's say if I want to create a neuron, or if a neuron wants to create itself, which gives a higher weight to x1 and x2 and close to zero weights to x3, x4, x5 till xn, then what it will do is that it will initialize the weights w1 and w to some values, and all the rest of the weights will be values which will be very, very close to zero. All right. And this aspect or this part of the neuron is known as the linear transformation that happens inside, right? But right now, let's just try to understand what are the different parameters that are being passed to this neuron. X are values, W are weights. The sum of all weights should not be 1. No. How do we identify weights? What are these weights? Don't jump to any further questions. If you want to learn about neural networks, just stick to what I'm talking about. I ensure you that I will be covering every technicality, right? So don't jump to questions such as how these weights are calculated and all. Just focus on what I am talking about. I will obviously be covering each and every aspect. Okay. Let's try to understand what happens inside a neuron, right? Now, the neuron or one single neuron in a neural network is a combination of linear plus non-linear transformation, right? Now, first we'll start with the linear transformation. What do we mean by the linear transformation? Okay. Now, the linear transformation is nothing but if I had go back to the previous example of house price prediction, right? I had a case wherein only the area and the location of the house were playing an important part, right? Now, for such a neuron, if I am getting three features as an input, that is area, location, and age. Obviously, if I want to give a higher weightage to only area and location, the weight associated with my age should be close to 0, and the weights associated with area and location should be high, correct? So what will happen inside that neuron is that neuron will do a linear transformation of all of these three variables. The linear transformation is what? Your input variable values, that is your x1, x2, x3, will get multiplied by a set of weights, right? So let's say your x1, x2, x3 get multiplied by w1, w2, w3, right? Once when you have multiplied those, a summation will be calculated, right? If you see, some value is x1 w1 plus x2 w2 plus x3 w3. This is nothing but your input features multiplied by the corresponding weights, right? Your input feature number 2 multiplied by the corresponding weight, and so on and so forth. You will calculate a sum value. Now, if you remember, in case of the linear regression model, you had equation y equals to mx plus c, right? So what was c over there? Intercept, right? So there had to be a constant value, or there had to be an intercept. Whenever we are doing a linear transformation, there will be a constant value that will be outside of the purview of your weights, right? Or outside of the purview of your input feature values. So just like that, over here as well, we have a bias value, right? So now if you see this equation, this is exactly the equation of a linear regression model, right? If you look at this, new sum, or whatever the linear transformation is coming out, is nothing but feature 1 multiplied by a weight value, feature 2 multiplied by the corresponding weight value, feature 3 multiplied by the weight value plus bias, right? And this is the first transformation inside a neuron, which is the linear transformation. The objective of the linear transformation is to only identify the variables which are going to interact together for that particular neuron, right? Now, it might happen that 50% of variable 1, 30% of variable 2, and let's say 5% of variable 3 go ahead and combine, go ahead and create a linear combination, right? When I said that only area and location matters, it might happen that age might play a very small role, or it might happen that the age might not play any role. So all of this will be determined by the weight values. Okay, so the linear transformation, we had our feature values, we had some weights. How are these weights identified? How do we arrive at these weights? That is something that is the objective of the neural network that we will be studying about later, right? But for now, just imagine that there are some weights which the neural network is able to identify. So we multiply these weights by the feature values, we sum it up, we add a bias value. The bias value, just like the weights, right? This value is also identified by the neural network, right? And then this constitutes the linear transformation. After the linear transformation has happened, we go to the next step, which is the non-linear transformation, right? So if you see, now statistically, weights determine the relative importance of the input. Now, in that given neuron, right? So go back to the example of the house price prediction. in the neuron which was taking only the area of the house and the location of the house, the weights will determine that area and location are important, and the weights corresponding to age will be close to zero, right? So mathematically weights are nothing but, if you see, this is nothing but this is the linear regression output, right? The equation that we get for linear regression, we are trying to come up with that, right? So weights just determine how important your given variable is, right? Now, why do we need weights? Will it rain if I wear a blue shirt? Now, if you see over here, there are two variables, right? There is humidity and there is the color of the shirt, that is blue. Now, see, as obviously it is not suggested that you feed variables which are not important, but still there can be confounding variables. There can be variables which you might feel important in predicting the target variable, but which they are not able to do, right? But how the neural network filters out these variables which are not important is through weights, right? Now, in this example, what do you think? The weight associated with humidity will be higher, or the weight associated with the color shirt blue will be higher? Humidity, right? So ideally, the neural network over here should not give a higher weightage to W2, because obviously it doesn't matter what color shirt you wear, right? It will not rain as per that. It might rain because it is humid or it is not humid, but it will never rain because the color of the shirt that you have worn is blue. So now if you see, weight in a way is identifying or is assessing the relative importance of a given feature, right? Okay. Now coming to the second aspect, that is the activation function. So the first part was the linear transformation. I hope everyone is clear on the linear transformation. The objective of the linear transformation is to, for a given node, find out what are the important players, what are the important features, right? And then go ahead and do a linear transformation and create a variable which is a combinational form of all these input variables. All right. Now, see, we have done the first step, that is, inside the neuron, we have been able to identify which features are important. Now, if you go back to the first example, at a given time, only some of the neurons were firing, right? All the neurons were not firing. Now, how can we make that happen? You remember, right? In the previous example, the house price prediction, what we were doing was that, let's say in the hidden layer, if there are 4 neurons, it might happen that out of 4, only 1 neuron gets fired and all the rest do not fire, right? Now, how can we make that happen? Now, that is something that that happens through the activation function. Now, the activation function is a nonlinear function which tells the neuron to fire or not fire, depending upon a given cutoff value, right? It will go ahead and it will say whether you need to activate yourself or whether you need to deactivate yourself, right? So now, if you see the activation function, now the activation function will be nonlinear. Nonlinear, why? Because see, these deep neural networks, they solve complicated problems. Now, every problem that we solve might not be linear in nature, right? Now, you can create a linear model by using nonlinear architecture or by using nonlinear functions, but vice versa will not be true, right? You will not be able to create a non-linear model using only a linear model, right? So the functions that we use over here, the activation function will be a non-linear function. Why? Because the objective is, so let's say if I am able to identify that all the house prices that are, let's say all the houses that are in a specific location, if I go ahead and if I plot the data, I'm able to identify that all the houses within this ring will have a lower prices and all the houses outside of this ring will have a higher price. Now, the non-linear function will only be able to help you in segregating this particular boundary line, right? If you look at this, so the nonlinear function will say if there is any input of the neuron which is greater than this range, then you can go ahead and deactivate it. Any input function which is less than this range, then you can go ahead and activate it, depending upon whatever the conditions might be, right? So the next step, the next stage within a neuron is the activation function, which which basically introduces non-linearity to the model, right? Now, in this particular case, in this particular example, you can go ahead and you can try drawing as many straight lines as possible, but will you be able to segregate these points? Now, the linear transformation of the variables that I had, right? Let's say the one that happened in the previous step, will it ever be able to go ahead and segregate these 2 points, the circles and the triangles? No, right? You can try drawing as many lines as you can, but you will not be able to. Now, obviously, if you go ahead and draw 4 or 5 lines, you might be able to, but we need one function which is able to achieve the same thing, right? Hence, we need a non-linear function over here. The non-linear function, if I'm able to draw over here, it will help me in creating a boundary line. Now, any value which is outside of the circle can be the neuron can be deactivated. Any value that is inside of the circle, the neuron can be activated. Ideally, if you want to separate it through a linear function only, you will have to add a third dimension, right? So this is very similar to, so let's say your mother, she went ahead and there were guests who were coming at your house and she had put, let's say, a new bed sheet on your bed, right? And you, being yourself, you went ahead and sat on the center of the bed and ate, let's say, something, maybe a chocolate, and the chocolate ice cream, whatever, right? It fell on the bed sheet, right? Now there are two things. Either you take away the entire bed sheet, right? Wash it, but then it means that the entire bed sheet, you cannot use it then and there, right? The other way is what? You pick up the bed sheet from only the part which is dirty, which has become dirty, right? So let's say the center of the bed sheet had become dirty. Now the original bed sheet had what? Had two dimensions. That is only a length and a breadth. When you go ahead and when you pick up the bed sheet from the center, you are also introducing a third dimension, which is the height, right? Now, as soon as you pick up the bed sheet, all you have to do is that you have to only go ahead and wash that center area, right? Once when you make sure that that is clean, you go ahead and reduce the dimensionality back to only the length and the breadth of the bed sheet, right? So just like that, you can go ahead and you can separate the data using a linear function, but that can only happen once when a nonlinear transformation has been done on the data, right? Activation function will the next step after linear transformation. Yes, Atul. Activation function. So after the linear transformation, you have the activation function, right? So there are different kinds of activation functions, right? Now see, if you summarize the activity that happens inside a neuron, right? What is it? The first step is that you will do a linear combination of all the input variables. Each and every neuron will have a different set of linear combinations. If there are 3 neurons in your neural network, the first neuron might have, let's say, might give a different weight to the different features. The second neuron might give some other weights to the same features, right? Okay. Now, once when you have done the linear transformation, then the second step that comes is basically the activation or the deactivation of the neuron, right? Now, in the second step, you try to go ahead and you try to decide whether this particular neuron will be activated or not, right? That is something that is decided by the nonlinear activation function that comes as the second step. After the linear transformation, you will have the nonlinear transformation, right? Krishna, that was just an example of how we can separate out nonlinear classes, right? So, but over here, the objective of the activation function is to either activate or deactivate a given neuron. All right. Now, see, activation functions, there are many, many different kinds of activation functions that we have, right? Activation function will be present in every hidden layer. Yes, Raj. Even hidden layers, even output layer, right? Now, the output layer activation function will help us in deciding whether it's a class. So if it will be a classification model, or if it is a classification problem that you're solving, the activation function will be an activation function which gives out probability. If it is a regression problem that you're solving, then the activation function will be a function which gives out continuous values, right? So the activation function will be applied to all the layers but the input layer. The input layer will not have any activation function. The hidden layers will have the activation functions. The job of these activation functions will be to either switch on or off a given neuron, right? Or to filter the amount of values that are going out from that particular neuron. The activation function in the output layer, the job of that is to limit the value to, let's say, between 0 to 1 in case of a classification problem, or make the value continuous in case of a regression problem. All right. Now, activation functions, there are many activation functions that we have, right? There can be different kinds of activation functions, sigmoid, tanh, relu, right? But how do we use them? Now, see, till now, you would have seen that there are so many variables in a neural network, right? Uh, can you guys tell me, till now, the architecture that we have seen, how many components to the neural network are there that can vary? Number of hidden layers, the first thing is what? The number of hidden layers, right? You can decide that. The second thing is what? The number of neurons in the hidden layers, right? Now, the third thing, if you see over here, is what? The activation function. Now, the activation function as well. Now, all of these things, right? These are hyperparameters. Just like in the case of your tree-based models, right? You had hyperparameters such as number of trees, or the depth of the tree, or the splitting criterion, right? Just like that, in case of a neural network, these are the hyperparameters. Because see, neural networks are very open-ended models. You don't have a fixed architecture. You need to define that, right? It is just like, it is not like a product from, let's say, see, you have your do-it-yourself products, right? So let's say if you go to an let's say to any DIY store, right? Wherein you get do-it-yourself products, right? You don't have the freedom to go ahead and experiment, right? But let's say if you want to create a table, and let's say you go ahead and get raw wood, right? It is totally up to experimentation. You can go ahead and you can experiment with anything, right? So just like that, your decision trees, random forest models, you can consider them as DIY kind of solutions. All you have to do is that you have to put them together, right? But the neural networks, the artificial neural networks, these are models that are totally customizable, right? Right from the architecture, right from the number of hidden layers, the number of neurons, the kind of activation function that you want to use, right? Even the weight initialization, right? I'll come to that later, but how do you assign the weights? How are the weights initialized? All of these things are customized, right? So now if you see, there is one more term that is added, that is the activation function. Now, it might happen that for your use case, a sigmoid activation function works the best. It might happen that for some other use case, a tanh activation works the best, right? I'll talk about what these activation functions are. Right now, I'm just trying to make you understand how do we play around with these activation functions, right? So just like in the case of the tree-based models, your Gini, right, your information gain, entropy, either one of the three could have worked, right? Just like that over here as well, for the activation function, depending upon your data distribution, it might happen that sigmoid works for you. It might happen that tanh works for you. It might happen that relu works for you. Unit function works for you, whatever, right? So all of these, the job of the activation function is to introduce non-linearity. But what kind of activation function is actually helping you in introducing the kind of non-linearity which is helping you in predicting the target variable? That is something that you will have to find out by building multiple variations of your neural network model and seeing which one is working the best for you. Now they are used to convert an input signal of a node in an artificial neural network to an output signal. The output signal will once again be whether you want to activate the node or deactivate the node. The output signal now is used as an input in the next layer. I'll explain all of this once when we move to the neural network architecture. Activation functions introduce non-linear properties to a network, right? A neural network without an activation function. Now imagine if I would have created an activation, if I would have created a neural network without any activation function. what will it be? It will eventually be a linear regression model, because each and every neuron is acting as a linear regression model. If there was only one single step, that is the linear transformation, all you are doing is that you are creating multiple linear regression models and you are adding them up, right? So it is the activation function, it is the presence of the activation function that gives the neural network the kind of power that they have today, right? Because if it would not have been for the activation function, your neural network will just be a linear regression model. I hope this line is clear to everyone, right? All right. So the sigmoid activation function, it can be used in the output layer if you want probabilities. It can also be used in the hidden layers as well, right? Now, the sigmoid function at times, it is also used as the activation function in the hidden layers, right? Yes, Malik. In one hidden layer, all the activation functions will be the same. For different hidden layers, the activation functions can be different. Step function is giving you values which is either 1 or 0. If you see, this is 0 or 1, right? The sigmoid function is giving you values in the range of 0 to 1. Now the tanh function, very similar to sigmoid if you see, but the only difference is that your output will vary. Your output now can vary in the range of -1 to +1. When in case of sigmoid, your output was varying between 0 to 1. In case of tanh, your output will vary between -1 to +1, right? Your input in both the cases can be bit from -infinity to +infinity, right? Now tanh is a function. Now, can you use tanh function as the activation function of the final layer, the output layer, that is? Can you think of any use case where tanh can be used as a activation function for the output layer? If you have three categories, then also you won't be able to do that, right, Atul? Your probabilities cannot be between -1 to +1. Right, exactly. So tanh is a function which is used more in the hidden layers, right? It is never, I have never used it as an output layer function. Maybe for some instances, so let's say someone is doing a prediction of a variable, target variable, which is ranging between -1 to +1, a continuous target variable in the range of -1 to +1. That can be for very, very specific cases. So let's say for sensor data, you have a kind of sensor which the output from which varies in the range of -1 to +1. You can go ahead and then you can probably use a tanh function. But generally, I have not seen tanh being used as an output function, right? It is more like most of the times it will be used as the activation function of the hidden layers, right? Now coming on to ReLU function. Now ReLU is a function which I would say is the Virat Kohli of functions in the world of neural networks, right? It is very popular, right? And 90% of the neural networks, ReLU function will help you in solving any kind of problems that you have, right? So if I talk about my experience, if I have worked on 20 deep learning projects, 14, 15 projects, I would have used this function really, right? Why? Uh, it's a simple function. What it does is that now if you see, it will deactivate the neuron for any values which is lesser than let's say a cutoff value, right? So the default function is x is less than 0.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
If x is less than 0, the output will be 0. So if you see, it is deactivating a neuron totally, right? But if the value is greater than a given threshold, then it lets the information flow depending upon the value of the input. So if you see over here, ReLU function acts as a proper tap. Either it will close the information totally, or it will let the information pass to a certain extent depending upon the value of the input that you have, right? Exactly. Okay. So as I said, ReLU function is so whenever you are working with deep learning models, maybe ReLU will be the first option for you. Go ahead and try that. If you see that it is not working, then maybe you can explore other functions as well, right? This will not provide any negative value. ReLU function is generally used as an activation function of the hidden layers, right? Output layer, I have rarely seen anyone using this function, right? You don't fix the threshold, Tanushri. That is what something the model decides, right? The model, after doing multiple iterations, so let's say the model says that whenever the combination of area and location of the house is greater than 0.5, you need to let the information flow. Whenever it is less than 0.5, you need to stop the information flow, right? So all of that is decided by the model. All right. Leaky ReLU is one function where this function does not attain a zero value. The objective of this is that when we are moving to gradient descent, right? I'll explain why this is used. At times when your function output becomes zero, right? So it becomes tough for the model to identify the correct direction of the weights, right? Right now, this might sound confusing, but don't worry about this. Leaky ReLU function is only a slight variation of the ReLU function. The typical ReLU function in more complicated problems, it becomes slightly tough with that function to identify the best possible values of weights. So in that case, what was done was that there was a slight variation that was done to the ReLU function, wherein it does not close the tap totally, it keeps the tap open very slightly, right? Why do we need to do that happen? Because we need to identify the direction of the weights, the correct direction of the weights. So leaky ReLU is also a function which is the variation of your typical ReLU function. All right. And then finally, we come to the softmax function, like leakage in a tap. Yes, right. The softmax function. Now, this function is used when you are working with multi-class problems, right? When you are working with classification problems, but this is not a binary classification problem. It is a multi-class classification problem. So softmax function will be used as the activation function for the output layer at that point of time. And the softmax function also, if you see, gives a probability as an output, right? In the range of 0 to 1. Right? So the use of this is that when you're using the softmax function, all the probabilities, the sum of all the probabilities will come out to be 1. If you have 5 classes, right? So by using the softmax function, if you would have used a sigmoid function instead of a softmax function, when you have, let's say, 5 classes, then the summation of all the 5 probabilities will never come out to be 1 if the function is sigmoid. But if it is softmax, then in that case, the summation always comes out to be 1, right? And that is because of the formula of the softmax function. If you see, if you have 5 classes, right? So the probability will be, let's say, the value of first class divided by the summation of all 5, right? The second will be value of second divided by summation of all 5. So obviously, if you sum it up, this will come out to be exactly equal to 1, right? And that is all about the activation function. So see, all you need to know here is to you need to know what are the different activation functions do you have, what are the formula, right? That probably is not very important. If you know that, it is good, right? But you should remember the distribution, how the activation function looks like, because if you're solving a kind of problem, then you should be able to identify which activation function will work the best for you. Right. So now we will be getting started with how does a perceptron train itself, right? So now the objective for us is to go ahead and understand. We know mathematically to a certain extent that what is happening in a perceptron, right? We know internally what happens inside a perceptron. What are the two steps? The two steps that generally happens are uh, whatever input features you have, right? They will get multiplied by a weight value. Now, till now, I have not talked about how this weight value is decided. So we are assuming, let's just assume that the neural network is coming up with these weight values, right? So the values of the input features will get multiplied by the weights, and we are going to sum it up. This is known as the linear transformation, because this looks, or this is very, very similar to how a linear regression model works, right? So that is the first step of data transformation inside the perceptron, right? The second step is the use of an activation function, right? An activation function's job is to go ahead and is to introduce non-linearity in the neural network model. By non-linearity, what we mean is that the activation function can go ahead and can give us non-linear outputs, right? So anything, so let's say if the linear transformation is giving us values in the range of minus infinity to plus infinity, the activation function can give me values in the range of, let's say, 0 to 1 or 0 to 5 or minus 1 to plus 1, right? So the second step is the non-linear transformation. That is nothing but the application of the activation function, right? Now we'll try to understand how, using this sequence, right, how does the neural network or how does the perceptron train itself? Okay. Now see, a very simple, the first thing that all of us need to understand is that how does data flow into the perceptron? Are you guys aware of how does the data flow into a perceptron? Let's assume that I have 10 rows of data, right? And I have a perceptron. How will the data go? Will it go at once to the perceptron, or will it go in a sequential way, or will it go in a haphazard way? Uh, do you guys know that? Sequential, right? So what will happen is that your perceptron will be given individual rows of data, right? One by one. So let's say if I have 10 rows of data, the first row of data will first go into the perceptron, right? Taking whatever values of the features are there, the weight values that were there in the perceptron might get updated or might remain the same, right? It will go ahead and it will give an output. Then the next row will go in. The same thing will happen. Maybe the weights get updated, maybe the weights don't get updated, right? And this process will go on and on and on until all the 10 rows of data have been passed to the perceptron. Now, generally, because your deep learning models are more complicated models, so what happens is that generally they need more iterations of your data. So even if you have only 10 rows of data, your perceptron might expect the same rows of data to be fed to the perceptron model again and again, right? Now, this is very, very synonymous to, let's say you decide to learn to play a new sport, right? So let's say you go ahead and you decide to learn to play badminton, right? Now, any sport is also, if you pick up any sport or if you pick up anything which is new, right? So let's say driving a car, sport, anything, right? Learning a new skill is more about repetition, right? When you keep on repeating the same drills, when you keep on repeating the same things again and again and again, right? Your movement actually becomes better, right? Your body flow becomes better. You are able to be in sync with things, right? So just like that, in case of these deep learning models, the data is fed to the models again and again and again. And each time the data is fed to the models, the model tries to extract some kind of a relationship or some kind of a pattern from this data, right? So that is what we do over here as well. This process goes on and on and on until the accuracy of the model reaches a stage wherein you are satisfied with it, right? So let's say you are aiming for an accuracy of 90%, right? After continuous training of the perceptron model, so let's say the first time when the model ran, the accuracy was maybe 20%, right? Now the model keeps on running, the data that we have keeps on going into the model, and the accuracy might keep on getting better, right? It's not that always the accuracy is going to go to 90%, 80%, 99%, depending upon whatsoever data you have, whatever kind of a problem you have, the accuracy will try to reach to its maximum possible extent, right? If your data is limited, if you don't have enough features, it might happen that the accuracy might saturate at 50%, right? If you have good enough amount of data, if you have used um, uh, relevant features in the data, right, it may happen that your accuracy starts from 20-30% and reaches to 90-95% as well, right? Okay, so now we'll try to understand how exactly training happens inside a perceptron. Now, what if you go ahead and for a neural network which would have done the job in, let's say, 2 hidden layers, you go ahead and you define 10 hidden layers, right? Now, when you're defining 10 hidden layers, you are complicating the model. When you're complicating the model, it will start to overfit, right? Let's say you are working on a problem wherein the model which had 5 hidden layers was supposed to be the best possible model, but you went ahead and you finalized the model using only 2 hidden layers, right? Now, in such cases, the model will underfit. Okay, so now let's get started. Now, see, what happens is that in case of when we are training a perceptron, now when the training starts, right, during the first iteration, once when we are passing the data for the first time. Now, one thing that you need to understand is the weights that we were talking about, right? The weights and biases. The training of any perceptron or the training of any neural network, the objective of this training is to identify the best sets of weights and biases, right? Just like if you remember in the case of a linear regression model, our objective was to find out the coefficients, right? Intercept and the coefficients. Just like that, here as well, in the case of a deep learning model, the objective is to find out the weights and biases. The only difference is that in case of a linear regression model, the weights or the coefficients will be equal to the number of features that you have, right? So if you have 10 features, the coefficients will be equal to 10, intercept will be equal to 1. So total you will have 11 parameters, right? In the case of a deep learning model, these parameters or these weights and biases, right, they don't just depend upon the number of features. They also depend upon the number of hidden layers and the number of neurons that you have given. Because you had seen previously, right, that each and every input feature is connected to each and every neuron. Each connection is a weight, right? So in case of neural network models, you might have weights and biases running into thousands and millions and billions as well, right? So that is why your neural networks are very complicated and the main objective of any model is accuracy, right? Now, let's say, I'll give you a very simple example. Let's say you decide to play badminton, right? Now, you go to play badminton the first day, and let's say you have played a fair bit when you were a child, and you think that you know how to play a a smash shot, right? Effectively. Now, let's say when you go there for the first day, your technique is corrected by the trainer, right? He tells you that you need to keep your hand at a certain uh, angle, you need to hit it with a certain power and so on and so forth, right? Now, do you think that right at day one, you will be able to achieve that particular specific form that has been asked for? Because there are too many things that you have to do together, right? You have to focus on the foot movement, you have to focus on the shuttle, right? You have to focus on where the shuttle is going to land, you have to focus on your posture, right? So there are so many varying parameters that the final output that you are expecting, you might not be getting that on day one. Is that correct? So what happens is that the thing that you know is that you have seen your trainer hitting a smash, right? And you know what the correct form is. So that is that is the aim with which you are playing. Your aim is that, okay, if I keep on practicing, I should reach that stage wherein I am able to hit the shuttle with this much power. I am able to hit the shuttle with this much, let's say, precision and all, right? But first day, maybe when you practice, you are able to reach only 10% of that. right? Now what happens? You go back home, you think of what you have done, what you were able to do right, and what you were able to not do correctly, right? Then the next day you go back and you try to better the mistakes that you did on day one, right? Now maybe on day two you were able to rectify some of the mistakes that you made on day one, but still there might be some aspects left that you need to cover or that you need to practice about, right? So maybe day two the error or the accuracy increases from 10 to 20%, right? Now this process goes on and on and on and on. Maybe 1 month down the line, or let's say 2-3 weeks down the line, you are able to perfect that shot, right? Now, in an exactly similar way, the training of a neural network happens, right? Now, if you see a human brain, the example that I took is of, let's say, a human playing badminton, right? A human being is playing badminton. Why? Because a human has a brain which which actually comprises of different neurons, right? So the learning process of a human will be very, very similar to the learning process of a deep learning model. So, right. So that is why I gave this example, because the learning process will be very similar, because this artificial neural network is also trying to imbibe or it is also trying to imitate the functionalities of a human brain, right? Now, if I come to this example, if you see, let's say this is the data that we have, right? So the data that we have is I have 3 horses and I have 3 dogs, right? I want to build a neural network model which is able to classify the dogs and the horses in separate classes, right? So now let's say this was the data when the neural network started training, or the first run that the model did with the first sets of weights and bias values, it got an error of 2. Why 2? Because there is one dog that is present in the group of horses, and there is one horse which is present in a group of dogs, right? Now, if you see, this is the classification boundary. This dog should have been here and this horse should have been here, right? Now, what will happen is that with the sets of weights and biases that has been given to the neural network, it realizes that the error is 2. Now, this is you on day one playing the smash shot, right? But obviously, you are not able to play it perfectly. So there will be some amount of error, right? But what happens is that the good part is that we have the ability to go back and we have the ability to focus on what we did correctly and what we did incorrectly, right? So now what happens is that the training once again happens for this perceptron, and this time the perceptron knew that my error was 2. I need to decrease the error as 2. And the perceptron also knows that this observation is misclassified and this observation is misclassified. So in the next iteration, the perceptron will try to adjust its weight in such a way that the horse comes here and the dogs goes there, right? Now, let's say in the second iteration, what happens is that the horse is actually moved to the correct set of classes, right? But the dog remains over here only. Now, once again, your error comes down to 1. Now, what has happened is that you have been able to reduce the error slightly. Obviously, when we are playing badminton, if on day one my error is, let's say, 50%, on day two I cannot make it as 0% straight away, right? It might come from 50 to 45 to 40 to 38, 33, whatever, and then eventually become 0, right? So like this process will keep on happening, right? Until your error has become minimized, or the error reaches a point beyond which it cannot go down, right? So this is generally how the training of a perceptron happens, right? Exactly. So x1w1 plus x2w2 plus x3w3 plus till dot 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 till xnwn plus your bias value, right? That will happen over here. So this is what, this is the linear transformation. After the linear transformation, we have applied the activation function, right? Activation function will introduce the non-linear transformation, right? And that will become the output of this particular perceptron, right? Now, if you go back to the horse example, earlier, my error was 2. In the first run of the perceptron, the error was 2. Now what happens is that whatever error I get, right, I need to feed this error back, or I need to divide this error back to the weights, right? Now, let's try to understand one thing. If I'm getting an error of 2, right? Let's say if I'm getting an error of any value, why am I getting that error? Am I getting that error because my features are presented in a similar, in a particular way, or because my weights might have been assigned incorrectly? What do you guys think? Let's say I run this and I get an error of 50%. So the whole sole reason, right, of that error is what is the weight values, because these weight values have been assigned randomly in the first iteration of the neural network. The neural network doesn't know, the perceptron doesn't know what are the correct sets of weights. That is the objective, right? The objective is to find the correct sets of weights. When we are trying to learn how to play badminton, the objective is to find the correct posture, the objective is to find the correct technique, the objective is to find the correct approach of playing, right? And there can be 1,000 different parameters, right? When you are playing a new sport, there will be hundreds of different parameters that you will have to focus on. Just like that, here as well, there are n number of weights, right? Now, whatever error I get, do you guys think that this error, now see, this is clear to everyone, right? That this error is coming because the weight values that we have defined are slightly incorrect, slightly incorrect, or let's say totally incorrect, whatever, right? So now what we do is that we take this error and we redistribute this error back to our weights. We try to find out which weight is contributing what percentage of this error, right? So let's say the error of 2, right? So let's say the 0.4 value out of 2 is being contributed by the weight W1, right? So what I'll do is that I'll go ahead and I'll try to adjust this weight value. Let's say if I try increasing the weight value, I realize that when I increase the value of weight 1, the error actually goes down. So in the next iteration, what I'll do is that I'll try to increase the value. Let's say for W2, it sees the model sees that the contribution of error coming from W2 is, let's say, 0.1 out of 2, right? And the model realizes that if I reduce the value of W2, then my error is actually coming down, right? So for W2, the model will try to reduce the weight, and then it will see that the error, now all of this will not happen separately, all of this will happen together, right? Now this error coming, which is W2, the model will try to reduce the weights, the model will try to update the weights and will try to reduce the error, right? So once when the first iteration of data, or once when the first batch of data has passed to the model, the error will be calculated. After that, the error will be distributed back to the weights. The weights will be adjusted, right? Now, coming back to the badminton example, let's say you went ahead and you played a smash shot, and your trainer comes to you and they tell you that this is the error, right? You have done these 5 things incorrectly. Now, will you be able to rectify all of these things in the next match, or will it take time for you to do that? It will take time and practice, right? Because there are so many movements that are happening simultaneously, and because this is a new sport for you, your body is not conditioned to move in that particular manner, right? So just like that over here as well, although I know that my error is, let's say, of 50%, but what I can do is that I can only gradually update my weights, and I can only gradually come to the best possible output, right? So this process will keep on happening, right? This process will keep on repeating. If you see this loop, right? This loop of your X1, W1 getting multiplied, bias getting added, activation function getting applied, right? This will keep on happening. This will give you an output. The output will give you the error. The error will take this back, the weights will be updated, and then this process will keep on happening, right? And this we are going to see in some time. Now, this process is known as forward propagation, right? In forward propagation, what we are doing is that we are multiplying the input values by weight values. We are taking them through the activation function, and we are getting an output. That is forward propagation, right? Once when we get an output, we calculate the error and we try to redistribute this error back to the initial sets of weights. This is known as backward propagation, right? This once when we'll start with our proper neural networks, at that point of time, these two concepts will come into picture. But for now, I'm just explaining this, that these are the Forward propagation is nothing but your weights getting multiplied by the features and getting the linear and the nonlinear transformation. Backward propagation is the calculation of error coming from the assigned weights and then redistributing this error to go ahead and update the weights in order to get a lesser error, right? Indu, when we say input, they will be, see, it depends upon the features. If you have 10 features, then your input will be 10 different values, right? So if I want to predict the price of a house, and if I have 3 features, right? So let's say area of the house, the age of the house, and the location, then my input each and every time will be these 3 features, right? Which activation function depends, right? You will have to go ahead and you will have to identify, we will have to test around different activation functions, right? Now, activation function is just like, now let's say when you're playing badminton, there is a different set of uh, like uh, interactions that you would try to do, right? And let's say when you are driving a car, right? So let's say badminton, your hand movement is free. You can move your hand from, let's say, right from the back of your head to the front, right? But when you're driving your car, your hand movement should be limited. Maybe the movement should be limited to only 10%, right? 0 to 10% movement. But when you are playing badminton, the movement can be 0 to 100%. Now, this will depend upon the activation function. If you keep an activation function which is making the hand movements in the range of 0 to 100% for a driving session, obviously you are going to go ahead and crash, right? If you make the activation function which gives an output of 0 to 10% for badminton, you will never be able to play badminton correctly, right? But this is something that you are able to identify as and when you pick up a new skill, right? So just like that, over here, the activation function is something that we'll have to find out which activation function will work the best over here. Backward propagation is a feedback loop only, right? Yes, Nathan. So backward propagation is a feedback loop along with the feedback. So backward propagation is the part wherein actually we apply gradient descent. Now, all of these things we'll be studying step by step. But in gradient descent, we also try to find out, the feedback loop will tell us what is the error, right? Gradient descent approach will tell us from where, from what all weights this error is actually coming up, right? So don't worry about that as of now. With time, we are going to understand each of those concepts. Each set of input is for one instance. So one row, right? Let's say you have 3 features for one row. They will go inside the perceptron, right? Then you will get a prediction, right? You will get an error. Error will get adjusted. Then the second row will go. The second row will go. Once again, the same thing will happen, right? All right. Now let's come to the right hand side flow chart of this, right? If you see the same points that I've explained, right? We have an input, right? We have a set of features. For those sets of features, we initialize the sets of weights, bias, and threshold values, right? Threshold, what are thresholds and all? We are going to cover that in due time. Don't worry, right? Calculate the sum and pass through an activation function. I hope this is clear to everyone. So this will be the linear and the nonlinear transformation. And through that, we produce the output. When we produce the output, we calculate an error, right? If the output is correct, we stop, right? But obviously in the first iteration, the output will not be correct. So what will happen? We will calculate the error, right? We know what is expected of us, right? What was the actual output? We know what the prediction is coming out to be. We will calculate the error. After calculating the error, we will update the weights, right? Now this piece of mathematics that you are seeing, this differentiation and all, right? Don't worry about this. This is gradient descent. I will be explaining gradient descent in detail. There will be one session only on gradient descent. This updation that you are seeing is nothing but gradient descent at play, right? How it works, all of these things we'll be covering. Right now, all you need to understand is that there will be a technique called gradient descent, which will help us in updating the weights, right? Once when the weights are updated, once again, you come back to this particular stage wherein you calculate the sum, pass through an activation function. Now, because my weights have changed, obviously the output from the linear and the non-linear transformation should also change, right? So if the output is changing, obviously your error will also change, right? Error ideally should go down, right? So this process, if you see, this loop will go on and on and on until you produce the correct output. Okay. And this is how the training of a perceptron or the training of a neural network happens. Make backward propagation happen after each and every row is passed. You can make backward propagation happen after the entire data is passed. You can make backward propagation happen after, let's say, chunks of data. Let's say after 5% of the data has been passed, right? So these are good questions. I'll be covering all of this in due time. But as I said, right, neural networks are highly customizable models. Everything that you can think of is customizable over here, right? How many times gradient descent needs to update the weights, that depends upon us, right? How many times a specific thing, let's say forward propagation is happening, that depends upon us, right? Gradient descent is an optimization method. Yes, Indu. So correct, if we reduce errors completely, so while we are training, right, we always keep a track of the training accuracy and the testing accuracy. So it might happen that the training accuracy becomes 100%, but if we start seeing that after the accuracy was 90%, the testing accuracy actually became stable or started to go down, you will have to stop then and there, right? So for any machine learning, deep learning model, the only respite that we have is that because these are supervised models, we know how well the model is performing, right? So you're totally correct that if we keep on updating the weights, the model will start to overfit, right? But that is where we need to constantly track how the model's performance is coming on your training and testing data. If till the point that the performances are very, very similar, you will keep on the training happening. But the moment that you see that the training accuracy is increasing and the testing accuracy has stabilized or going down, that means that your model has started to overfit, and that is where you should stop the training. Krunal, bias, just like weights, right? All of these are parameters. All of these will be identified for each and every iteration, right? Identified and then updated, right? The objective is to get the least value of error. Mosmi, for a neural network that you have defined, let's say you have defined sigmoid as the activation function. For that, for the training of that neural network, sigmoid will be fixed. You cannot do that the first 10 iterations will be sigmoid, the second 10 iterations will be tanh, right? Because the objective is to learn a particular activation function, right? But you can have multiple models, right? You can have one model having sigmoid, one model having tanh. Then you can go ahead and compare which one is doing the best job for you. Now, benefits of artificial neural networks, organic learning. Organic learning, what do you mean by that? That if you see over here, just like a human learns a new skill, just like that, the neural network is trying to learn how the data is behaving and all, right? So it's not, so if you compare this with the previous models that we have worked with, let's say a linear regression or logistic regression, right? What they were doing were, let's say any other model, a support vector machine, thing like that. These are predefined models. The model, linear regression says that whatever your data might look like, I will come up with the equation of a straight line. So you need to take care of this, that your target variable is linearly distributed or linearly related with the features that you have, right? But if you see, in case of deep learning models, there are no such constraints. The model is not assuming anything, right? So it just takes in the data, and provided that you are doing the training or you are training the model correctly by giving the correct sets of parameters, right? It tries to comes up with it will try to generalize that data into a mathematical function, right? So there are two things, right? The machine learning models, they give us convenience, right? The convenience, because you don't have to do any. So the machine learning models can be considered as, let's say, furniture that you have bought uh, from IKEA maybe, right? IKEA furniture, what you need to do, you just go ahead and you pick it up. But that might not be customizable for your specific house, right? Maybe you need something which is of a particular dimension, but what you are getting from IKEA is maybe a bigger object, or let's say a smaller object, right? You cannot customize that. So a machine learning model will be like that. Whereas a deep learning model is you going to the carpenter, getting raw wood, and then designing your own furniture, right? Which will fit your custom space. Right. So that is the difference. That is the major difference between ML and DL. And now you can see over here, there are two very stark differences. The IKEA furniture, it is all about convenience, right? You might not be looking for perfection. You might just be looking for that, okay, I need a lamp, or I need, let's say, a dining table. I don't want to invest too much time. I will just go ahead and I will buy it, right? But everyone might be having that furniture, right? Each and like if you go to your friend's house as well, they might also have the same furniture, right? But if you go ahead and if you custom design, or if you, let's say, get a dining table custom made from somewhere, it will obviously be more expensive, right? But it will fit more to the space that you have at your house, right? So first, it will be more time consuming. At IKEA, you can go ahead, you can pick the dining table within a couple of hours, it can be at your home, right? With the custom furniture, you might spend 100 times more time as compared to shopping at IKEA, right? But then the end product will be personalized to your space. The end product will be personalized to your liking, right? And that is the major difference between machine learning and deep learning, right? Non-linear data processing, obviously we have activation functions, right? So they will introduce non-linearity, right? So linear transformations plus non-linear transformations, when they work together, they do wonders, right? Fault tolerance, as you have seen, if there is any error, right, the model will try to rectify that. Through the training of the model, it will try to rectify those errors. Even if, let's say, you go ahead and you are using a deep learning model, right? And let's say that 3 months down the line, your customer behavior changes, and your model was built on, let's say, some other kind of customer behavior, right? If you're retraining the same model will be able to update its weights. You don't need to train the model again from scratch, right? So if I give you an example, so let's say before COVID, you went ahead and you trained a deep learning model, right? And then after COVID or during COVID, the customer data changed, right? So let's say that you were retraining the model after each and every month. As soon as the data of that given month is fed to the model, when the customer behavior has changed, the model will start to update its weights. It will not wait. It will not say that, okay, the data is incorrect. It will assume that the data is correct, and hence it will go ahead and it will update the weights, right? Self-repairing, fault tolerance, both of these are very similar, right? That self-repairing, once again, that it is able to repair itself. If you're training the model on a weekly, monthly, biannual basis, whatever, right? The model, by going through the distributions of the data, will automatically update the weights. Hence, it will automatically try to increase the performance of the model. So the 5 most common libraries that we have within deep learning, right? So these are these: TensorFlow, MXNet, PyTorch, Keras, and DL4j, right? So let's go through all of these. Now, see, one thing that you need to understand is that if you know how to, let's say, build model on Keras, you will it will be a very easy transition for you to, let's say, go ahead and build models on TensorFlow, right? It will be very easy for you to go ahead and build model on, let's say, PyTorch, right? So it is just like you being able to drive a Hyundai car. If you are able to drive a Hyundai car, you might also be able to drive, let's say, a Volkswagen, a Skoda, a Renault, a BMW, and Audi. It might be that there might be some differences. Maybe in a Hyundai, the indicator is towards the right hand side. Maybe in a Volkswagen, the indicator is towards the left hand side. But then still, you will be able to do that, right? It will not be a very drastic change. All right. So first is TensorFlow. Now, TensorFlow is an open source software library for high performance numerical computations. TensorFlow is a library which was developed by Google, right? The challenges with TensorFlow, now see, first of all, TensorFlow, obviously it can do anything. All of these libraries, right, they can solve any of the use cases, be it NLP, be it forecasting, be it text classification, tagging, Google Translate, be it, like, right, any level of problems you have, all of these libraries will be able to solve them. So the uh, level of complexity is not a problem for these libraries. In terms of the problem that you are solving, the complexity level is not a problem, right? Library selection depend on the size of the data. No, Aniket. Library selection generally, if I'm being totally honest, it depends upon what your client for which you're working for has on their environment or system, right? And generally your clients will have the most common libraries that I use. So right, so I have never worked on any other, like I have worked on TensorFlow and all, but from the last 4 or 5 years I have majorly worked with Keras, because Keras is a library that is easily uh, available. It has all sorts of functions. It has all sorts of libraries inside it, which will help you in building deep learning models, right? But let's say if you are working independently, then it depends upon you, right? Whichever library you are comfortable with. All of these 5 libraries are actually capable of working with huge amounts of data. They are capable of handling any kind of problem that you throw at them, right? Now, tagging is nothing but it you can take it as image tagging. So if you see in Google Photos, if you go ahead and if you upload 10 different images of yours and you go ahead and you label one image as let's say with your name, the Google Photos app will automatically update the rest of the 9 images to be of you, right? Next time when you go ahead and when you search with your name, it will give you 10 photos. Any new photo that you upload, that automatically goes to your Google Photos, right? It will automatically tag it to you, right? So tagging can have many use cases, right? So this is just one. Library selection doesn't work on the problem solved. That's what I'm saying, Kuldeep, right? All of these libraries can solve all of the problems that are out there. These libraries are not limited by, let's say, that one can solve forecasting, the other can solve text classification and all. Library is all about convenience, right? Whatever library you are comfortable with or whatever library is provided to you by your client, you will have to work on that, right? Keras is the most popular Indu. I would say 98 to 99% of the deep learning models are actually built on Keras, right? Okay. Now TensorFlow, the thing with TensorFlow is that TensorFlow is actually very complicated as compared to Keras and all. Why? Because the TensorFlow is kind of a base programming language, right? So it is more complicated. It has its own data types. It has its own processes. So TensorFlow is generally adopted by researchers, right? So I'll give you the use cases of when these libraries are used by whom. TensorFlow is a library which, let's assume that you are a researcher, right? And you are trying to come up with a new library or let's say you're trying to come up with a new optimization function for a neural network model, right? Let's say you are working on some variation of gradient descent and now you want to create a function which can be used as a library, right? So TensorFlow is generally for researchers, for people who are not doing day-to-day client work, right? Who are doing research, who are trying to make, let's say, these can be mathematical people or these can be PhDs in mathematics who are actually trying to come up with something new, right? So TensorFlow is majorly the 2% of people that I've seen using TensorFlow will be researchers, will be PhDs who are trying to better the current libraries or the current work that is out there, right? That is your TensorFlow. Now, if I come to Keras, Keras, if you see, is a high-level API around TensorFlow. At the back end, when you are using Keras, right, at the back end, it is only TensorFlow that is running, right? You can either choose TensorFlow as the backend, or you can choose Theano, or you can choose CNTK. All of these are base level programming languages, right? Which give you all the data science, all the deep learning, machine learning functions that you have, right? But what Keras does is that Keras actually simplifies the experience for you, right? Now, Keras is a library which is meant for people who are working on day-to-day jobs, right? So if your objective is to go ahead and use a model, right? Your objective is not to go ahead and uh, look into the inside mathematics. Let's say if you know that this is a random forest, or let's say this deep learning model, these are the number of hidden layers, these are the number of neurons. In Keras, it is as simple as calling a function, right? Providing all the different parameters and the internal functionalities, whatever is happening in TensorFlow, Keras is going to call that, and Keras is going to do that for you, right? So Keras is an high-level API around TensorFlow. Now, TensorFlow, I would say, is the base language over here, right? What Keras is doing is that Keras is just a wrapper around it, right? And that is why Keras is easy to use. It has all the libraries, it has all the functions that are required to build your deep learning models, right? And along with that, it is very easy to implement as well, right? So if you see, you have TensorFlow. What Keras does is that Keras creates layers on top of the on top of TensorFlow backend, and hence it actually gives you the best of both worlds. It gives you the mathematical capabilities of the TensorFlow library, along with a very easy to handle and easy to implement interface, right? Now the third one is PyTorch. Now this is once again a very similar library, a scientific computing framework developed by Facebook. Now, if you see, every major technical giant will come up with their own, right? So just like ChatGPT, if you see now, ChatGPT was launched. After that, someone else, Microsoft, went ahead and they launched something of their own. Facebook went ahead and they launched something of their own. So all of these are new. So TensorFlow and Keras, these are libraries that have been existing since uh, deep learning gained traction, right? All of these libraries, PyTorch, DL4j, MXNet, and all these libraries are fairly new, right? Now, PyTorch as well, this is Pythonic in nature, right? So in PyTorch, the plus point is that if you know Python, if you're comfortable with Python, then adopting PyTorch will be easier as compared to, let's say, other languages, uh, other libraries, right? Offers dynamic computational graphs. Now, in case of neural networks, right, in order to understand how the data is flowing, because if you see, in case of a simple perceptron as well, my input features get multiplied by weights, they pass through an activation function, the value is transformed, then we get an output, right? So all of these things can be represented through a computational graph at times. So in PyTorch, you have a function which will generate this computational graph for you. But speaking from experience, computational graphs are not things that are used a lot these days, right? Computational graphs are for those, once again, if I'll go back to the example, computational graphs are, let's say, for researchers who are trying to look inside the function and see how the transformations are happening. If you're using let's say, a deep learning model, a neural network model, and you don't have any doubts on the mathematics, right? Then obviously all you need to do is that you need to call that model. You need to use the model in a plug and play way, right? You don't need to go ahead and check the outputs, check what transformations are happening inside, because you know that, yes, you know the mathematics and you know that that works for you, right? Now DL4j, if you see now, this is a library, deep learning library, which is developed by Java, written for Java, right? A deep learning programming library written for Java. This is a base level programming language. This is, I would say, one of the most complicated uh, libraries in terms of syntax and all. Where is this used? This is majorly used for people who are taking things into production, who are, let's say, creating applications, right? Which involve, let's say, deep learning models, machine learning models, which are people who are creating products, right? Wherein your deep learning will be a component of a larger product or of a larger, let's say, application that you're building, right? So DL4j, it integrates very well with your distributed computing frameworks like Hadoop and Spark, right? And that is why it is like far more complicated. But then, uh, as I said, right, this is a library, or this is a tool that is used more by people who want to take, or who want to build applications around data science, around MLDL models, right? So that is DL4J. Can be used for any of the use cases: image recognition, fraud detection, text mining, parts of speech tagging, natural language processing, right? As I've said, all 5 libraries can solve any kind of data science use cases that we have, right? Then finally, MXNet. MXNet was uh, uh, like created by Apache Foundation, developed by Apache Software Foundation. MXNet can work with all of these, right? Python, R, Scala, Julia, right? It can also be used for all of these different use cases that are there, right? So these are the 5 major libraries that we have. Uh, During the duration of our course, we will be working with Keras majorly, right? TensorFlow, we will be having one short case study, but as I said, right, Keras is a library which is more than sufficient. And if you know how to build models on Keras, then other libraries, it will be fairly easy to pick up on them, right? Now, even if you, let's say, want to understand TensorFlow, Keras is the first step, because if you're starting with TensorFlow, you are going to something which is highly complicated. If you're starting with Keras, you are, let's say, able to achieve 50% of the complexity, then the remaining 50% you can go ahead and you can achieve while you learn TensorFlow, right? All right. So let's get started then. Simple neural network with NumPy, Vinod. Okay, so in this case study, right, we are building a simple, not even a neural network, we are building a perceptron, right? We are building a simple perceptron, and we are not using any of the libraries that we have seen, right? Neither TensorFlow nor Keras, right? Why we are doing this? I just want to show you how complicated it is, or not complicated, but how complex at least it is to build a neural network from scratch, right? Why do we have these libraries and all? Because these libraries, along with doing whatever mathematics is required, they also optimize the time, right? They will create the model in a much more faster way as compared to, let's say, if we would have gone ahead and we would have done the mathematics from scratch. It's not that you cannot do that. You will be able to do the all of this. If you are proficient in Python, you can go ahead and you can create neural networks from scratch as well. But these models will obviously be not as uh, efficient or as fast as compared to the ones that we have in the predefined libraries, right? So for this, we will be importing only our basic libraries like NumPy, Matplotlib, and Pandas, right? So I go ahead and I import the libraries. NumPy is NP, matplotlib.pyplot as PLT, and pandas as PD, right? Now, once when we have done this, I'll share, let's first try to understand what kind of a perceptron we are creating over here, right? Now, if you see, I have 3 features, right? Over here, I have X1. If you go through the code, you have X1, you have X2, and you have X3, right? If you see this X1, X2, X3, I have 3, right? And I have Y1 directly, right? This is my Y1. I have connections which are coming from here to here, right? I have connections coming from here to here. I have connections coming from here to here, and I have connections coming from here to here. So if this is my X1, right? This is my X2, right? And this is my X3, then this will become my Y, correct? So if you look at this, what I have defined over here is that X1 has a value of 4, right? X2 has a value of 5, and X3 has a value of 3. Okay. And Y is 36. So what we are doing is that over here, we have only one row of data, right? What we are looking for is something like this, right? I want an equation which will give me 36, right? So 36 is the output that I want to get. I should get that output by multiplying 4 with some weight, right? Plus, if I take 5 and multiply that by some weight, right? Plus, if I take 3 and I multiply that with some weight, right? If I go ahead and if I do this, I should be able to get the value 36. Does this make sense to everyone? Now, where will the W1, W2, and W3 be? So this, let's say this is W1, right? This is W2, and this is W3, right? So your weights are nothing but your weights are the connections that you have from X1 to Y, X2 to Y, and X3 to Y. Okay. So now the objective is what? The objective is to find out the values of W1, W2, and W3. Correct? Shall we proceed? Okay. So I have defined the values. So if you see all of the things have been mentioned here. X1, X2, X3 are the inputs, Y is the output, right? And what we are trying to do is that we are trying to go ahead and we are trying to generate uh, a perceptron model, which will go ahead and which will give me this output, right? We will try to see if this can be done. So let's start. I will initialize all the values. So the first thing that we do is that we initialize the different values. X1, X2, X3 is initialized, Y is initialized. Now, what do I need? I need my 3 variables, which will be weight, right? So because if you see weights are not defined, so what I'm doing is that, let's do one thing. So the next thing that I'm doing is that I'm defining a bunch of weights. Now, what is learning rate, right? Now, learning rate, this is something that you will be able to understand more when we are doing gradient descent. But let me try to explain this to you in simple terms. Now, learning rate is nothing but, see, when we are updating the weights, either we can update the weights by a huge factor or we can update the weights gradually, right? Now, it depends upon you when you are going to learn badminton, right? It depends upon you whether you are spending an hour a day or you are spending 10 hours a day. If you're spending, let's say, an hour a day, the learning factor might be lesser, right? But it might still be that you are gradually progressing towards a more stable learning outcome, right? What if, so if you would be, I think you would be able to relate with this, studying for 3 months at a sprint, right? Studying for 3 months for, let's say, a particular subject back in school, back in college, it was more fruitful as compared to, let's say, mugging up all of these things in, let's say, 3 days, 3 to 4 days, right? So learning rate is a parameter which tells the model by what factor it needs to update the weights. If I give a higher value, if I give a value of learning rate as a very high value, what will happen is that it is going to change the value of the weight drastically. So when it changes the value of the weight drastically, it might happen that we might miss out the correct value of the weights, right? So let's say the first iteration, my weights were 0, 0, 0. If I give a higher value of learning rate, it might happen that in the second iteration, my weights become 2, 5, and 8. Whereas my correct sets of weight might have been somewhere, let's say 1, 3, and 5, right? So I might miss on the correct sets of weight. So that is why as of now, what you need to understand is that learning rate is just a containing parameter which tries to limit the learning of the neural network. It is not. So if the neural network would have learned in 10 iterations, the learning rate is saying that I am fine, you take 1000 iterations, but I want you to be very sure that whatever weights you are coming out with are the final sets of correct weights, right? Does anyone have any question on learning rate? I think W1, W2, W3 should be clear. So because this is the first run of the neural network, I don't know the correct sets of weights as of now. So what I'm doing is that I'm initializing them as values equals to 0. And now I expect my model, I expect my neural network model to go ahead and to learn this. I leave you on the top of a mountain, right? We go on a hike. I leave you on the top of a mountain. I blindfold you, right? And you are blindfolded, right? You are standing on the top of a mountain. You are not able to see. right? And now I ask you to, the task that I give you is to, you need to come down to the, you need to come at the bottom of the mountain, right? You need to arrive at the valley, right? Where this particular mountain is situated. Now you are blindfolded. How will you proceed? What will you do? Will you take large steps? So let's say, just imagine yourself to be in such a situation. If you are blindfolded, or let's say you are at your house and power goes off, right? You are not able to see anything. It is completely dark. Do you take big steps towards your destination, or do you take small steps, baby steps, right? Because you will take a baby step and you'll see whether you are running into a wall or not, whether there is an object in front of you or not, right? So you are going to take smaller steps, right? So just like that over here as well, learning rate is that I know that I have to head in a certain direction. I know that I need to change my weights. Now if my correct sets of weight was 5, let's say I start with 0 and my correct weight was 5, I can have two approaches. Either I can go like this, 0, 0.1, 0.2, 0.3, and I reach at 5, or I can go like this, right? I can go to 0, then 2, 2 to 4, 4 to 6. If I'm doing this, if I'm taking a larger step, I might miss out on the correct sets of weight value, right? So that is why learning rate is a parameter. Now, learning rate parameter, it ranges between 0 to 1. If you keep it as a high value, it means that you are giving a higher step size. If you keep it as a smaller value, it means that you are giving a smaller step size. When the step size is smaller, it means that your model will take more time to converge. But on most occasions, that is fine with you, because at the end of the day, your objective is to find the correct sets of weights that your model needs. Okay. Is it clear now, Krishna and others? Usually, Ashwin, I think, see, anything between 0.001 to 0.1. I have never seen anyone going beyond 0.1. In a way, Nitin, yes, these are the increments for weights. These are like, this is the factor by which the weights will be increased, right? Learning rate will be applied to your weights and biases in the. This will impact performance, obviously, Ashwin. So see, if you are able to reach a destination in 100 iterations, learning rate, a small learning rate might take you to the same destination in 1,000 iterations, right? But then because we are sitting at a black box, right? I don't know that whether 100 will give me the correct or 1,000. So what I'll do is that, just to be safe, I will take small steps. I will not take larger steps. So if it is small, right, it will not impact the accuracy. Your model might take more time to converge. That is the only thing, right? Other than that, the accuracy will be actually better. All right, so let's move to this loop, right? Let's try to understand this loop first, then I will run this. So what I'm doing is that, now, if you remember, the first thing that I was talking about was that when we learn how to play a new sport, it is not that we learn it in one given day, right? We might have to repeat the same thing again and again. So if you see over here, I have defined a for loop, right? So my for loop says that this perceptron will iterate for 500 times. If you see, for Epoch, in range 500. So I'm saying that I want you to run 500 times and try to try to arrive at the best sets of weights, right? Once when I go inside, what is the first thing that I need to do? I need to do the transformation of the data. Now the linear transformation is the one that we are doing here. So what does my y pred becomes? If my y actual was 36, what does my prediction become? Prediction will be x1 into x1 into w1 plus x2 into w2 plus x3 into w3. Just focus on this line, right? Just this line. This is what I am trying to come up with, the predicted value. I know that the actual value is 36. I am trying to come up with the predicted value. And yes, in the first iteration, Ashwin, you are correct. It will be 0. Why? Because my weights have been assigned to 0, right? Atish, epoch is nothing but the number of iterations that the deep learning model or that the perceptron will do, right? Is this line clear to everyone? This is exactly what we have discussed, right? Over here, we are coming with a value. We are trying to come up with the predicted value. Now, obviously, because my weights are assigned or are initialized as random values, my prediction will be way off, right? Now, what I'll do is that I'll calculate an error, right? Now, the error that we are calculating is actual minus predicted whole square, right? Now, what was my actual value? Actual was 36, predicted was 0. So my error will be quite high, right? In this case, right, if you see, my model is only exposed to the input values, right? I am not exposing the model to the output. I am asking the model to learn. I am saying that I want an output of 36. I don't know how you want to get there, but I need an output of 36. The first iteration, the model has the weights as 0. This is equivalent to you first day going to play badminton. Maybe you don't understand anything. You only know that your end goal is that you want to play like your coach does. That is your actual. So the first day, whatever performance you are doing on the first day is your predicted, right? And that is what we are getting as 0 over here. For on the first day, you are not able to perform very well. Anuja, you can take your name. Any name can be there, right? Epoch we have taken because epoch is a variable that we have, is a parameter that we have. I'll be explaining this in detail as and when we move forward. But epoch is nothing but the number of times your data is passed to the neural network model. So that is why we have taken epoch. If you want, you can take it as any other variable. That is totally up to you. All right. Now I want you to uh, do one thing, right? I want you to, can you substitute the value of W over here and give me the output that we will get when W1, W2, W3 are all 0? See, this error function, right? This error function that we have on the x-axis, you will have the sets of weights. And on the y-axis, you will have the error, right? Something like that. Right? So on the x-axis, you have your the different values that you have. This is a function of x1, w1, w2, and w3, right? This is your x-axis. What do we have on the y-axis? On the y-axis, we have the error. If I take a square function, my error curve looks like this, right? Now, can you guys tell me that when I put W1, W2, and W3 equals to 0, the error that I'm getting, it will be on what part of this curve? Will it be towards the top side? Will it be towards the bottom side? On what location your error might be? Maybe somewhere over here, right? Error will be coming out to be what? 36? My 36 minus 0 whole squared will be what? 36 whole square. 36 whole square, whatever value that is coming out, it can be somewhere over here, maybe somewhere over here, right? Is everyone aligned on this? Now, if I would have taken just a simple error of actual minus predicted, right? If I would have taken, let's say, a simple error of actual minus predicted, my error could have been a straight line, right? And let's say in that case, when I took the weights as 0, I might have come over here, right? Now the objective over here is what? Our objective is to find the minimum of this error, right? This error, I want to come to this point. I want to arrive at the values of W1, W2, and W3 so as the error is minimum, right? In the case of a straight line, there will be no minimum value. This line can go till minus infinity, right? So that is why in order to simplify the calculation, we always take a squared error for any kinds of machine learning, deep learning models, because in case of a square error, right, what you can see is that, right, in case of a square error, your Your error can only oscillate between this curve. Your error cannot go beyond this curve. Does that make sense? Right? Now, if you see exactly, so maxima and minima, right? So for those who have studied maxima and minima in school or college, you should be able to remember this. For those who have not, don't worry. Once when we come to the gradient descent part of things, I will be explaining these things from scratch as well, right? But if you see, now all I need to do is that I need to identify the gradient, right? I need to identify the gradient, whether the gradient is positive or the gradient is negative, right? This over here, if you see, this will come out to be a negative gradient, right? If my error would have been over here, my gradient would have been positive. This we calculate by using the differentiation. I will be explaining all of this when we are talking about gradient descent. Right now, what you need to understand is that our objective is to bring this error from here to somewhere over here, right? Now, when my weight values were 0, 0, 0, my error was somewhere here. Now, can you go ahead and can you substitute the same equation with weight values equals to 1, 1, 1 and tell me what the error will be in that case? Now, if I go ahead and see, my neural network doesn't know that the error is minimum. Let's say I increase the value of weight. Now, I want you to substitute the value of W1, W2, and W3 as 4. What will the error be in that case? 4 into 4, 16, 5 into 4, 20, 36, plus 12, 48. So this will be once again 12 square. So this will once again come out to be what? 144. So when you have increased the value, so if you see over here on the x-axis, your W1, W2, W3 values will keep on changing, right? When the values were, I'm just going to write a single value. You can understand that it's for all three. When the value was 0, error was this. When the value was 1, the error was this. When the value was 2, the error was this. When it was 3, the error was this. But when it was 4, the error increased, right? So now my neural network or my perceptron, as soon as it sees that the error increases, it realizes that this is where your error is going to be the minimum, right? And it is going to stop here. It is going to take these weights as the final weights of the model. Does this explanation make sense? All right. So now if you see, right, this, now in the next few lines, what we are doing is that we are updating the weights. Now don't worry about these formulas that we have written over here. I will be explaining this again when we are going through gradient descent. Right now, we have not done that, right? So I don't want to explain this. But if you see, right, for those of you who understand differentiation, right, can you give me the differentiation of my error is what? Y minus y pred whole square. If I differentiate it, it will be 2 times y minus y pred. This explanation is only for those who understand basic differentiation, right? For people who don't understand, don't worry, right? Don't break a sweat. I will be explaining all of these things once when we are going to gradient descent, right? How slightly complicated TensorFlow can be when you compare it with Keras, right? Because as I said, TensorFlow has its own data, TensorFlow has its own functions and all. You need to convert your Python data frame into a TensorFlow data, and then only you can go ahead and you can use the functions, right? So what we are doing today is that this is just a small case study showcasing how TensorFlow works, how we need to convert our data into tensors and all, right? But for the entire duration of the course, we will be working with Keras, all right? Now, if you remember, TensorFlow was also a library which we can use in order to build our deep learning models, right? Now, what are tensors? A tensor is a multi-dimensional matrix in which in which data is stored, right? Now, just like your data frame, just like we have data frames in Python, right? Or we have arrays in Python, right? Just like that, if I want to use the library TensorFlow, I need to have my data in a tensor format, right? Now, tensor is given as an input into a neural network, right? Now, see, the comparison is if you were using Keras, you can straight away go ahead and give a pandas data frame as an input, right? You don't need to make any conversions to the data frame. But if you're using TensorFlow, in that case, you will have to pass your data to the TensorFlow functions, models, whatever, as a tensor, right? If you pass the data as a data frame, the function will give you an error, all right? So if you see, tensors are nothing but they are the data which you can feed into any deep learning model, right? Tensor rank, now depending upon the dimensionality of the data, whether your data is one dimensional, two dimensional, three dimensional, right? You find the tensor rank, right? So once again, all of these things are very similar to what we have been doing. It's just that the naming convention within TensorFlow has changed. So Aniket, that's what I'm saying, right? For TensorFlow is a library which is uh, relatively strict, right? It will not allow you to use pandas or data frame or let's say NumPy matrices as an input if you want to create a model using TensorFlow. But if you want to do the same thing in Keras will allow you to go ahead and use data frame arrays, whatever you want to use, if you want to go ahead and create models in Keras, right? Indo, if you go to the TensorFlow library page, you will find each and everything there. The documentation will be present. Right now, what is a tensor rank? A tensor rank of 0 means a scalar value, right? A scalar that is a single variable having a single value, just like s equals to 483, right? Rank equals to 1 means a one-dimensional vector, right? A one-dimensional array. So if you see vector over here, this particular vector, you can compare this to a list in pandas, right? So this is a one-dimensional list, array vector, whatever you call it. If you move to two dimensions, as soon as you move to two dimensions, it becomes a table, right? A matrix. So if you see, it will have two dimensions. One will be the row, the second will be the column, right? A tensor can be a tensor can have a rank of 3 as well. 3 tensor will be a three-dimensional data, right? And then like this, depending upon the dimensions of the data, your tensor rank will keep on increasing. All right. Now, there is something known as a computational graph. So see, a computational graph, once again, let me give you the idea. See, a computational graph is something which actually depicts how your data is progressing in a neural network, right? So let's say your input, it goes in, it gets multiplied by weights, right? It goes in through a function, through a mathematical function. After that, let's say there is one more layer. The transformed outputs once again go ahead and gets multiplied by the weights of the next layer, and so on and so forth, right? Now, if you want to basically backtrack, or if you want to see how your input is changing into an output, that is where a computational graph comes in, right? Now, a computational graph, I I have been working with deep learning models for over 7-8 years. But if you are working, let's say, as a data scientist, as a consultant, as let's say someone who is only using these deep learning models to go ahead and let's say leverage their potential to make predictions, in such cases generally you will not need a computational graph. A computational graph will mostly be required when you are, let's say, working on enhancing a particular library, or let's say enhancing a particular kind of a model, right? Now this once again will majorly be the job of researchers, or let's say PhDs, who are trying to come up with some new mathematical functions, right? But now over here, if you see, this computational graph might look to be very simple. Let's say the input to the neural network were A and B, right? So A was 10, B was 20. So both of these, let's say they get multiplied, right? Then you get a bias, you add the bias value, right? And that is where you get the output, right? Now, this you can see is a very, very simple computational graph, but you can imagine a neural network having thousands and millions of neurons. The computational graph for that will be so complicated, right? But the idea behind a computational graph is nothing but to see how your values or how your input data is getting transformed inside the neural network. Previous slide is not data type, Nitin. That is the dimensionality of the data. The first slide was tensors, which is the data type. The second slide is depending upon how many dimensions your data have, what will be the rank. The third slide is about computational graph. Okay. Now, the computational graph is executed inside a session. Now, depending upon, let's say you are doing some calculations inside TensorFlow, right? If you conduct a particular session, your computational graph will be run accordingly, right? So let's say if this is the session and this is what you're doing inside that particular session, then this computational graph will be created as and when your data is getting transformed inside the TensorFlow functions, right? Now, inside a computational graph, if you see the node, right, the node is basically, if you look at all of these multiplication and all of these things, right, these are known as the mathematical operations, and the edges are known as tensors, right? Your edges are basically the data. If you see this edge, this edge, this edge, this is the data that is flowing in, right? So the edge will be the tensor, and the nodes will be the mathematical operations that you're performing. Now, let's say if you try to create a computational graph for a perceptron, right, it will have two edges. Let's say you have two features, right? So edges will be two. Those two edges will be connected to a node. This node is going to sum up the entire uh, uh, input features after multiplying them by the weight, right? So like this, you can go ahead and you can create a computational graph, right? But again, as I said, I can speak from my experience that this is not something that you would be needing on for a day-to-day job as a data scientist, right? Because this is, we don't usually experiment with the models. We take the models as is, and then we try to tune the models, and then we try to come up with accurate predictions, right? Let's look at some of the program elements in the TensorFlow, right? Now in TensorFlow, just like in Python, we have variables, right? In Python, we have simple variables. Either it can be integer, it can be float, it can be object. In case of TensorFlow, we have three kinds of elements, right? We'll have a constant, we'll have a placeholder, and we'll have a variable, right? Now, what are these? Constants are program elements whose values do not change, right? So if you initialize something as a constant, let's say you initialize a variable as a constant, right? TF dot constant 10, then it will always remain 10 for the entire session, right? It is not going to change, right? Now, what's a placeholder? A placeholder is a program element to which we can assign data at a later stage, right? So a placeholder is something that, let's say you know that your output is going to, the output that is going to come out is going to be a string, right? So you can pre-create the variable, or you can create the variable, assign the data type, but do not assign any value. As in when you are able to fetch the value for this particular variable, you go ahead and you assign it, right? Now, if you see, these are simple operations that we have in Python, which are getting complicated over here, right? All of these operations will be handled by one single Python variable, right? If you want to assign a constant value, you can go ahead and you can assign a constant value, right? If you're not changing any variable, obviously it will not change, right? A placeholder, you don't need to define a variable beforehand, right? As and when you get an output value, you can directly save it to any variable, and depending upon the data type, it will automatically identify the data type. But over here in TensorFlow, we need to do it proactively, right? We need to go ahead and we need to define things beforehand. And finally, variable. A variable is a program element which allows us to add new trainable parameters to the graph, right? Now, variable is something. Now, if a constant is a constant, a variable is a variable that can change, that can take change the values. So your weights and biases and all of these things cannot be constant, right? If they will be constant, you cannot update them. So obviously they will be variable. So see, placeholder is thing, but let's say you go ahead and you need to get a predicted value, right? So if you see over here, when I had to get a predicted value, right, what I did was I went ahead and I just initialized a variable ypred and I assigned this value, right? In Python, I did this. But if I would have done the same thing in TensorFlow, right, I would have had to define my ypred first. I would have had to define my ypred as this, that tf.placeholder. So I need to create a memory instance for that particular output. It can be blank, right? So everything that we are doing over here in Python, in TensorFlow, it becomes slightly more complicated, right? Now see, just try to compare this with the previous example. Did we define any values as constant? I knew that I don't want to change my x1, x2, x3, right? Uh, so Ria, I think you had written W1, right? So W1 is not a constant. But if you see X1, X2, X3, and Y, these were constant values. These I did not have to change, right? In TensorFlow, I would have had to assign these values as tf.constant, right? But in Python, I just straight away go ahead and assign these values to different variables, right? Now, if you look at learning rate W1, W2, and W3, right? These values are variables, but we are not doing any separate treatment to them. Whenever we will have to go ahead and update the values, we can go ahead and we can do that. But in TensorFlow, you will have to initialize them as separate values. This is the difference that we are talking about. Okay, so you're talking from that perspective. Yes, from a modeling point of view, when you are running, you can assign the learning rate as a constant because for that particular model run, it will not change, right? All right. So now let's start working with TensorFlow. I'll just give you a quick case study on TensorFlow, right? Now we go ahead and we import the TensorFlow library, right? So import TensorFlow as TF. If you don't have TensorFlow installed, you will also have to do a pip install TensorFlow, right? I'm just commenting this out as of now, but you can go ahead and you can do that if you have not installed TensorFlow as well. You can do in collab, yes. Right now, let's see how the different types of variables works. Right now, we'll define a constant. Now, let's say if I want to define a constant which has a rank of 2, right? So this is a matrix which has 2 columns and 2 rows, right? So I can do a tf.constant and I can just go ahead and I can initialize these values. I can initialize a constant as a float. I can initialize a constant as a string. I can initialize a constant as a Boolean value, right? I can initialize the constant for all of these different types. It can be integer, it can be float, it can be string, it can be binary, right? It can be anything. So if you go ahead and if you print this, so these are the different tensors. The first tensor is this one. You are getting the shape as well and you're getting the data type as well. If you see, automatically it has been able to figure out the shape and the data type. The second one, the shape is 0. Why? Because the rank is 0. It is just a single variable and automatically it has been able to identify the data type as float, right? The third one is Sparta. This is a string. The fourth one is false, which is the data type Boolean, right? So you did not go ahead and you did not manually mention that this is a Boolean variable, this is a string variable and all, but it was able to identify it automatically, right? Now, even if you have to do a simple thing as, let's say, adding two constants or let's say multiplying two constants, either you need to declare these values before, right? And then you need to add the variables, or you will have to tell TensorFlow that this is a constant of 50, this is a constant of value 10. You need to go ahead and you need to add these. You need to multiply these, right? See, the objective of this case study is for you to compare this with your general pandas and NumPy. right? Just keep on comparing how all of these things can be done in only a single step in Python, NumPy, using pandas and NumPy, which by using TensorFlow seems to be slightly more complicated, right? Now, if you see, if you want to print the outputs, so addition output, multiplication output, anything you can go ahead and you can print. Okay. You can also do the addition and multiplication. It's not that the addition multiplication can only be done to your variables, one-dimensional variables or zero-dimensional variables, right? You can also go ahead and add lists, add matrices, arrays, whatever, right? So addition, if you see tf dot constant, I had this and I had this. I go ahead and I add the two and I go ahead and I multiply the two, and you will get, this will be a normal addition and a normal multiplication. This will not be matrix multiplication, right? If you see, this is a normal multiplication. 1 into 5 becomes 5, 2 into 4 becomes 8, 3 into 3, 9, 4 into 2, 8, and 5 into 1, 5, right? And addition, obviously, 1 plus 5, 2 plus 4, 3 plus 2, 4 plus 1, 4 plus 2, and so on and so forth, right? Now, similarly, you can do this for strings as well. You have two strings, I love, and then you have TensorFlow. You can go ahead and you can print them together. All right. Now, let's move on to the second part. Now, we need to, there is something known as eager execution, right? Eager execution is that if you want to run, now see, at times TensorFlow is also used to do things in a batch, right? You would want to, let's say, define 20 lines of code, and once when all the lines are defined, only then you would want TensorFlow to run it, right? So if you want to do something like this, then uh, eager execution needs to be turned off. By default, it will be turned off only, right? If you disable eager execution, then what will happen is that as soon as and when you are running each and every line, right, TensorFlow will go ahead and TensorFlow will generate the output. Otherwise, you will have to go ahead and you will have to generate the DAG, right? And then you can go ahead and you can get the output. So over here, because we want the outputs after each and every line, right? That's why we are disabling eager execution. So that means that as and when we are going to run the different lines, they are going to execute and they are going to give us the output, right? So now what we do is that, see, what I've done is that I've created a placeholder, right? I have not assigned any value, tf.placeholder, and this placeholder is a string, right? This can be anything. I could have given tf.float, tf.int, anything. But what I've done is that I've given tf.string over here, right? Now, I assign this particular string name1 equals to I am plus string name, right? And this string name will obviously be blank, right? If you see this, this is right now string name does not have any value to it, right? Now, if I do a session.run, right? I run this particular session, okay, and I call this name1 variable, and within name1, I pass the string name as Sam, right? So at the time of execution, this placeholder will be allocated the value Sam, right? If you see this, right? Now over here, if you see, we have the placeholder, tf.placeholder. That placeholder is a float, right? And we are creating a mathematical operation. So b equals to a plus 10. A does not have any value to it, right? So now what I do is that with tf.session as session, so I am basically creating a new session. Inside the session, what I am doing is that I am passing the different values that a will have, right? So session.run, I run the session, right? And I want to print the value of b. In the value of b, there is a variable which is a, which is not provided, right? So I create a dictionary, a feed dict, which will have the values of a, 10, 20, 30, 40. So what will happen is that inside this particular session, this will be run 4 times because a has 4 different values. And once when I run this, right, it will give me 10 plus 10, 20 plus 10, 30 plus 10, and 40 plus 10, each and every variable. So if you see the same variable that is A, that is the same placeholder, can assume different values over here, right? Now, see, this is a very simple operation which has been made complicated in TensorFlow. In Python, if I had to do this, I would have gone ahead and I would have applied a for loop straight away, right? But this is a very simple operation. This is a typical example of why TensorFlow is not used as much as Keras, because simple things which were very simple, or things which are very simple in Python, pandas and all, right, have been made way more complicated in TensorFlow. If you have any placeholders, or if you have any sequence of steps that you want to perform, which is a combination of your constants, variables, placeholders and all, you will be using sessions, right? Now see guys, the point over here is not to go too deep into this, because as I've said, we will not be exploring TensorFlow. The objective of me, like, of showing this case study, right, was to just showcase to you how complicated TensorFlow can be in doing basic things, right? When compared to your typical Python. So all of these basic things right now, I'm assuming you guys will be able to do pretty seamlessly in Python. But in TensorFlow, everything changes, right? Simple things will become slightly more complicated. Hence, see, it is not that this is not useful. All of this is very useful, but when you are creating large scalable frameworks, right? If you want to, let's say, do something in a very scalable fashion, if you want to, let's say, launch a product, if you want to let's say create an application and all, in those cases TensorFlow will obviously outperform your Keras and all, right? But for our objective, for us to learn, and even for your, from a work point of view as well, right, 95 to 98% cases, Keras will do the job for you, because the first testing that you do, that you will always do in Keras, right? The data scientist's job is to go ahead and come up with a prototype model. If let's say that model becomes, if the model gets approval from your business, then you need to sit with your production team, the DevOps team, and then you need to, they will actually help you in scaling the code up and taking it to a level which can be delivered to a larger audience, right? So that's what, that if you are able to code conveniently in some other language, if you go ahead and if you do that, that is what a data scientist is expected to do. Because production, taking a model into production, for that there are different teams. There are DevOps teams who will actually take your code, right, make it scalable. Maybe they need to convert it into a TensorFlow code for that. Maybe they don't need to do that. Maybe they just go ahead and they serve it using any other platform, right? Maybe Kubernetes, maybe something like that, right? Indo, it's quite the opposite. If you go ahead and if you see 100 job requirements, TensorFlow, I don't think will be written in more than 4 to 5 of them, right? Generally, people go ahead and people write everything. The HR teams and all, they will go ahead and they will write machine learning, deep learning, Keras, TensorFlow, XYZ, whatnot, right? But if you go deep down into the role, right, you will realize that people are mostly using Keras, right? Either Keras, nowadays people are more into using, let's say, your uh, GCP, Microsoft Azure functions, right? Your GCP and all have pre-built models, right? So people are not even using Python and Keras. They are finding that even way more complicated. Machine learning, deep learning models can be used in NLP. The only thing that is different in NLP is the uh, data pre-processing part, right? Now, the machine learning and the deep learning models that we are seeing, they are generally working on structured data, right? So no mathematical model can work on text data and all. So then what we do is that there are certain pre-processing steps where we convert that text data into a numerical form. So you can apply that to any NLP problem, these pre-processing steps. After that, you can go ahead and you can build your machine learning, deep learning models, whatever you are comfortable with. So NLP is not a part of deep learning. NLP is actually non-linear problems, right? See, a single layer perceptron, the one that we had built last time, it can help us in solving, let's say, something like this, right? Now, let's say if there are three green dots and one blue dot, and if I want a line that will separate this out, right? The single layer perceptron can do this, right? So if you see, I can go ahead and I can get the equation of a straight line, which is able to dissect both of these, the green and the blue points separately, right? But if I have something, if I have a problem which is non-linear in nature, right? A non-linear problem, such as if you look at this, right? There are three green dots that are present over here, and then there are two blue dots that are present over here, right? So in such cases, your single layer perceptron, because it is only a single neuron, right? It will not be able to effectively capture this particular output, right? So when the perceptron was being experimented on back in 1970s, I think, right? At that point of time, they realized that the perceptron was easily able to work with AND gates, OR gates, and all of these, right? But the XOR gate, right? If you remember, the XOR gate is what? If either of the values are 0 or 1, right? If both of the values are either 0 or 1, then the output will be 1. If any of the values become 0 or become 1, right, the output will not be 1. If you remember, the XOR output for XOR looks like this, right? Let's say you have A and B, and if you have the XOR output, if A is 0, B is 0, this will be 1. If A is 0, this is 1, this will be 0. If this is 1, this is 0, this will be 0. If this is 1, this is 1, then this will be 1, right? Now, this kind
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
of a relationship, your perceptron will not be able to solve individually, right? If I have a couple of perceptrons working together, maybe they can, right? Because see, a single perceptron can come up with a single equation of a line, right? Something like this. So that is fine. But over here, I cannot have a single line which can uh, dissect these points into similar spaces, right? I cannot have that. If I have two perceptrons working together, maybe then I can go ahead and I can create a linear boundary, right? Okay, so if you see, a single layer perceptron can only linearly separate problems, right? If the problem is not linearly separable, the learning process of a perceptron will never reach a point where all points are classified correctly. Boolean and or functions are linearly separable, whereas Boolean XOR function is not. So my perceptron can work decently with and or functions, but with the XOR function, the XOR function, your perceptron will not be able to figure out, right? Now, see, if the perceptron is not able to figure out non-linearly separable problems, then obviously it is not helpful to us, right? So then in that case, we need to do something which is way more complicated, right? And that is where the inception of the neural network happened, right? People thought that if a single neuron is able to give us a single decision boundary, what if we combine multiple neurons together, right? Along with that, what if we introduce an activation function which will make the boundaries to be nonlinear as well, right? So that is where the inception or the need for the neural network actually was created, and that is why we are studying neural networks now, right? So if you see, this is the problem, everything is same over here. A single layer perceptron won't be able to solve complex problems such as image classification. In such kinds of problems, dimensionality and complexity of the classification is very high, right? Obviously, if it is not able to solve a simple problem as a XOR gate, right, it will not be able to solve more complicated problems, right? And we know that neural networks are able to solve so many highly complicated problems, right? So that means that now, first of all, let's see some of the real life problems which a perceptron cannot solve, right? So let's say a complicated problem. Let's say that you have a problem which is this, right? So consider a case where you own an e-commerce firm, right? Let's say Amazon, Flipkart, something like that. You own them. You have planned to increase the traffic on your site by providing a special discount on the products and services, right? Now, you want to create awareness amongst your customers regarding this end of season sale by marketing on different portals like Google Ads, personal emails, sales, YouTube ads on different sites, LinkedIn, and so on, right? Now, this task is too complex for a human to analyze. As you can see that the number of parameters is quite high, right? Let us try to solve it using deep learning. Now, let's try to understand this problem first, right? What is the problem? See, assume that you are an e-commerce uh, firm owner, right? And you decide to come up with the end of season sale, right? Now, the end users of your website, of your application, will be people belonging to different stages of life, right? They can be youngsters, they can be teenagers, they can be, let's say, people who are working, they can be people who are married with kids, people who are not married, right? They can be people who are, let's say, greater than 40-50 years old, married with people who with children who are teens, right? We can have people who are retired. Now, depending upon what life stage you are in, obviously it depends the kind of communication that will be effective on you, right? Now, let's say a teenager might respond more to social media ads, right? Let's say someone who is in the age of 40 to 45 might respond more to websites, right? Maybe someone who is 60 plus might respond more to, let's say, a newspaper based communication, right? So in order to identify what marketing channels are effective, right, it's not that only one single channel might be effective. It might happen that Google ads are helping a specific genre of your customers, right? It might happen that a YouTube ad is catering to some other part of your customers, right? So you need to figure out how you need to spend on the different marketing channels, right? So that is what we are trying to see, and if we can solve this using a perceptron. Exactly, Bhagirath, right? So now if you see marketing, if I have, let's say, $1 billion, I have $1 million that I have to spend on marketing efforts, right? How do I distribute that, right? Do I distribute it to email, direct mailers, paid ads, referral programs, social media, and so on and so forth, right? You can either just use one platform for publicity or use a variety of them. Each of them will have its own advantages and disadvantages, but lots of factors would have to be considered. The increased traffic on your portal or the number of sales that would happen is dependent on different categorical inputs, their categories and their parameters, right? Now, computing and calculating profit in terms of popularity and sales from so many inputs and their subcategories is not possible just for one perceptron, right? Now, if you see over here, if in this situation, I had a single perceptron, right? Now, a single perceptron might be able to focus on, let's say, one particular marketing channel, right? But it will not be able to come up with non-linear interactions that all of these channels might be having, right? So if you look at this, so now you know, right? So if you look at this, this is a single perceptron, right? Now a single perceptron, if I go ahead and if I pass all of these inputs together, right? Now let's assume that there is a customer, there is a type of a customer who responds better to emails, right? And this customer also responds better to social media, right? Now let's say that there will be a fraction of customers who will be of this type, right? Now there can also be a customer, let's say, who only responds well to organic search, right? And let's say direct mailers, right? Now this is a person who does not use social media. He or she, they do not access any emails outside of work, right? They only are triggered by, let's say, direct emails or organic search that they are doing on their own, right? Now, you can also have, let's say, a group of people who respond well to referrals and, let's say, paid ads, right? Now, there are three kinds of people over here, right? Now, do you think that a single perceptron will be able to capture as many inputs? See, it can capture one kind of an interaction. It can go ahead and it can say that, okay, either the people who are responding to emails and social media, it can go ahead and it can generalize that, or it can generalize referral programs and paid ads, or direct and organic search, right? But it cannot do all three on its own. Right. So what if we don't have a single perceptron? What if we have multiple perceptrons, right? Now, if you see, before getting into the solution, let's recall one of the previously discussed topics, that was a feed-forward network, right? Now, this was a feed-forward neural network. If you remember, I think this should be clear to everyone, right? We had input data, we had a hidden layer which contained multiple neurons, and we had certain outputs, right? Now, this, I believe, everyone should be able to remember. Feed-forward neural network is the most simple artificial neural network containing multiple nodes arranged in multiple layers. Adjacent layer nodes have connections or edges where all connections are weighted, right? So your input layer, your hidden layer, your output layer, everything will be connected. All of these layers will be connected, and you will have a feed forward loop which will give you an output. There will be a backward loop which is going to update the errors and the weights, right? And on the basis of that, the training happens. So this was the typical structure of a neural network that we have studied about. What happens inside these neurons? Inside these neurons, there will be a linear transformation. That is nothing but your weights getting multiplied by the input values, followed by a non-linear transformation, that is the activation function. So now let's try to discuss the same problem that we have talked about before, right? The same problem. Now let's try to see how a multi-layer perceptron or a neural network will help us in solving this problem, right? Now, a multi-layer perceptron or a artificial neural network or a deep neural network, right, is, if you see, an MLP is a deep artificial neural network, right? So see, your ANN artificial neural network, it has multiple names. If I come to you and if I say that you need to create a multi-level perceptron, multi-layer perceptron, that is a neural network. If I ask you to create a deep neural network, it is a neural network, right? If I ask you to create a feed-forward network, that is a neural network, right? If I ask to create an ANN model, artificial neural network, that is also a neural network. So there are many names to the same model. Okay. Now, an MLP is comprised of input layers. Input will be your features. Output layer, output will be the output, and a set of hidden layers. Depending upon the architecture of the model, it will have a set of hidden layers, right? Each node apart from the input nodes will have a non-linear activation function, right? If you remember, apart from the input node, there will be activation functions that will be present in each and every layer, right? For each and every neuron. An MLP uses backpropagation as a supervised learning technique. Backpropagation, the same thing that we have studied in the case of perceptrons, that your error will be calculated. After calculating the error, your gradient descent will come into play and it will adjust the weights, right? So now let's try to see how the MLP will solve this kind of a problem, right? Now, this is nothing but this is showing how the transformation is happening. Now, if I have the input layer, right? If you see, if I have features X1 and X2, right? If I look at this particular neuron, so what is happening inside this particular neuron is the linear summation. So first of all, if you see W0, right, is the weight associated with the bias. So W0 into 1 will become the constant value. Plus W1 is this weight multiplied by X1 plus W2 into X2. Right. So if you see just this part, that is just this equation inside this is the linear transformation. After that, if you see this linear transformed value is being passed to a function, right? This function is nothing but the activation function that is present inside the neuron, right? So output from the highlighted neuron, if you look at this neuron, the output will be what? This linearly transformed value, right? W0 into 1, W1 into X1, W2 into X2, passed through an activation function. If you look at this denomination, this is function receiving the input as this particular value. Whatever output comes out, that will be the output from this particular neuron. All right. So if you see 3 nodes, input layer, bias is there, your features are there. I think all of this is clear to everyone. Y1 and Y2 are outputs, right? Then you will have the hidden layer. Hidden layer will have your hidden layer neurons. Hidden layer neurons will have the linear and the nonlinear transformation. So these are all the same things that we have talked about previously, right? And then we will have the output layer. The output layer will be will be getting the outputs from the neurons of the hidden layer, and these neurons are going to give you the final output. So outputs of each perceptron becomes inputs of MLP. Not output. See, each and every perceptron, if you see this orange node, right, neuron is a perceptron in its own, right? If you see this, if you look at this, this is a perceptron on its own, right? One single neuron taking in 3 inputs, right? All the values going into this neuron, and this particular neuron giving 2 outputs. See, that is just how the architecture is shown over here. In this case, maybe they require 2 outputs. This is just a, they're just showcasing how a neural network works over here. Y1 and Y2 will be predictions, right? They will not be averages. They will be predictions. So let's assume you have a categorical variable which has 2 values, right? Let's say buy or not buy, or let's say rain or not rain, right? So the Y1 node will have the predicted probability for, let's say, rain. Y2 will have the predicted probability for, let's say, not rain. There will be 2 separate outputs, right, Ashwin? How can the output be average of Y1 and Y2? If you want to predict whether it is going to rain or not rain, let's say if rain probability is 90%, not rain is 10%, will the final output be the average of 90 and 10%? Are you interested in that? You are interested in finding out whether it will rain or not rain. If the probability of raining is 90%, that means that it is going to rain. Just like how it used to work in the classification models, when you were working with decision tree based models, logistic regression and all, if you have worked on it properly, you will realize that the logistic regression model gives out 2 probabilities, right? It will give out the probability, one probability as, let's say, of true and the second probability of false. Then you will have to choose the probability that you are interested in. What if you have 3 classes to predict? In that case, will you have one particular output? What if you have to predict whether it is going to rain, whether it is going to snow, whether it is going to be a windstorm? See, the outputs will be 3, right? Now, on the basis of that, let's say on that day, you get that the probability of snow is high, 90%. Then you go ahead and you take that particular probability, which is the highest, and you say that it is going to snow today, right? Right? And let's say social media. So the weightages associated with this neuron will be high for emails and social media, and it will be low for all of these or equal to 0, right? Let's say that there is a person who only responds to organic search or direct mailers, and let's say to a certain extent, this person also responds to paid ads, right? Now, it might happen that the weightage associated to this one is high, right? So let's say the weightage to this is 0.5, but the weightage to this, the paid ads, let's say that the weight over here is only 0.01. So the neural network will be able to alter the weights, right? Now, there can be one person who responds to every kind of marketing, right? Let's say that there is one person who responds to each and every kind of marketing, but the weights associated with all of these will be, let's say, are not very high. Let's say the weights are low. So for this person's case, the weights coming from all of these neurons might be very, very small, right? So if you see what this neural network will do is that this will capture different interactions. Now, let's say a new customer comes in, right? A new customer comes in, and for this customer, this is a kind of a customer who responds more to emails and social media. So in that case, what will happen is that this particular neuron is going to fire. All of the rest of the neurons are not going to fire. And using the data of this customer, the model is going to tell me whether or not this particular person will go ahead and buy whatever, or let's say whether or not this person will be a part of the sale or buy something in the sale. Have you guys not have you guys not done machine learning before this? We have the target variable, right? Or don't we have the target variable? So the target variable will tell, right? See, all of this is historical data. Historical data will train the model. If I see historically that Abhishek has been responding to emails and direct ads, right? And Abhishek is a 20-year-old BTech student who is living in Bangalore, right? Now, let's say someone else comes, right? So let's say a new person comes. This particular person, let's say uh, someone else, right? Let's say Dheeraj, right? Now, Dheeraj is also a 20-year-old male. He is also complete. He has also done his BTech and he is also living in Bangalore, right? Now, for Dheeraj, can I go ahead and can I say with confidence that this person will also respond to emails and let's say social media campaigns? All right. So if you see in this case, right, in this particular case, what a perceptron was not able to do was the perceptron was not able to come up with different interactions. Now, this neural network can identify different kinds of people. It can identify teenagers, right? Maybe the effect of teenagers is captured in one particular neuron. It can identify old age people. Maybe that effect is captured in some other neuron. Whenever an old age person's data is going to come to the neural network, that particular neuron will fire, which has all the elements that an old age person usually responds to, right? So that is why neural networks will be more capable in solving such kinds of complicated problems. That depends upon the activation function. Ashwin, we have gone through all of this before. If you remember, we have gone through the activation functions. If my activation function is a continuous activation function, right? Let's say a linear function, in that case, it will give me a linear output. And all of these things I have covered previously, that if it is a regression problem, the output layer will have only one single neuron. If it is a categorical problem, the output layer will have as many number of neurons as the unique values that your target variable has, right? I'm not sure. See, this is what I've been talking about right from day one. If the basics are not clear, you will get confused towards the end. I am requesting this once again because I cannot solve all of these basic doubts time and again, right? All of these concepts have been covered in the initial sessions. And that is why from last week onwards, I was saying that just make sure that you are able to understand whatever we have covered till now. So make sure that you go through that as well, because all of that, all of what we have done till now, we are going to tie that up together, right? And it will get confusing if you have not gone through that. If you just attend these sessions and then you come the next day, you are not doing your homework, you are not going through the deck, you are not going through the content, obviously it will get confusing. So I hope the need for perceptron is clear now. The need for a neural network model and the limitation of a perceptron is clear now to everyone. A perceptron can only identify singular patterns, right? Whereas a neural network, which is a combination of perceptrons, will be able to identify multiple different patterns, and it will be able to create one big network out of that, right? Which will obviously be able to solve much more complicated problems. All right. Now let's take one more example. Now this example is with data, right? Now let's say suppose we have the following students marks data set, right? We have the hours studied and we have the midterm marks, right? Now let's say hours studied are 35, midterm marks are 67, final results are 1, right? Hours studied 12, midterm marks 75, final result 0, right? Now the two input columns show the number of hours each student has studied and the midterm marks, and the final result is the target variable that we have to predict, right? Let's see how we can do this using a neural network. Now, suppose we want to predict whether a student studying 25 hours and 70 marks in the midterm will pass the final term or not, right? This is our test data, right? If you see, this was our training data, right? I will go ahead and I will train my model using this particular data, right? And then once when my model is trained, I need to make a prediction on this student, right? For this student, the hours studied are 25 and the midterm marks that the student has gotten are 70. I need to predict whether this student will pass or not pass, right? What kind of a problem is this? This is a binary classification problem. I have two I have a target variable which has two unique values, right? Now let's see how the neural network will go ahead and how the neural network will try to identify, or how the neural network will train itself, right? The process by which the multi-layer perceptron learns is called backpropagation, right? That is what we will be learning now. All right, so let's do one thing. I will not proceed further because this example is slightly longer. I don't think that we will be able to cover this in 10 minutes. And I can see that there are many doubts that you guys are having. So let's not proceed further for today at least. I will be giving you 10 minutes for questions, right? Any questions, any doubts that you guys have, you can ask those now, right? Because this particular example is fairly mathematical. I can see that there is confusion already, so I don't want to confuse you even further. Take today's time, go through the concepts that we have covered, make sure that you are able to understand everything. Before we start tomorrow, ask questions, right? Before we start, you can ask as many questions as you want. If you have gone through the theory, if you have gone through the previous sessions, ask those questions, right? But once when we start the session, then if you are going back 3 sessions, right, and you are asking questions from there, then it will break the momentum of the entire class, right? So let's stop here for today. For those of you who have questions till here, right, till this particular point, you can go ahead and ask them. Mosmi, see, neuron is a single unit, right? Now, if you see, if you look at this particular example, if you look at this is a neuron, okay? But if you look at the entire connections that this particular neuron has, right? Now I want you to focus on all the inputs that this particular neuron is getting and all the outputs that this particular neuron is giving. If you focus on that, what will that be? That will be this, right? All of these blue dots are the inputs, right? If you see, all of these blue are connected to this green neuron, and these two outputs are coming out from this green neuron, right? So this will be a perceptron. Okay. All right, Bhagirath, thank you. For those who don't have any questions, you can drop off. Right? No need to stay. Eager execution, Prageet, eager execution is nothing but, see, in the case of eager execution, as soon as your session runs, you will get an output. If eager execution is turned off, then you will have to create a DAG each and every time, right? So, see, my suggestion would be don't get confused on those things, TensorFlow and all, right? Right now, pay more focus to the neural network aspect of things. right? Eager execution, this is just one command that we give in order to get the outputs faster, right? So nth layer in the network, by nth layer, do you mean the last layer, output layer, or do you mean the hidden layer? Last hidden layer, it can happen that the last hidden layer has 200 neurons, but the output layer has only 2 neurons. So in that case, the 200 neurons from the last hidden layer will have connections to the 2 neurons in the output layer, right? So it is not a one-to-one mapping. You don't have to go ahead and, let's say, if your output has only 2 neurons, your last hidden layer will also have only 2 neurons, right? That is not how it works. Your hidden layer can have any number of neurons, right? Then depending upon the output layer, let's say if the output layer has 2, then whatever number of neurons you had in the hidden layer, they will be connected with these 2 neurons, right? And depending upon the weightages, they are going to see. So let's say for output layer number 1, out of the 200 neurons, there are 50 neurons which are contributing to the output node 1. So they will have connections. Maybe for output node number 2, there are 120 neurons that have a connection, right? So they will go ahead and they will set up a connection with the output layer. Right, so this is a categorical problem statement, classification problem. So our target variable will be final results, which either can take value 1 or 0, and the features will be R studied and the midterm marks, right? So, and using this data, we want to create a model, right? And then using that model, I want to make predictions for a new entry, which is this student who has studied for 25 hours and has gotten 70 midterm marks, right? We need to predict for this student whether this particular student will pass or not pass, right? So this is a binary classification problem where a multi-layer perceptron can learn from the given examples, right? So now what we'll do is that we'll go ahead and we will see how an MLP model actually fits itself or trains itself on such kind of a data, right? Now, the process by which a multi-layer perceptron learns is called backpropagation, right? I believe this is something that I had talked about previously, not in detail. We are going to start talking about this in detail in this particular module. But if you remember, the any perceptron, MLP, whatever we have, it will have two components, right? The first will be the forward propagation. In the forward propagation, we go ahead and we multiply the feature with the weight values. We do the mathematical transformation and all, and we get to a predicted value, right? Now, because for the first iteration, my weights would have been random values, my predicted value will also be way off, right? Then what we do is that we compare the predicted value with the actual value and we try to adjust the direction of the weights so that the error will actually go down, right? So this component of identifying the error and then redistributing the error to the different weights is known as backpropagation, right? So now let's try to understand how the neural network will train itself over here in this particular case. If you look at this, if I go back to my data, the first row in my data was what? Was 35 hours and 67 marks, right? So let's go through this and let's see. So my input, which is 35 and 67, goes into this neural network model, right? Now, when I will give that particular input, the 35 and 67, with the random sets of weight values, which would have been given to the neural network in the first iteration, right? I will get some output for my output neurons, right? So assume that the predicted output, right, the predicted probability for this particular row comes out to be 0.4 for the as the probability of passing and 0.6 as the probability of failing, right? How did that probability come to? All of that we are going to see slowly, but right now let's just try to understand what happens in the backward propagation. Okay, so let's assume that this sorry, so if you see this 0.4, right, and this 0.6, These are the probabilities, these are the predicted probabilities that would have come out from this particular, from these two output neurons, right? So this output neuron would have given this 0.4, this output neuron would have given this 0.6, right? So now what will I do? I need to calculate the probability of pass and fail, right? I have my actual value. My actual value for this data point, do you guys remember what was it? Was it a pass or a fail? For 35 hours studied and 67 midterm marks. So if you look at this over here in this data, this particular student had actually passed, right? With these marks and these many hours studied, this student was a pass. So my actual data will become what? My actual data will become 1, right? So that's why you see a 1 over here. So actually the student had passed, but the probability of passing that I am getting after the first iteration is 0.4, right? So my error will be what? My error will be 0.6. Okay. Now, similarly, if you see the probability of fail, actually, in reality, my student has actually passed. So probability of fail, the actual probability of fail is 0, right? Whereas my model is saying that this probability is 0.6, right? So your probability of fail, so from this as well, you can calculate the error value, right? So this is incorrect over here. This should be minus 0.6 only. Actually, this should be error square, but just to keep this simple, they have gone ahead and they have just created the error value, right? This is just to explain how the backward propagation happens, right? So if you see, the figure has two nodes in the input layer, which takes the hours studied and the midterm marks. These features will go into these two neurons. It also has a hidden layer with two nodes. The output layer has two nodes as well, with the probability of pass and fail, right? Okay. Now, yeah, this node, if you see, right, this node on top, what they have done is that they have just gone ahead and denoted the bias as a node only, as a neuron, just to make things simple. If you see, this one is nothing but your bias node, right? This will also have a weight attached to it. Now, let's say if the constant value needs to be 5, the value of the weight W1 will become 5, and 5 multiplied by 1 will become 5 only, right? Similarly, for the output node as well, this is the bias value. Okay. Now, in classification, we generally use a softmax function as the activation function to ensure that the outputs are probabilities and they add up to 1. If you remember, when we were studying about the different functions, activation functions, I had told you that the softmax function is a function if you have more than 2 classes, right? 3 classes, then what it does is that it gives you all the probabilities, the summation of all the output probabilities that are coming out, the summation of that will be 1, right? Tanushri, softmax can be used for any, right? Multi-class is basically more than one class, right? So 2 is also multi. Okay. Now, if you see, this is the same explanation. They are explaining what will happen. Now, when 35 and 67 are fed to this particular neural network, what will happen is that with the initialized sets of weights and bias values, we are going to get a predicted value, right? What will happen for this 35 and 67, the linear transformation will happen. These values will get multiplied by W2 and W3 bias. You're going to add that. Then this goes into the different neurons. The different neurons are going to apply the functions, the mathematical functions, and they are going to transform the value, right? And then similarly, one output will come out. This output will get multiplied by the weight over here, right? And then for the output neuron, whatever function you are using, that particular function will do a final transformation of the output. I've explained this just now. This is nothing but your bias value. Your bias, we have given the neuron as value 1. When we give the value as 1, whenever it gets multiplied by any weight value, right? Weight will be what? Weight will be a numeric value only. So this will become a constant. Just to make the visualization simple, we have gone ahead and we have put the bias in a neuron. Now, suppose the output probabilities from the two nodes are 0.4 and 0.6, right? So what will happen is that because the weights will be random, the output probabilities are also not going to be correct. So let's assume that the probabilities were 0.4 and 0.6, right? Calculated probabilities are very far away from the desired probabilities, right? If you see 0.4, the model is giving us the probability of passing, 0.6 as failing, which is very far compared to the desired probabilities, right? Hence, the network in the figure is said to have an incorrect output, right? Now, because I have an actual label, I can go ahead and I can compare whether the predicted value is closer to the actual or not. If it is not, then I will go to the backward pass, right? Now, if you see in the second step, what we do is that we do a backward propagation and we update the weights, right? We calculate the errors, right? So if you see over here, once when the forward pass has happened, we go ahead and we calculate the error, right? And once when we have calculated the error, then we use an optimization method, right? Such as gradient descent to adjust all weights in the network with an aim to reduce the errors at the output layer, right? Now, this is also the same thing. What we do once when we have calculated the error, we go back and we try to redistribute the weights, right? Now, this is as simple as, let's say you go ahead and you apply for a competitive test, right? Let's say you go ahead and you apply for CAT examination, right? And let's say you went ahead and you gave the test and you got some marks, right? Let's say the CAT was of 240 marks, whatever, I'm not sure, right? And you were able to score 120, right? So once when you know that, okay, the aim for you was 240, maybe 200, but you scored 120. What is it that you do? You will come back home and you are going to see what were the questions that you were able to work on, what were the questions that you were not able to work on, right? Let's say you are able to identify certain topics for which you were not able to answer any questions, or let's say you were not able to answer most of the questions. What will you do? You are going to go ahead and maybe the next time you are going to lay more focus on those topics, right? Just like that over here as well, when we get the error, we come back and we see which neurons are actually contributing more to the error value, right? And that is the gradient descent part that happens. How gradient descent helps us in doing that, all of that we'll be covering in this slide only. Gradient descent is also a hyperparameter, Bhagirath, because there are different variations of the gradient descent model, and along with that, the learning rate, right? If you see, the learning rate is nothing but learning rate is associated to the gradient descent technique only. So learning rate becomes a hyperparameter. Along with that, the kind of gradient descent that you have to use, that also becomes a hyperparameter. Now, if you see, this is what happens in backward propagation, right? If you see in backward propagation, we try to adjust the weights for each and every neuron, right? Now, what exactly happens over here? So let's now not get into the mathematics of this because gradient descent is a separate topic in this deck only. But so just for now, you can just imagine that gradient descent will give you an output and it will tell you how for the different nodes, do you want to increase the value of the weights or do you want to decrease the value of weights? Once again, I will reiterate, gradient descent is a separate topic in this slide only. Once when we reach that, we are going to talk about that, right? For now, let's just try to understand once when the weights have been updated, then what happens, right? So all of this that you are seeing, right? Dy by dx and all, d error by dw, all of these things we will be covering. But for this slide, just try to understand that whatever error we would have gotten, that error would be fed to the gradient descent model, and the gradient descent then will come out with the adjustment factors for each and every neuron that are there in the hidden layers, right? So that is where the weight updates will happen. So once when you are able to update the weights, right? Now let's say what happens is that you went ahead and you were able to update the weight of all these connections, right? All these weights will be updated, all of these weights will be updated, right? Now, let's say in the second iteration, when you feed in the same data, the 35 and 67 to the model, this time, let's assume what happens is that the probability of pass becomes 0.8. This is the predicted probability, and the probability of fail becomes 0.2, right? Now, if you see, the error has actually reduced. Previously, my error was quite high, right? It was close to 0.6 and 0.6, right? Now my error has actually reduced to 0.2 and minus 0.2. Okay. Now, if you see, this process goes on happening, it goes on and on and on until your error has been minimized. So now if you see this training that has happened, we have shown this for only one particular row, but what will happen is that all the rows of the model will be passed, right? And the weights will be adjusted accordingly, right? Once when the training has happened, now what we need to do is that, once when the training would have had happened, I would have gotten all of these weight values, right? Now, let's say that the model had these many weights, right? So you'll have a weight for bias. So let's say this was 0.4, right? Let's say this was 0.3. Let's say this was 0.2, right? Similarly, you will have the weights from here to here, all the connections. So once when the training would have had happened, it means that you have been able to identify all the weights and bias values for the model, right? Now, any new data point that comes in, all we have to do is that we have to feed that data point to the model, right? Now, let's say for 25 hours and 70 marks, I will give the 25 and 70 over here. Because I know the weights of my model, the model will go ahead and make a prediction, right? It can be a probability of pass can be high, or the probability of fail can be high, right? So this is how typically your neural networks or your multi-layer perceptrons work. Okay. And now we will be getting into the mathematics of each and every aspect, right? The back propagation, the gradient descent, all of these things. Forward propagation, I believe, is clear. So now we will be moving on to backward propagation. Any questions? The next example is going to be purely mathematical, right? We are going to talk about how the different values get multiplied, how the activation functions are applied, right? Now, the next example will be a purely mathematical example. So all the concepts till now should be clear. All right. So let's move to the next slide. Now, the back propagation algorithm is a supervised learning method. All of this you guys know, right? We get a predicted value, we get an actual output, and then we compare, right? So it sees that the output is a gorilla, but the actual value is something else. So it will know that this is an error. It will go ahead and it will try to adjust the weight values. So if you see in back propagation, the weights are getting updated, right? Let's try to understand this with the help of an example. Okay. Now, let's consider the following table. My input is 0, 1, and 2, and my output is 0, 2, and 4. All right. Let's see what happens in this case. Now, let's assume that the model goes ahead. We have to create a model which will take as an input 0, 1, 2 and give as an output 0, 2, and 4. Right. So the model will start with what? The model will start with random weight values. Right. Let's assume that the model starts with the weight value of 3. Right. Now, when the model starts with a weight value of 3, my 0 gets multiplied by 3, which gives me the predicted output of 0. My 1 gets multiplied by 3, which gives me a predicted output of 3. My 2, which is the input, gets multiplied by 3, which gives me a predicted output of 6, right? What do I do next? I will go ahead and I will calculate the error, right? With the weight equals to 3, I am getting an absolute error of 0, 1, and 2, and I am getting a square error of 0, 1, 4, right? Okay, so this means that my model is not able to predict correctly because my error is high, right? So next, what the model tries to do is that, let's assume that the model decides that I will increase my weight value. I will change my weight value from 3 to 4, right? As soon as I change my weight value from 3 to 4, what happens is my error actually increases way further, right? If you see, when my value becomes 4, my output becomes 0, 4, and 8, and my square error becomes 0, 4, and 16. Right? because my predicted was 4, actual was 2. So 4 minus 2 is 2 square. So that will be 4. And over here, 8 minus 4 will be 4 square. That will be 16. Correct? But now, do you think that the model is changing the weights in the correct direction, or do we need to change the direction of the weights? Right? So it's clear that as soon as we increase the weight values, the error also increased, right? So what we need to do, we'll go ahead and we'll try to reduce the weights, right? So now I update this output table. I run this for weight equals to 2, right? As soon as I run this for weight equals to 2, now this is also incorrect, right? This should have been 2 only. There are lots of misprints. So this you can assume is 2. And if this will be 2, then obviously your error will be 0, right? As soon as my output, my weight becomes 2, my outputs become 0, 2, and 4, right? Which is what I was expecting. Hence, my error actually reduces to the minimum possible, which is equal to 0, right? So we see that the weight is reduced, the error also decreases. Error should become 0 only here, right? Because W equals to 2, 2 into 0 will be 0, 2 into 1 will be 2, and 2 into 2 will be 4. Right? So this is exactly how the weights actually try to adjust themselves. So that is why there will be multiple iterations, right? Now see, this was a simple example which had only one single weight value. Now imagine a neural network which contains thousands of weights, right? Now in order to identify the direction of change of each and every weight, it will obviously take time, right? Because it might happen that if you increase all the weights, your error does not change, because it may happen that for some weights you had to increase it, for some weights you had to decrease it, right? So to identify for each and every weight what is the correct direction, we need to have a mathematical technique, or we need to have a technique which will help us in giving the weights uh, accurately, right? Giving me the direction of the weight change accurately. See, if I know the direction of the weight change, then it depends up to me if I want to change the weight value by a very large percentage or by a small percentage, right? So let's say if I have a technique which tells me that weight 1, you have to increase the value. Weight 2, you have to decrease the value, right? Now I can go ahead and I can decide the step size, right? Now the learning rate parameter will help me in deciding the step size, whereas gradient descent will help me in deciding the direction of weight change, right? Okay, now let's try to see how does backpropagation work, right? What exactly happens? Now, let's take an example, right? We have actual value and we have predicted value, right? And let's say we have actual, we have weight, and we have predicted, right? Let's say my actual value is 10, right? When I take a weight of 0, my predicted becomes 0, right? So I will also have an error, right? So my error becomes, let me take two errors. I will take error and square error. Okay, so my error becomes what? Can you guys tell me? If my actual is 10, predicted is 0, my error will become 10. And what will this become? The square error, 100. All right. Now, once again, my actual was 10. My weight, let's say, becomes 1. And when my weight becomes 1, my predicted becomes 5. Right. Now, what will happen? My error will become 5. My square error will become 25. Right. Okay. Now, actual remained 10. Let's say the weight becomes 2. Predicted becomes 10. Error becomes 0. right? Square error also becomes 0, correct? Right? Now, let's say once again, my actual was 10, my weight was 3. In this case, my predicted was 15, right? My error becomes 5 once again, and my square error becomes 25 once again, right? Now, this process will keep on, this will go on and on and on, right? If I have a weight of 4, this will become 20, this will become 20, so this will become 10, this will become 100, right? All of this is an assumption only, Arvindan, right? I'm not taking any data, I'm just creating one example for you, right? Now, if you see what the square error is doing, the square error is giving me a much higher variation of the error value, right? So the output for your square error will be something like this, right? In case of your error, in this particular example, it is still something which looks like this. But when you are working with non-linear problems, right? When you are working with problems which might be non-linear in nature, in those cases, your absolute error might look like a straight line, which is like this, right? Now, your error function either can be a U-shaped curve like this if you're taking the square. If you're not taking the square, if you're taking the absolute value, your error function can look like this, right? Now, in this U-shaped curve, it is easy for you to go ahead and find out the minimum of this error curve, right? If I'm sitting over here, I know that I have to, from here, I have to reach somewhere over here, right? But if my error function would not have been a squared, right? If let's assume then I was sitting somewhere over here, right? You don't know the extent of where you will have to go to in order to reach the minimum of the curve. This will give you more number of iterations, and for non-linear and more complicated problems, you will never be able to find out the minimum of the error. So that is why we use the square of the error. I have explained this, I think, yesterday or day before yesterday as well. Okay. So that is the logic of using the error. Soham, is that clear to you now? All right, so let's try to see what happens in backward propagation, right? Now, I think one thing should be clear to you by now, that this error curve is what? This error curve, for this error curve on the x-axis, we will have what? We will have the weights of the model, right? So let's say I have 3 weights, W1, W2, W3, right? So my weight of the model will be over here. Or let's say if I look at an example which contains only a single weight, right? Let's say I just have one weight, right? So my weight value will be on the x-axis, and corresponding to this weight value, you will have an error. Is that correct? If you see the previous example only, this one, right? If you see this example only, my weight value is actually changing, right? So I started from a weight value of, let's say, 0, right? 1, 2, 3, and 4, right? Now you can see that when my weight value was 0 over here in this example, my error was quite high, close to 100. When my weight value became 1, my error decreased to 25. As soon as my weight value became 2, my error became 0. Then when I increased the weight value, error became 25 once again. And then if I made this 4, error became 100 once again, right? So now it is the value of the weight, right, that is driving the error. Okay, and that is what we are trying to minimize over here. Now, the good part with the U-shaped curve is that you can if you are here, you know that you have to go down. If you are here, you know how you have to go down. How do you know that you have to go down? That is gradient descent, right? So if you see, if you're sitting somewhere over here, you know that you have to increase the weight. If you're sitting somewhere over here, you know you have to decrease the weight. That's it, right? Right. So our objective is we need to reach the global minimum, right? If we are sitting somewhere over here, I need to increase my weight. If we are sitting somewhere over here, I need to decrease my weight. Now comes a slightly mathematical part, right? See, visually, if I ask you that when my error is somewhere over here, what will you do? Will you increase the value of the weight or will you decrease the value of the weight? But see, when we are working with n-dimensional problems, when we have so many features, this error curve will not look like this, right? Assume you have a model which contains 100 different weight values. So your error function will be a function of all the 100 different weight values. As soon as one weight value changes, even if the remaining 99 remains constant, right, your error will fluctuate, right? So it is impossible for us to visualize the error curve. When we are working with highly complicated and highly complex problems, it is, we cannot go ahead and we cannot visualize the error curve, right? And that is one thing that you can actually never do, because you are actually blindfolded, right? You, when you run the model once, you get one error value, right? Now that error value, what error curve or how the error is fluctuating, if you want to get that, you will have to run the model again and again and again, right? So is this clear to each and everyone that when we are actually working with high dimensional problems, your error curve or your cost curve will not look like this. It will not have just one x-axis and just one y-axis. It will have as many dimensions as the number of weights that you have. If I am not able to visually inspect, mathematically, how can I find out whether I have to increase my weight or I have to decrease my weight? Now, if you guys remember when you were in school, maxima and minima, you would have studied, right? So we used to calculate the gradient, right? If I go ahead and if I calculate the gradient over here, right, my gradient comes out to be something like this, right? So my gradient will come out to be positive. If my gradient or if my angle looks like this, my gradient comes out to be negative. So it is as simple as, if my gradient comes out to be positive, I know that I am sitting towards the upward part of the cost curve. So that means that I have to decrease the weight, right? I need to decrease the weight. If my gradient comes out to be negative, that means that I am at a land wherein if I increase my weight, the level of the land is going to keep on going down, right? So that means that you have to decrease the weight. And this is what happens in gradient descent, right? Now, if you are familiar with mathematics, you will know that when I do a differentiation of any function with respect to the variables that that function has, right, it will give you that when you increase the value of, let's say, x by a very small amount, is the value of the function increasing or decreasing, right? If you remember x plus delta x, you go ahead and you calculate x plus delta x, x minus delta x, and on the basis of that, you go ahead and find the differentiation value, right? So all that is exactly what happens over here. Now, from a deep learning data science point of view, you don't need to go into such details, right? All you need to understand is that gradient descent, what it does is that it identifies the gradient. Why does it identify the gradient? For this cost curve, right? If you see, if I sit somewhere over here, if my error value comes out to be this, what I will do is that I will increase the value of my weight slightly, right? And I will see if my error is increasing or decreasing. If my error is increasing, it means that I am at a positive gradient. If I am at a positive gradient, I need to decrease the value of my weights in order to minimize the error function. So Raj, no. Do you remember the example? So let's say I leave you stranded on top of a mountain, right? You are blindfolded, right? How will you go down? Can you imagine yourself to be in a situation wherein you are on top of a mountain and you have to go down? What will you do? So let's say you take a small step towards your left hand side, climb down, but you are blindfolded, right? How do you know which direction is down? Just try to think about the first step that you take. So let's say that as soon as you take one step towards your left hand side, you realize that the level of the land is upwards. It is actually towards the upper side. So will you go in that particular direction, or will you try to change the direction? Right? So let's say towards the left hand side, when you take a small step, the level of the land was high. That means that the gradient is positive, right? When I say that the level of land is high, it means that the gradient is positive there, right? So what you do is that you take the opposite direction. You take one step out and you see that the level of the land is now going down, right? So what do? When you saw that your gradient was positive, you took a different direction, right? You took the opposite direction because you know that that direction will take you down, right? Now let's say if in the first instance only, the gradient, when you had looked for the direction, the level of the land was going down in the first try only, then what will you do? You will directly take one step down, right? So it is just like that over here. If you see, it is exactly like that, right? The gradient is nothing but we are trying to find out what the level of the error curve is my error increasing or is my error decreasing, right? And then on the basis of that, we go ahead and we take a decision. Pooja, it is not trial and error, right? It is, see, it is, you know the direction, right? But you cannot take large steps. When you are standing on top of a mountain, you might know that the direction to go downwards is, let's say, towards your front. But you will obviously not run down the hill, right? You are not going to run down the mountain because you might die, right? So you are knowing the direction, but you are being cautious. You are going into in that particular direction slowly, right? So Raju, when you're standing on top of a mountain, that is a three-dimensional thing, right? You will have in a mountain as well. It's not that you can just step to the front, right? You will have different directions, correct? So let's say you go towards the right hand side, then after some point of time, when you're going towards the right hand side, the level of the mountain starts to go up. Then what will you do? You might change the direction to slightly towards the left hand side, right? So you are keeping in mind, when you're going down a mountain, you are keeping in mind all the different directions that you might have to change, right? So just like that, if I have 20 weights, so you can, if you are able to understand the complexity of coming down a mountain, which is only three dimensions, you should be able to understand how complicated it will be for the neural network of a gradient descent to identify the direction of the minimum cost curve, minimum error in, let's say, a space as big as 20 dimensions, right? So which weight to increase, which to decrease. So that's what I'm saying, right? You need to differentiate your error with respect to the different weight values. So let's say the differentiation of error with respect to weight 1 tells you that you have to move in a positive direction. Let's say that differentiation of error with respect to weight 2 tells you that you have to move in, let's say, some other direction. So you are going to consolidate all the moves together and then you are going to move. All right, so let's move forward. Right now, we'll try to understand the mathematics behind backward propagation. And this is where we'll go for a break, because this is where it will get mathematical, right? So now the next part, we are going to understand internally how the neural network model does its calculation, right? We are going to take one feature, right? Multiply it by the weight values, calculate the activation function. This is going to be the mathematical part. This is going to be slightly complicated, right? So if you're able to follow, it is great. Even if you're not able to follow it totally, I would Everything is 2, right? Correct. These bottom nodes are what? These are the bias values, right? And what are these values? 0.15, 20, 25, 30. These are, for our example, these are weight values that have been already predefined as of now, right? We'll see how these values go ahead and multiply. And inputs are what? If you see I1 is 0.05, I2 is 0.1. These are the input values, and O1 and O2 are output values, which are 0.01 and 0.99. All right. I hope everyone should be able to understand this. Okay, now what will be the first thing that we will do over here? Can you give me the input that will go to the node H1? I want you to think of this. I want you to give me the input value that will go to node number H1. I am only talking about the linear transformation, right? Not the non-linear transformation. You have all the values that we have seen till now, right? What input is going to go to node H1? What is the value? All right, this is the image, right? So let's see what happens in H1. Net H1 is what? Whatever is going inside this. So as you guys had said, it will be 0.15 into 0.05, 0.2 into 0.1, right? So if you look at this, 0.05 into 0.15, that is 1. Now 0.1 into 0.2, because this is the weight 2, right? Weight 2, they're taking this, weight 3 as this, and weight 4 as this. So that's okay. We got confused. I think they have not given the weight values in a very correct visual way, but that's okay, right? I hope this is clear to everyone. And then if you see the bias, 0.35 into 1. Okay. So this will go as an input to the node H1, which is this node, right? And this is what? This is the linear transformation, correct? Now, assuming that we had the sigmoid activation function. Now, what will happen? If we have the sigmoid activation function inside this particular neuron H1, what will happen is that the sigmoid activation function will get the input value as 0.3775, which was the linear transformation. Am I correct? And the output that will come out from H1 will be this, right? 1 upon 1 plus e to the power minus net H1, because this is the formula for your sigmoid activation function, right? And minus net H1 is nothing but minus 0.3775, which will give me the output as 0.593269992. Is this clear to everyone? You can go ahead and you can do the calculations once when we are done with this. But if you'll calculate this, you'll be getting the similar values. Mosby bias is a constant. So I am giving the feature as the value of 1 only. If you see, bias is not any feature. It is just a constant value. If you'll multiply it by 1, obviously it will remain the bias only, right? Exactly. Now we need to do the same thing for the output, right? Now, just like we had 0.05 and 0.10 here, now for H1 and H2, we have the values as 0.6 and let's say 0.6, right? So let's say 0.59 and 0.59. So what I have over here now is I will be having this value as 0.59, right? And once again, this value is 0.59. What do we need to do next? We need to now multiply this 0.59 by the different weight values, add the bias values, and get an output. The output node will also have a function, right? We are going to do the same process now. Is this clear to everyone? All right, so let's go to the next part of this neural network. Now the output from O1, right? We need to go to O1 now. O1 is this. What will that be? If H1 and H2 both are giving me 0.59, output of O1 will be what? 0.59 into 0.4. and 0.59 into 0.5 plus 1 into 0.6, correct? This will be the value that will be going into O1, right? So if you see 0.4 into 0.59, 0.45 into 0.59, whatever weights they have taken, plus 0.6 into 1, this is the input value that goes in the function input, right? In your output node O1, this is the linear transformed value. Now let's say over here as well, we are using the sigmoid function because we wanted, let's say, probabilities, right? So here as well, you can see that this 1.1 will go into the sigmoid function and we will get an output probability of 0.75, correct? So you can see that output O1 and output O2, both values have been calculated. Now these are what? These become our predictions. For the first iteration or for this particular iteration, whenever my weight values were equal to this becomes my output, correct? Now, what will be the next thing that we need to do? Is there any more forward propagation that is left? No, right? We have reached towards the end and we have gotten the predicted values. Now, what is the next thing that we need to do? Error. We need to calculate the error and then we need to get started with the backward pass, right? Now, what we need to do is that we need to calculate the error. Now, the error formula that we are taking over here is half of target minus output whole square, right? We are taking the square error, right? And we are taking half of this. Why are we taking half? This is just for mathematical convenience, because if I go ahead and if I take the error as, let's say, x square, right? And I differentiate it, right? So my differentiation will become 2x, right? If I take half of x square, in that case, my differentiation will become only x, right? Because it will become 2 divided by 2x, which will come out to be x, right? So that is why, just for mathematical convenience, we are going ahead and we are taking it as half of actual minus predicted whole square, correct? So let's go ahead and let's calculate the errors. Now we have the actual value, we have the predicted value. The actual for O1 was 0.01, predicted was this. I go ahead and I get the error value as 0.27, right? Similarly for O2, my error comes out to be 0.02. This is less because my O2 actual value was 0.9 and my predicted was somewhere around 0.78, right? So that is there. I go ahead and I calculate my total error, which comes out to be 0.2983. Now comes the slightly complicated part, that is to identify what is the contribution of error from the different neurons, right? That is what we need to understand now, right? Now, let's try to look at this, right? Now, my error total, if I come to this particular slide, the error total that I have calculated, right? Whatever that value is coming, error total, right? It is 0.29 something, whatever it is coming. It is what? It is a function of both my output nodes O1 and O2, correct? Right? Because we have gone ahead and we have taken a sum of both of these, right? Now, if I want to find out what contribution of, see, now there will be two things. When I do the backward propagation, I will go from right to left, right? After this, let's say I understand that the error coming from O1 is 80% contribution. The error coming from O2 is 20% contribution. Let's say if somehow I am able to understand this, right? Then I will go back and I will break down this 80% and see what are the previous neurons which are contributing to this error. Maybe H1 is contributing 60% and maybe H2 is contributing 20% of this, right? So that's what we are going to do now. So let's try to understand what happens in backward propagation. Now your error total, if you see error total, right, is a function of out O1 right? Out01 was what? Out01 was the activated, was the activation function, the output from the node out01, which was the sigmoid activation function applied to the linear transformed value. Is that correct? Whereas your out01 was a function of your net01. Your net01 is a function of W5, W6, B2, right? Your bias 2. So if you see, your error total is actually, if you look at this, even a value, even your weight W1, right, will have a contribution to your error total. Even the weight W2, W3, W4, this bias, all of these values will have a contribution to error total. Right? So Mosmi, what I'm saying is that this error total, right? How is this error coming out to be? This is coming out because I had all of these different values. Now W1 will also have a contribution to this error. W2 will also have a contribution. W3, W4. All of these weights will have a contribution. If I want to see what is the contribution coming from the previous neurons, what I need to do is that first I need to calculate. So let's say I am able to find out that if my error total was 100%, right? I am able to find out that out01 is contributing 80% of that error, right? Let's say from out01, I understand that only 60% was coming from net01 and the remaining 20% was because of the sigmoid function, right? Just 1 second, guys, I'll be back. Okay. So let's say if my error total was 100%, and let's say I am able to find out that for that 100%, 80% is coming out from your entire out01, right? Then see, out01 is what? Out01 is the sigmoid function applied on the linear transform value, which was net01, right? So let's say then I'm able to figure out that out of this 80%, error total is what? Error total is summation of out01 plus summation of out02, right? So right now we are just focusing on O1. So the remaining 20% is coming from the previous, the second neuron, which is O2, right? Exactly. So out01, which is nothing but the sigmoid function on the linear transformation. So let's say the sigmoid function is contributing 20% to the error, right? The remaining is the 60%. Now this net01, how did we go ahead and how did we create this net01? It was nothing but W5 into the value, W6 into the value, right? Now let's say we are able to find out that W5 gives a contribution of 15%. This gives a contribution of 25%, and this gives a contribution of 20%. Right? Now, just like this W5, W6, and B2, right? Even if you go ahead and even if you split this further, all of this W5, W6, W7, W8 will also be a function of W1, W2, W3, and W4. So even the errors that we are seeing over here will be further divided to the previous layers as well. So if you see, each and every weight is actually contributing to the error, right? And that is what we need to now figure out, that how are the different contributions coming out and how do we need to adjust the values of weights. See, now the first thing that we need to do is that if I need to find out the error contributions from all of them, first thing I need to find out the error contribution from out01, right? So my error total and out01, I need to find that out, right? Now, how will I do that? So if you see in the backward pass, right, what we are trying to do is that the first thing, or let's say what I try to do is that I try to identify the error contribution of W5, right? Now, what is W5? W5, if, see, this is basic differentiation, only weights. Yes, Aniket, so now see, if I want to calculate the contribution of, if I do a differentiation of error with respect to W5, can I do that directly? My W5 is contributing to the function net01. Net01 is contributing to out01, which is contributing to error total. So I cannot do this directly. If I need to find out differentiation of error total with respect to W5, I need to find out differentiation of error with respect to differentiation of E total with respect to out O1, right? Then I need to find out the differentiation of out O1 with respect to net O1, right? And then I need to find out the differentiation of net O1 with respect to your W5, right? This is what will give me the contribution of W5 to this error total. This is differentiation. This is the chain rule that we have in differentiation, right? So that is what we are trying to do. So Maulik, net O1, whatever error is coming, that is from W5, W6 only, right? Net O1 is what? Net O1 is nothing but a combination of W5, W6 and B2. So that's why we are directly finding out W5. If W5, W6, all of these will be correct, obviously net O1 will be correct and out O1 will be correct, right? So if you see, we are applying the same chain rule over here. If we go down, right, if I need to calculate the contribution from W5, right, I need to calculate differentiation of error total with respect to W5, right? Differentiation of error total with respect to W5 is nothing but error total by out O1, right? I'll come to this diagram over here, right? Error total by out O1 will be the first differentiation. Out O1 by net O1 will be the second, and net O1 by W5 will be the third. Okay, is this clear to everyone? This part? This part. This should be clear. Okay, so gradient descent is by far the most um, uh, popular optimization method that is out there, right? Used in machine learning, deep learning at the moment. It is used while training your model, can be combined with every kind of model and is easy to understand and implement, right? Now, see, what is the objective of us building a machine learning or a deep learning model? What is the objective? If I look at the model from an errors perspective, the objective is what? The objective is to reduce the error to a value as small as possible. So the objective is to minimize the error. Now, minimizing the error, see, there can be two ways, right? One can be, so let's say one can be a brute force method, right? That I go ahead and I try out all the possible weights that are there in the world, right? And then I see which model is working the best for me, right? Or the second way can be the way of gradient descent, wherein we keep on checking at each and every point whether my error is increasing or decreasing, and we take that direction where my error is decreasing, right? Out of the two ways, which one do you think will be more fast and will be more accurate? The one wherein you are trying out all the different weights? Gradient descent, right? Because see, in the first one, it's a brute force method. Now you can imagine that if I have a million parameters for a neural network, right? And each and every parameter is a numerical value, is a continuous numerical value, because weights are what? Weights are continuous numerical values, right? So you can imagine that the brute force method, you might take months, even years to find out the best parameter of a neural network model, right? Okay, so that is why what we do is that we apply gradient descent. Now, see, uh, the idea is simple. Let's say if you have to go from point A to point B, and there are 10 different roads that are taking you in that particular direction, it is not that you will go ahead and try out all the 10 different roads. Maybe you take one road, right? Maybe at a point wherein you are seeing multiple one road being split up into multiple roads, you stop and you ask someone that I need to go to this point, right? Which path should I take? Right? Maybe the person says that you have to take the left road, right? So you go ahead and you take that. Then let's say wherever the left road ends, there is a roundabout, right? At the roundabout, maybe you once again ask someone that you have to go to this particular place, right? Now that is what we are doing in gradient descent. We are not reaching our goal in one go, right? Obviously, there are multiple updates that are happening, our path is changing, our weight values are changing. But then what we are doing is that we are taking that direction. We are taking one direction and we are sticking to it, right? We are trying to find out the best possible outcome from that particular direction only, right? So gradient descent obviously will be faster because it will be performing less number of iterations, right? And it will be more accurate as well because we are actually applying a mathematical approach and we are trying to see where the error curve is actually decreasing, right? Gradient descent is an ensemble method. Indu, why do you think so that gradient descent is an ensemble method? Do you think that gradient descent is a machine learning model which is predicting any target variable, or do you see any multiple tree-based models that are being built in gradient descent? Gradient descent is an uh, optimization model, right? It optimizes whatever metric you are passing to it. Can be combined with every algorithm. So every algorithm, obviously, the objective of each and every machine learning, deep learning model is what? Is to reduce the error, right? So if you would have heard of gradient boosting machines, GBMs, light GBMs, these are all tree-based models, right? And these are also models wherein gradient descent is being used to reduce the error. All right. Now, gradient measures how much the output of a function changes if you change the inputs a little bit, right? Now, see, this one line will explain what gradient descent does, right? What gradient descent is trying to tell us is that if you change the direction of the weights, let's say in a positive direction, this is how your error is going to respond, right? If you change the same weights to, let's say, a negative direction, this is how your error is going to respond, right? Now, accordingly, obviously, you have to take that direction where the error is actually decreasing, right? You can also think of gradient as a slope function. The higher the gradient, the steeper the slope and the faster the model learns, right? Now, if you see, gradient is nothing but you are calculating the steepness of a function, right? Now, here as well, if you see, when we were calculating the gradient, right? So let's say if I am somewhere over here, right? So let's say if I'm somewhere over here, obviously over here, my gradient will be slightly steep, right? And if the same error, let's say I do some weight changes and I'm able to find myself over here. Over here, you will find that the gradient will be almost equal to 0, right? So gradient is nothing but the slope of a function. If you see over here, the slope or the steepness of this particular, at this particular point is quite high, but over here it is quite low. The objective is to reach a point where the gradient is close to 0, right? All right. Okay, so now let's come to how does that work? I think I've explained almost everything over here, but still let's go ahead with this. How does it work? If you see B, which is the updated weight, right, is equal to your A, which is your previous weight, subtracted by this particular sign. I'm not sure what this is. Let's assume this is tau, right? So tau, which is the learning rate, right, multiplied by the gradient of your error curve with respect to this weight, right? If you remember, this is what we had done in yesterday's example as well. The updated weight was what? The previous iteration of the weight minus learning rate into the gradient that you would have calculated, right? So this is what happens in gradient descent. Okay, then it is gamma. I'm not sure. So A minus gamma, right? And then gradient of the function A, right? So this is the weight updation that happens. Now this part, the delta of function A or the gradient of function A, this is something that we were calculating yesterday, right? If you remember, This was something that we were calculating yesterday. And after that, we had multiplied that by the learning rate value of 0.5, and we had updated the weights for each and every weight that the neural network had, right? W1 plus whatever you have written. Then your A will be the previous value of W1. N is the learning rate, which over here is gamma, and your differentiation of error total with respect to with respect to W1 is your gradient, right? So that's exactly correct. Now this formula basically tells you the next position where you need to go, right? So this will give you the updated weight. Gradient descent can be thought of climbing down to the bottom of a valley instead of climbing up a hill. This is because it is a minimization model, right? That minimizes a given function. Consider the graph below where we need to find the values of W and B that correspond to the minimum of the cost function, right? Now, if you see, this is a three-dimensional output, right? Now, see, over here in this output, this axis which is coming out would have been the error, right? This axis that is coming out is the error, right? Or, right? And this is W and this is B. Now, if you see, as W is increasing, your error is also increasing. As B is increasing, your error is also increasing. So W and B are actually working together. So your W and B weights, right, together they are going to impact the error curve, right? So now if I go ahead and if I calculate the gradient of this error with respect to W, I will find the direction, or I will find the gradient of W, right? I should be able to find something like this, right? So let's say if the gradient is somewhat like this for W, right? I will be able to know that if I need to increase the value of W or if I need to decrease the value of W. Similarly, when I differentiate the same error with respect to weight B, right, then I should be able to find out what I need to do with the weight B. Do I need to increase the value or do I need to decrease the value? So just like this, you can imagine that if my neural network contains thousands of weights, right, then this error function, right, or this error will be a function of those thousands of weights, right? Any single weight, if I'm not able to update the value correctly, right, it will impact the error. Does this make sense? Is everyone able to understand this? Right? So the same example that I had given yesterday, that you are standing on top of a mountain, you are blindfolded, right? So assuming the same example, let's say that your error is somewhere over here, right? When your error is somewhere over here, now you can take multiple directions, right? From a W point of view, you can go down like this, right? If you take B into account, you can go down like this as well, right? So at the end of the day, you might reach somewhere over, you might want to reach, let's say, somewhere over here, right? So, but for that, you need to adjust both the weights W and B appropriately, right? Okay, so now to start with finding the right values, we initialize the value of W and B with some random numbers. This is also something that we have talked about, that your weights and biases initially will be assigned as random values, right? Generally what happens is that in case of neural networks, we initialize these values as values which are very, very close to zero. Not exactly zero, but close to zero, right? And then we proceed from that direction. Let's say a particular weight wants to has to be negative, then the weight will be taken to a negative direction from zero. If let's say a certain weight needs to be positive, then from zero, the weight will be taken to a positive direction, right? And so with the random values, what will happen is that gradient descent, once when you apply gradient descent, it will start giving you the direction of the weights. Then it takes one step after the other in the steepest downside direction till it reaches the point where the cost function is as small as possible, right? I hope all of this is clear to everyone. Now the impact of learning rate, right? Now, this is also that something that we have talked about. If the learning rate will be very high, what will happen? Let's say that your error was somewhere over here, right? right? So let's say in the first iteration, when you had the weights and bias values initialized as random values, your error comes out to be somewhere over here, right? Now, let's say if the learning rate is high. If the learning rate is high, what will happen? Maybe the first iteration you come from here to here, error decreases, you are happy. Maybe the second iteration you come from here to here, error decreases, you are happy. In the third iteration, the error might come from here to here, right? You will see that the error remains the same, right? In the fourth iteration, the error will increase once again, right? So if you see, this will keep on happening and your model will be stuck in a loop, right? But if instead of this, we have small learning rate values, what will happen is that same output, right? If we are taking small steps, right, we will converge slowly, but we will be sure that we are converging in the correct direction, right? Now here, if you see, as soon as the error starts to increase, right, I will know that the error is increasing and I will come back to my original value, which was the most small value for error, right? So impact of learning rate, I think this should also be clear by now. So Indu, see, that is one thing that we cannot know, right? We can only guess. Now, see, the error functions that we are talking about, these are highly complicated error functions. And the limitation that we have is that we don't know the distribution of this error curve. If we had known the distribution, obviously gradient descent would not have been required, right? So you cannot know for sure whether you have reached the global minima or not. That is why you need to do your due diligence. You need to run the models as many times as you can. You need to test it with different values of learning rate as well, right? Because in some cases, it might happen that a big learning rate might actually help you. How? Let me show this example as well. So let's say I have an error. See, the error curve will always not look like this, right? Now, this is the perfect error curve that any machine learning, deep learning model will expect, right? But the reality is that this doesn't happen. In most cases, error curve might have local minimas, global minimas, and so on and so forth, right? Things like this. Your error function will not be as smooth as the one that you are seeing over here. Now, let's assume your error function was like this, right? Now, over here, let's assume that you landed at this point, right? Now, if you land at this point, what will happen if you take a small value of learning rate, right? You might keep on taking small steps, right? When you are taking small steps, you might stop over here only, right? You'll say that now error is going up and I'll stop over here. But if in this place, I would have taken a learning rate as a bigger value, right? So let's say I come from here to here, right? Let's say I come from here to here. The next jump will happen, learning rate will come from here to here. It will see that the error has gone down. The next jump that will happen, the learning rate will come from here to here, right? But the problem is that after this, the learning rate will come from here to here, right? And then here, and then it might stop somewhere over here, right? But see, so in such cases, what we need to do is that we need to run the model first with a higher learning rate value, so that we are able to identify the value that we need to minimize, right? So over here, if you see, if I would have run this neural network with all such values, I would have gotten a minimum error of somewhere over here, right? My minimum error with a higher learning rate would have been this. My minimum error with a lower learning rate would have been this. Now I know that if the learning rate is high, the minimum error that I'm getting is somewhere over here, right? As soon as I come to this point, what we do is that over here, then we go ahead and we change the learning rate to a small value. So see, learning rate, that is why learning rate, I would say, is the most important hyperparameter of any neural network model. So you will have to play around with the learning rate value in order to see whether you are stuck in a global minima, whether you are stuck in a local minima, right? Learning rate can help you, can get you stuck in a local minima, and it can also take you out from a local minima as well. So no, right? Because unsupervised learning, as I said just now, if you're not able to calculate the error, you will not be able to apply gradient descent. Now, in unsupervised learning, if you remember, you don't have any target variable. If you don't have any target variable, right, you can only get your clustering results, such as this data point belongs to cluster 1, cluster 2, and all. But do you have any actual cluster value or something with which you can compare that? No, right? So that means that you cannot apply gradient descent on unsupervised models. Right. Now, the next concept that we need to understand is epoch. Right. What is an epoch? And that's what we will try to understand now. Now, see, an epoch is nothing but, first of all, when an entire data set is passed forward and backward through the neural network only once, right? One epoch means that if, let's assume, your data contains 100 rows, right? One epoch means that all the 100 rows have gone into the neural network model, right? Uh, only once, right? That means one epoch. But as I said before, these neural network models, right, they need more iterations of the data. So the same data, right, the same 100 rows of data need to be passed to the neural network again and again and again, right? This is just like you learning a new sport, right? Let's say you try to learn to squash. You go ahead and you want to learn squash, right? Your trainer might tell you that you have to do this, but it might take you days and days of practice to get a particular shot right. Right, so just like that, you might go to the squash court daily and you might practice the same shots again and again and again, right? So just like that, the neural network as well needs to be fed the same data again and again and again, because it keeps on extracting new information, right? It keeps on updating the weights, right? Because each and every time when the weights are getting updated, you obviously need to pass the same data to check the performance, right? So let's say first iteration with some values of weights, you get an error of, let's say, 100. Second iteration with weight values updated, right, you get a error of, let's say, 98, right? Now this process goes on and on and on. So obviously we need to keep on passing the data again and again to the model, right? Okay, one epoch leads to underfitting of the curve in the graph, right? Now if you see, if you pass your data only once to the neural network, do you think that the neural network will be able to train itself properly? Correlate this with the example of, you go ahead and you want to learn squash, you just attend one session. Will you be able, can you go ahead and can you call yourself a squash player after attending only one session? No, right? So that is what will happen is that if you are giving only one single epoch, or if you're passing the data only once, obviously this is when your model had just started to train itself. So that will actually result in in a model which is not fitting very well to the data, right? It will not give you a very good accuracy or performance, right? Now, see, let's say you go ahead and you are not sending, or you don't have epoch equals to 1. Let's say you go ahead and you give a epoch which is uh, somewhere around 50 epochs, right? Now let me give you an example first, right? Now let's say when you are going to learn squash, there can be three things. Either you just go for one day, right, and you feel, you think that whatever you have done in day, you should be able to do it well, but obviously you will not be able to do that because picking up a new skill will take time, right? So this is one single epoch. You have not trained too much, so obviously you will not be very good at squash, right? The second is, let's say you go ahead, you keep on going, right? And daily what you're doing is that you are only practicing that one shot that your coach has taught you, right? You are not practicing any other shot. You're not playing any games. You feel that if I perfect this shot, right? So let's say if I talk about the backhand, you feel that if I perfect this backhand, I should be able to win all the matches, right? So what you do is that for continuously 6 months, you go there daily and you only practice your backhand, right? Will you be considered as a good player then? No, right? Because it might happen once when you go to the actual match, right? The opposite player might know that, okay, this person has a very good backhand, right? But they will also be able to figure out that the forehand is not good or the drops are not good, right? So they will focus on those shots of yours which are actually not good, right? So this is something which is known as, which in the world of machine learning and deep learning, we call as overfitting, right? Overfitting is what you have practiced something to such an extent, right, that you might be very good at playing this particular shot alone, but if you bring this together in an entire game, obviously that is not everything that is expected, right? So if you increase the epochs to a very large number of value, right, that is also not going to help you, right? A smaller epoch value is also not going to help you because you are not training enough, and a very high epoch value will also not help you because you are training too much, right? So epoch, so there should be a very good balance in the epoch value. Now, either the epochs can be 50, 100, 200, whatever, that depends upon the data. But this is something that we will have to find out, right? So you can add one more hyperparameter to the deep learning models that we have been talking about, that is the epochs, right? So epochs as well need to be chosen very carefully because a higher epoch will lead to a model which is fitting more to the data, overfitting. A lower number of epochs will lead to a model which is not giving you a good accuracy, right? Which is giving you a lower fitting, right? Underfitting. So we need to we need to have those many number of epochs wherein we are getting the optimum performance from the model. All right. So if you see, this is the optimum one. All right. Now moving on to the next part. Okay, one more thing on this epochs, right? Now the uh, we have been able to understand what epoch is. Example also we have done. But from a point of deep learning or from a point of models, how will you identify the optimum epoch value? Do you guys know that? See, in order to identify the optimum epoch value, right, there is a very simple fix. What if I go ahead and I evaluate my models training and testing performance simultaneously for each and every epoch, right? So what I do is that I will keep on assessing the model's performance on both training and testing data. Now see, generally, if I keep on increasing the epochs, my training accuracy will keep on increasing, right? So if you keep on increasing the epochs, your training accuracy will keep on increasing. It will never stop, right? But if you also keep a tab on the testing performance, testing accuracy, it might happen that your testing accuracy starts being similar, then after some time it starts to decrease, right? Now, if your x-axis was your epochs, right? If this was your epochs and this was the accuracy of the model, right? Now, all you have to do is that you have to find out this particular point, right? This point, maybe this point, where the testing accuracy and the training accuracy are highest together, right? So let's say this comes out to be 50 epochs, right? So you will stop your model training at 50 epochs, right? Because you're seeing that at this point, what is happening is that beyond this point, my training accuracy keeps on increasing, but my testing accuracy stabilizes or starts going down. So that means that beyond this point, your model would be actually starting to overfit, right? So there's a very easy fix when we are training the model. When you go ahead and when you run it for different epochs, right? All you will do is that you will keep a tab on the accuracy of the model on both testing and training data, right? The point when you feel that the testing accuracy starts to decrease and the training accuracy is increasing, that is where you need to stop your model training. All right, now moving on to the next part, that is batches and iterations, right? What are batches and iterations? Now, see, batches is, now this pertains to the previous question that someone had asked, that if one epoch means one gradient descent or something like that, right? Now, batch size will define after how many rows have passed to your model, gradient descent will come into picture, right? So if you see, the total number of training examples present in a single batch is referred to as the batch size. since we can't pass the entire data set into the neural net at once, we divide the data set into number of batches or sets of parts, right? Now, you might you might have, let's say, 1,000,000 data points, right? In your data, you might have 1,000,000 rows, right? So passing 1,000,000 rows to the model, then updating the weights of the model, right? That will become a very, very cumbersome ask, right? Because it will take a lot of time for 1,000,000 rows to pass through the model. Then you will update the weights, then you will apply gradient descent, update the weights and things like that. So that will be a very slow process. So generally what we do is that we divide our data into batches, right? So let's say if I have 1,000 rows of data, I will say that I will pass these 1,000 rows of data in 50 batches, right? So when I'm passing these in 50 batches, every batch has 20 rows, right? So these 1,000 rows I have divided into 50 batches. One single batch has 20 rows of data. What I do is that once when the 20 rows of data or one batch has been passed, I initiate my gradient descent, right? Or I call my gradient descent, and my gradient descent will update the weights, right? Once when the weights are updated, then the next 20 rows of data will be passed. Once again, your error will be calculated on these 20 rows with the updated weights. This process will go on and on and on and on, right? So this is known as batch size. Batch iterations is nothing but iteration is the number of batches needed to complete one epoch, right? So iteration will be, if your batch size is 50, right, and your total number of rows are 1,000, how many iterations will be required? 20 iterations, right? So your 50 or your one batch multiplied by 20, that will be the number of iterations that will be required, right? Exactly. So epochs, batch size, iterations, right? All of these things are important hyperparameters. Epoch can be greater than 1, right? Should be greater than 1, right? One epoch can be further divided into batches, right? So if you have 50 batches, that means you have 20 data points per batch, right? And that means that you have 20 iterations, which will be required to cover one particular epoch, right? Suppose you have your we have your data. We have data about 10 rows. I'm just taking my actual value and I'm just taking my predicted value, right? Let's say my actual was 10, my predicted was 5, right? My actual was 20, my predicted was, let's say, 25, right? My actual was, let's say, 15. My predicted was 12. My actual was 24. Predicted was 27. Right. My actual was 50. Predicted was 50. And let's say my actual was 40. Predicted was 30. Right. Now this is my data that I had. If I go ahead and if I calculate the errors, if I calculate the fluctuation in the error, right? So let's say the error square, right? I'll take the error square. Will be what? Will be 25 over here, 25 over here as well, 9, 9, 100, 100, correct? Right? If I take the average of this error, right, what will I get? Average will be 200, 250, 268 divided by 6, right? So that will be 44.66, right? So your average error comes out to be what? Comes out to be 44.66. Is that correct? Right? Now see, if I would have passed this entire data, that is, if I would have not divided this data into batches, right? If I would have passed the entire epoch and then I would have called the gradient descent, my average error is being calculated. Now, if you see, average error is somewhere in between, right? But if instead of this, let's say I had given a batch size, or I had calculated gradient descent after each and every row, right? If you see, the fluctuations in the error in that case will be very high, right? I will start with 25, my error will go to 9, right? Then my error will go back to 100. Whereas if I am only sticking with average error, my error is coming out to be somewhere over here, right? 44. And when we are applying gradient descent, what is it that we want to see? We want to see more fluctuations in error. Is that correct? Because the more fluctuations we are going to see in the error, the more we will be able to find out what the minimum error is coming out to be. And if the minimum error is coming out to be 9, I would want my model to go ahead and achieve that for each and every data point. Does that make sense? Right? So in a way, these batch sizes, the dividing your data into batch, right? This will actually give more fluctuations to the error. And the more number of fluctuations in the error that we are having, it means that there is a higher possibility of us finding out the minimum error value. Instead of, if we would have passed the entire data and then we would have calculated the gradient descent, in that case, as well, it's not that I'm not saying that you will not be able to find the minimum error, but that process will be more long. It will be more time consuming. Whereas if you are calculating your gradient descent time and again after batches of data, because each and every batch might be different, your error fluctuations will be very high. When your error fluctuations will be high, you will be able to find out what the minimum error is coming out to be, right? So hence you will be able to track the error curve in a much more efficient manner, right? So all of these values also have a impact. Your batch size also has an impact on the accuracy of the model, because your batch size, dividing your data into batches, will actually give more fluctuations to the error that can help you in finding out the minimum value. So Maulik, in this example, see, every batch is going in a sequence, right? So if let's say for the first batch, the weights that were initialized were 0, for the second batch, whatever error we are getting from that batch, right, the weights will be adjusted, right? Now, for the second batch, maybe the weights become values which are 0.1 for some, 0.2 for others, minus 0.1 for some others, right? Then once when this batch has passed through, once when the error has been calculated, maybe the error goes down now slightly. Then once again, the weights will be calculated, right? So all of these things are happening in a sequence. Puja, gradient descent I've been explaining from 3 days onwards, right? I will not be explaining each and everything. What are your doubts? You can ask your doubts. I can clarify those. How increasing batch size will reduce the errors? I'm not saying that by increasing the batch size, the error will reduce, right? I'm saying that if you divide your data into batches, your data or your error is going to see more fluctuations, right? If you don't divide it into batches, you are getting the average error, right? You calculate the average error, and if you are calculating the average, let's say for 1,000 data points, even if let's say the error would have reduced for a couple of rows, the overall error is not going to be impacted that much, right? But if you divide your data into batches, the fluctuation in the error will be higher. Batch, right? After every batch is passed through the model, gradient descent is applied. So over here, the batch size is what? The batch size is 1,000, and I have 50,000 rows in total. So 50,000 divided by 1,000 will give you how much? 500. So 500 times gradient descent will be applied in this data. Whatever your batch size is, after those many rows have been passed to your model, your gradient descent is calculated, right? Okay, now the variants of gradient descent. So now if you see gradient descent as well, it has many variants. Batch gradient, stochastic gradient, and mini batch gradient descent, right? So let's try to see what do we mean by these three variants of gradient descent, right? Now we'll see this with an example. Let's assume we have 6 images in the data, right? Now, what batch gradient descent does is that it takes the entire data set at a time. So this is just like what we were talking about. If you don't divide your data into batches, if you pass the entire epoch to the model and then you calculate the gradient. This is something which is known as batch gradient descent, right? So back propagates the loss for all the 10 images, not 10, 6 images at a time, right? So in batch gradient descent, you are not dividing the data into batches. Opposite, contrary to the name, you are passing the entire data as a single batch, right? Stochastic gradient descent is exactly opposite of batch gradient descent. In batch gradient descent, we were passing the all the rows together and then we were calculating the errors. Over here, what we are doing is that after each and every row of data has been passed, right, we are calculating your error and then we are applying gradient descent, right? So if you see, your stochastic gradient descent is nothing but your gradient or your weights updation is happening after every single row of data is being passed to the model, right? So you can see that the complexity, or if you have 1,000 rows in your data, then 1,000 times your gradient descent will be applied in one epoch. If you give 10 epochs, then 1,000 into 10, 10,000 times your weights updation is going to happen, right? Somewhere in the middle of these two, we have mini batch gradient descent. That is what we have discussed just now, right? If I divide my data into batches, if I have 1,000 rows, I divide these 1,000 rows into 10 batches of 100 rows each, right? Now this, if you see, will take in the best of both the worlds, right? This is also giving you fluctuations in the error because each and every batch will give you a different error value, right? And this will also be faster, right? So it will not be as slow as the stochastic gradient descent or as fast as the batch gradient descent, but it will be somewhere in the middle. But from a performance point of view, your mini batch gradient descent is the most popular gradient descent that we usually work with, right? The challenges with others is that if you look at this stochastic gradient descent, this is very slow to run because after each and every row has been passed, your gradient descent is applied, your weights are updated, right? So you can imagine that the time complexity will go up, right? In batch gradient descent, the fluctuations in the error are not very high. So the convergence for batch gradient descent will be very slow, right? It's not that it will not converge, right? It will converge, but the convergence will be very, very slow, right? But if you look at mini batch gradient descent, this is tackling with the problems that both the above gradient descents have, right? That is, it is also seeing fluctuations in the error, and it is also not updating the weights as frequently as the stochastic gradient descent. Hence, the time complexity will not be very, very high. All right. Now, tips for gradient descent. Plot cost versus time, right? This is one thing that I also told you, that we need to plot the error as and when we are increasing the number of epochs, right? So we need to plot the error of your training data, of your testing data, in order to see whether you are able to get an overfitting model, underfitting model, or a properly fitting model, right? Play around with the learning rate. The learning rate value, it can be as small as 0.0001 or it can be as big as 0.1, 0.5, right? So we need to try out different values for your problems and see which one works the best, right? So it's not that always a smaller learning rate is going to work the best for you, right? It might happen that a larger learning rate might help you in reaching a lesser error in a much more fast way, right? So you need to try out different values. Rescale inputs, generally for all these deep learning models, right, just to ensure that the calculations are happening smoothly and fast, right, what we do is that we scale or we normalize our data always. So make sure that you normalize your data, because if you're doing that, then all your features are coming out to be in the same scale. When all your features are coming out to be in the same scale, then consequently your weights also come in the same range, right? In the same range or scale. If you're not standardizing, then maybe you have a feature which is spend, which is varying in tens and thousands, and maybe you have a feature which is quantity, which is varying in, let's say, between 0 to 10 or 0 to 20, then the weights associated with these two will be very different, right? So hence, if the model is giving a higher weight to a one single feature, then overfitting can happen, right? So hence we need to standardize, or we need to normalize our data before we pass the data to any deep learning model. Now, there are certain other variations of gradient descent as well, which are slightly more advanced, right? So one is known as ADAM. ADAM is nothing but adaptive moment estimation, right? What do we mean by ADAM? So if you see, now if I show you a cost curve, which looks like, let's say I have a cost curve, which looks like this, right? Okay. And let's say you start from somewhere over here, right? The first instance, you were somewhere over here. All right. Now, if you see for this, if you give a smaller learning rate, right, then it can also be a problem, because a small learning rate can get you stuck somewhere over here, right? If you give a bigger learning rate, then it can also be a problem, because you might skip this part and you might jump from here to here. Correct? What if I had a gradient descent method, or what if I had a gradient descent variant which was able to adapt the learning rate according to the gradient that it is seeing, right? So if you see Adam, what it does is that when the gradient is high, right? When the gradient becomes too high, then what it will do is that it will lower the learning rate, because it knows that even a small learning rate will give me a good enough decrease in my error value, right? So if you see, what will happen is that as soon as the gradient becomes small, right? Sorry, the gradient becomes large, the learning rate will become small, because it knows that over here, even with a small learning rate, right, your error is actually decreasing, right? As soon as the gradient becomes flat, or the gradient becomes low, it will try to increase the learning rate, right? So if you see, if it increases the learning rate from here to here, it knows that it has gone down. Then if it increases the learning rate from here to here, it knows that it is going down. It will once again increase. This time it sees that the gradient has increased, right? So what it will do is that it will once again take smaller steps now, right? So this is just like exactly like how you as a human will behave, right? If you are standing on top of a mountain, if you feel that the level of the land is quite steep, right, you are going to take baby steps. As soon as you see that the land has become flat, you will not take baby steps. You might start to run, or you might start to take huge leaps, right? As soon as, let's say, you take a leap and you realize that the level of the land has starting to go down, right, you will once again go back to the baby steps, right? So if you see, your Adam actually works like this. So it will give you the adaptive learning rate. All right. Adam is a very successful gradient descent variation. So we will be trying this as well once when we work with the case studies. Shake, it's not possible to see the curve, but it is possible to assess the land where you are, right? It is possible to assess the gradient where you are currently sitting. You might not know what the error curve looks like, but you might still know that if you are standing at you are standing at a steep land, or you are standing at a flat land, right? So that's what it tries to do. Now, see, this is something that we have seen before as well, that there are many libraries, right, which will help us in building deep learning models, right? Now, why do we prefer Keras? Uh, so there are certain positives that we'll talk about. Now, Keras prioritizes developer experience, right? Now, this is basically if you are a developer as well, right? If you want to, let's say, take any library from Keras, and if you want to update that library as per your requirement, right? You have the freedom of going ahead and doing that. Keras does not limit you to just using the functions and the libraries that it has, but in Keras, and this is something that I'll show you as well, you can go to the function definition, right? If you are importing a certain library, if you're importing a certain function, and if you double click on that particular function, you will be able to go to the definition of that. So it's not that the code is hidden or it is a black box, right? So you can go ahead and you can actually uh, modify some of the functions that Keras has if you feel the need for it, right? Keras is broadly adopted in the industry and among the research community. Now, this is something that I have talked about previously as well. 95 to 98% of the deep learning models are actually built in Keras only, right? If your job is to go ahead and apply a deep learning model to a business problem, right? Then Keras will be the library to go to. If your job is to go ahead and create, let's say, any components of deep learning models from scratch, then maybe Keras might not be the best library for you. But the kind of jobs that we are looking for, the kind of jobs that you guys would be wanting to apply for or transition into, they would not require you to go ahead and to build models from scratch, right? 99% of the usage is taking these models, being able to take the deep learning models and being able to create them for any specific client problem or for any specific use case, right? Keras will be used for everything, Atul. So now we will be using Keras for building the ANN model. Then later on, we will be using Keras to build the CNN model, convolutional neural network. Then we will be using Keras to build the LSTM model. So every deep learning model that we have the option to build that model in Keras. All right. Keras makes it easy to turn models into products, right? Now, taking your code to production is easy with Keras because Keras integrates very well with the different ML deployment tools that we have, right? So it's not that if you build a model in Keras, after that you will have to convert that to some other language in order to take them into production and all, right? So it is easy to take the models into production. Now, Keras supports multiple backend engines and does not lock you into one ecosystem. Right now, if you remember, we have talked about that Keras is built around TensorFlow, right? So Keras is a library that is a wrapper around TensorFlow. So it's not that only TensorFlow is the option. There are two other languages as well that Keras supports as backend, right? So if you don't want to, let's say, code using TensorFlow as the backend, you can pick up the other two options that we have as well, right? Although this is not something that is generally required to do, but then still for some cases, let's say someone is working on Linux, Ubuntu or things like that, right? Then in those cases, maybe they would want to change the platforms, right? Keras has strong multi-GPU support and distributed training support. So if you have the option of GPU training, if you have the option of utilizing GPUs, if you have the option of distributed training, right? Keras as a model, Keras as a library will support that, right? It's not that so there are some libraries or there are some packages that we have that do not support parallel training. So even if you might be working on a GCP on Spark and all, the library does not support, right? So it's just like that. It might happen that your service provider, your telecom service provider might be providing 5G. But if your phone is not able to, let's say, provide that to you, if your phone is not 5G, you will not be able to leverage the services, right? So just like that, you might have PySpark, you might have distributed computing, you might have cloud computing, right? But if the libraries that you are using are not supporting that, you will not be able to you utilize them, right? So that is not the case with Keras, right? In Keras, you can actually go ahead and you can train models simultaneously, parallelly. Things will become faster as compared to other libraries. Distributed training, Maulik, is that you parallelize the training process. Now, if you see, when we are building the neural network models, the learning process is that each and every neuron will have to learn, right? Your forward propagation, backward propagation. So in case of distributed training, you can distribute you can what you can do is that the training of different neurons can happen side by side. When this happens side by side, if let's say originally you were taking an hour to train, maybe by distributed training you are able to do the same thing in 15-20 minutes. Sixth, Keras development is backed by key companies in the deep learning ecosystem, right? So all of the major tech giants, right? They are actually using Keras, right, to build their models. If they're using Keras to build models, then obviously their researchers, their teams, right, they are actually contributing to Keras directly. It's not that Google has their own platform, Amazon has their has their own platform, right? Now Google has GCP, but GCP is integrated with Python, wherein they are actually using Keras to build the models, right? So Microsoft and Nvidia, right? All of these tech giants that you see, they are actually, they do almost entire all of their work, right, pertaining to data science, ML, deep learning, using Keras only, because they are doing this, and because these are companies which are creating so many complicated solutions. So they are continuously evolving, they are continuously adding on to whatever is there in Keras as a library, right? So there has been a lot of development in the last 6-7 years in Keras as a library. Nowadays, if you see, earlier still it used to happen that there was a lag of 2 to 3 months for us to get something new in Keras, right? So let's say a new model was launched, right? Let's say Light GBM is a new model. Back in 2015, Light GBM was uh, uh, introduced, right? But for Light GBM library to be there in Keras, I remember it took a good 1 to 2 months, right? Because someone would have worked on that, then they would have tested that, then they would have provided that particular library to the rest of the folks. But now that rarely happens, right? Before something will come to the market, you will have a package of that, you will have a library of that in Keras, because of the fact that the major tech giants that we have, right, they are contributing to Keras on a daily basis, right? So this this is what actually makes Keras accessible. This is what makes Keras very fast to upgrade, right? Whatever uh, upgradations are happening, right? Whatever new things are coming in the world of data science, they are already there before you know about it. All right. Now, what is Keras? Keras is nothing but it's a high-level neural networks API. Why high level? Because if you see, it is written in Python and can run on top of Theano, TensorFlow, or CNTK, right? It is designed to be modular, fast, and easy to use. So your backend can be anything between Theano, TensorFlow, or CNTK. By default, it is TensorFlow always, right? Now, these are just some historical facts developed by Francois Chollet, right? Uh, the main concept behind developing Keras was being able to go from idea to result with least possible delay is key to doing good research, right? Now, let's say if you want to do something, right? If you want to build a deep learning model, building the model from scratch itself may take you a good amount of time, right? So obviously in Keras, we don't have to do that. We have the packages which are pre-built, right? Keras does not handle low-level computation. Instead, it relies on a specialized, well-optimized tensor manipulation library to do so, serving as the backend engine of Keras, right? So see, at the backend, it is TensorFlow which is working, right? And TensorFlow is way too fast as compared to other libraries, right? So, but what Keras does is that Keras makes it easy for us to use TensorFlow because it's an API. So the functions that we will have in Keras, the functions and calls that we give in Keras, at the end of the day, they call the functions that were written in TensorFlow only, right? So Keras is the high level API for a low level API. Application programming interface, Krishna. Right now, there are two kinds of models that we can make. When I say two kinds of models, it is not artificial neural network, recurrent neural network, convolutional neural networks, and all, right? So if you club all of these models together, right, these models can be divided into two kinds, right? So let's try to understand what kinds of models do we have in Keras, right? Now, we can create two types of models in Keras. One is sequential and the other one is functional, right? Let's try to understand what do we mean by sequential models first, right? Now, see, sequential models are models where the flow of the input is from one direction and goes to the other direction, right? The flow of the input is not coming from multiple directions. Now, if you see the neural network that we have seen till now, if you uh, focus, right? If you look at this, my input gets transformed, right? My input is connected to hidden layer number one. Hidden layer number two is connected, hidden layer number one is connected to hidden layer number two. Hidden layer number two is connected to output, right? It's not random, right? I don't have any connection such as, let's say layer two is connected to input layer, right? We don't have connections such as, let's say layer two is connected to input layer, or let's say layer one is connected to output layer. Everything is sequential here in nature, right? So there are multiple neural network models. So all the models that we will be studying, that is
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
ANN, artificial neural network, your convolutional neural networks, your LSTMs, these are sequential models. Sequential meaning that your preceding layer will be connected to the succeeding layer, right? It will not be the case that the succeeding layer is connected to the first layer of the model, right? Everything will be connected in a sequence, right? So Keras, the first kind of models that we can build in Keras are the sequential models. Under the sequential models, we have models such as artificial neural network, your convolutional neural network, your LSTMs and all. All right. So if you see, sequential model is a linear stack of layers. You can create sequential model by passing a list of layer instances to the constructor. Stacking convolutional layers one of the other can be an example of a sequential model, right? So we will be, throughout the duration of this course, we will be working with sequential models only, because those are the models that we are learning about. Now, other than sequential, there are also models which are known as functional models, right? Now, what are those? Now, see, this is just a demo of the code of sequential models. We will be seeing this today, right? Moving on to the second kind of model, right? The functional model is a model which might look like this, right? So there are certain models like GANs and uh, self self-organizing maps and all, right? Which actually have the connections in any order. Now, let's say your input is this, right? And let's say you have one hidden layer over here. I am defining the layer horizontally, and you have, let's say, one hidden layer over here, and let's say you have the output, right? So if you have something like this, wherein this becomes the input, this becomes, let's say, hidden layer number one, this becomes, let's say, hidden layer number two, this becomes the output. So there are models wherein the connection can happen in such a way that your input layer is connected to hidden layer number one, input layer is also connected to hidden layer number two, right? Hidden layer number one and two are connected to output, and input can also be directly connected to output. Now, if you see, these are not the sequential, this is not a sequential model, right? If this is your input, right? This is hidden layer one, right? This is hidden layer two, and this is your output layer, right? If this would have been a sequential model, then input would have only be connected to hidden layer number one. Hidden layer number one would have been connected to layer two would have been connected to the output, right? But that is not the case over here. If you see, all the connections are totally random. Any layer can be connected to any other layer, right? So Hindu, it can be anything, right? So in this example, H1 and H2 are not connected, HL1 and HL2 are not connected, but we have advanced deep learning models, right? Such as your GANs, your self-organizing maps and all, right? Over here, the connection depends upon you. You as a data scientist can go ahead and you can go ahead with the connections. If you want the hidden layers to be connected as well, you can do that as well. So in order to get all that freedom to connect any layer with any other layer, we have the different kinds of models which are known as functional models, right? So Keras offers to create both kinds of models. You can create sequential models. Under sequential models, we will have the models that we are studying about: artificial neural networks, convolutional neural networks, recurrent neural networks, LSTMs, and all. All of these are sequential models, right? Under functional models, it also gives you the option to create functional models. Functional models are highly advanced deep learning models, right? So like SOMs and your GANs and your autoencoders and all, right? We can use feed forward in functional model, but we cannot use, let's say, a self-organizing map in a sequential model, right? See, if in functional models, we have the freedom to connect the layers. So if you want to if you want to make the connection in a sequential aspect using a functional model, you can do that, right? And that is something that we'll be doing as well during once when we move to the hands-on part. But vice versa, you cannot do. You cannot create a functional model using a sequential model, right? So if you see, Keras will offer between both. Keras will offer you functions that can help you in creating both kind of models, right? Be it sequential or be it functional. Vijay, what do you mean? What is the difference between structure? What is different between structure? What? So this is sequential, right? What you have written, input connected to hidden connected to output. But over here, if you see the image that I'm showing, over here, my input is also connected to output. My input is connected to hidden layers. Then my hidden layers are separately connected to the output, right? Backward propagation will happen in all the neural network models, Hindu. That is how the models run. That is how the models are able to learn, right? So any model, be it sequential, functional, backward propagation is bound to happen. So that's what, right? Whatever concepts we have studied, all of these concepts will be applicable to even the highest and the most complicated deep learning models. There is nothing different that is happening in the different deep learning models. It's just that how you are establishing the connections might change. And we have case studies on all. We have case studies on sequential. We have case studies on functional models. We have everything. Don't worry about that. Difference is in connectivity among the layers, not the direction of propagation. So Atul, generally, yes, right? See, howsoever the layers are connected, the direction of propagation is also going to be in that order, right? Now, see, over here, if you look at this example, in this example, my direction of propagation is obviously forward. Generally, it will be this only, right? So direction of propagation will, because your input will generally be the first point, the output will generally be the last point, right? So your overall direction will remain the same. But when in case of sequential models, we just had a straightforward path like this, right? Over here, we have a slightly random path, right? It goes from here, and it goes from here, then it comes from here, and it comes from here, then it goes from here to here. All right. So this is just to explain that Keras has both kinds of models. We will be going through different case studies. We have case studies on functional. We have case studies on sequential. We have everything, right? So don't worry about that. HL1 can also be connected to HL2. Yes. So you can also do that, right? Now, this is just an example that I have given, but it can also happen that HL1 is also connected to HL2.
Can we say combination of sequential? No, Vishnu. See, sequential is sequential, right? Just try to understand this as you are standing in a queue to, let's say, buy something, right? So the queue, if the queue is managed, it will be sequential, right? Whomsoever person is standing in the first row, they will buy whatever they want to need, and then they will move out. Then the second person will go in, then the third will go in, right? Or try to imagine a toll booth, right? Imagine a toll booth where properly your cars are stacked in a sequential manner, right? You know that if you are standing at the back of that particular line, eventually you are going to arrive at the toll booth, you are going to pay and you are going to be off, right? The other case can be that one toll booth and there are cars flowing in from two, three ends, right? When there are cars flowing from two, three ends, obviously you might have three different connections, right? So now you can see that the information flow is kind of haphazard. That is not sequential, right? So the only difference over here is same. See, the direction of movement is the same. Every car is going towards the toll booth in both the cases. When you have a single queue as well, the cars are going to the toll booth. When you have multiple queues for one toll booth as well, the cars are going to the toll booth. But it can happen that some of the cars are going through layer the first row, some of the cars are going to the second row, and some of the cars are going to through the third row, right? So just like that over here as well in the functional model, your information flow can be divided. Some of the information can be going from the top half of the functional model. Some of the information can be going through the bottom half. Some of the information can be fed directly, right? All of these things that we are looking at, right? We are definitely, I don't want to spend too much time on Keras PDF at least, because for Keras we have lots of notebooks, and the more we spend time on the notebooks, the more we should be getting familiar with how Keras works, right? All right, so if you see, this was the sequential model, then this is the functional model. Three unique aspects of the Keras API is we define the input, connect the layers, create the model. I will be doing this multiple times, right, during this week and the next week. So don't worry about all of this. We will be covering this, right? Defining the input, this is just the code for that. We need to define the input layers and all, right? Just one second, connecting the layers, creating the model. All right. So I think what we can do is that we can stop over here because from this point onwards, we will be doing let's do the case study first so that you guys have a good enough idea of what happens in Keras. Once when I'm back on Friday, I will try to complete this case study today or maybe the majority part of it, right? And then so that you guys have 2 days and you guys can spend your time on going through the different notebooks, right? So that is why I just want to complete the notebook first at least. Right now, we have covered all the important aspects, right? What Keras is, what kind of models there are. Let's go through to the first case study. It will be a simple case study, but using Keras only, right? Using the Keras library, we will be trying to understand the case study. Once when you see things in action, it will get more clear to you, right? And then once when I'm back on Friday, we will be completing this theory. We will be taking your doubts, and then we will move forward to the rest of the case studies. Does the plan make sense to everyone? I hope everyone is aligned on this network, right? So by a multivariable, nothing but you have data which contains many rows and you have to create a neural network on that, right? So as a starter, what you will be doing is that you will be trying to build this neural network in Python from scratch, right? That is assignment number one for you, right? Now, today we will be going through the same problem, similar problem. We have some data, we are creating some data, and we will try to create a neural network model using Keras library, right? So let's do that. And once when we will be able to do that, I want you guys to attempt the same problem, the same assignment. The first one will be to create the neural network using only Python. The second one will be to create the neural network using Keras. So I'm importing NumPy over here, right? And I'm creating two random data sets, right? I am creating
arrays. One is the X train and the second is Y train, right? Now, can you guys tell me what X train, how many rows, how many columns will X train have, and how many rows and columns will Y train have? How many rows and columns in X train? 5,000 rows and 32 columns, exactly. And in Y train, we will have 5,000 rows and only one column, right? So by default, my X train will be the sets of features. So let's assume that X train are the features and Y train is the target variable. So if I show you this, your Y train is this, right? So these are just one values, single values each, and your X train is nothing but your each and every row containing 32 rows of data. I'm sorry, 32 columns of data, right? If you see, this is X train. Now, can I consider this data as a set of features and the target variable? Now, this is totally random data. That's fine, but we are just trying to see how we can run deep learning models using Keras, right? So let's say this one is the X train, right? And let's say this one is the Y train. We can do that, right? I hope everyone is aligned on this. All right. Now, with the aim of creating a model which will try to encapsulate a relationship between this Y train and X train, we will go ahead and we will run this and we will see how we can run the model using our Keras library, right? So the shape, if you look at the shape, Y train has 5,000 rows, one column, X train has 32 columns, right? So all of these things. Now, if you are running the model first time, if you are running Keras first time, you will have to install TensorFlow and Keras, right? So just go ahead and uncomment this and you can run this exclamation mark pip install TensorFlow, pip install Keras, right? You can go ahead and you can do this if you are running it for the first time. If you're working on Collab, I don't think that there will be a need for you to do the same, right? Indu, you can talk. Target is a continuous variable. It is a regression problem. So you will have only one single neuron. Now in between, see, this part is totally up to us. How many hidden layers you want to have, right? This is up to you. Can have 10 hidden layers, you can have 5 hidden layers, you can have 2 hidden layers, you can have 1 hidden layer, right? This part depends up to us. But as soon as you have a look at the data, right? As soon as we have the first glance at the data, we can say with surety how many neurons my input layer will have, how many neurons my output layer will have, correct? All right. Now, moving on with this information, we will go ahead and we will see how can we build the model using Keras, right? Now, let's focus on this piece of code, right? Now, this one, what I do is that I may divide this. Right. So first, what we will do is that from Keras, we will import models. Right now, models is nothing but models is a function which will contain the sub functions which are sequential and functional. Within models, we will have functions of the type sequential and functional. In this case, we will be building a sequential model, so we will be calling models.sequential later. Right. From Keras, we import layers. Right. What do we mean by layers? Now, if you see these connections that we have from input layer to hidden layer, from hidden layer number 1 to hidden layer number 2 and all, right? So we will have to define the layers, right? So these are dense layers that we have because every neuron of, let's say, hidden layer number 1 will be connected to every neuron of hidden layer number 2. So in order to define these hidden layers, we also need to import a function known as layers, right? So we do that. Over here, what I do is that I take the shape of my X train, right? Input shape 1, X train dot shape 1, which will come out to be 32 as my input dimension. Why? Because when I will be defining my input layer, I need to tell Keras, right? Keras will not automatically know that my data has 32 neurons. I will have to tell Keras that my input layer will have 32 neurons, right? So that is why what I'm doing is that I'm taking xtrain, I'm taking the shape of the columns, right, which will give me 32, and I'm saving that in a variable known as input. Okay, so now moving on to the next piece of code, right? So let's now see, till now we have only imported the libraries, whatever is required, and we have declared a variable input dim, which contains the number of neurons that my input layer will have, right? Now what I need to do is that before I move on to the architecture definition, defining the layers and all, I need to tell Keras what kind of a model I'm building, right? If I'm building an artificial neural network, what kind of a model will it be? Will it be a sequential model or will it be a functional model? Sequential. So I tell or I instantiate a model object of Keras, right? If you see, this models is coming from Keras, and within this models, I am importing or I'm calling sequential. So this model object that I'm creating is of the type of sequential Keras model, right? So this first line, what it does is that it instantiates a blank model object of the type sequential. Okay. Once when we have defined the model, all we need to do in Keras is that we need to keep on adding the different layers, right? Now, what do you think what my first layer will be in this particular model? Right now, I have just gone ahead and I have just instantiated a blank Keras model object. Let's say like this. Now, while defining the layers, if this is a sequential model, which will be the first layer that I'm going to define? Input, obviously, right? Because this is a sequential model. So if you see over here, the first code that I refer, the first layer that I create is I do a model.add, right? Model.add will add something. And then I call a layers.dense. Now, why do I call layers.dense? Within layers as well, there are different kinds of layers that we have in Keras. We call dense because this is something that I've explained before as well. If let's say my input layer had, let's say my input layer had 5 neurons and my hidden layer number 1 had 3 neurons. So I'm telling Keras that this will be a dense connection, right? When I say dense, every neuron will be connected to each and every other neuron, right? If you look at this is nothing but this is a dense connection that we are talking about. So that is why I'm just telling Keras that I want you to create layers, but I want you to create dense layers. When I say dense layers, it means that every neuron of the hidden layers or every neuron of input layer will be connected to each and every neuron of the hidden layer. Is this clear to everyone? If you see, this is the dense connection that I'm talking about. And that's what I'm telling Keras over here, that the layer that we are defining is a dense layer. When I say a dense layer, any layer that is going to come after this, automatically Keras will make connections of each and every neuron of the previous layer with each and every neuron of the next layer. Okay, so if you see, this is the first layer that I'm defining, right? Model.add. I do a layers.dense and then I tell Keras, right, that I want to have, right, if you see over here, this is the first hidden layer being defined. I am saying that I want 16 neurons in the hidden layer number 1. The activation function I am saying is going to be ReLU, and the input dimension. Now see, Keras knows that before this hidden layer, there will be an input, right? There will be an input layer. So I am telling Keras that my input layer will have 32 neurons. If you see input dim equals to this, I am telling Keras automatically that it will have, the input layer will have 30 neurons. So as soon as you do the first model.add, right? Keras will go ahead and Keras will define the input layer having 32 neurons and the hidden layer number 1, which will have 16 neurons, right? So it is only in the first layer definition that we need to define how many input neurons we need to have, because it is the first hidden layer that will be connected to the input layer. All right. So after, once when we would have run this code, right, your architecture of the model will start having the input layer and the hidden layer number one, right? And these two will be connected by a dense connection. Why 16, why 4? I have talked about this previously as well, that all of these are hyperparameters. This is just an example that I am giving you. But when you will be actually running these deep learning models, you will have to test around, you will have to see your model's performance with different values of the neurons. I have talked about this previously as well, that the number of neurons is a hyperparameter, right? This is just an example that I'm giving you. For the example, we need to have some values, right? So we have given 16. Renuka, activation function is also a hyperparameter. If you remember, I have asked you guys to keep on maintaining a list. The number of hidden layers, the number of neurons, the activation function, gradient descent, all of these were hyperparameters. This is just an example. I'm just explaining you how we can build a neural network model. But all of these values that you are seeing, you will have to decide them by trying out different values. All right. Now, if you see, once when you have defined the hidden layer number one, which will be connected to the input layer, right? After that, it's as simple as doing a model.add. If you want to add a new layer, you go ahead, you do a model.add, right? A dense layer, I'm saying 4 neurons, activation is sigmoid, right? Now, if you see, I'm not telling Keras that this layer needs to be connected with the previous layer. Keras automatically knows that whatever layers are coming after the definition of some layer, right, they will be connected in a sequential manner. How does it know that? Because it knows that this model object is of the type sequential, right? So it will automatically keep on making the connections as and when you keep on defining the different layers, right? Now here you see, I have gone ahead and I've added 1, 2, 3, 4, 5, 6, 7, 8, 9 layers, right? So this model in total will have 10 hidden layers. Now, you guys will be wondering, I know, that why did we go ahead with 10 hidden layers? What is the answer with to that? Layers is also a hyperparameter. This is just an example that I'm giving, right? This is just an example. 4 neurons, 10 hidden layers, activation function, whatever you are seeing are just hyperparameters. How do we arrive at these hyperparameters? All of that will come later, right? Not just now. Right now, our objective is to understand how how can we build the deep learning models using Keras. Okay, so don't worry about why I'm using sigmoid, why I'm using 4, 16 and all. I have explained this before as well. These are hyperparameters. How do we arrive at the best value of the hyperparameters? We will know that once when we are comfortable with defining and creating these neural network models. Okay. If you see, if I go to the last layer that I have, I'm doing a model.add layers.dense 1 and activation I'm giving as softmax. Why do you think that I'm doing a dense of 1 over here? Can I go ahead and can I give 2 or 3? Right? So if you see, only the number of neurons of my output layer and the number of neurons in the hidden layer are fixed. All others are totally upon your mercy, right? You can go ahead and you can give any value, but ideally you should give that value which is giving you the best accuracy of the model. That is hyperparameter tuning. That is for later. All right. 3, 4 hidden layers, right? I'm just defining some connections and then you have 1 over here. So your architecture is complete over here. So finally you will be getting all of these over here. Okay. I hope everyone is able to understand this piece of code, the one that I've highlighted. So if I run this, my model will be defined, right? The layers will be defined. I have a function known as model.summary. This function will give me how many parameters in total this model contains, right? All right. If you look at this function, which is summary, what this tells you is, it tells you that how many number of neurons your hidden layer number 1 has, how many 2 has, 3 has, 4 has till the last hidden layer. And it also tells you the number of parameters that this layer will have in total, right? Can you guys tell me how did we arrive at this 528 value? Maulik, so if you see, right, this will happen over here in this part automatically as soon as you say that the input dimension is 32 neurons. Keras will know that the input layer which needs to be defined first will have 32 neurons. After that, we are defining the hidden layer number 1, which will contain 16 neurons. So this statement, this single statement is actually defining 2 layers for you. It is first defining the hidden layer, and then it is defining the, it is first defining the input layer with 32 neurons, and then it is defining the hidden layer with 16 neurons. Exactly. So the rest are bias nodes, right? How? Because if you remember, assume that you have 4 neurons in the hidden layer. Assume that you have assume that you have 4 neurons in the input layer and 3 neurons in the hidden layer number 1, right? How many connections will these 4 and these 3 have within them? If we talk about the dense connections, I have shown that to you just now. How many connections in total will these have? 12, 4 into 3, right? But this 4 into 3, 12 will be what? Will be the set of weights, right? These will be the sets of weights only, correct? So 3 connections from this neuron, 3 connections from this neuron, and so on and so forth. But after that, if you remember, we had bias also. Bias was there in the hidden layers, right? So you will have 3 bias values for 3 neurons. So the total number of connections that you will have will be what? It will be 12 plus 3, 15, right? So just like that over here as well, I have 32 into 16 gives me 512. So these are 512 weights. But then I will have 16 biases as well for the hidden layer. So this becomes 528. Now, can you go ahead and can you tell me how did we arrive at this 68? Right? So 16 into 4 plus 4. 16 into 4 is what? 64 plus 4 is 68. Right? So like this, you should be able to calculate the parameters of the entire neural network. If you see, this neural network will need 761 parameters. If this neural network trains itself, right, it will need 761 parameters in order to get done with the training. All right. All right. So step 1, right? If you see step 1, whenever we are defining the model, we define the architecture of the model. That is what we have done. Now, if you see, I have not passed any data to the model. I have not told the model what kind of gradient descent. So till now, it is just that you have created a skeletal framework of the model. You have just told that, okay, this is how the structure will look like, right? You have not given any data. You have not given any instructions to this model till now. Right. Now, the next part that we have is the compiling part, right? First part is model.add, wherein we add the different layers. The second part is compiling. For compiling, we need to have the optimizers. Optimizer is nothing but your gradient descent, right? And we are importing optimizers and metrics from Keras. And in model.compile, we tell the model what kind of gradient descent, right? What is the loss function that you will have to work with? Because gradient descent, if you are applying gradient descent, you should also have a loss function, right? Loss function will be what? It will be the error that the model or that gradient descent will try to capitalize upon. So if you see, I do a model.compile, I tell my model that the optimizer that we will be using will be Adam. Adam, if you remember, is a kind of a gradient descent. Don't ask me questions like why Adam, why this. I have asked you to stay patient, right? All of these things we will be covering later, right? So optimizer, as of now, just see that the gradient descent that we have used is Adam. The loss function that we have used is MSE. Why MSE? Can anyone think of this? If you remember the loss functions or the evaluation metrics for regression models, they were generally what? They were MSE, RMSE, MAPE and all, right? Now, this is a regression problem that we are solving. Very good, right? So that is why the loss function becomes mean square error, right? The metrics become accuracy. Metrics, that is the metrics that the model is going to show as an output when we run it, will be accuracy of the model, right? So these are three parameters that we need to pass in the compile stage. So I go ahead and I do that. So we have added the different layers. We have combined, we have compiled the model, or we have told the model that while running, you need to use Adam as gradient descent, loss function as MSE, and you need to print out the accuracy of the model for the user to understand. Accuracy is accuracy, Indu. That's what I explained just now, just 30 seconds back, that the model will print out the accuracy for the end user to see. The metrics that the model will be printing or will be displaying will be the accuracy of the model. All right. Now, finally, we move to the fit part, right? Model.fit, right? We start with adding the layers. We move on to compiling the model. Then finally, we fit the model. In fit, we are passing both the training and testing data, right? X train and Y train. We pass the batch size. What is the batch size? I hope you guys remember batch size and epochs. So if I have 5,000 rows over here, and if I'm giving a batch size of 100, how many times gradient descent will be called in a single epoch? Very good. 50, right? Because 5,000 rows in total, I am giving a batch size of 100. So 50 times gradient descent will be called in a single epoch. I am giving an epoch equals to 100. So how many times gradient descent will be called totally in this model? 5,000, right? Very good. So now if you see, if I run this, the model training will start. Right? If you see the first epoch, if you just look at this output, right? In the first epoch, the model, it took 3 seconds for the model to run the epoch. The loss function at this point was 0.3255 and the accuracy was equal to 0, right? The model will keep on doing this, but here you can see that even after 100 epochs, nothing is changing, right? The loss is remaining the same. The accuracy is coming out to be 0. Why do you think this is happening? The model is not able to create anything. Accuracy is 0. Loss is not going down. Why do you think this is happening? Learning rate and all will be automatically defined in Adam, right? So don't worry about that. Learning rate will be predefined to 0.01. Very good, Atul, right? This is happening because our data is totally random. You cannot expect deep learning to go ahead and exactly, right? There is no relationship in the target variable and the feature that we have defined. If you remember, this data was totally random. So random data, how can the neural network learn, right? All right. Any questions on the model training part as of now? So this is how we create models in Keras, right? This is how this is as simple as it gets, right? If you look at this, it's a 3-step process, right? You add the layers, you compile the model, and you fit the model by passing through the data, right? So before asking these questions, just make sure that you at least have gone through the entire content, you have been present, right? We have gone through gradient descent so many times. Last week, the final class that we had gone through all the different types of gradient descent, right? We had talked about batch gradient descent, stochastic gradient descent, Adam, everything has been done. So then how can you ask this question? If you were absent, Shouldn't you not go ahead with the recording first? All right. Any questions on the training part, guys? I hope, see, the objective of this case study was to just see how we can build a deep learning model using Keras. Our data is random. I have not fixed the hyperparameters by going through some logic. This is totally random, right? We are just showcasing you how you can build a deep learning model using Keras. If you're able to understand that for now, that is what the objective was, right? Don't worry about why I have taken Epoch 100, batch size 100, optimizer Adam, loss MSE, because all of these things we'll be covering later. Nitin, the first step is adding the different layers that we are doing over here. The second step is compiling the model, which we are doing over here. And the third step is fitting the model with the data that we have that we are doing over here. All right. So now, Sheetal, all of that depends on what you are trying to solve, right? Hang on, just hold on. Once when we are working on case studies, I will tell you. See, it does not mean that if you're using a deep learning model, it will give you 100% accuracy every time. If you see over here, our data was random, so the model was not able to do anything, right? So the model was not able to do anything. So if it depends upon what problem you're solving, how complicated it is, right? But what you can generally see is that if your traditional machine learning is giving you an accuracy of X%, if you train the deep learning model properly, your deep learning model will always give you a better accuracy than that. Okay, so now let me do one thing. What I'll do is that I will comment this out and let's create some logical data, right? What I'm doing is that now instead of having random data, I'm creating data which is coming from a normal distribution, right? If you see, my training data is coming from a normal distribution and my my X train is coming from a normal distribution and my Y train is also coming from a normal distribution, right? So let's try to run this and let's try to see if my model is able to converge or if my model is able to give us something that is not equal to 0, my accuracy not being equal to 0, right? Shall we do that? All right. So I'll do a run all, right? I create the data. All of the same things will happen, right? My model training, I'm defining the same model architecture. Everything remains the same number of hidden layers. This is the summary. You can see that the parameters will remain the same. This is the model, right? And if you can see that your model is running, right? And over here as well, we can see that the accuracy is totally equal to 0 and the loss also does not change, right? Now, why does this happen? This happens because even though it is coming from a normal distribution, right, there is no relationship between X train and Y train, right? My data internally might have some distributions, but your X train and Y train should be related to each other, right? So because we are using totally random data, your neural network will not be able to, actually it will not be able to work properly, right? But if you go ahead and if you give this neural network any logical data, let's say data which is, I'll reiterate, don't worry about the hyperparameters as of now. Don't worry about why I have used 10 layers, why I have used 100 epochs and all, right? Uh, right now, we will just try to get familiar with the coding part, right? Once when you are familiar with the syntax, why we are doing this, why we are doing that, after that, we will come to the part wherein we will focus on defining or how do we define the hyperparameters, how do we arrive at the best values of the hyperparameters, right? If you see, all of this is nothing but the sample code. So as of now, let's not get into this. Once when we will be moving to functional and sequential models. I have two different case studies that are there already, right? So now we will move on to the what are the different kinds of layers that we have in Keras, right? Now that we have a decent understanding of how Keras works, right? Let's try to understand the different kinds of layers that we have in Keras. All right. Now, see, layers, again, it's not that we will only have hidden layers in the deep learning models, right? Depending upon the kind of neural network model that you're building, the type of layers will keep on changing, right? So there can be a layer known as a convolutional layer, which we apply in a convolutional neural network, right? There can be a layer known as pooling layer, which once again we apply in convolutional neural networks. There can be something known as the recurrent layer for the recurrent neural network, right? So there are different kinds of layers that Keras has to offer because there are different kinds of deep learning models that we have, right? So for, let's say, for an ANN, there might be 2 to 3 kinds of layers that we use. So for an ANN, generally we just go ahead and we use the dense layer, right? We can also use the normalization layer. Normalization layer, we have convolutional layers, we have noise layers, pooling layers. Embedding layers are for embedders that we create, right? Locally connected layers, merging layers, recurrent layers, advanced activation layers, right? So there are different kinds of layers that we have, as in when we will be talking about the different kinds of models, we will be going through some or most of these layers that are defined over here. All right. So what the objective of this slide is that Keras actually offers you a lot amount of freedom to work with different kinds of neural network models, right? Now, do you guys understand what we mean by the word uh, uh, regularization, this word? Are you guys aware what this means? Regularization. You should have studied this during the machine learning part of this course. Regularization is not scaling. Regularization is not normalization, standardization. Regularization is a totally separate term, right? So don't confuse this with scaling or standardization or normalization, right? All right. So are you guys aware with underfitting, overfitting, proper fitting, appropriate fitting? What do we mean by this? Okay, so let's say I have a model which is giving me a testing accuracy of 80% and a training accuracy of 99%. What will you call this model? Training accuracy of 99% and a testing accuracy of 80%. Overfitting, right? What if I have a model which is giving me a training accuracy of 50% and a testing accuracy of 45%? Underfitting, right? Now see, underfitting, overfitting, both of these things are not something that you would want your model to do. Now, underfitting is obviously your model is not even able to perform on the training data, right? So that is something that people generally not get confused with. Now, overfitting is a term that is generally people who build models, they are not able to understand whether it is overfitting or not. So why overfitting is important? Because it kind of gives you a false sense of satisfaction that your model is doing well, right? On training data, your model can give you 90%, 99%, even 100% accuracy, right? But that is not the objective, right? What is the objective? The objective of building the model is for the model to go ahead and replicate the same performance, whatever it was doing on the training data, to replicate the same on the testing data, right? Do you have the use for a model which is giving you an accuracy of, let's say, 100% on training data, but an accuracy of only 70% on testing on unseen data? No, right? The objective is to use these models to make predictions so that we can take decisions on the basis of whatever we are getting from these models, right? So overfitting is something that generally we do not want our models to do, right? Now, generally, we can limit overfitting by regularizing the models, right? Now, what do we mean by regularizing? What do you mean by regularization? Let's try to understand that, right? All right. So let me give you an example, right? So let's say that you are you are the coach for a cricket team or something, right? And you have two options for a team, right? There is one team which consists of 11 players, and all these players are medium level players, right? None of the player is, uh, let's say, a star player, and neither of the player is, let's say, a player who's a underperformer, right? All of the players, if you say, if you talk from a skill point of view, are medium skilled, right? No one is exceptional and no one is too poor, right? And then you have a team with, let's say, the second team, which consists of two star players, right? Two, one star batsman, one star bowler, and all the nine players, all the rest nine players are actually poor players, right? They are actually maybe not even players who are not at par with their game, right? I'm not going to say that they are good players. I'm not going to say that they are average players. I'm going to say that the remaining nine are actually bad players, right? Now, which team will you prefer to choose? Will you prefer the first team, which consists of 11 uh, average players, or will you consider the team which has two exceptional players and nine players which are below average? Why the first one? Because looks more stable, right? See, the second team, it might happen that the second team might beat the first team on occasions. Why? Because it might happen that when the star performers are performing, right, then they perform to such an extent that they go ahead and they beat the other team, right? But generally, cricket is a team sport, right? So, see, there can be off cases wherein, let's say, team two might go ahead and might beat team one. But what are the chances? The chances are that team one is going to beat team two on most of the occasions, right? Because cricket being a team sport, you cannot rely on only one performer, right? Indian team cannot only rely on, let's say, Virat Kohli, Rohit Sharma to go ahead and win the matches. They might do it in a game or two, but they cannot do it for the entire series. They cannot do it for the entire World Cup, right? Now, just like that, when we are building a model, right? Generally, models that overfit are those models which give a very high amount of weightage to some features, right? Now, see, just like players form the team, just like that, the features, the variables that you have actually form the model, right? Now, if you have one model which has, let's assume, 10 features, and all the 10 features are given average weightage, right? No feature has been given over weightage, right? And then you have another model wherein you have 10 features, 8 of the features are ignored. The weights associated with those features are close to zero, but there are only two features which actually go ahead and which get a high amount of weight, right? Now, do you think which model is going to perform well? Is it the first one, or is it the second one? See, the second one, right? Now, the second one will underperform whenever you start getting outliers, or whenever you start getting incorrect values for those features, right? The two features that are actually over indexing, the weights for which are over indexing, you cannot depend upon the model, because it might happen that 99% of the predictions are coming from the values of these two features only. Now, if these two features go off, right, or if these two features start behaving in a contradictory manner, your model will start to give predictions which you might not be expecting, right? Hence, we have something known as regularization. Now, what regularization does is that it prohibits the model from going ahead and giving too much weightage or too much importance to any particular one feature. What it says is that you go ahead and you use each and every feature that you have been given. Right now, when I say each and every feature, it does not mean that every feature will have, let's say, a similar amount of weightage, right? It should not be that. See, obviously, when I have 10 features, it might happen that um, two features out of those will have relatively higher importance as compared to, let's say, the remaining eight, right? But it should not be that the remaining eight are getting no importance at all, right? So your weightages assigned to the different features, it should not exceed beyond a given point, because if it starts exceeding, now if I, let's say if I go ahead and I say that Virat Kohli has an importance of 20, and the rest of the players in the Indian cricket team have an importance of, let's say, 1 each, right? So the overall score of Team India will become 30, 20 into 1 plus 10 into 1, right? So whenever Virat Kohli is not performing, the overall team's performance is going to decline, right? I don't want that. I want that if Virat Kohli fails, then others should also be there who are able to actually go ahead and make us win the match, right? Just like that, if I have 10 features, if let's assume that out of the 10 there are two features which somehow the values are outliers that are coming inside the model, right? Now, if my model would be giving only weightages to these two features, my predictions are going to go off, right? If all of the rest of the features are having a decent amount of weightage, my predictions are not going to go off by a very huge margin, right? Does this make sense, everyone? Any questions? This is not dimensionality reduction, Aniket. Regularization in deep learning is slightly different, right? Regularization like lasso and ridge, in that case, ridge can be used as a dimensionality reduction model as well, right? But I think not needed, that's not needed as of now. Exactly. So regularization is nothing but reducing the complexity of the model, right? Bhagirath, normalization, standardization is scaling, right? It is not playing around with the weights. Your normalization and standardization, they will scale the features, right? If you have features, let's say you have one feature which is varying between 0 to 1. You have other feature which is varying between, let's say, 0 to 1,000. You have third feature which is varying between, let's say, 0 to 1 million. So what scaling, what normalization, what standardization will do is that it will bring all of these variables in the same range, right? It is not working on the weightages of these features. It is working on the absolute values on these features, right? Regularization, on the other hand, is actually working on your weights that the models assign to these features. All right. So I hope this slide is clear to everyone. Just go through this once and let me know if you're able to understand this. Now, if you see what overfitting is, right? Overfitting is generally beyond a certain point, right? So now, if you look at your neural network models, a lot depends upon the epochs as well. See, what is overfitting? Overfitting is you keep on training the model again and again and again and again, right? Now, see, what do we understand by epochs? Epochs is nothing but how many times your entire data is being fed into the model, right? Now, let's say I do one thing, right? I want you to study for a test, right? And I give you, let's say, a particular book, or let's say I give you a particular question bank, and I ask you to go through that question bank, right? Now, in order to prepare well for the test, whatever you were supposed to give, right? What you do is that you go through this particular test, sample test, let's say 20 times, right? Now, the my objective of you, of me giving this test to you, was for you to go ahead and practice the questions, so that whenever you are getting similar kinds of questions, you can go ahead and you can solve those, right? But if instead of going ahead and understanding whatever questions were there on the test, you just keep on going through that, right? Maybe 20-25 times. And what happens is that you will start remembering things which are very, very specific to the test, right? Now, once when you actually go and appear for a test, obviously the questions that will come will be different, right? The way the questions will be written, the way the questions will be asked, right? The values and all will be different. Now, this is something that is known as overfitting. So, see, in the case of the neural network models, if you keep on passing the data again and again and again, right? The model does not have any way to start to limit the weights, right? If you are passing on the data again and again, the model will think that you want it to train, right? And what it will do is that it will keep on adjusting the weights. So in case of neural networks, if you see, overfitting is directly associated with the number of epochs that you are giving, right? Because if you keep on increasing the number of epochs, what will happen is that the model will keep on learning new weight values, and eventually it will start to overfit, right? Now, how do we contain that? Now, see, it's a simple fix. If I run my model for 50 epochs, right? What if I go ahead and I track the accuracy of my model, right, for all the 50 epochs? Let's say my accuracy, both training and testing, keep on increasing till 30th epoch, right? But after the 30th epoch, I realize that my training accuracy keeps on increasing, right? But my testing accuracy, I realize that it has now stabilized, and then eventually it starts to go down, right? Now, what does that mean? That means that 30 epochs is the hyperparameter value for epochs after which your model will start to overfit, right? So if you look at this over here, on the right hand side, on the x-axis, you have the model complexity, right? So as and when your model complexity starts to increase, your model complexity will increase when you keep on increasing the epochs, or you keep on passing the same data to the model again and again, right? So if you see, your error on the training data will keep on going down, right? Your accuracy will keep on going up, which means that your error will keep on going down. But beyond a certain point, right, your testing error, right, your testing accuracy will start to decrease, your testing error will start to increase. And this is the point that is known as your, or this is the point beyond which your model will start to overfit, right? And this is what we want to contain. Further, now regularization, if you see, how do we perform regularization using Keras, right? Now, if you see, regularization is a technique which makes slight modifications to the learning model such that the model generalizes better. This in turn improves the model's performance on the unseen data as well, right? So we have gone through this. Now, how does regularization help reduce overfitting? So if you see this, right, if let's say this is my model, if you see this is a very heavy, this looks like a complicated model, this might be overfitting, right? Overfitting, if you see over here, my output could have been as simple as, or my line could have been as simple as this, right? It could have been this, but only to classify these 2 points correctly as well, the model has gone ahead and it has changed its course, right? If you look at this, this is what overfitting is all about. Now, if I would have reduced, or I would have stopped the model, let's say in the appropriate number of epochs, right, my model would not have gone ahead and would not have made these complicated decision boundaries, right? So regularization will help in containing this. All right. So what it does is that regularization will penalize the weight matrices of the nodes. Now, if you see over here, all of these hidden layers, right? All of these hidden layers will have the hidden neurons, right? So what regularization will do is that it will penalize the weight matrices. It will not allow the neural network to give more than the stipulated amount of weight, or more than the required amount of weight, to any particular neuron, right? And how is it able to do that? See, it's able to do that. See, everything is being tracked through the accuracy of the model. As soon as the function knows that the accuracy of the testing data has started to decline, or the error on the testing data has started to go up, it knows that overfitting is starting to happen, right? As soon as it starts to happen, what it will do is that it will start containing the weights over there only, right? Now, if you see, assume that our regularization coefficient is so high that some of the weight matrices are nearly equal to zero, right? This will result in a much simple linear network, and slight underfitting of the training data will happen, right? Now, let's say if over here in this particular neural network, I go ahead and I deactivate some of these neurons, right? If I deactivate some of these neurons, which are important, what will happen is that you can see that the model has created a very simple model, right? Now, this is something that looks like as an underfitting model, right? Why? Because ideally, my output should have been this, right? My decision boundary should have looked like this. right? But over here, if you see, the model that I'm getting is kind of like a straight line, which I don't want to expect, right? So see, even if you contain the weights too much, right, this will be a problem for you, because you might end up getting a model which is underfitting. Even if you give a very higher importance to weights, even then that will be a problem for you, because your model might start to overfit, right? Hence, I am hoping that every one of you is able to understand the complexities here, right? That see, working with neural network models is exciting, and everything, right? But in order to find out the best model, which is the best fit for your data, that requires a lot of calculations, that requires a lot of effort from your end, because you will have to test out the model again and again, to see if whatever performance it is giving, if it is true to unseen data as well, right? Now, what we want is something like this, right? We need to optimize the value of the regularization coefficient in order to obtain a well-fitted model as shown in the image below, right? Now, see, regularization, when we perform regularization, there is something known as the regularization coefficient. Regularization coefficient is nothing but it is a mathematical value which tells the regularization model how much capping it needs to do on the weights, right? Now, if you give the value of regularization coefficient as a high value, it might end up and it might start clipping off those neurons or the weights from those neurons as well, which are actually helping you in creating a good model, right? So this is not something that you want. You want the regularization coefficient to be such a value that it only goes ahead and it only clips off those neurons and the weights associated with them which are actually over indexing, right? Now, how do we need to find all of this? I'm assuming that you guys would be having this question. Now, all of this, as I've said, is just iterations. We have to go ahead and we have to try out different values. It is trial and error. The only thing that works in our favor is the accuracy of the model. At each and every point of time, we will be able to track the accuracy of the training and the testing data. So if I'm able to track the accuracy of the model in training and testing both, right, I should be able to find out whether the model is overfitting, whether the model is underfitting. Correct? A regularization and learning rate in do are different. Learning rate is by how much factor you are adjusting the weights. Once when the weights will be adjusted, right, after that regularization will come in. But the only similarity between these two is that both of these are actually working with the weights of the model, right? That is the only similarity. But whereas learning rate is you are making an adjustment, right, on the basis of let's say a factor that you have provided, right? Learning rate will be step one, that because of the learning rate your weights will get adjusted. Because of gradient descent, right, you will get the error, right? You will get the contribution of each and every weight for the error, right? And because of the value of the learning rate, you will get an adjustment factor of the overall weight that you have, right? Now, once when you have adjusted the model, once when you have adjusted the weight, then your model will start giving you a different performance. The training accuracy, testing accuracy will change. That is when regularization will come into effect, right? So let's assume even if learning rate goes ahead and says that you need to increase this weight by 1, right? If regularization realizes that by increasing this weight by a unit of 1, my training accuracy will increase, but my testing accuracy will decrease, it will not let that happen. It will contain that depending upon the regularization coefficient value. On the sample code, right, there as well, you would have seen that after every epoch, accuracy will be calculated. See, calculation of accuracy is not heavy, right? It's not a time consuming process, right? What is heavy is applying gradient descent, adjusting the weights and all. So, but accuracy calculation, obviously, that will be required. Now, see, just try to correlate this to whatever we try to do on a daily level. You trying to learn something new, right? You have your benchmark, and you, after doing something, you will go ahead and you will assess your performance, right? You cannot just go ahead and work on something blindly without being able to track it, right? So that is why accuracy tracking is necessary. After every epoch, we will have to calculate the accuracy, because epochs are heavily actually influencing whether your model is overfitting or not. So if you're not keeping a tab on the accuracy, maybe after the 30th epoch, your model starts to overfit. If you're not keeping a tab on the accuracy, how will you be able to tell that the model is overfitting? Right? Now, see, in Keras, right, or for our deep learning models, we have something that is known as dropout regularization, right? Now, what dropout regularization does is that it it's a regularization approach, right, which tries to find out the neurons which are actually helping you in making predictions, right? Now, I'll give you an example. So see, uh, creating neural networks, right? A lot of it depends upon the number of hidden layers that you would have defined, the number of neurons that you would have defined, right? Is everyone aligned with this? That the number of neurons and the number of hidden layers that we have in a neural network, that will at the end of the day define the accuracy of the model. If I have more hidden layers, if I have more neurons than required, it might be an overcomplicated model that I'm making, which might not be the need of the hour, right? Now let's assume that you were able to identify that the model needs to have two hidden layers, right? But now see, when it comes to neurons, generally what we do is that we define the neurons of hidden layers in the power of 2, right? So you will go ahead and you will say, let's say hidden layer number 1 has 32 neurons, hidden layer number 2 has 16, right? Hidden layer number 3 has 4 or 8, whatever, right? So generally, see, it's not that you cannot go ahead and you cannot give random values to the neurons, right? But generally, this is what we do. Why do we do this? Because this actually makes it easy for the computations, right? These are binary defined values, right? 2 to the power something. So from a processing point of view, it becomes easy for the model. It not becomes easy, but you are actually using all the resources that you might have, right? But now let's assume that I define 32 neurons for one hidden layer, right? But for this hidden layer, ideally, I needed only 27 neurons, right? Now, what will the 5 neurons that are extra do? Do you think that they are going to sit back and not do a thing? No, right? What will happen is that these 5 neurons will start to, uh, let's say, they will start to create weightages on those features, or they will start to create interactions of those features which might not even be important, right? Because I have told the neural network that you need to build 32, you need to create a hidden layer with 32 neurons. Although in reality, I might have required only 27, right? But I don't know that. I'm just playing a guessing game over here, right? But if I say 32, maybe the 27 that are required are doing their job appropriately. But the 5 that are not required, but they are still there on the job, right? So it is just like that. Let's say a team is created for by your manager, right? And in that team, you have 10 people, right? But the requirement was only of 5, 6. Now, 5 and 6 of you are able to go ahead and are able to do whatever is required to do. But the remaining 4, you will have to delegate some work to them, right? Maybe at the end of the day, they spoil the work for you because they are intruding in what you are doing. They are actually not being helpful and things like that, right? So just like that, let's say the 5 extra neurons that we have over here, they will not sit idle. They will try to create interaction of variables. They will try to extract some information from the data. Now, this information might not be important for us, right? But still, because we have said 32 neurons, one hidden layer, the neural network will go ahead and do that. Is every one of you able to understand what I'm saying? Now, see, what dropout regularization does is that in neural networks, dropout regularization is a regularization technique which deactivates neurons that are provided in the hidden layer. Now, let's say I had 32 neurons, right, in my hidden layer number 1, and I applied dropout regularization with a dropout coefficient of 0.2, right? If I apply this with a coefficient of 0.2, 6 neurons out of the 32 will get deactivated, right? Now, what will happen is that these neurons are going to get deactivated randomly, right, in a random fashion. For each and every epoch, for each and every gradient descent calculation, right, the neural network will randomly keep on deactivating some of the neurons, right? Now, let's assume that when the neural network goes ahead and out of the 32, it deactivates 6 neurons, and all of these 6 were actually important for the model. What will happen? Will the performance of the model, the accuracy of the model go up, or it will go down? Down. It will go down on both, right? Both training and testing will go down. Is that correct? So now the model will realize that the neurons that were deactivated were actually important. Now in the next iteration, what will happen is that it will go ahead and it will deactivate a different set of neurons, right? Now let's say this time what happens is that the model's performance remains the same, right? It does not go up, it does not go down. Now, what might have had happened would have been, let's say that the 3 neurons that were deactivated were important, and the 3 neurons that were deactivated were not important, because of which the overall effect actually cancelled out, right? Now, what will happen is that the regularization model will go ahead and it will deactivate. It will activate some of the neurons from the 6 that it has deactivated before, and it will deactivate some others from the remaining 26 that we have, right? This will go on and on and on, right? This is not a one-time thing. You can see over here that this is totally trial and error, right? Regularization coefficient is trying to pinpoint the neurons, right? This is kind of like a like, let's say, a project manager who has been assigned, who has been given a role of singling out those who are not actually contributing, right? So just like that, the regularization coefficients or the dropout regularization's job will be to identify the neurons who are the culprits, who are not increasing the accuracy of the model on the testing data, right? So let's say that it goes ahead and it finds a combination of 6 neurons for whom the training accuracy, when the neurons are deactivated, the training accuracy goes down, right? When I will deactivate these 6 neurons which are actually which are actually overfitting or which are not important, what will happen is that the training accuracy will go down. But do you think that the testing performance will also go down in this case? No, right? So for these set of 6 neurons, when the model is able to identify this, it will realize that the training accuracy goes down. That's fine, but the testing accuracy remains same. Even in some cases, testing accuracy might get better as well, right? So, and this is how your dropout regularization will generally work. So we can apply dropout regularization after each and every hidden layer. So what will happen is that it will keep on checking which neurons are important, which are not important. Now here, if you see, a very important aspect is the regularization coefficient, right? Now the regularization coefficient is a value that will vary between 0 to 1. If you give it as 0.5, it means that the regularization will deactivate 50% of the neurons, right? If you give it as 0.1, it will deactivate 10% of the neurons. Now, if you go ahead and if you give a high value, right, your model will have no choice but to deactivate important neurons as well. So hence, the value of the dropout coefficient as well is also very important, right? We also need to try out different values, and we need to see for which particular value actually we are able to reduce overfitting, right? And if you start giving a higher value, you will realize that the overall model performance will also decline, right? So this is overall. Now this is what dropout regularization does, right? If you see over here, every iteration, it randomly selects some nodes and removes them along with all their incoming and outgoing connections, right? So if you see, for each and every iteration, it keeps a track on the performance. And so if you see, this is how it works. If let's say if I apply a dropout layer of 0.5, it will randomly deactivate 50% of the neurons, right? So now dropout regularization, you can understand that creating neural networks, if I have thousands and thousands of neurons, right? It might not be required for me that all thousand of neurons are actually contributing in my model's performance, right? Then I need to find out those neurons which are actually not helping me, right? And once when we are able to do that, we just go ahead and we deactivate them. This entire process is nothing but dropout regularization. No, Malik, it cannot have your input feature nodes. See, when you are deactivating the weights for, let's say, hidden layer number one, in a way you are deactivating the inputs only, right? The weights that will be coming from input to hidden layer number one will be the weight. So let's say if you make the weight as 0 for a certain connection from input features to hidden layer number one, what it will do is that it will make that feature 0, right, for that particular neuron. So Nitin, as I said, right, there is no fixed p-value over here. The regularization coefficient is something that you will have to identify after running it for different combinations, right? Because it might happen that, see, if I, let me give you an example. Uh, let's say that the appropriate number of neurons that I wanted to have for a hidden layer were 26, right? And I went ahead and I defined 64 neurons for that layer. What will be the dropout coefficient that you would want to give for such a case? The dropout coefficient will be somewhere around 60%, right? 0.5 will be 32. If I take 0.6, it will be somewhere around 60%, right? Will deactivate somewhere around 38 neurons and the remaining 26 will be there, correct? Now, similarly, if let's say you went ahead and some other person, right? Let's say they went ahead and they defined only 32 neurons in this layer. For them, will 0.6 work? No, right? For them, 10% will work, 0.1 might work. So there is no, it all, see, neural networks are customizable, right? You might give ahead and you might go ahead and you might give 1,000 neurons for a layer that requires only 100. So in that case, either you will decrease the size or you will give the regularization coefficient as 0.9. So Indu, how can dropout is different from k-fold cross-validation? In the k-fold cross-validation is not affecting the weights of your model, right? K-fold cross-validation is testing the model performance on different samples or different snapshots of the data. It is not in any way manipulating the weights of the model. Your dropout regularization is deactivating some of the neurons, right? It is not letting some of the neurons contribute, right? So I think you're getting confused by how it is working. If in case of k-fold cross validation as well, you are creating different combinations. So in a way, how it is selecting the neurons, that how that is happening in k-fold cross validation, that you can call it as somewhat similar, not even all that similar, but then k-fold cross validation is just creating snapshots of data, whereas your dropout regularization is something that works at a model level, right? It is actually affecting your weights of the final model. Now, see, in Keras, applying dropout is very simple, right? If you see over here, the layers that we had defined, right? So we will be doing this, obviously. All we have to do is that we have to add a parameter of dropout, right? If you remember, we had done this. We had given the input dimensions, the number of neurons, the activation function and all. Just in that part, all we need to do is that we need to mention the function dropout. From keras.layers.core, we will import the dropout layer and we will just call that function and give the dropout coefficient, right? If I give 0.25, what will happen? My 25% of the neurons will get deactivated randomly, right? If I give 10%, 10, 0.1, then 10% of the neurons will get deactivated randomly, right? So it's as simple as that. Right now, data augmentation. What is data augmentation? I will talk about this more once when we get started with your convolutional neural networks, right? So data augmentation is nothing but see, when we are working with images, uh, so let's say I'll just explain this concept simply now, and then once when we move on to the convolutional neural network, then I will talk about this more. Right now, if I go to the images of dogs, right, you can see that the images for dogs can be so many types, right? Now, this is a dog which is sitting. This is a dog which is side pose, right? This is a dog which is close up, right? Now, so if you see what image augmentation is, let me see if I can get some examples. Yeah, so if you look at this, right? If you look at this cat, I had one image of a cat over here, right? If you see, the input was one image. But what has happened is that through this one image, we have gone ahead and we have created 9 or 10 different kinds of images. Now, the first image is the actual cat. The second image is the cat, but it is rotated at an angle, right? Now, the third image, it is the half image of a cat, right? So if you see, data augmentation is nothing but creating additional images from your original data, right? Now, assuming you are given 10,000 images of dogs and cats, right? Now, you can go ahead and you can actually augment the data and you can create, let's say, 50,000 more images. Now, why do we need to do that? First thing is that when we have created a model, right, we cannot expect the end users to go ahead and, let's say, if you ask them and if you say that your dog must be sitting, right, every user will not do that. Maybe someone is in someone's photo, the dog is sitting, but the dog is very far out, right? Maybe in someone's photo, the dog is sitting, but only his face is visible, right? The body is not visible. Maybe in some photo, the dog is sitting, but he's sitting at an angle, right? Something like that. So for that, what we do is that we actually augment our data, right? When we augment our data, augmentation is nothing but you can shift the image, right? You can shift up, you can shift down, you can shear the image, you can shift and scale, you can shift the image and you can zoom in, zoom out, right? You can rotate the image and things like that. So in Python, there are functions which will help us in augmenting the data. When we mean by augmenting, whatever images, whatever input images we pass, right? The depending upon the parameters that we are passing, let's say if we pass the parameter then that we need to shift the images by 10 degrees, right? If we need to, let's say, shear the image by, let's say, 10%, things like that, right? If we give all these parameters, the function will automatically go ahead and create new sample images for on which you can train your model on, right? So that is data augmentation. If you see, it is as simple as we need to import image data generator and whatever data. So let's say if I have images and I want to do a horizontal flip equals to true. For all the images, I want to flip them horizontally, right? So I will just call this and I will do a data gen dot fit. If my training data had 20,000 observations, now it will have 40,000 observations. 20,000 will be the original images and the remaining 20,000 will be the horizontally flipped images that you would have gotten from the image data generator. Now, like this, you will have other parameters as well. But this is something that we will be working more on once when we start with the convolutional neural network models. Now, moving on, we have something known as batch normalization. Now, batch normalization is nothing but your typical normalization that we have, right? So when we are working with our traditional ML models, right, we generally standardize the data only once, right? We go ahead and we standardize the data before passing it to the machine learning model, whatever you might be building, right? Now, over here, let's assume I have such a neural network which I have created, right? Let's say these are the hidden layers, 4 hidden layers in between, and let's say I have 2 outputs, right? So let's say this is my input layer and this is my output layer, right? And these in between are the hidden layers, right? Let's say this is hidden layer number 1, hidden layer 2, hidden layer 3, and hidden layer 4, right? Now see what will happen is that, let's say I have an input value that is coming from here, which is, let's say, 20, right? Now this 20, you know this that this 20 will go over here, right? This 20 will be over here. Now this value will get multiplied by some weight and will become some other value, and whatever comes out from this, it might happen that this 20 that is coming out becomes 0.2. Is that something that makes sense? Maybe let's assume the 20 becomes 0.2, right? Now let's say this 20, when it goes from here to, right, so let's say this 20, when it goes from here to here, and then it comes out from here to here, right? So let's say this 0.2 now over here becomes 0.001. Can this be possible? Anything can happen, right? Anything, at the end of the day, anything can happen. My values can keep on becoming anything, right? Now over here it can happen that once again, once this values goes from here to here, it might become even more small. Maybe here it becomes 0.0034, something like that. Now see what happens is that uh a value which was 20 keeps on getting transformed and becomes a very small value, right? Now this generally becomes a problem for gradient descent, right? In some cases it becomes a problem for gradient descent, because let's say that from gradient descent I get that you need to adjust this weight by 10%, right? Let's assume I need to adjust this weight, right? From the gradient descent model, I get this, that this weight needs to be adjusted by 10%. Now, if you see this 10%, if I adjust this over here, 0.0034, if I adjust this for 10%, do you think that this will make any difference to the output that we are getting? Because 10% of 0.0034 will be such a small value, right? So what happens is that it actually becomes complicated for gradient descent to go ahead and update the weights. Hence, we have something known as batch normalization. What batch normalization does is that for every hidden layer, right, the inputs that they get, it will normalize that. All the values that are going as an input to the hidden layers, they will be in the range of 0 to 1 only. You can have whatever transformations you are doing inside the neurons, whatever value is coming out, that value will be normalized, right? Every value will be in the range of 0 to 1, right? So if instead of this, let's say I had values over here, let's say this 20, let's say this value I had 0.5 over here, the transformed value. Let me change the color. So let's say the first transformed value was 0.5. Now let's say the second transformed value was 0.8, right? Let's say the third value was 0.2. The fourth value was, let's say, 0.4, right? Now all of the values are actually in range, and your gradient descent will be able to update the weights properly. Otherwise, your gradient descent actually gets stuck, right? So in order to basically bypass this thing from happening. Now, this can happen, might not happen, but just to be sure, what we do is that we normalize our data, right? Normalizing is before your input is going into the hidden layer, right? For all the hidden layers, whatever input is going, it will be normalized, right? Batch normalization normalizes each batch by both mean and variance. It is just another layer you can use to create your desired network architecture. It is generally used between the linear and the non-linear layers in your network, because it normalizes the input to your activation function, right? So if you see, if this is your layer, right? If let's say if I add a new layer with 64 neurons, activation is ReLU. Over here, if you want to add normalization, right? You can see that we have added normalization here. Model1.add layers.batch normalization. and then you follow it by the activation function. Generally, normalization is applied before the linear and the non-linear transformation, right? After the linear transformation and before the non-linear transformation. So if you want, you can apply batch normalization there. Is it mandatory to apply normalization? Krishna, it's a good practice. We should be applying, because if you're not applying normalization, your gradient descent might get stuck and might not update the weights appropriately. If it is not updating the weights appropriately, your model might never converge. You might never get a good performance, right? So Indu, normalization is nothing but it is scaling of your data before every hidden layer, whatever input is being passed, right? That needs to be normalized. If you are not normalizing that, what will happen is that your values for the subsequent layers might get either too small or too big. When it becomes too small or too big, then gradient descent or updation of the weights for gradient descent becomes a problem. So Pooja, see this batch normalization automatically in Keras, right? When we will be applying this batch normalization layer, automatically it is applied between the linear transformed layer and the non-linear transformed layer. The linear transformed is what? It is the weights multiplying by the features, adding the bias. After that, you input this output to the activation function, right? So before inputting this to the activation function, we actually normalize, right? But this is not something that you need to do manually. Automatically, Keras will take care of this. Whenever we are applying batch normalization, it will automatically be applied between the linear and the non-linear transformation. Indu, I have not talked about vanishing gradient descent as of now, but in a way, if your inputs become too small, your gradient descent, when you are applying gradient descent, right? If let's say one weight value is 0.00001, if you will apply gradient descent to this, whatever updates will happen to this weight, right? It might become 0.000015, right? At the end of the day, it is not a very big change in the weight that you're doing. So when the weight is not changing by a huge margin, your output will also not change. When your output is not changing, your accuracy will also not improve, right? So that is why, in a way, now vanishing gradient, for those who don't understand it, don't worry about this now. Once when we move to recurrent neural networks, we will be talking about vanishing gradient descent and all. Can it be applied between two hidden layers? Atul, it is generally applied for a given hidden layer only, right? Because your hidden layer is the one which is transforming the output. If you have two hidden layers, you will have to apply two batch normalization layers, one for each of the hidden layers. Nitin, normalization, see, generally it does not ensure that everything, every distribution or every input will become normalized to a normal distribution. At the end of the day, what we mean by normalization is that your mean becomes 0 and your standard deviation becomes 1. It might happen that your data might not still resemble a normal or bell-shaped curve, right? But the properties of normalization, this is something that you should have covered in the machine learning part, is that your mean will become 0 and your standard deviation will become 1. And this will happen for all the variables. If you have 10 variables, then for all 10, your mean will be 0 and standard deviation will be 1. All right, so let's get started. Now, when we start, we will import the libraries. I'm importing from Keras, I'm importing the models. I'm importing from layers. I'm importing dense layer because my neural network will use dense layer, and I'm also importing the dropout layer, right? What is dropout? Dropout is the dropout regularization that we have talked about, if you remember, right? From Keras.utils, I am importing two categorical. This is for the target variable. I will talk about this. From Keras.datasets, right? If you see, Keras as a library has inbuilt datasets as well, right? So from here, what I'm doing is that I'm importing the MNIST data. So this is the digit data. So today we'll be working on an image data, right? So we'll talk about how image data works. Now this is SVG. This is just to display something, right? So I'll talk about this. This is about the live loss plot, right? Now live loss plot is a function that will automatically keep on plotting the losses or the accuracy of your model as and when the epochs progress further, right? So let's say if on the x-axis you have the epochs, right? And on the y-axis, let's say you have the accuracy, right? So what will happen is that first time when the first epoch runs, right? So let's say once when the first epoch runs, your training accuracy is somewhere over here and your testing accuracy is somewhere over here. So it will plot that. As soon as the second epoch runs, let's say your training accuracy goes from here to here and testing goes from here to here. So this will update that, right? Now, as soon as the third epoch is done, let's say the training accuracy goes from here to here, testing goes from here to here, right? So just like this, what it will do is that it will keep on plotting the accuracies, right? So that you are able to realize. So let's say after the fifth epoch, my training goes up, but my testing stabilizes, right? Right? Then let's say this goes once again up, this goes down, right? This goes up, this goes down, right? So your live loss plot is kind of a dynamic way of plotting how your model is performing, right? As and when we proceed through the epochs. Into this is just an example, right? It can be anything. It can be parallel, it can be totally off, it can be anything. This is just an example that I'm giving you. All right. So for that, I need to install the live loss plot function, right? Library. So I've installed that, right? And then let's get started with the case study. Now, all right. So I have, after installing live loss plot, I have imported this live loss plot library, right? And then I have just instantiated the model object of this. As of now, this is not required. Just don't worry about this. And I have declared some variables, right? Let's try to understand the data first, and then we will come back to this, what is rows and columns and all, right? Okay, I have created a function. This is data summary, right? This particular function will give me the data summary. Let's load the data and let's have a look at what this data looks like, right? If you see mnist.load data, how am I able to do that? From keras.datasets mnist, I have already imported, right? Now all I need to do is that I need to do mnist.load data, and this will give me the data, right? Now I believe all of you know that the images, right? The digital images that we see are nothing but numerical values, right? Let's say if you have a given image, that image will have.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
Different pixels, right? It will have small pixels, and the pixels will have intensities, right? Now your pixel intensity can vary anywhere between 0 to 264, right? 263, 264, whatever, right? Now, if you see, all of these pixels will have certain values, right? So let's say if this part of the image is black, maybe the pixel value over here for this pixel becomes, let's say, 0, right? 0 to 255, yes, right? If let's say this part of the pixel is, let's say, some other color, maybe the value becomes 128, right? Now, if you look at this, any image that we have, right? Any two-dimensional image that we have, right? Will at the end of the day be comprised of all of these pixels that I'm talking about, right? That is why if you see your HD images will have high number of pixels, maybe 5,000 cross 5,000, maybe 10K cross 10K, right? So all of this is nothing but pixels that we are talking about. But at the end of the day, every digital image that we have right, is an image which is basically a numerical data, right? Your image is nothing but your pixel intensities that are varying for the different pixels that you will have in that particular image, right? So if I go ahead and I tell you that this image, right, this image that we see over here is an image with 64 cross 64 pixels, right? What will you understand? It means that there are 64 cross 64 pixels in this image, right? 64 into 64 pixels, and each and every pixel will have a specific value. Is that correct? Right? Now, let's assume that I start writing something, right? Let's say I go ahead and write the digit 7 over here, right? If I go ahead and if I write the digit 7, now what will happen? All these pixels, right? All the ones that are colored in black, will they have a similar pixel value? All these, the the pixel value will be same, right? Exactly the same, right? And all the ones which are, let's say, not black, so let's say that the background is white. Now, if the background is white, so all the rest of the pixels will have the same value. It might be, let's say, 0, correct? Now, similarly, if I take the 7 away and let's say I go ahead and then I write an 8. If I write an 8, what will happen? This time, do you think that the pixels which have black value will be different as compared to the ones which have which we had for 7, or will they be the same? Maybe some of them will be common. So if I write both a 7 and an 8, maybe some pixels will be common, right? So these pixels will be common, these will be common, these will be common. But if you see, for majority of 7 and 8, the pixels are different, correct? Now, if you see, right, if I go ahead and if I convert this two-dimensional data into a one-dimensional matrix, right? So let's say this two-dimensional data, I go ahead and I convert this into a one-dimensional array, right? So let's say this is the data. This is the data for 8, let's assume. So for 8, it might happen that my pixels are varying like this, right? So let's say first every pixel is 0, then let's say this is, I'm just giving a value of 0 and 1, right, to make it simple. So let's say this is then once again 0, then 1 1 1, right, something like this, right? So let's say for 8 this is what I get, but if I do the same thing for 7, maybe I get a different pattern, right? Maybe for 7 I get, mostly starting will be zeros because it will be blank, let's say, then this, right? Does this make sense, guys? Do you think this will happen? The pattern will be different, right? Now, for most of the sevens, the pattern will be very similar, and for most of the eights, the pattern will be very similar. Is everyone able to understand? Now, see, this is the idea on which we actually try to work when we are working with images, right? Now, if I go ahead and if I give the label over here for this as 8 and for this as 7, do you think my mathematical models will be able to identify this pattern easily? See, if for every 8, the pattern is almost similar, if for every 7, the pattern is almost similar, your model should be able to find this out, right? Is everyone able to understand this? Any questions? All right. So if you see this now, if I show you this data, right? So what we'll do is that we'll first read this data. Now this mnist.load data, you can go ahead and you can look at the definition as well. If you just press a control and click on this, right, you can go to the definition. This will only happen in Google Colab, right? This will not happen in your Jupyter notebooks and all. So you can see that this is the load data function, right? And here, if you see, this load data is actually returning 4 data frames: X train, Y train, X test, and Y test. I'm using Mac, Prageet. So for me, it is Control plus click. You can try this on your system as well, right? If you just go and I think if you press Control and click on the function, it should open the definition, right? So if you see, this function is returning 4 data frames. So what I'm doing is that I am actually collecting, when I call this function, I'm collecting the values in 4 data frames in an exactly similar manner, right? And when I collect this, so let's start from the start, right? I will run this. Now this, what you're seeing is that my data that I have, it has 28 rows and 28 columns. The image data that I have, right? It is 28 cross 28 pixels. The total number of classes that I have in this data is 10. That is the total number of digits are 0 to 9, which will be 10. Batch size and epochs you can leave for now, right? This is for the model only, but we have declared it over here. Then I have called this function, this data summary. In this function, I'm just passing all of my data, and this function is doing is that it is printing the shape of your train and test. It is printing the labels that your train data has, right? And now if I call this, right, if you see, I am saving this data to X train, X test, and Y test, and then I call the data summary function. Now you can see that this is how the data is splitted. Your training data contains 60,000 images and your testing data contains 10,000 images. The shape of the training data you can see is 60,000 cross 28 cross 28. Why? Because there are 60,000 images. Each image has the size of 28 cross 28 pixel. Right? Your labels, that is your target variable, will have only 6,000 values because these are digits in the range of 0 to 9, right? Similarly, my testing data has 10,000 samples and my testing label has 10,000, right? And the train and test labels, you can see that these are actually digits that the images correspond to. So my first training data, right, is the image 5. My second training data is the image 0. This is only digit images, right, Kronal? This MNIST data is only for digits. All right. Now, as next step, let's try to plot this data and let's try to first of all plot and see whether the images, whatever we are getting is correct or not, right? So what I'll do is that I'm defining a variable which will just take the index of which image I want to print, right? So I take a Y train of that particular index, right? So if I do Y train 0, so Y train 0 should come out to be what? Can you guys tell me? You can see the output over here. Right? If you look at Y train 0, it is 5, right? That's what we are seeing over here, right? Exactly, very good. So then what I'm doing is that I'm just plotting this. So X train sample. Now see, if I do an X train of 0, right? It will select the first image, right? And for the first image, you can see that it will give you the 28 cross 28 pixels that we have, right? So like this, visualizing this will be a problem. So what we'll do is that we just go ahead and call the function imshow. plt.imshow in matplotlib, imshow is a function which will plot any image, and I'm passing this image, right? If you see, I'm passing the pixel intensities for this, right? And I give the color map as gray. I want a grayscale output. And you can see that this gives the image 5 and the train label is also 5. So we are checking two things, what the image is over here and then what my label contains. Now like this, you can check this for possibly any image that we have in our data, right? If you see, this is 1 and this is also 1. Now this is because this is a 28 cross 28 pixel image, so this is highly pixelated, but still I think this will do the job, right? You can try out for any value and your label should be correct. All right. So this ensures, this just tells us that our data looks good and the labels are also created in a correct way, right? You can go ahead and you can check it for any number of, you can just check this for different values that we have, right? right? And the target variable is the number that is present in the image. All right. Now we know the shape of the data. My training data is 28 cross 28, right? If you look at now, if you see all of this, right? So obviously my data is 28 cross 28. I need to standardize my data, right? I need to standardize the data before I even pass it to the neural network model. Now, the good part with image data is that you don't need to do any fancy standard scalar, min-max scalar and all. What we need to do is that we need to divide the input by the number 255. Because my pixel values are in the range of 0 to 255, what will happen is that if I divide this by 255, automatically my data will come in the range of 0 to 1. Does that make sense? Yes, Indu. So when we are giving 4000, it means that we are giving the index as 4000. And for the 4000 index, 7 is the label, the target variable value, and that is what we are seeing in the image as well. Right? So for standardizing our data, all we need to do is that we need to convert that into float and divide this by 255, right? And if you can see that I have done that for both training and testing over here, right? All right. Now, as next steps, do you think that we can go ahead and now, if you look at the target data, this is how our target variable looks like. Can I go and can I pass ahead these values to my model? Now this is okay. First of all, is this a regression problem? Is this a classification problem that we are trying to solve? Is this binary classification or multi-classification? Multi. So now my target variable as of now, if you see, right, my target variable looks like this. My target variable is a single column, which let's say if my first value is 5, it will be 5, then it will be 0. Let's say it is 0, then 3, maybe 4, maybe 3, maybe 2, maybe 7, maybe 8, right? Now, can I pass this to my model as it is? What do I need to do? See, if I pass this as it is, my model does not know that it is a classification problem, right? It will consider all of these classes as continuous values, right? So I time that you guys are working on a multi-class problem. So let me explain this. Now see, a multi-classification problem is nothing but you will have to create as many binary variables as the number of unique classes that you have, right? So I'll give you some example, right? So let's say if this is the data, I will have to convert this data from this form to this form. What is this form? This form is nothing but, so let's say this is 0, right? This is 1, this is 2, this is 3, this is 4, right? This is 5, and so on and so forth till 9, right? Let's say this looks like this, like one hot encoding exactly, right? So for the first row, what will happen is, for the first row, this will become 1, correct? And all the rest will become 0, right? For the second row, this will become 1, all the rest will become 0. For the third row, this will become 1 and all the rest will become 0. Does this make sense to everyone? This will become 1, all the rest will become 0. Right? I cannot pass my target variable like this. I need to do one hot encoding of the target variable. Only then will I be able to create a multi-class model, right? So that's what we do as next steps in order to prepare the data, right? If you see, this is how my Y-train looked like. Now, the two categorical function that I had called before, if you remember, I'm calling that function. I'm passing my Y-train and I'm passing the number of classes that this variable has. This I have already defined as 10 because I have 10 classes 0 to 9. If I do this and then I call Y-train 0. Now, if you see Y-train 0 was what? It was 5. And this 5 is present at the 6th index over here, right? 0, 1, 2, 3, 4, 5, right? So basically, if you see this 5 is actually present at the 5th index, it is starting from 1 over here only. So hence it goes and it gets mapped to the 5th index, right? Now, if you look at the second value, the second will be 0. So if you see, the first value has become 1 and all of the rest have become 0. No, so this is not scaling. If you see, we are reshaping our data. Our data was originally of the size 28 cross 28, right? But I cannot pass two-dimensional data to any mathematical model, right? All the mathematical models that we have, right, they can only work on one-dimensional data. Right? Yes. So we are converting that 2D data to 1D. So if my 2D data had 28 cross 28, right? It had 28 rows and 28 columns, right? I am converting this into what? What is 28 cross 28? 724, something like that, right? Let's assume it's 724. I don't remember. So it will have 724 columns, right? For each row, 784. Right? So this will have 784 columns for each row, right? So what I've done over here is that first I have actually reshaped my data. The reshape function, what it does is that if I show you this, if you see, it has now gone ahead and it has converted your data to 784. Now, earlier, my data, which looked like 60,000 cross 28 cross 28, which was three-dimensional, now it has become 60,000 rows and only one, just one, just your 784 columns, right? So now my image has been converted from 2D format to a single dimensional format. And then after that, we have gone ahead and we have standardized it by dividing by 255. Why 255? Because I have my pixel intensities are varying between 0 to 255. Automatically, if I divide this by 255, my values will come in the range of 0 to 1. Right? Now, if I call the data summary function on the transform data, you will realize that all of this has changed. Train image earlier was 60,000 cross 28 cross 28, and now it has become 60,000 cross 784. My train labels was 60,000 only. Now it has been converted to 60,000 cross 10, right? So this is a sequential model which we create. In this model, we add a dense layer of 512 neurons, right? Activation becomes ReLU. Input shape of the data, that is the input neurons, will be how many? If you remember, I have 784 rows, right? I have 784 columns. And this number of rows and number of columns we had defined during the starting of the code. These variables had the same values, right? Num rows is also 28, num columns is also 28. Right? Hence, if you see, there will be 784 neurons in the input layer. Now, if there are 784 neurons in the input layer, then a general logic of defining the hidden layers, right? Now, generally, let's say 784 neurons, so you should have at least half neurons in the input layer, because you can expect interactions from each and every neuron. You can expect uh, interactions being created between the different pixels and all, right? So generally, the neurons of the input layer will not exceed the number of features that you have, right? So if in this case, if you see, the number of features that I have are 784, so the next best alternative for me is to go ahead and maybe define neurons which are somewhere around half the number of features that we have, right? This is just a basic understanding that this is how we do things. It might also happen that these 512 neurons might be too much for you, right? It might happen that you need, at the end of the day, you need only 100 neurons in the input layer. But just to get started, just to see how our neural network will perform with, let's say, a basic number, we go ahead and we do that, right? So you can see over here that I have instantiated the first hidden layer with 512 neurons. Activation becomes ReLU, and I need to give the input shape. Why? Because this is the first hidden layer. So we will have to define how many inputs or how many features are coming from the previous layer, right? So that is why, if you see, we have done this. Now, after that, I'm also adding a dropout of 0.5, right? So when I'm adding a dropout of 0.5, so it says that 50% you go ahead and you randomly deactivate 50% of the neurons, right? Now, can you guys tell me why I went ahead with 512, why not with 500, why not with 400? Why I have specifically gone with this number, 512 to 56? What do you think? Power of 2, right? So as I said, binary calculations happen inside the Python tool, right? So if you are giving neurons which are 2 to the power something, then the computations will be slightly faster, right? And so basically you will be using all the processing power that you have, and you will not be giving any processing power away for free, right? So that's why, if you see, we are using 512 over here. Then we added dropout of 0.5. We add one more hidden layer, this time 256, and we add a dropout of 0.25. And finally, we add the output layer, which has 10 neurons, and activation function becomes softmax. If you remember, softmax was the activation function for multi-class problems, right? What did softmax do? Softmax actually converted whatever input came to this function, it will convert them into probabilities, right? So if I have 10 neurons, I will be getting 10 probabilities associated with each and every neuron, right? So we go ahead and we run this, and this will define our model architecture. Addition of all probability would be 1. Yes, Pooja. This is something that we'll see as well. So that's the objective over here, that all the probabilities, the summation of all the probabilities should come to 1, and that is something that softmax function will enable us to do. All right. Now, if we go ahead and if we look at the model summary, now the next part was what? We need to compile our model, right? So for compiling the model, I'll do a model.compile. I'm passing the optimizer as Adam. If you remember, Adam was the adaptive gradient descent, right? Which will adapt the learning rate and all, right? Loss I am giving as categorical cross and entropy. Why? Because this is a categorical, or this is a classification problem. If this would have been a regression problem, my loss function could have been RMSE, MAE, whatever, right? And the metrics that the model will populate while training itself is accuracy, right? So I go ahead and I compile the model with these parameters. This is not required. Let's leave it. And then we move on to the model dot training. Model dot fit. We fit this model, right, with the data. Now we have added the different layers. That is, we have defined the architecture of the model. We have compiled the model, that is, we have told the model that the optimizer will be this, the loss function will be this, the metrics will be this, right? And now we move on to the part wherein we will pass the data to the model, right? Now I do a model.fit, pass my X-train and Y-train. Along with that, I'm passing my batch size. Batch size, if you remember, we had defined earlier at the start only, right? We have defined a batch size of 128, right? Once again, if you see over here, we have taken a batch size of 128, that is 2 to the power, right? So generally, whenever you are passing any parameters to these neural networks, you try to pass these parameters as power of 2 values, right? Epochs, I have given the epochs as 20. and callbacks, right? Now, callbacks is a hyperparameter, which basically, if there are any callback functions, let's say, once when one epoch training will be complete, right? Are there any functions or are there any things that you want to print, right? Now, I want to call this plot losses function. If you remember, we had installed this live loss plot function, right? At the start we had called this particular function plot losses, right? If you remember, if I go up, right, this is the live loss plot which we had instantiated. And if you see plot losses, live loss plot dot plot losses Keras, this is the function that we had already called, right? But till now we have not used this function anywhere. So now in the callbacks part, so generally whenever you want to have any function print the status of what training is happening, what is the training accuracy, what is the testing accuracy and all, you are going to do that in the callbacks, right? Now, verbose equals to 1. Verbose is a variable which varies between 0, 1 and 2. 0 means that the model will not print any status while it trains itself, right? The window that you're seeing over here will be totally clean, right? This part. If I make it as 1, the model will print minimal details about what is happening during the process of training. If I make verbose equals to 2, this will print details of each and every epoch, right? That for this epoch, the accuracy was this, training accuracy was this, testing accuracy was this, and so on and so forth, right? And then I'm passing the validation data. Validation data is basically, once when you have trained this model, then what is the data that we need to give to this model in order to calculate the testing accuracy or validation accuracy, right? So that is X test and Y test. So if you see, these are the parameters that we are passing in model.fit, right? In the loss function is defined over here, categorical, cross, and entropy, right? Live loss plot is a function which will plot the losses of your training and testing data when the model is actually training itself, right? Tanushree, I'll explain verbose through an example if that is not clear. All right, let's just leave this parameter out. I'll just show this to you when I run the model, how it changes things, right? And let's take this away. All right. Now, if you see, when I have run this code, right, I'm going to run this code once again, but just to explain to you what verbose does, right? If you see over here, when this code had run previously, I was getting this as the final output, that I am just getting the model's accuracy after the last epoch is completed. If you see, after the last epoch is completed, the loss that the model is seeing is 0.0372. The accuracy on training data that the model is seeing is 98.77%. The accuracy on testing data the model is seeing is 98.5. Now, this particular line that is coming, right, this is coming because I have given my verbose equals to 1. Now, when I'm going to rerun this, I will make the verbose equals to 2 and you will see what the difference will be, right? So I will just copy this code, right? And let me rerun this. And I will explain this graph as well to you in that case, right? So let's rerun this. I will make the verbose equals to 2 now. And let's rerun this and see what happens. Now, if you see, this is the first epoch that is being run right now. Once when the first epoch will be completed, the callback function, okay, so this will be an issue. Just 1 second. We need to clear the weights. Okay. Okay, so I guess you guys remember this, right? Now this is with verbose equals to 1. Now what I'll do is that I'll rerun the entire notebook with verbose equals to 2. Why do I need to rerun the entire notebook? I will tell this to you in some time. Generally, what happens is that if I rerun the same model, the deep learning model, without restarting the session, what will happen is that the previous weights that the model would have trained on, it will start with those weights only. It will not start with a random set of weights. Now, if you see, I have done verbose equals to 2. For my first epoch, when my first epoch is completed, right, it will plot the accuracy of your training data and your testing data over here in this particular, in these two frames, right? If you see accuracy and loss, it will plot the, now if you see, 2 epochs are completed. For the first epoch, right, for the 0th epoch, my accuracy was around 88%, right? For my 0th epoch, that is the first epoch, my loss was at somewhere around 0.12. But once when the epoch changed from 0 to 1, you can see that the accuracy has increased from 88% to somewhere around 95%, right? If you see, this is constantly updating itself. As and when the number of epochs are changing, this graph is actually updating itself. And you can see that the accuracy, overall accuracy of the model as and when the epoch is increasing, is actually going up. And you can see that the loss as and when the epochs are increasing is actually going down, right? Now this will keep on updating itself till the 20 epochs are completed. And along with that, just one second, let this complete. Right? I hope this is clear to everyone. Any questions on this? How these graphs are getting populated? So this is what the live loss plot function is doing, right? If you see, this is plotting the, and you can see that the model performance. Now, if you see both the training accuracy and the testing accuracy, right, actually stabilized at epoch number 9. Now at epoch number 10, my validation accuracy increased. At epoch number 11, my validation accuracy and my training accuracy actually came back to be in the same range, right? And similarly, you can see for the loss function as well, right? So let's see once when this is completed. So Krunal, all of these questions, what happens when the epoch is increased to 100 and all, I want you to test, right? You will be having this notebook and go ahead and test this. If you give a reasonably high number of epochs, right, then obviously this is something that I have talked about previously as well. Guys, can you tell me what will happen if I give an extremely high number of epochs? Overfitting will happen, right? Exactly. So if you give more number of epochs than it is needed, the model will start to overfit. When the model will start to overfit, you will realize that the validation accuracy starts to go down. And I think you should have realized that by now. Can you guys see that the model has started to overfit beyond the 12th epoch? The validation accuracy has stabilized, whereas the training accuracy is kind of still going up. Can you see that? Right? Now, if you see, the training is done, okay, and this is what the output is coming out to be. Now, what do you guys think? Is 20 epochs a good enough number for us, or should we change it? We can reduce, right? So if you see somewhere over here, which is somewhere around 12, right? The model's training accuracy and the testing accuracy both were very similar, right? And you can see over here as well, or I think even we can go at 10, because you can see that till 10, the loss of both your training data and your testing data were actually very similar. After that, the loss has remained the same, right? At 12, I can say that the loss has bettered slightly for the training, for the testing data. Now, this can be your call. Do you want to stop at 10? Do you want to stop at 12? You can go ahead and you can take a call there, right? So let's go ahead and let's run this for 10 epochs. I hope that's fine. And this time I will make the verbose as 0. Let's go ahead and let's run all. Let's see what happens then. So now you can see that the training will start once again with 10 epochs. Now the data will be passed to the model only 10 times, because we have seen that 20 epochs was actually resulting in overfitting. Overfitting was not of a very high order, but still I could see that the training accuracy and the testing accuracy were kind of different, right? So we'll go ahead and we'll try to see if we can get a model which gives us similar performances both on training and testing data, right? So let this run. In the meanwhile, if you have any questions, you can ask those now. And now you can see that as soon as I made the verbose equals to 0, right, it is not printing out the accuracies of the model, right? It is not printing out anything. This accuracy and loss that you're getting, this we are getting from the live loss function. This we are not getting from the model.fit, right? For the model.fit, if you want to look at the accuracies, right, we need to give verbose equals to 1 if you want to look at the accuracy of each and every epoch. If you want to look at the accuracy of only the last epoch, then you need to give the verbose equals to 2. Right? You can go ahead and you can play around with all of these parameters. Emmanuel, so verbose equals to 0, it will not print any accuracy. You remember there was a line over here which was giving us the loss on training data, accuracy on training data, loss on testing, accuracy on testing, right? So if I make verbose equals to 0, nothing will be printed that you are seeing over here right now. If I make verbose equals to 1, right, then only the accuracies of the last epoch will be printed. Whatever is happening in the middle epochs, it will not be printed. So it is kind of a selective print mechanism. If I make verbose equals to 2, then it will print all the accuracies of all the epochs one by one, right? Go ahead and play around with this parameter and you should be able to see how it works, right? It's not a very important parameter, but still you can go ahead and you can do that. Only 3 options for epoxy, Satish, right? So if you see now, my accuracies are quite similar and you can see that till this point as well, right? Your loss is also very similar, right? So I hope that this is good to everyone. All right, so let's look at the performance of this model, right? So what I'll do is that I will call an evaluate function. Now my model training is done. If I want to evaluate the model performance, I can call this function evaluate, and I'm passing the testing data over here. When I pass the testing data to this model, you can see that the accuracy on testing data that I'm getting is 98.36 and the loss is 0.05. Right? Means that this model is doing a good job. What do you guys think? Right now, let's go ahead and let's get the predictions on testing data. I will go ahead and I will get the predictions and then we will compare these predictions with the actual data just to see what the outputs are coming out to be, right? Now, I use the model.predict function and I pass my testing data, that is X test, to the model, right? And I save the predictions, which is a list, in a array format, right? Now, if I show you this predictions, right, this will contain all the 10,000 data points for our test data, right? It will get the predictions for all the 10,000 data points. Now let's look at what the prediction is coming for our first testing data point, right? Now our first testing data point, the prediction is coming out to be this. Are you guys able to understand what these predictions are? What this means? Right? So if you see, what I've done is that I have printed the image of the first testing data, right? If you see, this is Y test, this is X test, and the index that I'm passing is 7. So the first test image is of the number 7. And if you see over here, this is the output that we are getting. How will we get the probabilities? Now, if you see this, the first probability is the output for digit number 0, right? Second is for digit number 1, 2, 3, 4, 5, 6, 7. Now, if you look at 7, what do you see? The probability is 9.9 into 10 to the power minus 1, which will become what? Which will become 0.99. And if you see for all the others, the probabilities are a very small value, right? 10 to the power minus 11, 10 to the power minus 9, 10 to the power minus 8, right? So what you can see over here is that for the index 7, right, this model is giving you an output probability of 9.99, right? And that is something that you can see in the y-test data as well, right? So this is the y-test data, and you can see that the actual value was 7. Now, if you go ahead and if you change this to, let's say, some other value, let's change this to index number 10. Index number 10 is the digit 0. Let's see what the predictions are coming for index number 10, right? Can you see that for the 0th index, it is giving us a probability of 9.99 once again, right? So the model is doing an excellent job. You can go ahead and you can test this for all the different values, right? And your model will be, because it is giving you an accuracy of 98.4 something. So obviously there will be very less mispredictions that this model is doing. So the new image will be 28 cross 28. You cannot make predictions of images which have greater or lesser pixels than 28 cross 28. Why? Because my model expects 784 pixel values, right? So if your input image is 28 cross 28, then you will have to convert that to a one-dimensional form, right? You will have to convert that to a one-dimensional array. It should have 784 features. If it has 784 features, all you will do is that you will go ahead and you will call this predict function on that particular value. Let's say X test or whatever your image is, you save the one-dimensional form of the image to the data frame X test. You will go ahead and you will pass this, and once when you pass this, you will get the predicted probabilities, right, from the model. Okay. The 10th image in the testing data is the image of a 0. When it is the image of a 0, if I get the predictions, you can see that for the 0th index, I am getting the probability as 9.99. This 10 is not telling you the probability number, right? This is just the index of the digit. I can make this as 100. 100 means that this is the 100 sample. This is what? This is a 6, right? Now, if I go ahead and if I look the predictions for the 6th, for the 100th image, you can go ahead and you can see that this is giving you 9.99 for the 6th index. You can count 0, 1, 2, 3, 4, 5, 6, right? And you can see that even though the 6 is slightly tilted, right, slightly twisted, right, still it is able to identify that this is a 6. All right, so now if you see, I am importing pandas, NumPy, I am importing TensorFlow, importing Keras. From Keras, I have imported model. From Keras.layers, I have imported all the layers. If I do import star, it will import all the layers that Keras has. I have imported optimizers and I have imported two categorical, right? These are the libraries that we have imported, right? Now, if you see what I am doing is that I have already saved this data, right? Train.csv and test.csv in this folder. If you see this data set for in-class demo, train CSV and test.csv, and this is the one-dimensional data of the same images that we had converted, right? So this will not open here. Let's see this over here, right? Now, if you see, I have two data frames, the train and the test, df train and df test. If you look at df train is nothing but you have 784 pixel values. If you see from pixel 0 till pixel 783. So I have the 784 pixel intensities, and then I have the label that is what image or what number this particular image was of, right? So if you see, the first image is of the number 0. The second image is of the number, the first image is of the number 1, second is of number 0, third is of 1, fourth is of 4, right? Fifth is of 0, and so on and so forth. So all the transformations that we were doing over here, right, that is not required to do. We are already reading in a data which is converted into one-dimensional format. It has 784 features and it has one target variable, that is the digit number, right? I hope this is clear to everyone. Any questions on this? All right. So if you see, I have read the training data and I have read the testing data. Now our shape of the data have changed. My testing data is 28,000, right? And my training data is, I think, 4,200. right? In total, I have the exact same 7,000 samples, but now we have increased the testing data size to 28,000 and the training data remains 42,000, right? If you see over here, it has 42,000 rows. 42,000 plus 28,000 is 70,000. And for the previous example as well, we had 70,000 rows. In that example, we had 60,000 in training and 10,000 in testing, right? What do we need to do next? Can we go ahead and can we visualize this data, image data, in the same form that it is? So in this form, we cannot go ahead and we cannot visualize this data, right? This is one dimensional. So either you will have to convert this into 2 dimensions, or you cannot go ahead and you cannot visualize this data, right? But we have already visualized this in the previous case studies. So we are not doing that. We will directly move on to the steps wherein we are selecting the task variable features and all, right? So if you see, I do df features. What are my features in this data? If I select the first index till the last index, that will become my features. So I'm doing a df train.ilog and I'm selecting from the first index till the 785th index. 0th index is my label, so I'm ignoring that. For my df label, I'm only selecting the 0th label, right? Similarly, for my X test, what I do is that I select the labels from 0 to 784, right? My test data, the df test data, right? It does not have the target variable because this is my test data. It only has the features, right? Yes, Indu, we have already converted the data in a one-dimensional format. Right now, if you see for your test data, we have only 784 columns. That is, I do not have the labels for my test data. And this is how things will work in the real world, right? In the real world, the data on which you are going to test the model on, or let's say real world data, will only contain the features. It will not contain the labels, right? That is what your model is going to give to you. Once when the model makes predictions, it is going to give you the same, give you what number that particular image belongs to, right? So let's go forward then. Now this is our df features and df label is my training data. X test is my testing data, right? And what we do is that for the training data, whatever training data we had, right? For that as well, because we will be building the model, we are assigning 20% of the rows to testing size, right? To the testing data. If you see, for the df features which contains 42,000 rows, I'm going ahead and I'm dividing this further into 20% test data, because while building the model, I need some amount of testing data to cross validate, to see if how my model is performing on new data, right? Training accuracy, testing accuracy and all. Right. So now if you see, if I split this using 20%, basically 20% goes to testing, 80% goes to training. Now I end up with 33,600 rows for my training data and 8,400 rows for my testing data. Okay, so now I am just converting this to NumPy arrays. Why NumPy arrays? Because generally your data frames take more memory, right? And your Keras models actually work with both. They can work with data frames, they can work with NumPy arrays as well. Generally, when you will be working with real world data, you will be converting any data into a NumPy based format because it occupies significantly lesser memory and space as compared to your pandas data frame, right? So if you see, what I'm doing is that I'm just converting this to NumPy. And just to be sure that all my data has 784 features, right? I'm just reshaping this to 33,600 and 784. Although I can see the shape from here that the shape is same, just to be sure, right? Why do we do this? We do this because sometimes you create automated pipelines. When you create automated pipelines, right, there might be certain data transformation steps which might mess up the shape of the data, right? So finally, before going into the model, we just go ahead and this is just kind of a precautionary measure. We go ahead and we apply the reshape, and we say that, okay, because I need 784 features, I will go ahead and I will do this, right? So if you see, I am just manually, explicitly, I'm going ahead and I'm reshaping this data to this so that it has 784 columns, right? I do this to both my training data, my cross validation data, and my testing data, right? And after this as well, if you see, the shape remains the same, right? The shape of your train CVX test remains the same. So this is just a precautionary measure that we have done, right? Now we need to standardize. Now, if you want to standardize, you can see that if I take any data sample, if I take the minimum value, maximum value, it will always be in the range of 0 to 255. If it is in the range of 0 to 255, all we need to do is that we just need to divide the data by 255. So I convert all the three data that we have to float, because if I'm dividing by 255, I want values in the range of 0 to 1, right? I want float values as well, 0 0.1, 0 0.3, whatever. So then I go ahead and I divide all the three data, training, cross-validation, and testing by 255, right? And then finally, the number digits equals to 10. And if you remember, two categorical, my label over here was also a single column. I had to convert that to 10 categorical variables. So we go ahead and we do that as well, right? And you can see that now your cross validation target variable, your Y train, right? All of them will have 10 columns, each column representing one single digit. Indu, that's what I was saying, right? That our testing data only contains the features. If you look at the testing data, it does not contain the target variable in this case. If you see, this is starting from pixel 0 and going till pixel 783. So you don't have any target labels for the testing data. That is why we are going ahead and we are dividing our training data into our training data of 42,000 rows is further divided into 20% validation data, and the remaining 80% becomes the training data. All right, so everything is done now. Now this is how my data looks like. If you look at this, Y train 0, Y train 3. Now each and every image has been converted. The target variable for each and every image has been converted to a categorical form, right? Now we will go ahead and we will get started with the modeling. Now this time we are doing a functional model, right? We are not doing a sequential model. So I'm defining all the different parameters beforehand. That is the number of input neurons, the number of neurons in hidden layer 1, hidden layer 2, 3, and 4, and the number of digit, that is the number of neurons that will be there in the output layer, right? So I'm just defining these over here, and then let's proceed to this, and let's see how the syntax is different over here. Just go through this code and see if you feel that the syntax is different. Do you think that the syntax is different from the previous model that we have built using the sequential approach, or do you think that it is the same? Now, if you see, this is the array. If you look at, let's say, x train 0, so that is one image, right? X train 0 will be the features for one particular image, and you can see that these are the 784 pixel intensities, right? The values which were 0, obviously it remained 0. And the values which were, let's say, which had some pixel intensities have been converted to a numeric format, right? Now, if you go ahead and if you change this to, let's say, for the first index, some other pixels will have some values, right? So you can see that there are patterns that are already existing in the data. Okay. All right. So Prageet, that's what I'm saying, right? Now, this is a functional API. This is not the sequential API. It will be different, right? So now let's try to understand how we are defining the model over here. In case of functional API, the syntax will change slightly. I will first have to define how many inputs are there or how many neurons are there in my input layer, right? If you remember in the sequential API, we were just passing the number of neurons while we were defining the hidden layer number one. Over here, we don't need to do that. Over here, we need to explicitly define how many neurons will be there in the input layer, right? So you can see over here that I call the input function, right? And I pass the shape of my input layer, that is my input layer will have 784 features, hence it will have 784 neurons, right? Now, when I move on to the second layer, right, I do an x equals to, that is x equals to basically gives you the architecture of the model till that particular point, right? I define a dense layer, the number of neurons I define. Now, if you see, this syntax remains the same, right? This syntax till here remains the same. I am defining a dense layer. I am passing or I am creating 300 neurons. Activation is ReLU. Name of the layer is hidden layer number one, right? We need to give the name of the layer as well over here. Why? I will tell you this. Now, if you look at this, over here, what I'm doing is that I'm explicitly telling that this hidden layer number one, right, will be connected to the previous layer, which is the input layer. When I do this, right, when I give this layer in brackets, this tells the Keras functional model that this hidden layer will be connected with this input layer, which is already defined. So that is input will be connected to hidden layer number one. Yes, Aniket, you can give that as well. Not zero, it will be xtrain.shape one, right? Because 0 will give you the number of rows. If you see, this will give you the number of rows. So you will have to give 1, which will give you 784. Okay. Now let's move on to the second hidden layer. Now for the second hidden layer, the same syntax goes. I just change the number of neurons to 100. Activation becomes ReLU, name becomes hidden layer number 2. And now I connect this to the previous iteration of X. What was the previous iteration of X? The previous iteration was this dense layer, this hidden layer, which was connected to the input layer of 784. Now, if you see, the sequence will keep on going. Now, this input layer is connected over here to the hidden layer number 1. This hidden layer number 1 is connected over here to hidden layer number 2. This hidden layer number 2 is connected to this hidden layer number 3. Hidden layer number 3 is connected to hidden layer number 4. This hidden layer number 4 is connected to the output layer, right? If you see, this is how I am making the connections. Now, because this was a sequential model, my connections are also sequential. But let's assume that you wanted to connect a particular layer to the output layer. You can just go ahead and you can directly give that, okay, let's say this layer was Y. So you can go ahead and you can say that this output layer will be connected with X comma Y, right? So as soon as you give X comma Y, this will have two connections. But right now we are not studying about functional models. We are working with sequential models only, but I'm giving you an example of these sequential models using the functional API, right? So if you see, I define all the hidden layers. I keep on connecting the hidden layers with the previous architecture of the model. Finally, I define my output layer, which is dense. Number of digits is 10. That is, number of neurons are 10. Activation becomes softmax. Name becomes output layer, and it gets connected to the last iteration of X, which is already connected to all the previous hidden layers in the input layer, right? Then we move on to the model creation. Over here, we will have to call the model. Now, in Keras, we were calling the sequential model. Here, we just need to call model because model by default will be functional. To the model, I'm passing the first layer of the model and the last layer. When I pass input layer, the model knows that 784 neurons. When I pass the output layer, my output layer has all the previous connections till the input layer. So the model will be able to go ahead and will be able to identify all the connections automatically. And you can see if I print the summary now, it has 2,97,910 parameters, hyperparameters, right? All right, so two people are saying break, others are saying let's complete. So let's complete this then, I think, or all right. I think let's go for a break, guys, because this still has some element. So let's go for a break, and then when we are back, we will resume with this. Okay. Now, one thing that we need to see over here is that if we have, see, if our image is black and white, right? If let's say our image will be black and white, then it will be a single matrix, right? It will be a single matrix which will be consisting the pixel intensities, right? But if your image is colored, right? As soon as we start dealing with colored images, what happens is that, let's say this is one set of pixel values. On top of this, there will be another set of pixel values, and on top of this, there will be another set of pixel values. So three matrices of the exact same size will be overlapping each other, right? Now, each of these matrices will be belonging to different color palettes, right? So if you look at this over here, so let's say this becomes red, this becomes green, right? And this becomes blue. Now, if you would have done basic art and painting back in school, right, you would know that these three colors, red, green, blue, if we combine these colors in varying intensities, we can make all the colors of the spectrum, right? Whatever colors you want to make, right? Whatever possible colors you want to get as an output. Now, let's say you want to make a color which is a combination of red and blue. Then the pixel intensity for green matrix will become 0, and the pixel intensities for red and blue will be set to the appropriate value. Now, whenever you look at any colored images on your computer, on your laptop, on your mobile, right? That is, all those images will be a combination of three frames which are actually stacked on top of each other. Whenever you see a black and white image, that will be a single frame. All right. So if you see, depending on the resolution and the size of the image, it will see a 32 cross 32 cross 3 array of numbers, right? Now, if you see, 3 refers to the RGB values. Now, 32 cross 32 is one single matrix, right? If I multiply this by 3, it means that you have 3 matrices which are stacked on top of each other, right? Each of these number is given a value from 0 to 255, which describes the pixel intensity. These numbers are the only inputs available to the computer. So any digital images that you are seeing, right? Any digital output that you are seeing is a combination of these different pixel intensities, right? So this is just an example, right? This is not the actual pixel intensities that have been created. This is just an example. That is why you don't see too much variation. Mosmi 32 varies. What do you mean by that? That this 32 can change, right? So this is the image size, right? Now your image, depending upon the pixels, can be anything. It can be 64 cross 64. It can be 512 cross 512, right? 4084 cross 4084, anything. All right. So now let's try to understand what were the problems of our artificial neural network. If let's assume we went ahead and we used an artificial neural network for image processing, right? For image related problems. All right. Now let's assume that I have an image which contains 28 cross 28 cross 3 pixels, right? Now this is a colored image which contains three matrices which are stacked on top of each other. Now, can you tell me how many input features will be going, or how many features will be going in the input layer once when I convert this into a one-dimensional format? Can you guys tell me how many features will go into the model? So if I have an image of 28 cross 28 cross 3, right? My question is that how many pixels or how many features will be creating the first or creating the input layer of the model, of the artificial neural network model? Answer is given 2352, right? Because if you remember, we were converting our data to one-dimensional format, right? So this data as well, once when we'll convert this into one dimensions. So see, let's try to understand how this will happen. Now this 28 cross 28 cross 3, I hope all of you can understand that this is, let's say, one matrix, second matrix, and the third matrix, right? So let me just a normal one. So let's say this is one, this is another, and this is another, right? I hope this is clear to everyone. Let's assume this is for red, this is for green, and this is for blue, right? Let's assume this is the case. Now, these three matrices individually, obviously you can go ahead and you can convert them into one-dimensional arrays, right? So let's assume the one-dimensional arrays that we get from here start looking like this, right? Let's say this is for this one, red, this is for green, and this is for blue, correct? Now, if I go ahead and if I combine these three, I will finally get a one-dimensional array, which will be a combination of all three, and which will be a big array. Now, this, if this was 28 cross 28 cross 3, my original image, right? This will be how much? This will be 2352, right? Correct? I hope this is clear to everyone. All right. Now, if let's assume, so see, if let's assume in my hidden layer number 1, right, I have 32 neurons. Can you tell me how many weights will be there from input layer to hidden layer number 1? This is my input layer. Let's assume that from here, I have a hidden layer, right? Let's assume after this, I start building my neural network and I have my first hidden layer, right? Let's assume that my first hidden layer has 32 neurons, right? How many connections will be there from this input layer to this hidden layer number 1? Right? Exactly. Very good, Kumar, Indu, Pooja. So 2352 into 32, right? My input neurons were 2352. My hidden layer neurons were 32. So you can imagine that only in the first level of hidden layer, I have so many hyperparameters or I have so many weights that needs to be trained, right? Aniket, yes, that's the exact answer. Very good. So if I do 2352 into 32 plus 32, right, I get 75,264 weights, right? So 75,000, close to 75,000 weights only for one hidden layer. So don't you guys think that for an image, now if you go back to the image, this image is a very pixelated image, only 28 cross 28. The size of the image is 28 cross 28. And you have seen that when we were working with the example, for the previous example, digit 1, the images that we had taken were 28 cross 28 and they were so pixelated, right? So don't you think that we are actually creating an overly complicated neural network for a problem statement that might not be as complicated, or for an image which is not very complicated? Now imagine that you are given an actual image, right? An actual image, let's say you head and you get an actual image which contains 5,000 cross 5,000, or let's say 4,000 cross 4,000 pixels, right? Now, I'm not talking about HD, Super HD images. I'm talking about normal images that you have, right? Even if they have the dimensions of, let's say, 4, 4K cross 4K pixels, can you imagine how many weights will be there for such an image from the input layer to the hidden layer? Indu, it will always be a square. Generally, it is a square, but if you have any other image size, let's say you have a landscape image or you have a vertical image, in that case, it can also not be a square, right? But generally, when we work with these images, it will be a square only, right? Okay, so now let's take the example. Now, see, this is a very simple image. This is a very low resolution image for which we have around 75,000 hyperparameters. Now, let's say if my image becomes 4K, right? 4K means that 4,000 into 4,000 into 32, correct? So these many neurons in the input layer will be there, right? If you do the multiplication, you will realize that 4,000 into 4,000 into 32 will be such a high value, right? And your neural network will keep on training, right? And for an image which is decently sized, it might happen that your neural network keeps on training for days. Now, this is something that is way too complicated, right? Ideally, we should have a model which is able to deal with image data in a relatively faster amount of time, right? So the ANN model that we had built on the image, right, yesterday and last week, right, we were able to do that only because our image size was way too small, right? But when you think about real world use cases, when artificial intelligence is being used for day-to-day activities, for real-time predictions, right? I don't think that an ANN model or the complexity that comes with an ANN model will be able to survive and give us real-time predictions, right? And that is why the concept of convolutional neural networks had come, because they actually try to do some transformations on the image which will reduce the size of the image, right? What are those transformations, how they happen? That is something that we'll be studying today, right? Are there any questions on this? I hope everyone is able to understand the problems that we had with the fully connected layer, right? And then this will be multiplied by the number of neurons that your hidden layer number one will have. Then hidden layer number one will be multiplied by the neurons of hidden layer number two, right? So you can see that how complicated or how many weights a simple neural network model might even start to having, which will increase the processing power, which will increase the time during which the model runs, right? So, and this is something that is generally not acceptable. So that is why we need to have convolutional neural networks. So also we will have several such layers of neurons leading to several parameters. Thus, this connectivity would be a waste as a huge number of parameters would lead to overfitting, right? Now, this once again is first of all from a size of the neural network point of view. This is an overly grown neural network for a relatively simple image that we had, right? So now we will move to CNNs and we will see how CNNs or convolutional neural networks, right? They help us in overcoming this problem, right? So, all right. Now, before moving on to CNNs, let's try to understand one thing, right? Now, let me give you an example. Let's say if I go ahead and let's say that it's dark, right? You are standing outside, you are standing on a road, and you are standing on a highway, and there are different types of cars and four-wheelers and two-wheelers that are actually passing by you, right? Now, it might be totally dark, right? You might not be able to look at the uh, object properly, but still, would you be able to tell, let's say that there are different vehicles that are passing by you, right? Let's say it's a truck, right? There is a truck. there is a sedan car, there is an SUV, there is a bike, right? Now, standing in the dark, let's say you have 10% visibility, 20% visibility, do you think that you will be able to make out the differences between a truck, a sedan, an SUV, a bike, a hatchback? Will you be able to do that? So, see, generally speaking, now don't assume that it is pitch dark, right? It's dark, it's let's say nighttime. But generally speaking, even if let's say the color of the car is not visible to you, even if let's say the model of the car is not visible to you, you might be able to look at the silhouette of the car, right? You might be able to see whether it's a car, right? Whether it's a sedan. If it is a sedan, it will be low and it will be stretched. If it is an SUV, it will be slightly higher. It will have a kind of a boxy shape, right? If it's a truck, it will obviously be large, right? So you should not be able to confuse a truck with a car, right? If it's a bike, then obviously the shape will be totally different, right? Now, see, even though you are not processing the entire image, right? Even though the entire all the features of the image were not visible to you, right? When I say features, that means that you did not see the color of the car, you did not see the edges that were there on the car and all, right? You just looked at the silhouette of the car. The silhouette is what? The silhouette is the outlining of the object, right? Just by looking at this silhouette of the vehicle, you were able to make out, you will be able to make out whether it is a car, whether it is a truck, whether it's a sedan, SUV, bike, whatever, right? So, what we take away from this example is that probably we do not need all the features, right? Whenever we are, let's say, trying to identify objects, whenever we are trying to, let's say, classify images, right? Probably we do not need all the features that are there in the image, right? Probably there are some features which are redundant as well, right? And depending upon what kind of problem you're solving, right? So let's say if I go ahead and I ask you to create an object detection model, right? Now, what is so in our case, the object detection model is what? Object detection is, let's say I give you 10 kinds of images as input. Your model should be able to predict what the input contains. Let's say one image is the image of a dog. So your model should go ahead and predict that it is a dog. Let's say other image, it is the image of, let's say, a cat, right? Let's say the third image is the image of a human being, right? Fourth image of a giraffe, right? Now, all you need to do is that you need to classify these objects into the different categories that they belong to, right? Now, for such kind of a problem, do you think that all the features of an image will be required or only some features will do? Some will do, right? Because see, it doesn't matter what the color of the dog might be. The color of the dog might be black, might be brown, might be white. But if you focus on, let's say, the ears of the dog, if you focus on the snout of the dog, right, the nose will be long, right? If you compare that with a cat's face will be totally round, right? A cat's ears will have slightly different shape, the body of the cat will be slightly different, right? And obviously, if you compare that with a human being, right, a human being will have a totally different silhouette. If you compare that with a giraffe, right? So probably all the aspects of, like, let's say the texture, the color, all of these things might not be required, right? So what convolutional neural networks try to capitalize upon is that they try to select the relevant features that are there in the image, right? They try to get rid of the irrelevant features, right, from that particular problem point of view, and they try to limit the size of your data by only keeping the important features, right? Now, if your original image size was 4000 cross 4000 cross 3, right, after doing after going through the different layers of a convolutional neural network, you might end up having an input size of, let's say, 500 cross 500 cross 3, right? Now, if you see, you have reduced your data size by a huge margin. Earlier image was 4000 cross 4000, new image is 5000 cross 500 cross 500. So you have reduced the image size by 64, 1 by 64, right? 64 times you have been able to reduce the image of the size. And all of this you have done by keeping intact the features which might be important for the image, right? So if let's say the silhouette of the image is important, that is kept intact. If let's say the shape of the ear is important, that is kept intact. But if let's say the color of the image is not important, that is taken away, right? So in a way, we are trying to reduce the size of the image by keeping with us the important features which will help us in classifying whether this object is a dog, cat, human, giraffe, whatever, right? And taking away those features which might not be very important for us. All right, so let's move on then. Now, if you see, CNNs are like neural networks that we have studied before and are made up of neurons with learnable weights and biases, right? So CNN is nothing but artificial neural network only. But over here, each neuron receives several inputs, takes a weighted sum of them, passes it through an activation function, and responds with an output, right? So everything is similar. Whatever we were doing in an artificial neural network, all of those things still we are doing over here as well, right? But along with those things, we are also doing some transformations which are known as the convolutional layers. The convolutional layers are the layers which will transform your image from higher dimensions to lower dimensions, right? And make the input a much more simplified one, right? Okay, so if you see, the whole network has a loss function, and all tips and tricks that we developed for neural networks will still apply on CNNs, right? A convolutional neural network, which is also known as a connet, right? If someone asks you that, do you know what a connet model is? Then yes, it is a convolutional neural network model, right? It perceives image as volumes, that is three-dimensional objects, rather than as flat canvases to be measured only by width and height, right? Now, let's try to understand one basic difference. Now, when we were creating the artificial neural network model, the input that we were giving, was that one-dimensional or was that three-dimensional? The input to the model in case of the artificial neural network, the one that we were giving, was that one-dimensional or three-dimensional or two-dimensional? One-dimensional, right? We were specifically converting the image to one dimensions. One single image would be a one-dimensional image, right? But in the case of CNNs, in the case of convolutional neural networks, what happens is that we are actually giving your image in the original shape as an input, right? If your image is this, then this goes as the input to the convolutional neural network model, right? This will go as the input to the CNN model. We don't need to explicitly convert this image, this 2D image, to a one-dimensional image, because that is something that the CNN will be able to take care of. Right now, this is the first basic difference between the ANN and the CNN. Right? What do you mean by but X and Y, Nitin? The target variable will be separate, right? I am just talking about the image over here. The target variable obviously will go. That will be a separate target variable. But keep talking strictly from an image or from a features point of view. In case of one-dimensional, in case of your ANN model, one image was being converted into a one-dimensional array and then fed to it. In case of the CNN models, there is no need to convert this image to a one-dimensional form. We can go ahead and we can directly give in the two-dimensional images that we had, right? Yes, Krishna. Okay, so we are directly passing the 2D images over here. Right? Now let's try to understand how the CNNs are actually different from your general ANN models, right? Just 1 second. All right. Now, before moving forward to the architecture of the CNN, right, let's try to understand what do we mean by convolutional, what do we mean by convolution, right? Now, if you see, to convolve means to roll together, right? From a mathematical perspective, a convolution is the integral measuring of how much two functions overlap as one passes over the other. Think of convolution as a way of mixing two functions by multiplying them, right? Now, see, convolution, just try to understand what convolution is. If, let's say, my original image was this big, right? If I convolve this image, right, I might be able to get an output, right, which is smaller than the original image, right? If you see this image, if I convolve, so let's say you have a bed sheet, right? You spread that particular bed sheet on your bed and it will be, let's say, wide. It will be big, right? What if you pick the bed sheet from center, right? Take it up and then place it at the center of your bed, right? Now the same bed sheet, which was probably spread on your entire bed, right? Now you are able to represent the same bed sheet on your bed, and now it occupies less amount of space, right? Yes, there are some aspects of the bed sheet that are not visible to you, but at the end of the day, let's say if you wanted to identify whether it is a bed sheet or not, in both the cases, when the bed sheet was spread on your bed properly, or the case when the bed sheet was convolved on your bed and put at a specific, let's say, at the center of your bed, in both the cases you should be able to make out that it is a bed sheet, right? So convolve, the meaning is to roll together, right? And over here, in case of convolutional neural networks, we will try to convolve the images, right? We will try to reduce the size of the image by keeping intact the features that might be important for us to go ahead and classify objects, to go ahead and do whatever job we are supposed to do, right? Don't worry about the mathematical aspects of this as of now. Once when we move on to the different layers, I'll be talking about this. Right now, if you are able to understand the definition of the word convolve, right, then, and if you're able to understand the intuition of how convolution actually affects the size of the image, we are reducing the size of the image, Pooja, that is true, but we are reducing the size of the image by taking into account the important features, right? We are not dropping away the important features. We are only dropping away the features which might be redundant in nature, right? Now let's try to see what happens in a convolutional neural network. Now see, convolutional neural network pass many filters over a single image, each one picking up a different signal, right? I will be talking about all of these things: convolution, ReLU, pool, what these are. These are actually the different layers that we have inside a convolutional neural network, right? What these layers do and all, that is something that is going to come in the subsequent slides. But right now, just try to understand the overall effect of all of these layers combined together, right? Now, let's assume that this is the original image that we had, right? Now, if you see, this image contains so many features, right? You have the colors, you have the different shapes and all, right? Now, what convolution tries to do is that, what convolutional neural network tries to do is that it tries to identify different features that the image contains, right? Now, if you see, if I try to identify the vertical edges of this image, right? If I just go ahead and I apply a filter which will somehow give me this output, right? The edges of the image, I might get an output which looks like this, right? If similarly I go ahead and I apply a filter, now what are these filters? How are they applied? All of this we are going to study. But I want you to understand what convolutional neural network actually does. It actually breaks down an image to different features, right? Now, if you see, this image has been broken down into vertical edges, has been broken down into horizontal edges, right? Now, it might happen that, let's say, for me to identify whether this is like what this image is of, let's say vertical edges of this image, this feature might be an important feature. So I will try to preserve that. So the first step that you need to understand here is that we are trying to extract the features of an image. When I say features, what I mean is that when you look at a dog can be a combination of, let's say, the silhouette of the dog. It can be the combination of the color, right? What color it has. It can be, let's say, the edges that the dog has, right? So there are multiple features that will be present in the image of a dog, right? But in order for me to go ahead and tell that whether it's a dog or not, I might only need to look at only a couple of features, right? I might not need to look at the color of the dog. I might not need to look at the texture of the dog, right? I might just have to focus on the edges of the dog, right? And I should be able to identify whether it's a dog or a cat, right? So what the different convolution layers try to do, the object of these different convolution layers is to extract these features, right? And then the objective of the neural network at the end is to find out which features are important and which are not important. The features which are important are kept, the features which are not important are at the end of the day dropped, right? So this is just an example through an image which I just thought that maybe this will make it easy, but we will be going through each and every step now, right? We will try to understand what exactly happened. It's performing scans, not exactly scans. It is trying to break down the image into significant features, right? So now let's try to see what exactly happens inside a convolutional neural network. This is still non-technical, but let's try to understand, right? So if you see, convolutional neural networks will pass many filters over a single image, each one picking up a different signal. So when I say many filters, what I mean is that you can have one filter which identifies the vertical edges of the image, right? You can have one filter which identifies the horizontal edges of the image, right? You can have one filter which, let's say, detects how blur the image is, right? You can have one filter which maybe detects how sharp the image is, right? So you have different kinds of filters that we apply on an image, right? That's the step one. Each one picking up a different signal. Signal is basically the feature that I'm talking about, right? By a different signal, let's say one filter picks up on the vertical edges, right? One filter picks up on, let's say, the horizontal edges. So a signal is nothing but the feature of the image that we were talking about, right? Now, at a fairly early layer, you could imagine them as passing a horizontal line filter, a vertical line filter, diagonal line filter to create a map of the edges in the image, right? CNNs take those filters, slice of the image feature space and map them one by one. They create a map of each place wherever the feature occurs. By learning different portions of a feature space, convolutional nets allow for easily scalable and robust feature engineering, right? So if you see all of this text that is written, all of this relates back to the same concept that what the convolution layers are trying to do is that they are trying to extract the features which are important, and they are trying to reconstruct the image by using only the important features, right? Whatever features might be unimportant, whatever features might be redundant in the image, right? We are trying to take away those, right? And all of this happens through these different layers that we have. Now, in a convolutional neural network, there are three separate layers that we'll be talking about, which were not there in the case of the ANN model. One is the convolution layer, the second is the ReLU layer, and the third is the pooling layer, right? Now, these three layers combined, when we keep on applying these layers again and again and again, two things happen. One, your image size, let's say my original image size was 4,000 cross 4,000, this size will go down, right? I might get an output of 500 cross 500, and two, the output that I will get of 500 cross 500, right? That will only contain the significant features that will help us in predicting whether the image is of a cat, of a dog, of a human, of a horse, whatever. A simple convolutional net is a sequence of layers, and every layer of a connet transforms one volume of activations to another through a differentiable function. There are four layered concepts, right? So there are four layers that we have in a convolutional neural net: convolution, ReLU, pooling, and the fully connected layer, right? Now, what do I mean by this? I can, let's say I had an image, right? How the transformations happen is, let's say I had an image which was like this, right? I fed this image, let's say, to a convolutional neural network, right? Now, what will happen is that I will have, let's say, the first layer that I am having is the convolution layer. This will be followed by ReLU. This will be followed by pooling, right? Let's say this is the transformation that we had to do. After this transformation has happened, we will go ahead and now see after this transformation, probably my image size, which was, let's say, after this transformation, right? Now this image, which was way too big, after these three transformative steps, this image would have been converted to a single dimensional image of a lesser size, right? So let's say this becomes my output, right? So if my original image was, let's say, 64 cross 64, right? This array might only be, let's say, 128 cross 1, right? So you can see that what these layers have done is that they have reduced the size of the image, and along with after reducing the size of the image, they have also kept intact the important features, right? Now it is a simple job for me. What I need to do is that, if you remember, after this, it is nothing but your simple ANN model that we had, right? We need to connect our artificial neural network over here. We need to define the different hidden layers and all, and that will give you the final output, right? So the thing that is different over here, right, is this part, the convolution, ReLU, and the pooling. These layers are different. These layers, their objective is to reduce the size of the image while keeping intact the features that the image has. If instead of this, let's assume I would have gone ahead and I would have used a simple artificial neural network on this image, right? My input would have been what? My input, let's say I compare this to a simple model, let's say an ANN model, right? In that case, this one-dimensional array would be how much? It will be, so instead of doing this, instead of us going ahead and creating a larger model, which would have overcomplicated things, instead of doing this, we are doing this, right? Now, when we do this, you can see that this 4096 has been transformed to 128. FC is the fully connected layer, Mosmi, right? FC is not the output. Fully connected layer will have the output layer as well, right? Soham, have I yet gone ahead and explained pooling? I've been repeating this thing that right now you just need to understand the architecture. I have not explained convolution layer. I have not explained ReLU, pooling, whatever, right? I'm just trying to make you understand how the architecture of the CNN looks like. Okay, is there anyone who is not able to understand this architecture? What are the different layers? How do they work? Right? We will be talking about this. So let's do one thing, right? I will take an image of a dog, put it over here, right? Now, what I'll do is that I will reduce the size of the image, right? Let me reduce it to 20. Right? Can you see the size of the image has gone down? Original was 24, compressed was 7. But are you still able to make whether it's a dog or not? Are you still able to make out that it's a dog? But if you look at the pixels, right, the pixels would have gone down drastically. You have reduced the size of the image by 72%, right? Let me take this to minimum quality, that is 10. Are you still able to make out that it's a dog or not? Right? So if my original image, let's say my original image had pixels running into thousands, right? And our objective was to only go ahead and identify whether it's a dog or not. Is it required for you to go ahead and say, like keep all the pixels as input? Because see, if you go to the original image, if I go to this image, right? This image is very high dimensional, right? When it is high dimensional, then what is happening is that in this area, let's say, if I talk about this area, in this area itself, you will have thousands of pixels who will have the exactly same intensity of the color green, right? But if I reduce the size of the image, right? Let's say I go ahead and I reduce the size of the image. Now you can see that this same area, right, has a significantly lesser number of pixels. That is why you can see some pixels over here, right? So probably if in the earlier case, this area had, let's say 10,000 pixels, now this area has only, let's say 100 pixels, but still you are able to make out that it is a green patch, right? So there is a loss of information, but all you are doing is that you are dropping out the redundant features. When I say redundant, instead of showcasing this green patch with 10,000 pixels, which at the end of the day will become my features, what I do is that I showcase this patch by only 100 pixels. These 100 pixels then become my features. So I am reducing the complexity of the model by taking away the irrelevant features, right? So see, in this example, we have only reduced the size of the image, and you have seen that the size have drastically gone down. Still, the image is of the image of a dog, right? In case of a CNN, it will be image compression along with keeping intact the significant features. So in case of CNN, right, the dog will remain intact, but the features that are around the dog, which might not be important, will be taken away. So will CNN only be used for image-based data, or there are use cases other than image? Renuka, we can use CNN for image, for video. Even CNNs can be used for structured data, but they are, I can talk about this once when we are done with the understanding of the CNN. But right now, you can just focus on the fact that CNN generally works the best with image or video data, right? CNN will reduce the size without impact once when we apply convolution, ReLU, and all of these things, right? So if you see, every layer of a coordinate transforms one volume of activations to another through a differentiable function. Now the differentiable function that they are talking about over here is the ReLU function, right? That we have seen. How is it applied? All of these things will be understanding uh, in the next slides, right? In NN, we used to differentiation. Here, integration is used. Where have we mentioned integration, Atish? Differentiation. See, whatever is happening in an ANN will be happening, right? Whatever was happening in the ANN will also happen over here. It's just that it will be partnered with some convolution layers. So let's see some examples of CNNs, what it does. So if you look at this, if let's say I have an image of X and an O and I pass this through a CNN, right? So the CNN will be able to give us the prediction whether the image belongs to X and or an O, right? This is a very simple use case. But let's try to understand how it actually identifies whether it's an X, whether it's an, right? Now, if you look at X, someone can X write in multiple different ways, right? You can go ahead and you can write X in a very structured format. You can write X in a bold format. You can write X in, let's say, not at the center of the screen, maybe towards the left, right, whatever, bottom, down, right? Or you can write X which might be tilted, right? Similarly, if you see O can also be written in different, like if let's say someone is, if let's say I take images which are handwritten images, obviously, handwriting of different people will vary, right? It is going to keep on varying. But at the end of the day, the overall structure might remain the same of the alphabets, but the placement or the design, right? There might be certain aspects that might keep on changing, right? Now, if we are building a model, our model should be able to identify all of these aspects, right? Now, the different layers that we were talking about, right, along with reducing the size of the images, they also try to conserve these patterns. They will also try to understand that, okay, this X is similar to this, similar to this, and similar to this, right? So that is why it is not only image compression that is happening. Because see, when I say that my model is able to classify every image of a dog,
right? Your dog might be sitting, your dog might be standing, your dog might be running, your dog might be behind another dog. Your CNN model should be able to identify that it is a dog, right? So that is what we are trying to do. Hence, only image compression will not help you, right? Along with the image compression, we should be able to identify the important features and we should be able to preserve them. Okay. So if you see here, there are multiple renditions of X's and O's. This makes it tricky for a computer to recognize them. But the goal is that if the input signal looks like images it has seen before, the image reference signal will be mixed into or convolved with the input signal, right? Let's see how this actually works, right? Now, see, a simple approach will be what? Let's say if I go ahead and let's say in a perfect world, my X, the image of an X, right, looks like this. That is, these are the pixel intensities that an image of an X will have, right? And let's say I go ahead and I get an input which looks like this. Now, a very simple, very naive approach will be just to compare the pixels point by point, right? So if I go ahead, if I compare these two, so let's say I start comparing the pixels. Let's say I compare this pixel from this pixel, right? I compare this pixel from this pixel, right? Similarly, I keep on comparing. Let's say I compare this pixel to this pixel. So do you think that this will be the correct approach to identify whether an X is an X? No, right? Why not? Because obviously my input image is skewed. My input image is, now see, this is also an X. Although you can see that this is an X, which is kind of aligned, but this is an X which is slightly skewed, right? But ideally, my model should be able to identify these, right? So a naive approach of comparing pixels by location does not look good, right? So when comparing two images, if any pixel value doesn't match, then these images don't match, at least according to the computer. So if my naive approach is to compare the pixels, obviously my dog, let's say in my input image, when I'm training the model, my dog was at the center. But let's say when I get a sample image on which I have to make a prediction, the dog was on the left hand side top of the image. So if I go ahead with a naive approach of comparing the pixel intensities point by point, then obviously it will be incorrect, right? So let's look at what we need to do over here in order to bypass this situation, right? So, all right. So this is once again the same X. Now let's try to understand what happens, right? If we just search normally and compare the values between a normal image and another rendition of X, right, we would get a lot of missing pixels, right? If you see over here, if we are overlapping these two images and we are just looking at the common pixels, you can see that only these five are coming out to be common, right? All the rest of the pixel intensities are not matching. Hence, you cannot go ahead and you cannot say that this was an image of an X, right? This is the naive approach that we were talking about, right? I hope this is clear to everyone. You can see that through this approach, the common pixels are only these five. Through these five, I cannot say that this is an X, right? Now let's see how CNN models will try to solve this problem, right? Now, instead of comparing the entire image, right? Instead of comparing the entire uh, image, like overlapping the image, stacking the image on top, what CNN does is that it identifies individual features, right? So let's say it identifies that this is a diagonal feature, right? If you look at this, this is what? This is a diagonal feature, right? So if it identifies this, what it will go ahead is and do is that it will try to identify similar features, right, over here in the input image. Not this. If you see this and this, right? Right. So if you look at this output over here, right, what it will do is that it will identify features. Now, let's say this diagonal feature that it identifies, it realizes that this diagonal feature is present over here and here, right? Similarly, it goes ahead and it finds out that this diagonal
feature is over here and here, and this feature at the center of a smaller x is present here, right? Now, if you go ahead and if you scan this image on any other pixel areas, right, you will find that these exact features are not present, right? And on the basis of this, now if we move ahead, right, now if you see, it identified this as a feature, this diagonal as an important feature, and it is able to find out that over here. It identified this diagonal, that is the reverse diagonal, as an important feature, and it was able to find that out over here, right? So, right, if you see, each feature is like a mini image, a small two-dimensional array of values. Features match common aspects of the images. In the case of X images, features consisting of diagonal lines and a crossing capture all the important characteristics of most X's. These features will probably match the arms and the center of any image of an X, right? Now, if I go ahead and if you go ahead and if, let's say, you take this particular filter, right? Let's imagine that this is the filter that you are taking. If you'll apply this filter over here, will that be a match? This will only be a match over here, right? Now, in my original X as well, this feature was present, right? Now, see, if let's say if I denote this feature as the value 1, right? Let me just showcase this to you with the proper example. So let's say this is your feature 1, right? And let's say this diagonal, reverse diagonal, is your feature 2, right? And let's say this center part is your feature 3, right? If this is your feature 3, if these are your feature names, how can I denote my X? My X can be denoted by 3 at the center, 1 over here, 2 over here, right?
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
And then 2 over here, sorry, and 1 over here. Is that correct? Any X can be represented by these features: 3 at the center, 1 and 1 at the diagonals, and 2 and 2 at these diagonals, right? Now, if you look at this particular image over here, do you see that the same pattern is being followed? If you look at this over here, this is 2, sorry, this is 3, right? Over here, this is 1. Over here, this is 2. This is 2. And this is 1, right? So an exactly similar pattern is being followed. The only thing that is different is the placement of this feature along with that, with this 3, right? Now it's a little off, right? So now what the model will give me is the model gives us probabilities, right? So when the model gives me a probability, it might give me a probability of this being X by, let's say, 80%. Right? This will not give me that the probability of this being X, this being an X is 100%, right? But because almost all of the features are exactly matching, the placement of the features might be slightly off, but that is something the model will learn because it knows that different people will write X in using different parts of the page, right? So this is what will be accounted for in the probability. And X, which will be written in the most perfect manner, probably will have the probability of 100% being an X. And X, which is, let's say, slightly skewed, will have the probability of that being an X by, let's say, 80%, 90%, 70%. Right? But don't you think that this is a better approach to identify objects and features in an image as compared to the previous one, wherein we were comparing the entire image at once? So, Prageet, yes, see, one can also fit over here and two can also fit over here, right? So this depends upon the CNN, how it actually see. It can also happen that the CNN only identifies two features. Let's say this diagonal, this is present over here, this is present over here, right? Then let's say this is present over here, and then let's say this is present over here. Then it identifies this diagonal, it is present over here, present over here, present over here, and present over here, right? So how it tries to identify the features and all that depends upon how many image samples you have and what is commonly occurring in those image samples, right? But at the end of the day, this is how it will try to break it down. This is just an example. It will try to break it down to the most simplest feature possible, right? So over here, if you see this, the most simplest feature is what is a diagonal, right? So it can go ahead and it can actually use all diagonals, or it can go ahead and use, let's say, some diagonals, some crosses, right? That depends upon the input samples that we are providing. All right. Any questions till now, guys? I hope everyone is able to understand. Till now, we have not gotten into any specific aspects of what happens inside the different layers. Till now, we were only talking about the general aspects of a convolutional neural network, how it tries to classify images, how it tries to extract features and all. Now we will be moving into the different layers, right? So we'll be starting with the convolution layer first. Indu, you take any digital image, right? If you will read it in Python, it will automatically be converted into. So in Python, once when we read an image, right? So if you see when we read an image for our previous case as well, the digit data, it was automatically in numbers. So you don't need to do anything. If it is a digital image, and obviously in today's world, 99% of the images that you will be having is digital. If the image is not digital and you, let's say, capture it through your mobile, right? If you bring it to your computer, automatically it will become digital, right? So a digital image by default will have numbers, right? And when you read it in, let's say, a photo viewing app, it will not show you the pixels because the photo viewing app is designed in such a way that it will show you the image. If you open it in Python, if you open it in, let's say, R or any other programming language, it will automatically open as a digit based, like it will automatically open as an array or a matrix. You don't need to do anything on the top. Automatically, it will be numbers only, right? So an image is actually not converted into numbers. Numbers are converted into an image. So by default, the default structure of any image is actually numbers, the pixel values, right? So you don't need to do anything specifically over there. All right, so now let's move on to the concept of convolution, right? Let's try to understand what convolution is. We might not be able to complete this, but at least let's get started, right? Now convolution, it's the first layer of a CNN. When presented with a new image, the CNN doesn't know exactly where these features will match, so it tries them everywhere in every possible position. In calculating the match of a feature across the whole image, they act as filters. The math used to perform this is called convolution, from which convolutional neural network gets their name, right? We have 4 steps in convolution: line up the feature, multiply each image by corresponding feature, add the values, find the sum, divide the sum by total number of pixels in the feature. I'm pretty sure that no one would have been able to understand what I spoke of, correct? Now let's try to understand what exactly happens in convolution, right? I will come back to this slide, but let's try to understand mathematically what happens in convolution, right? Now, let's say that this was my input image, right? Let's assume that this was my input image, and we had a filter, we had a convolution filter, which looks like this, right? Now, first of all, what is the job of these filters? These filters act as agents and they try to extract similar filters from the input image, right? If you remember, I have talked about that when I want to classify an image into a dog or a cat, I am looking for specific features. These specific features I am able to extract through the different filters that I have, right? So over here in my convolution layer, what happens is that we apply different kinds of filters. There are different filters that we can apply, right? We apply different filters to our input image and we try to see if the filters are matching or not, right? Or how many subsets of the original image the filters are actually matching, right? So if you see over here, let's say this was my input filter, this was my convolution filter, this was my input image. So what will happen is that, so Mosmi filter, if you remember, we were talking about identifying edges, identifying vertical edges, identifying diagonal edges, horizontal edges and all, right? So a filter is nothing but a smaller matrix, yes, which we are going to traverse through the entire image and it will try to find out how many vertical edges are there, how many horizontal, how many diagonal. If you see, this is a diagonal filter, right? If I traverse this diagonal filter across my entire image, I will be able to find out how many diagonal features are there in this image, right? Now, what happens is that we generally start from the first 3x3 possible matrix, right? Now, do you guys think that this convolution filter and this one that I've selected, the black subset, do you think that it is matching? It's not an exact match, right? But some proportion, some percentage is actually matching, right? So let's take example of, let's say if I go ahead and if I apply this filter, right? The filter that we are seeing over here on this part of the image. It is an exact match, right? So ideally, if I apply this filter over here, I should get an output as 1 because this is an exact match, right? So let's see how this happens inside the convolution layer, right? So first thing that you need to understand is that this filter will be traversed through this entire image, right? I hope you're able to understand that. The filter, Nitin, can be anything. We will have to define the size of the filter, right? It can be anything. It can be 2x2, 3x3, 4x4. So if you see, the filter will start moving from here. Then maybe the next time it goes from here to here. Then maybe the next time it goes from here to here, right? Like this, it will keep on going. Let's say it comes to this part. It will go from here to here. It will keep on going and it will conclude over here, right? It will conclude the mapping session somewhere over here, right? So Mosmi, yes, whenever we call the convolution layers, we will pass how many filters we need. Let's say you say 32 filters. So 32 randomly generated filters will be passed to the image, right? These filters will be the most commonly occurring filters, right? 3x3 is not the standard size. The size depends up to you. You can use a 2x2, 3x3, 4x4, whatever, right? This is just an example as of now. 4R minus 5R plus. So the output will be what? 1 by 9. It will be 1 by 9 only. So is everyone able to understand this? All right. So this is what happens mathematically. We'll stop here. Dheeraj, just go through this and see if you're able to understand. And through the different kinds of filters, the CNN model tries to arrive at the features that the image might contain, right? When I say features, it might be vertical features, horizontal features, your edges, right? Your blurred image, your color, your tint, and things like that, right? So let's try to understand what happens in convolution. Now, if you look at this, if this becomes a filter, right? Now, if you see, this filter is a diagonal edge detect filter. So if you try to understand this, right, these values, what it is doing is that, so if you just focus on this filter, right? Now, if you will multiply this filter by any area of the image, right? Any subpart of the image, essentially what will happen, right? So if you see, only the diagonal elements are the elements, or only the diagonal pixels are the pixels which will be activated, right? These are one. So for all, for those areas in my image where the diagonals will also be one, I will get an output which will be equal to one, right? And for other areas, right? So let's say when a diagonal is not matching, right? When, let's say, some other pixel is a one, in those cases, because it will get multiplied by a -1, right? What it is doing is that, in a way, it is actually deactivating that, right? So what it does is that it highlights, at the end of the day, it will highlight the diagonal edges that your image contains, right? So that's what we had seen yesterday. What we do over here is that we multiply each value from the corresponding value in the sub part of the image, right? So if I have this, right? If you see, this was the first value in my filter, this will get multiplied by the first value of whatever subpart you have selected, right? If you look at the third value, right? All of these multiplications, last value will be multiplied by the last value. Because this is an exact match, right? Because this is an exact match with the filter, I get the value as 1, meaning that this is a proper diagonal edge. This part of the image is a proper diagonal edge, right? If I overlay this filter on some other part, and let's say the value comes out to be 0.5, it means that that part of the image is only 0.5. It's matching only 50% of the elements that are there in the filter, right? Is this part clear to everyone, or there are people who don't understand this? The calculation part, at least. It will always be between 0 to 1 for overall calculation. Yes, Aniket. Because it is matching, right? It will always give you the output. Now see, over here we are taking 0, 1 values, right? But for colored images, there can be, see, from a pixels point of view, your pixel intensities can vary from 0 to 255, right? Generally, we take 0, 1 when we have black and white images and we have scaled that image, right? And 0 and 1, basically 0 becomes white, 1 becomes black, right? But if you have, let's say, colored images and you have different red, green, blue, right, uh, parts of a photo, in those cases, your values might, let's say, range between 0 to 255. In that case, your output will always be in the range of 0 to 255, right? Whatever range your pixel intensities are taking, the output will be in that range only, right? Now, see, let's try to understand this. If I apply this convolutional filter on a 3 cross 3 matrix, what is the that I, is it a 3 cross 3 matrix, or is it a single value, or is it something else? It's a single value, right? Because if you look at this over here, when I multiplied this filter to this part of the image, right? When I'm multiplying this filter to this part of the image, what I get is this single value, right? So if let's say I traverse this filter through the entire image, what will be the output? What do you think will be the output, or what will be the size of the matrix that will come out from this? Try to understand, right? See, this one application will give me one value, right? So let's say I go ahead and I draw that. So let's say I get 1 pixel from here, because this one 3 cross 3 filter is going to give me one single value, Now what I'll do is that I will move this filter to the right, one step to the right, correct? I will get one more pixel, right? I move this once again towards the one step more towards the right. I will get one more pixel as an output. Each and every time my filter is being applied, I am getting one single value, right? Let's say I apply this one more time. I get one more value. I apply this one more time. I get one more value. I apply that one more time, one more pixel value, and apply that one more time. I get one more pixel value. Can I, or do I need to apply it now once again towards the right hand side? Do I need to go out of the frame? Like, do I need to do something like this? No, right? So how many pixels did I get now? In when I was applying this on a 9x9 matrix, how many pixels did I get in my columns? 7, right? If I count the rows, what will I get? Will I get 7 only, or will I get more, or will I get less? 7 only, right? So if you look at this, the output from this particular step will actually be a reduced matrix, right? So if this was 7, let's say this will also be, these will also be 7 pixels. Right? How did I arrive at this 7? Can you guys think of a formula over here? Is there any formula that we can apply? My original matrix was 9x9, right? I multiplied this by a filter of 3x3, and I got an output of 7x7, right? This was 1. Let's take one more example, right? Let's do one thing, that what I'll do is that I will, this time, let me take a 5x5 filter, right? Instead of taking a 3x3 filter, what if we take a 5x5 filter? If I take a 5x5 filter, what will happen? I will cover the first 5 pixels of both rows and columns, correct? How many values will I get from here? 5x5 is the filter size. How many value will I get from this one particular filter application on my image data? One single value. If I move this further, right, one more value. If I move this further, I will get one more value, right? One step further, one more value, and then the last step, the final value, right? So what I get is a 5x, I'll get a 5x5 matrix, right? So let's write this over here. If I do a 9x9 into 5x5, I get a 5x5 matrix. Can you think of a formula? Do you think that there is some kind of a relationship between this output matrix and the input and all? Right? It will be, this is not permutation and combination, right? So it's simple, right? It will be, let's say the size of your input matrix. Let's say the size of your input matrix is n cross n. The size of the filter is, let's say, m cross m, right? Then the output matrix will be n minus m plus 1, right? Correct? And you can see this formula will be applied now on, if you apply this formula on all of these examples, you will see that it will stand true. Right? So what is the first step of convolution doing? It's doing two things, right? It is, first of all, it is trying to uh, find out the features, right, which are in line with your image, right? Depending upon whatever feature matrix you have. Let's say if it is a diagonal filter, if it's a vertical edge filter, horizontal edge filter, whatever, depending on that, what it is doing is that it is going ahead and it is applying that filter, right? And it is getting a convolution output, right? Now, along with that, it is also reducing the size of the image, right? So if my 9 cross 9 filter, if my 9 cross 9 image, right, had 9 cross 9 will have how many? 81 pixels, right? My output that is coming out, which is 7 cross 7, will have how many? 49 pixels. So you are actually reducing the size of your image by 42 by 81, by a factor of 42 by 81. Let's say close to 50%, right? Okay, sorry, 32 by 81, right? So this will be how much? Let's say close to 25, 32, 64, right? Let's say close to 25%. Is it 25? Yeah, right? So you are also reducing the size of the matrix and you are also highlighting the important features that the image will have. So now if you see, if I keep on doing this, if I keep on populating the values of each and every sub part of the image, for this 9 cross 9 input, I got an output of this 7 cross 7, right? Okay. And you can see over here that this edge, right? This particular edge is the edge where the diagonal filter is actually applicable. You can see that most of the values are close to 1 or 0.55 in one case or greater than 3/4, that is 0.77 in the last two cases. Now to complete the convolution, we need to repeat this process, take answers from each convolution, make a new two-dimensional array. Map of matches is a filtered version of the original image. It's a map showing where in the image the feature can be found. Values close to 1 show strong matches. Values close to -1 show strong matches for the photographic negative of our feature, right? Now, see, one thing, now all of you guys would have used filters on your phone, Instagram, Facebook, right? All of those filters are nothing but this, what we are seeing over here, right? That is, all of that is exactly the same thing. Now, I will be showcasing you some filters when we'll be working on Python, right? How by the application of some filters, we can, let's say, smooth an image. We can convert something to black and white, right? So all of these filters, whatever you are seeing on these Instagrams, these applications, your phone and all, that is nothing but this step happening, this convolution step that happens, right? Now see, you would have seen filters which actually makes everything too smooth, right? You will click a photo and you will realize that your skin has basically become so smooth, right? There are no freckles, there are no marks that you are able to see, right? So what is happening is that when you so what we are doing is that we are taking a bunch of pixel values and we are combining them. Now, what happens is that, let's say that there is an area, so right, so right, so let's take one example. If I go ahead and if I zoom this image to as big as possible, right? Sorry for this, but I just want to give you an example. Let's say if I zoom this image over this part, right? Now you can see that most of the area over here is smooth. right? There is one area where there is a freckle present on this person's skin. Now, when you will apply the convolution layer, right? When you will apply the convolution filter, depending upon whatever values you are giving to the filter, it will actually go ahead and assign you 1 pixel for this. When it assigns you 1 pixel for this, it will take the value which the majority of the pixels are having. Now here you can see that the majority of the pixels are smooth. So if the majority of the pixels are smooth, what will happen is that it will go ahead and it will actually uh, nullify this particular freckle that you are seeing over here, right? So everything, all the filters, the black and white filters, the smoothen, the blur, right? All of the things that you are seeing on social media on your phone is nothing but what we are seeing over here, right? Okay, so let's move forward now. Now see, whatever we have done over here, next step is to repeat the process in its entirety for each of the other features, right? Now, what we did over here was one set of features, right? I hope you understand this, that this is one diagonal feature, right? Now, like this, I can also apply other features, other filters. Let's say I apply a vertical edge feature, I apply a horizontal edge feature, I apply a blur feature, I apply a tint feature, right? So let's assume that if I had gone ahead and if I had applied 3 filters to this image, essentially what will happen is that I will get 3 outputs, right? For this one 9x9 image, I'm getting 3 outputs of the size of 7x7, right? The first output, the blue one, is the feature map using filter number 1. The second one is your output using filter number 2. The third one is your output using filter number 3. Now, it might happen that out of these 3, only the first filter and the third filter might be important, right? So this is the process that the model will identify, or this is something that the model will identify during training, which filters are important, which are not important. The ones which are important will be kept. The ones which are not important may be swiped for some other filters, right? Is this part clear to everyone? Any questions? No, Mosmi. So let's assume this is a black and white image, right? I'm saying that for this one black and white image, don't confuse this for red, green, blue. Assume that this was a black and white image, right? And on this black and white image, we applied 3 separate filters, right? If I apply 3 separate convolution filters, this was one filter that we had applied, right? So by applying one filter, we are getting one output of 7x7. But this is a diagonal filter. What if I also want to identify vertical edges? What if I also want to identify horizontal edges, right? So let's say I applied 3 filters to this image. One was diagonal edge, one was horizontal, one was vertical. So these are the 3 outputs that you're seeing. Into the color is just to segregate between the 3 filters. This is not the color of the image. This is just to this because this is coming from a heat map, right? That is just for differentiation. All right. Any questions, guys? I hope all of this is clear to everyone. Atish, this is an example. We apply lots of filters, 30, 60, 100, whatever, right? So this is just an example. Bhagirath, in landscape size as well, this will work, right? So let's say you have an image which is, let's say your image is this, and it is, let's assume 100 cross 500, right? Let's assume the size of the image is 100 cross 500. Now, if you go ahead and if you apply a filter, a convolution filter of, let's say, the size 5 cross 5, right? So 5 cross 5 will be able to iterate through your entire frame, right? Even if you apply, let's say, 3 cross 3, it will go ahead till 99, and then for the last pixel, it will move out. And because it has to cover that pixel, it will go from 99 to 102, right? So Tanushri, all of these outputs will be taken to the next level, right? So see, one image is being broken down into multiple distinct features. Now, right, so if you take this example only, this was my original image, right? If I apply different kinds of filters, now these filters are totally random, but if you will apply the kind of filters that we do, each and every filter will try to come up with something new about the image, right? And all of these filters together, right, are going to go ahead and are going to help us in, let's say, classifying whether the image is of a cat or a dog, right? Now, if I go back to the example of classifying between a cat or a dog, right? So the major features that will help us there are what? The major feature can be, let's say, the silhouette of the cat and the dog. It can be, let's say, the colors of the cats and dogs, right? It can be, let's say, the shape of the eyes, right? It can be, let's say, the shape of the nose, right? Now, all of these, the shape of the eyes might be identified by the horizontal edge feature. The shape of the nose might be identified by the vertical edge feature, right? So all of these features, each and every output, right, is highlighting one specific feature of the image. So all of these will be fed forward, and then through the training of the model will try to identify which features are actually important and which are not important. The ones which will not be important will be replaced by some other filter. Designed values, right? When I talk about the CNNs, these are random filters. Now, that is why the training of the convolutional neural network models takes so much time, that there will be thousands and thousands of random filters that are there. Let's say I apply 32 filters to the image, and none of the filters are able to, let's say, increase my accuracy of the model. That means that these filters are useless. Now, the next time when back propagation will happen, the values of these filters will change, right? Maybe some other value will arrive at the filters, right? But generally, what Keras does, what Python does is that when, let's say, I go ahead and I say 32 filters, it will take those filters automatically, which actually work the best on image data, right? So from a probability point of view, it will go ahead and it will take edge detect features, vertical, horizontal, diagonal. It will take tint based features, blurring features, sharpening features, and things like that, right? So these filters are not designed. Generally, these filters are created through your data only. But because Keras in Python as a library, they try to help creating the model in a faster way. So these filters that are selected, once when you go ahead and you say that I want 32 filters, right? So the 32 filters will have those filters which generally work well with image data. Now, let's say if your image is slightly different, if your image is coming from a different domain, maybe those 32 do not work, right? If those 32 do not work, when your forward propagation will happen, while calculating the accuracy, the model will know that these filters have not been able to actually highlight any important features. So while the backward propagation happens, these filters will be updated, right? Minus one, see, one and minus one, no. One and minus one, these are just the filters, right? This is saying that whatever values are coming over here. So see, while scaling the data, you can scale it in any possible way. So for this image, you can understand that minus one is 0 and one is 255. Don't get confused by that. Any other questions? So this was the convolution step. We are done with the convolution step. I hope this is clear to everyone. Our objective over here is to, for any given image, our objective is to find the best set of filters which are helping us in solving whatever problem we are solving, right? So the overall training process is identifying these filters, right? So that is why we are actually going ahead and we are applying so many filters. Finding a good filter means that that filter is helping you in reducing the loss or increasing the accuracy. A filter is good only if it is helping you in, let's say, identifying a cat from a dog. If the filter is not being able to do that, then obviously it is not good for me. Right? So now let's proceed with this information. Let's say I had an input image of, I'll go with my example only that we were taking. Let's say I had an input image of 28 cross 28, right? And I applied, let's say, 5 convolution filters of the size 3 cross 3, right? What will the output be for me? Can you tell me what will be the output for one filter? If it is 28 cross 28 and 5 cross 5, what will the output be? 28 minus 5 plus 1. So 24 cross 24, right? Into 5. Is that correct? Because I have 5 filters. So this will be 24 cross 24 cross 5. So basically 5 matrices of the size of 24 cross 24. This will be the output that I'll be getting. Now, when my original image, right, if you look at the original image, this contained how many? This contained 784 pixels, right? This one, if you look at this one contains how many? 576 into 5, right? Correct? Are you able to understand this? So this will contain 2880 pixels. So in a way, if you see, we have not decreased the size of the image. We have actually increased the size of the image. Because we had one image of the size 28 cross 28, and then we went ahead and we exploded the image to 5 different images, right? And these 5 resulted in a combination of 2880 pixels. So at the end of the day, the more number of filters that you apply, your overall image size is going to explode only, but that is important, that is necessary, because we are trying to identify the important features, right? We are trying to identify the features which will help us in categorizing, let's say, whatever we are trying to do. Mostly 5 separate images will be the output, right? So 24 cross 24, you will have one image, which will be the filtered image. And similar to this one image, there will be 4 other images that will be there, right? So as the size of the filter will increase, the size of the image will decrease. As the number of filters will increase, the size of the resulted image will increase. Tanushree, that is also correct. Yes, as in when you increase the filters, the number of images will increase. But as I said, that is important because we are trying to find out factors, right? We are trying to find out important features. Now, for image data, this is only how we can proceed, because an image is a combination of all of those pixels working together, right? So there is no other way for us to go ahead and to identify the important feature. The number of filters that you have to apply is a hyperparameter, Indu. This will be a hyper.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
Parameter, if you go ahead and let's say if you apply 32 filters and your accuracy becomes 90%. Let's say you go ahead and you apply 64 filters, your training accuracy becomes 95%, but the testing accuracy remains 90% only. So that means that 32 filters were actually doing the job for you. All of this we'll try to see when we are actually building these models, but this will be the number of filters will be hyperparameters. Right. So now let's move on to the ReLU layer. Now, if you see ReLU layer, right? ReLU is an activation function. If you remember, so if you remember the function for ReLU layer, what was that? The function for this, the objective of this function was to make any value which was less than 0 equal to 0. Any value which was greater than 0, it will make it as the same value, right? Now, if I apply the ReLU function on the convolution output, what will happen? So let's say if this is the output over here, if this was the output, if you see all of these values, right? If I go ahead and if I apply the ReLU function on this particular output, let's focus on the top one. What do you guys think will happen? All the negative values becoming 0, what does that signify for the image? What are we doing? So what we are saying that all the pixels where they were not matching with my filter, where they were opposite to my filter. Negative value means that for those areas of the image, right, those areas of the image are actually exactly opposite of whatever you are trying to find out. If you were trying to, let's say, find out a diagonal filter towards the right side, right, this is a diagonal filter towards the left hand side, right? So what I'm saying is that I do not want to keep any of these pixels because this is not highlighting my important feature. My important features are the diagonal features. So I only want to keep values which are greater than 0, right? So hence what we do is that we apply the ReLU filter over here, right? The function, and the ReLU activation function, what it will do is that it will actually get rid of all the subparts or all those, not get rid of, it will neutralize those pixels. It will make the value as 0, right? For all those pixels where the feature is exact opposite to the feature that we have applied on the image. Now, if you see, ReLU is an activation function. This function activates a node only if the input is above a certain quantity. When the input is below 0, output is 0. When the input rises above a threshold, it has a linear relationship with the dependent variable, right? We have considered a simple function. This is just an example. Now, if I apply the ReLU layer over here, right? It's a small but important step in CNNs. Its math is also very simple. Negative number, wherever you see a negative number, it will become 0. This helps the CNN stay mathematically healthy by keeping the learned values from getting stuck near 0, right? So if you see, when I apply this ReLU activation function over here, what will happen is the 0.77 will remain 0.77, but the minus 0.11 will actually become 0, right? So if you go ahead and if you apply this to the entire output, right, this is the output that you will get. Now this output is slightly incorrect. If you see all of these negative values, they have made them as only positive, but these values ideally should have been 0 over here, right? So don't get confused by this. Now this would have been a 0, right? Similarly, this would have been a 0. Now, after the application of this function, ReLU function, do you think that the size of the image will change? Will we see any change in the size of the image? No, right? It will remain exactly the same. I will be having same number of pixels and all. It's just that we are actually negating those parts of the image, or we are negating those subsets of the image which are opposite to our feature map. If our feature map was vertical edge, and let's say this is a horizontal edge that is present, I am going to nullify that effect. Using these two features
maybe the model goes ahead and tries to make predictions, right? So hence, if you see, all of these outputs will be combined. Now, whatever patterns you are seeing, so let's say when it goes ahead and it identifies a dog from a cat, right? So maybe a dog can be black, maybe a cat can also be black, but let's say there are specific shades which a dog can be but a cat cannot be, right? So then if you combine all of these things together, now it can happen that a cat and dog both might be black, right? But it might happen that, let's say, the edges of the nose of a cat or the edges of the snout of a cat might be different as compared to that of a dog. So when you combine these two, now in certain cases it can happen that certain cats and dogs might have same snout. So if you take a pug, for example, and compare that with a cat, it looks similar. But if you take the color of a pug and if you compare that with a cat, then in such cases you will be able to differentiate that, okay, maybe the snout is round, but along with that, the color that a pug has might be different as compared to a normal cat, right? So here we have only two uh, feature spaces, but if you apply more number of features, more number of convolution features on your image, then every single feature, right, might or might not play an important part in making a classification. But whatever features will be present in your model, they will be contributing to certain images, right? Object detection, right? So we will be doing object detection today as well, because obviously CNN, as I said, 99% of the use convolutional neural network models is around image and video based data, right? So the data that we have over here is Cypher 10 data, right? Now this data contains around 60,000 samples, and all of these image samples are of the size 32 cross 32, right? Now 32 cross 32, the size is small, the size is very small, but that is what we can work with in a 2-hour class, right? Otherwise, if we go ahead and if we start building a model on slightly larger images, it will exceed the model building time. So we are working with this, but once when we'll be done with this case study, you will have the code and you will have the tools to go ahead and apply this on any data, right? Then you can go ahead and you can download maybe images from different domains, maybe interest, and then you can go ahead and you can try to create CNN models which might be able to differentiate between the different kinds of images that you have, right? Now the 10 different classes that we have in this data are, if you see over here, are aeroplanes, cars, birds, cats, dogs, horses, ships, and trucks, right? Now you can see that there are categories which might be very similar in nature. Like, let's say if you take cats and dogs, right, and horses, there are categories which might be very dissimilar in nature as well. If you see aeroplane and birds, right, aeroplane and deer, so there is no correlation, right? So we'll see if we can create a CNN model which is effectively able to classify all of these objects, right? Now see, all of these objects are coming from uh, different areas, right? It's not that these are related. The objects can be totally random, and we'll try to see if the CNN model is able to capture the patterns and is able to make effective predictions on these objects which are coming from varying uh, domains, right? Multi-class, right? Exactly. So this will be a multi-class problem. I have 10 classes, right? Now, problem statement is image classification using deep CNNs in Keras image detection operation, right? So let's proceed with this. Let's import the libraries that will be needed. So we will be using NumPy, Matplotlib, which is standard. CV2 is a library for visualization. And then from TensorFlow.keras, we are importing datasets, we are importing models, layers, optimizers, because all of these will be used. Uh, from TensorFlow.keras.preprocessing, we are importing image data generator, right? If you remember, image data generator is a function which will basically add new samples of the same image, right? We are also importing two new functions, which is model checkpoint and early stopping. So I'll talk about this once when we reach this, these functions are being used, right? And this, all of this is not required. We have just imported those. So we'll see whatever functions will be, whatever libraries will be used. I will be explaining about those, right? So I define my variables beforehand, something that generally you will do once when you have a vision of the data, right? But right now, because generally what we do, all the variables, anything that you want to change in your code, right? That you generally define towards the start. So whenever you have to run the code, right, you don't have to go inside the different cells of the code to change different variables, right? So make it as a practice whenever you are coding. So this will not happen in the first iteration of the code, because obviously in the first iteration of the code, you are still writing the code, you are still thinking about the approach and all. But once when your code is finalized, once when you know that, okay, this is what I need to run and this is the code that I need to run, then what you need to do is that you need to bring up all the variables that you are, say if somewhere you are defining epochs, right? Let's say somewhere if you are defining the batch size, right? All of these things, then you will try to bring them up towards the first or second cell. Why? Now, the next time, let's say if you want to run this code, all you to change the values. If you need to change the value of any variable, you just need to change the values of of a single cell that probably will be present somewhere on the top, right? And then you can run the entire notebook and it should, right? So that is why if you see, we are defining the batch size, number of classes, epochs, and number of predictions over here, right? These variables will be used at a later stage. Number predictions, Aniket, is for the evaluate function. Once when we have built the model and we want to evaluate it, then it will make predictions on a batch of 20. We'll be using this today as well, right? Now, once again, we are using the Keras data. So we are using datasets.cyfar, right? So if you see Keras as a library, right, it will have lots of datasets. Right? If you see, I have these many datasets. I have Boston Housing, Cypher 10, Cypher 100, Fashion MNIST, IMDb, MNIST, Reuters, right? Can go ahead and you can play around with any of these data, right? What we are using over here, we are using the Cypher 10 data, right? So if you want, so let's say if you do this, right, let's see what it returns, right? So you can see that, let's go to this function as well, right? Load data, it is these four things only, right? So if I go ahead and assign this over here, right? So if you want to read, let's say Boston housing data, you can read that, right? Now, if you want to go ahead and if you want to explore this data, you can also. Now, this will also be mostly image data only. So let's look at the shape. I'm just telling you how you can explore the, right? Okay, so this is not image data. This is housing related data, right? So if I show you this, this can be used for your structured data problems. So X train is this, and if you see Y train, right, this is your Y train. Now this is a data which is for Boston house price prediction, right? You have different factors such as the area, location, and whether a house is not, things like that. And then you have the target variable, which is the price of a house, right? So you can use all of this data. So this data can be used for the ANN model, Cypher 100, Cypher 10, all of this data can be used for your CNN. So in Keras, you can see you have lots of options. And you can just directly download the data and you can start using it. So in our case, we are using the Cypher 10 data, right? So we load this data And once when we load this data, we see that this is what we are getting, right? So let me load this. And then I print the shape of your X train, and I print the number of samples, right? So if you see X train, my training data contains 50,000 images of the size 32, 32, 3, right? So are these colored images or black and white images that we have? RGB, right? Now, let's try to understand one thing, right? Let's say you are given a data, and let's focus on this problem that we have, right? Now, the problem that we have, the data, the images that have been given to us contain one image will contain three subparts, right? One red, one green, one blue, right? Now, do you think that for this problem, that is object detection, do you think that can we using black and white data, or do we need to have color data if that is given to us? If let's say I had a plane in colored, and let's say I had a plane in black and white, will I or will I not be able to make out the difference between an aeroplane and let's say a bird in the first case when they are colored and in the second case when they are black and white? So it doesn't matter, right? Now the color of, in this particular case, the color doesn't matter, right? Because obviously in most object detection is about identifying the silhouette of the objects, right? And then being able to classify them correctly. So now if I would have gone ahead, and let's say if I go ahead and if I use the colored image, right, my accuracy of the model might not change, but the complexity of the model will definitely change, right? Because instead, if my data size was X in black and white, in colored, the data size will become 3 times of X. Is that correct? So whenever you are actually working on such problems, first thing that you need to understand is that, do you need to have colored images? Can you make do with black and white data, right? That is the first thing. Now, because if the problem that you're solving is solvable using black and white images, then there is no need to complicate your data. There is no need to explode the size of your data by taking colored images. Now, can you guys think of any use cases of a CNN model wherein colored images will be required and you might not be able to make out things with black and white data? If you talk about self-driving cars, right? Now, in case of a self-driving car, let's say if my color of the sky is color of, let's say, an object in front of me is also blue. If I convert that into grayscale, obviously they will be looking very, very similar, right? Traffic signals, right? Yes, Ayush, that's a good example, right? So if think for very, very highly complicated problems, because even for MRIs, even for medical scans and all, you might go ahead and see, generally all the scans that we get, they are black and white only, right? Why? Because you are able to differentiate whatever growth, whatever aspects you want to see inside the human body, right? You are able to see that in black and white as well, clearly, right? So for medical imaging as well, mostly in most of the cases you work with black and white data. Object detection, facial recognition, anything you want, right? You will see that generally your black and white images will work, right? So always whenever you are working, you need to take a call, because see, your input image might your input image will always be coming in as a colored image, right? But if you take in the same colored image into the model, right, you are making your model complex by 3 times. Whereas if you convert that to black and white, reduce the size of the data, go ahead and process the image, get a prediction, and just go ahead and give that, right? That is a much, much more easier and faster thing to do, right? So just keep this thing in mind, that whatever problems you're solving, just once go ahead and do a sense check whether you want to use colored images or you want to use black and white images. So let's look at the shape of our training data. Training data contains, sorry, not train. Okay, so this is the Y train data. So if you look at this was X train. X train contained 50,000 images. These are colored images of the size 32 cross 32. Y train contains 50,000 outputs, right? And obviously 50,000 comma 1 because these are the labels that we have, right? If you look at one image, this is the size of one particular image, right? 32, 32, 3, right? I believe all of these things we know. If I look at Y train are nothing but, if you see if Y train for the first image is 6, that image will be of what? That image will be of a frog, right? Because the label 6 belongs to a frog, right? The second image, that is of 9, object 9. Object 9 is what? It is a truck, right? So now what we'll do is that we'll try to visualize these images and we'll try to see what we are actually getting in the image and what is there in the labels and is the mapping correct, right? So I create a label dict which just creates a key value pair of, if it is 0, then if it is an airplane, if it is 1, then it is an automobile, if it is 2, then it's a bird and all, right? So we create a label dict and we try to visualize the data, right? So to visualize the data, what I'm doing is that I am taking an index, any random index. I select my X through that index. I select my Y through that index. I go ahead and I do a plt.im show, right? I run this and you can see that this is what we are getting. So let's start with the 0th index. 0th index was a frog, and this is what you're seeing. Now, for most of you, I think all of you might not be able to make out the frog properly, but if you see, here we have the frog, right? Now, the images are not high dimensional because of the reason that we cannot process more than uh, this, right? We have 60,000 images. Every image has 32 cross 32. So that is once again a large number of pixels, right? So only for that reason, we are working with smaller images. Generally, your CNN models, you will not be able to create or deploy these CNN models on your standalone systems, right? You will have to go ahead and you will have to use some kind of let's say uh, distributed computing, maybe cloud processing, right? Things like that, cloud computing and all, in order to train more complicated CNN models, right? So if you keep on changing the index, the image will change. Now, if you see, this is also a truck. Let's say if I check for the 22nd, right? So this is also a frog. Let's say I check 2 to 3. This is an airplane, and you can see that this is only a part of the airplane, but still, this is what we are getting over here, right? So the bot sees this kind of pic to make judgment. Obviously, Nitin, whatever we are passing, only the bot, there is no bot, it is a CNN model, right? But yeah, you're correct. We can call it a bot. But whatever images you are passing, that is what it is going to see, right? What are the minimum specs to run CNNs? So Krishna, this model, this code, you can even run on your locally hosted computer, right? But this you can see over here is not a very effective image. This is just a sample that we are working with. But once when you work with real-time images, then obviously you might need to have distributed computing. You might need to have cloud computing, because otherwise you will not be able to run on your locally hosted machines. I'm sure if you have GPUs, if you have TPUs, in those cases, maybe, not maybe, you can. But I'm assuming if you are planning to run a CNN model, you would want as many samples as you can. Even if you, let's say, start working with a million samples of images, assuming that each sample is 4K into 4K pixels, right? So you can imagine that how complicated your CNN model will become, right? Exact flow, what you need to do is that you need to organize your image in such a form You need to create a folder known as dataset. You need to create two folders inside the dataset folder, which is class 1 and class 2, and depending upon whatever number of classes you have, right? And then image 1, image 2, whatever images you have, you will place them inside this folder. Once when you have placed these, right, all you need to do is that you need to give your path over here. You need to give the input shape of input shape of the images, right? This is image data generator. Let's leave that for now. But all you need to do is that if you call this image data generator, if you
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
pass this, right? If you see over here what they are doing is that train data gen.flow from directory. You give the path over here, right? Train data directory, and it is calling. It will call all the images that you had in your folders directly over to Python, right? If you want a simple solution, what if I don't want to use image data generator and only want to import existing images, right? If you don't want to do all of this, see, this has written a function for you, load and pre-process images. You can go ahead and you can use this as well, right? So all of these things, you can just do that. Just go to ChatGPT, try getting the code, and you should be able to understand the code. Okay. Into all of that, you should be knowing, right? If you're coming with a problem that you have to identify 10 categories and all, now that is something that you will have to do. How many classes, how many categories, right? All of these things you should obviously be knowing. You cannot go ahead and, let's say, feed a bunch of images to the model, and you cannot expect the model to tell you how many classes are there, right? So the data is your responsibility. Whether it is 10 classes, 20 classes, 100,000, that is something that you will have to identify. You will have to structure and provide to the model. All right, so now let's prepare our data, right? We'll prepare our data for the model. So the target variable, do you think that we can go ahead and we can use the target variable as it is? If you see, this is how the target variable looks like. Or do you think that we need to change the target variable here? What do you guys think? One hot encoding, right? So we need to do one hot encoding of the target variable. So I'm calling the label binarizer over here. Label binarizer is a function. You can use one hot encoder, you can use dummy variable encoder, whatever. This time we are using label binarizer. I call the model object label binarizer. I fit transform my train data and I fit transform my test data, right? As soon as I do this, I am able to change the shape of my Y train and Y test both, right? If you see Y, let's say if I show you Y train 0, Y train 0 was index 6, right? So you can see that 0, 1, 2, 3, 4, 5, 6. Sixth index is actually 1 over here, right? This was required because our target variable, this is a multi-classification problem. So we had to pass the one hot encoded values to the model, right? This is just an example. So you can see that the same thing we can do using one hot encoder or pd.get dummies, right? We have used over here a label binarizer, right? So whatever you're comfortable with, you can go ahead and you can use that, right? So this is all the pre-processing that we have to do. Not there is no data exploration, no amount of, right? If you're able to read the images, if you're able to visualize the images on Python, it means that they are not corrupt. If they are not corrupt, that means that your data, that your features are correct, right? And all you need to do is that you need to check how many features in or how many samples in the trained data, how many samples in the test data, what kind of a target variable you have, do you need to change the target variable and all. So that is what we have done till now, and now we can directly proceed to the model building. See, EDA and all this will be minimalistic in case of CNN models, right? But if you try to look at this from a real world perspective, collecting data, organizing that data, all of that is something that will take more time. Whereas with structured data, you can just directly go ahead and import that. But structured data, accumulation of structured data, once when you have a pipeline, will be easy as compared to accumulation of such unstructured data, right? Like images, videos, and all. All right, so let's proceed to the model building part now. Now, for the model building, I will be showing you one snapshot of the model, right? That is how we can add the different layers and all. But I want you guys to then go ahead, take this notebook and explore different kinds of models, do hyperparameter tuning. That is something that I've already shown you in the case of ANNs, right? How do we do the hyperparameter tuning? So over here as well, I expect you to do that, right? I am showcasing a very complicated model over here, right? Which will be using many convolution layers, many ReLU, many max pooling layers, and so on and so forth, right? So let's have a look at the model. The model that we are creating will have these many layers, right? If you look at this, the first we'll start with a convolutional layer of 32 feature maps of the size 5 cross 5 and a rectifier activation function. This will be followed by a batch normalization layer, right? I hope you guys remember the batch normalization layer. What does the batch normalization layer do? It standardizes our data, it normalizes our data before it is being fed to the different layers, right? We have studied about this in the ANN part. Then we are applying one more convolution layer, 32 feature maps, followed by batch normalization, followed by max pooling, followed by dropout, right? So over here as well, if you see, when I add a dropout of 25%, what does that mean? A dropout of 25% means that if you have 32 feature maps, right? Out of these 32 feature maps, 25% feature maps will be dropped off, right? So over here as well, you can see that just like in case of neurons, when we were adding dropouts, we were deactivating the neurons. Over here, if we, let's say, add 32 filters and we want to randomly deactivate certain filters and see which filters are contributing, which filters are not contributing, then over here as well, we can add dropout, right? So people who are asking questions such as how will we identify the filters, which filters we need to apply and all, the answer is you don't need to do that. This is the part of the model training. Identifying the important features, identifying what convolution filters to take, what not to take, is not your job. It is the model's job, right? Then after that, it is followed by another set of convolution layers, 64 feature maps. Now we have reduced the size to 3 cross 3, batch normalization, once again dropout, once again convolution with 64, batch normalization, followed by max pooling, followed by dropout. Then finally, we go to max pooling layer. Then we add the fully connected layer with 256 units. We add dropout at 50%, and then finally we have the output layer, right? So this will be the architecture of the model. Let's go ahead and have a look at it, how it looks when we code this. Model, you cannot arrive at in the first go, obviously, right? You will have to try out different variations, different combinations. So whatever hyperparameter tuning we have worked on, all of that will stand true here as well. You will have to try out different permutations and combinations, and you will have to see which one is working the best, which one is giving you the best accuracy, right? So don't think that this is something that you will arrive at in the first go and the second go. You will still have to run tens and twenties of iterations and see which combination of different layers is actually working the best for you, right?
All right, so let's proceed. The shape of my input data is this is 32 comma 32 comma 3. If you remember this, now this is where we are creating the model architecture, right? So at first, I do not pass any batch size. I instantiate the model. If you let's look at this row by row, right? The first line over here is your models dot sequential, right? Why? Because CNN is also a sequential model. If you see, we start from the image, we go to the convolution, ReLU, max pooling layers, right? We apply these layers again and again, right? For a defined number of times. This is followed by the flatten function, which is then followed by the ANN model, right? Now, all of this is happening in a sequence. All of this is sequential. So your CNN is also a sequential model. If it is a sequential model, I need to initialize a sequential model, right? So I do a models.sequential. Now I start adding the different layers. Now, if you see last time when we were working with the ANN model, all we had to do was we had to call the dense layer, right? But this time, if I do a model.add, I am passing the different kinds of layers, right? So this time first of all, I take from layers, I take the function convolution 2D. So this will add a convolution layer in my sequential model. So the first layer that will be added will be the convolution layer, right? This convolution layer will have 32 filters. I'm saying that this layer will have 32 filters and the size of each and every filter will be 5, 5.
Coming to the first question on these top deep learning interview questions set, the first question is what are the differences between machine learning and deep learning? This is a very common question that's asked, and it is very important that you know the basic differences that lie between machine learning and deep learning. One very good commonality is that both of these are actually subsets of artificial intelligence, and deep learning itself is actually, a part of machine learning. So when we talk about machine learning, we're making sure that we find a way where we're training machines with a lot of data. We give it some data and we hide some data from it, in fact, and we use the hidden data later, which we also call as the testing data, to make sure that the machine learns something, and to verify if it has actually learned from its experience. When it comes to deep learning, we try to find methodologies and ways where we can sort of trick the machine into making it think like a human being, making it use the human brain structure in terms of working. In the concepts of neural networks, the entire concept is named after neurons and the use of neurons as well, just because how very similar to how it works in the human brain. So this forms to be the basic difference between machine learning and deep learning. Moving on to the second question, it says, what is perceptron? Perceptron is a very important concept in deep learning because it actually matches what we see in an actual neuron in a human brain. So coming to how it works in deep learning, a perceptron actually receives inputs from a variety of entities, and then later it takes these entities, applies some transformations on it, what we call as functions. It applies functions on this, and then it becomes the output. So input, perceptron, applying function, output. That is how the order goes. So if you have to talk about when perceptron is mainly used, it is actually used when we go on to perform binary classification, where we use an input, we try to see if we can classify something based on the output. There's so many factors when we talk about the functions as well. There is weights, there is biases, and there's a lot of things in a neural network in deep learning that has a lot of impact. And in this system itself, perceptrons play a very important role to take an input and transform it and work on it to give you a valid output in the case of classifiers as well. Now, coming to question number 3, it states, how is deep learning better than machine learning? Both deep learning and machine learning are very powerful in their own ways. To solve most of the complex problem in a very simple way, machine learning has got it covered. But then when you talk about deep learning will overpower machine learning, especially when it comes to working with data that has huge number of dimensions. Think about an Excel sheet which has about, let's say, 100 columns with 35,000 entries each, something like that. So when there's a lot of data in your data set, and and the dimensions are very large, deep learning will be exponentially efficient at working with things than compared to machine learning. So if your data is large, then a deep learning deep learning model will work very efficiently to actually solve it, handle it, and it'll make it easier for you to program and work with it at the same time as well. So this is how deep learning is having the upper hand over machine learning in a very simple and a concise way. Now, moving on to the fourth question, it states, what are some of the most used applications of deep learning? Again, this is a very common question that can be asked in your deep learning interviews. So at least make sure you mention at least 3 or 4 fields, and in fact I've put up around 6 fields on the screen right now. Everything from sentiment analysis, mostly Twitter, and all of that. Then we have computer vision to analyze graphics. Then we have automatic text generation, we have object detection, we have NLP, natural language processing, and image recognition. There are more fields. You can name about 10 to 12 offhand if you have worked a little bit on deep learning, but then it doesn't it doesn't really add a lot of value if you just list 10 to 12. So rather just tell 5 or 6 and just explain 1 or 2 lines about what each of them mean. That way the interviewer has an idea that you are concrete with respect to all the concepts there as well. Now with this we can come to question number 5 that states, what is the meaning of overfitting? Overfitting and underfitting are actually two very common issues that have to be dealt with whenever you're working with data sets and whenever you're working with deep learning. Overfitting, as the name suggests, is a scenario where you have a deep learning algorithm, and your deep learning algorithm is looking very hard into your data, and it is trying to hunt for meaning. It is trying to find some meaningful correlations in between the data in the data set. Now in a way, what happens in overfitting is that it will start vigorously hunting for the data, and this makes it pick up noise, what we call as noise, rather than any sort of useful data. So with this noise, it hurts the efficiency, it hurts the detection capacity of the model. So rather than picking up any useful valid information, your model will start picking up noise, and that is not a good thing. So what happens is, at the end of the day, you'll have a very high variance in your data and a very low bias. This way, of course, you would already know that your model will be very, very inaccurate in terms of detection and very inefficient at detecting new things, even if it has a good level of accuracy as well. So when you think about it, overfitting needs to be fixed, and underfitting is just the reverse of this. Anyway, coming on to the 6th question, it states, what are activation functions? Activation functions are very important entities in deep learning, because these are the actual functions that will take your input and make sure that you have something usable on it. So the transformations that happen, right, it is all because of the activation function. So what an activation function is basically is that it has the capability to decide if a neuron actually needs activation or not in that particular array, in that particular set of neurons, to see if there has to be anything modeled from that particular neuron in the chain in the neural network, or if it adds a value to the next set of neurons as well. So this is actually done by calculating the weighted sum of it and then taking the bias as well. So at the end of the day, whenever you're making use of an activation function, the model output will be non-linear. And if you have to talk about the types of activation functions as well, so there's rectified linear unit, or ReLU for short. You have softmax, sigmoid, linear, tanh, and many others as well. So it adds value that you answer it in a way where you tell what activation functions are, how they're calculated, what the output will look like, and what are the types of activation functions as well. With this, we come to the 7th question that states, what is Fourier transforms that is used in deep learning? Fourier transform is very vital to deep learning, because it is one of these packages that is used to manage and work with a lot of data when we work with deep learning. As you already know, in deep learning we will be working with huge data sets, so we need methods and tools and techniques where we can process these in real time, and we can make sure that we can handle it and work with it easily and quickly as well. So Fourier transforms is one of these packages that will make sure that you have high efficiency whenever you're working with data. And with Fourier transforms, your model is now open to a lot of signals where you can have the data processed from multiple entities, and just make sure that you're opening up a dimension when you're working with the data as well. So Fourier transforms are a very vital part of deep learning. Now, with this, we can come to question number 8 that states, what are the steps involved in training a perceptron in deep learning? There are about 5 to 6 steps whenever we have to talk about the perceptron learning or training a perceptron, as it's also called as. And these are the 5 steps. Firstly, the first step is always to initialize all the thresholds and the weights of the network. Then, of course, we'll be providing the actual inputs. The outputs are calculated based on a lot of things. Then we have back propagation, all the algorithms that run in the back end. And after which we'll have the steps where we'll be upgrading the weights in every single step. So after the weights are upgraded, then we'll again provide another set of inputs. We'll be calculating the weights again, and this goes on from the starting initial node all the way till the last node of the output neural network. And this is how simple it is to actually train a perceptron in deep learning. Now with this, we can move on to the 9th question that states, what is the use of the loss function? Whenever we talk about neural networks and deep learning, we need a methodology, we need a number, we need a numeric where we have the ability to see if the model is working towards its goal or not, right? So the loss function is a measure of accuracy here as well, because we're trying to see if the neural network actually learned something useful from the data or not. And a loss function is a negative metric where if the loss function's value is less, then it's good for the model. If the loss function value is high, it means that the model is not performing well. So at all times, it is very vital that you mention that the loss function has to be kept to a minimal extent. Now with this, we can come to the 10th question that states, what are some of the deep learning frameworks or tools that you have used in the past? Now this is a very common question that's asked in the interviews because they want to find out, the interviewers want to find out about the experience that you have with all of these tools. So just make sure to mention of all the frameworks, tools and techniques that you might have used in your projects or your certification programs, or whatever it is that you have used, the methodologies that you have used to learn. Of course, there are many top deep learning frameworks out there. We have an entire video on that on the channel as well. So make sure to check that out after this video. Among the top deep learning frameworks, we have TensorFlow, we have Keras, we have PyTorch, we have Cafe2, we have CNTK, that's Microsoft's cognitive toolkit. Then we have MXNet, we have Theanon, we have many others. In fact, you can list about 12 to 15 very good top deep learning frameworks out there. But then just make sure to mention 3 or 4. But then if you of course used more than that, then do make sure you mention that as well. But then make sure that you are very honest about it, and do not I would suggest that you do not state a deep learning framework that you might have not used, as that might lead to you being asked questions on that, and you not being able to answer as well. So make sure to take care about that. Now with this, we can come to the 11th question that states, what is the use of the swish function? So the swish function is nothing but an activation function, as we discussed a while ago. So it's something called as a self-gated activation function, and it is developed by the people at Google. So one thing to note about the swish function is that it is extremely popular because Google has put up a very good claim that it outperforms all of the other activation functions that exists today in terms of efficiency. So we discussed the different types of activation functions as well, right? Tanich, Relu, and all of these. So then Google came about, they devised an algorithm, the activation function algorithm, and they put up saying that this will outperform everything else that already exists. So that is one of the reasons why this particular activation function has seen so much limelight as well. Now with this, we can come to the 12th question that states, what are autoencoders? Autoencoders itself are artificial neural networks, and this is something which is very important that you know. And of course, they do not have any supervision, as they have the ability to automatically try and map inputs and to find out outputs and work with it on their own. So it's a very interesting concept to work with autoencoders, and these are very efficient as well. But then when we talk about autoencoders, it is very vital that we talk about two important things. One is the encoder and one is the decoder. These two are the very important entities that we have to discuss about. An encoder will make sure that the input is taken and it is converted into a format which is understood by the neural network into an internal computation state, of course. And then we have the decoder, which does the exact opposite of this. It will take the computational state data and it will make sure to convert it back into the output. So encoders, even though the name only has encoders, there are two operations that's going on. One is the encoder operation and the other one is the decoder operation. Now, with this, we can check out the 13th question that states, what are the steps that have to be taken, whenever you make use of a gradient descent algorithm? There are actually 5 to 6 steps that have to be discussed whenever we talk about initializing and making use of the gradient descent algorithm. The first step is always, you have to initialize all the biases and weights for the network as well. And after you have initialized all the biases, you have to send the input data throughout the network, which forms to be, of course, the input layer, the first layer of your neural network. And then we'll actually calculate the loss function, right? So you'll have an expected value that you're expecting at that point of time, and there will be a value which is predicted by the model as well. So calculating the difference between this will give you the error of how far away the neural network is from the actual goal. Now, after that, you will actually change all the values in the neurons to make sure to find ways where you can minimize this loss function, this difference that we just found out in step 3. And after which, of course, this entire process is an iterative process. You'll be looping it and doing across multiple iterations to find out what biases, what weights, and how best you can do to keep the loss function at its minimum. So these are some of the steps that have to be followed whenever you're working with gradient descent algorithm as well. So with this, we can come to the 14th question that states, differentiate between a single layer perceptron and a multi-layer perceptron. We already discussed that, if we're talking about a perceptron, in case if it's a single layer perceptron, it will not have the ability to classify non-linear data for us, but then a multi-layer perceptron completely can, classify non-linear data. And a single layer perceptron is a bit limited in one aspect where, the number of parameter that it takes in is very less when you compare to a multi-layer perceptron. And this in big deep learning models can have a very, very, disastrous effect as well for efficiency, for effective working and whatnot. So again, for the second point, I think multi-layer perceptron wins. And when you talk about the third difference, of course, a single layer perceptron has many things that it can do well. But if we are talking about efficiency when making use of large data, again, a multi-layer perceptron of course takes the higher end because it is extremely efficient to work with in the case of large data sets. Now with this, we can come to the next question that states, what is data normalization in deep learning? So data normalization is a very, very important step. It is actually a pre-processing step where we try to make sure, we can move around the data, rearrange the data, and we can make sure to refit and pack this data into one particular range. This is the entire process of normalization. Why we do this is to make sure that, if your data is in one particular range, it means that your network has the ability to learn very effectively and be very efficient as well. So, when you're performing steps like backpropagation, having a data in a very structured range, a specific range, will make sure that your network can learn that much faster as well. So these are one or two reasons why, this pre-processing step that we take called as data normalization is very important. Now with this, we can come to the 16th question that states, what is forward propagation? So backward propagation is the scenario where, we work from the output layer to the input layer, and here in forward propagation, it is the exact reverse. We follow in the order of the neural network. So, we go from the input layers to the hidden layers and then the output layer. So, when you're talking about a complex neural network, there'll be more than one hidden layer. So for every hidden layer, the output of the activation function is actually calculated, and this is done until the next layer can actually be processed. The reason they call it forward propagation, as I just mentioned, is to make sure we work from the input and towards the output. And this is the exact opposite of the backward propagation algorithm as well. So to make sure that we use the output of the activation function and to calculate it for the next layers, forward propagation is very, very important. Now with this, we can check out the 17th question. Again, coming back to the very main important question, your interview could start with this question itself. What is backpropagation? So backpropagation, instead of talking about what, the first thing you have to always discuss is why backpropagation is even important, right? So it is to make sure that we keep the loss function or the cost function less, and to see how the values changes whenever we, work with a variety of biases, a variety of weights. Whenever we change all of these, even a slight change can have a very big impact on your model. To understand how these work, we require the backpropagation. It's called backpropagation, of course, because it starts from the output layer, works backwards towards the input layer direction. So how is backpropagation calculated? Well, it is very easily calculated whenever you work, by understanding the gradient that is calculated at every single hidden layer itself. So it's as easy and straightforward as that. Now with this, we can check out the 18th question that states, what are hyperparameters in deep learning? So when you talk about hyperparameters, even though the term is very complex, they're nothing but variables that are actually used in deep learning to actually determine the structure of a neural network. So these variables are put into place to make sure that we have an easy way of understanding so many different factors and parameters in the deep learning model, be it the number of hidden layers that are present or the learning rate of the model and much more. So hyperparameters are very important variables that will give us a lot of insight into how the model or the neural network is functioning as well. So moving on to the next question, it states, how can hyperparameters be trained in neural networks? So training a hyperparameter is very important, and understanding how you can convey this to the interviewer is also very important, because these are long procedures and your ability to concisely answer it is very important. So, to train a hyperparameter, we'll require 4 very important components. It's the batch size, the number of epochs, and there's something called as the momentum, and there's a metric called as the learning rate. So what happens in batch size is that we'll take the input, we'll split it into batches. Batch size can be varied depending on however it is required based on the efficiency and a lot of other things. These batches can be cut into further sub batches as well, if that is the requirement. So instead of pushing all the input into a concurrent pipeline, we just make sure to dig it up into batches and then vary it across. Now, when you talk about epoch, an epoch is basically a denotion of how many times the training data is run through the neural networks where it can train. So the number of epochs is the number of iterations at which the neural network trains as well. So it's an iterative process. The number will depend on so many different factors. Doesn't mean that if you have a large number of epochs, that your model will be very, very accurate with every single iteration. That it'll go up to a point, and then of course your model will work, in fact, in the opposite direction. Now, when you talk about momentum is actually put into place where we have an idea to check out what happens in the next consecutive steps. Whenever data is being moved around in a neural network, it is vital to understand what happens next, right? So, there is no point if your model is very inefficient where it's passing around data and not driving any momentum from it. So momentum is this particular track where we make sure we understand what's happening next as well. Now, coming to the last component, it's a very important component. It's the learning rate. Learning rate is what we are all after when you work with deep learning, because this is used as a very important parameter where we're trying to denote what is the time that's required to actually update all the parameters when your model learns and when your neural network is ready to take in certain inputs and give you meaningful outputs as well. So these, 4 form to be very, very vital, very important components in the world of deep learning whenever we go on to train hyperparameters. Now with this, we can come to the 20th question that states, what is the meaning of a dropout in deep learning? Now, dropout might seem like a very common term, but it is actually a technique in the world of deep learning. Dropouts are a very important technique, in fact, because these are used to avoid overfitting. Overfitting and underfitting are common problems, as we discussed a couple of questions ago. So to avoid overfitting, to make sure that your model doesn't hunt for noise, what we actually do is, we purposefully remove a bit of data which might not be useful for the model to learn as well. So if you have a dropout value to be very low, it will have a minimal effect on learning because you're not removing enough data and your model can still go towards overfitting. But then if you remove a lot of data, then what will happen is the model will not have enough data to learn. So it will underlearn and then cause inefficiency as well. So this value, right, this drop off value should be very, very vital, because if you have it too low, it will not have an impact. If you have it too high, then your model will not learn effectively anymore. So understanding this is a key concept. Now, coming on to the 21st question, it states, what are tensors? Tensors, you might have heard of these. These are another name of arrays, guys. So tensors are actually multi-dimensional arrays that are mostly used in deep learning, where we have to represent data across either one dimension or in fact multiple dimensions as well. So why can't we just call them arrays and not tensors, right? So tensors have the specialty of a name because they have been very famous. They have been very vital whenever we work with data of higher dimensions. So one very big advantage when we talk about tensors is that whenever we make use of it in any of the programming languages, right, the syntax is very readable. It's a very high level syntax. So what that does is it gives us a clear picture of tensors, even though if we do not have very high amount of training in terms of making use of tensors or its terminology. As soon as we look at the programs, we'll have a keen idea about what tensors are and what they might be doing in the program as well. So this is one very good advantage when it comes to working with these multidimensional arrays called as tensors. Now we can move on to the 22nd question that states, what is the meaning of model capacity in deep learning? Model capacity is again a very important metric that we have to discuss about, because model capacity deals with the capacity of the model to actually take in a variety of mapping functions. So how many mapping functions can your model handle? How many can it concurrently work with as well? One thing we drive out of this metric is that higher the model capacity, it literally means that there is a large amount of information that can be stored and worked with in the network. If the model capacity is low, as the name suggests, it means it cannot handle and effectively a large amount of information at a time as well. So model capacity is something which is very straightforward, but yet it forms to be a very important concept in deep learning. Now with this we can come to the 23rd question that states, what is the Boltzmann machine? Boltzmann machine sounds very complex, but it is actually a type of a neural network, that we call as an RNN, or a recurrent neural network, where we make use of binary decisions, biases, and to do a lot of functioning and working for us as well. So Boltzmann machines are, like as I mentioned, RNNs. They are hooked together to create something that we call as DBNs, or deep belief networks. So these deep belief networks are extremely sophisticated. They have multiple number of hidden layers, and they're put into place because we have complex problems that require effective solving. So the entire goal of deep learning, in fact, is that we have extremely complicated problems and we need to find ways to make use of the power of computing to simplify that to a good extent for us, and a Boltzmann machine will do exactly that. Now, after understanding this, we need to check out what are the advantages of making use of one of the top deep learning frameworks out there called TensorFlow. So, of course, this could be a very important question in case if you work with TensorFlow, because understanding the advantages of it is very vital. So TensorFlow has many advantages, and to me the most important advantage is where it will give you a lot of flexibility and platform independence whenever you're working with it. The platform independence is very vital because we all have multiple operating systems, multiple platforms that we work on, and of course, so it has the ability to power through and train on both CPU and your graphical processing unit as well. And with new technologies with GPUs, it just makes it very efficient to work with tensors too. And then when we talk about auto differentiation and the features it brings with it, is again a huge impact. When we talk about threads and its ability to handle asynchronous computation, this is where TensorFlow wins over many other deep learning frameworks as well. The second most important advantage to me is that it's open source. It has a beautifully large community, so you don't have to pay for it, but then at the end of the day, there are so many things that are being added in terms of features, technologies, fixes, and so much more. And this entire community of open source is just a beautiful thing, and I'm sure you can relate to this if you work with TensorFlow as well. So with this, we come to the 25th question that states, what is a computational graph in deep learning? So a computational graph, as the name suggests, is a scenario, or is a graph itself, where we try to take inputs, arrange them into meaningful entities called as nodes, and later create a graph structure out of it. So these are done to simplify certain mathematical calculations and to visualize them better. So in terms of deep learning and in terms of backend functionality, it helps a lot whenever we're working with parallel processing, as it provides a huge performance boost over a single threaded performance in terms of making use of actual computational graphs, as your processing power is now 2, 3, 4, 5 or 10 times, 10 folds better than how it was before as well. So computational graphs are very important units when it comes to working with deep learning. Now, we can come to the 26th question that states, what are CNNs? CNNs and RNNs are very different types of neural networks. CNN stands for Convolutional Neural Network, while an RNN stands for Recurrent Neural Networks. Now, coming to the talk of CNNs are mostly used to perform visual analysis, or working with a lot of images and classification as well. You can have multiple images of many channels as well. So when we talk about images and channels, mostly we talk about colored images and black and white images. colored images will have like 3 channels, red, green and blue, RGB structure, and so much more as well, right? So a CNN has the ability to easily work with, classify and give you meaningful outputs on all of these images and visual data. Now if we talk about a little bit more about CNNs, the next question can be saying what are the various layers that are present in a convolutional neural network. So when the talk is of this, understand that there are 4 important layers in a convolutional neural network. One is the convolution layer, we have the ReLU layer or the activation function layer as it's also called. Then we have the pooling layer and the connectedness layer. So when we talk about the convolutional layer, this is where we apply things and entities called as filters across the main data to have them as parameters to teach and train the network. So after the convolution step is done, we'll use the activation function to squish it and bring it into a range which is workable and understandable by the neural network. After the activation function is done, then there's something called as pooling. Pooling is where again we shrink the data to make sure we are not losing any of the existing data, and what happens after convolution is we lose certain data as well. So we do stuffing in the pooling layer as well to make sure that we add certain bits, dummy bits, to make sure that the size of the image is actually maintained after every single iteration. So with every iteration the image shrinks a little, and with padding we make sure that we are not letting it shrink out of context as well. And then when we're talking about the 4th important layer of the convolutional neural network, it's connectedness. Here we're just making sure that all of the activation functions are applied correctly by making use of the bias and generally checking that the entire neural network is connected thoroughly and it's working as expected as well. So as the name suggests, this is a very important layer to verify the understanding of the neural network. So these are the 4 very, very important layers that you have to know about in this particular order itself. Whenever you're mentioning the working of it, the questions can be like, what is the working of a CNN, or what are the layers that are present as well. So this will develop as both of those questions. Now, when you talk about RNN, as I just mentioned, next question can be, what is an RNN in deep learning? So RNN, as I discussed, it stands for Recurrent Neural Networks, and unlike CNNs, the working here is very different. The use of it is very different because RNNs, or recurrent neural networks, are very, very efficient at working with a lot of string data, textual data, genome data, handwriting data, and much more. So if you have already worked with any basic use cases where you're performing, let's say, handwriting prediction or detection of handwritten letters or whatnot, then there's a good chance that you've made use of an RNN. RNN uses the technique called as backpropagation that we've already discussed for all its training requirements, and it is very, very effective at doing this as well. Just like how CNN is very effective for working with images, it shows similar girth whenever you're working with textual data as well. So this is again a very important aspect in deep learning. Now with this we can come to the 29th question that says, what is a vanishing gradient whenever you make use of recurrent neural networks? A vanishing gradient, to be honest, can be considered as a scenario, because we already saw in the last answer that RNNs make use of backpropagation, right? So if there is backpropagation, then there's the calculation of the gradients at every single step. And whenever we work with backpropagation, whenever we calculate gradients, they tend to get smaller and smaller as the data works backwards from the output layer to the input layer. So since the value becomes extremely smaller towards the end as we approach the input layer, it causes a problem. So this basically means that your model will learn very slowly and it cannot be efficient. It will underlearn sometimes and it will cause a lot of problems. So this is a scenario of occurrence where your gradient values are becoming very low, and that scenario is what we call as the vanishing gradient. Now, I hope this is clear. So with this, we can move on to the 30th question, which states, what is exploding gradient descent in deep learning? Just like vanishing gradient, exploding gradients are another issue which work in a very different way, because here is a scenario where we're clumping up all of the gradients. Means what it does is it will create a large number of updates for all of the weights in the model whenever it's training. So your model weights are being updated constantly more than required, and and we already know the working of gradient descent, right? So it's based on the condition to keep all of these updates small to make sure that your upgrades are controlled, and only then can your gradient descent have some meaningful impact on your deep learning model. So with this, we have to understand that whenever you control these updates that happen to the weights of the model, right, this will have a huge impact, in fact direct impact on the efficiency of the model as well. So this is another scenario, what we call as the exploding gradient descent, where we have large number of updates that happen to the weights which make it very, very inefficient at the end of the day too.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.